So in this video, we will complete the remaining 55 problems from our NeetCode 150 list, and other problems have been completed in part 1 and part 2 of our NeetCode 150 playlist, which you can find right over here. After completing all of these 3 parts, you would be able to complete every single technical interview. I can guarantee you that. And for that, we have NeetCode, a famous YouTuber who created this list for us, to thank. So once again, I tip my hat towards NeetCode. Thank you so much for creating this. And I just have one small request to make, that it took a lot of time and effort on my part to come up with this entire list, and I would really appreciate if you can support the channel, support my work. I'm a big believer in free education. That's why I put everything for free on YouTube. I would appreciate if you can become a member, like this video, share, subscribe, do all sorts of things, because it will really help me out and motivate me to make other videos like this. Now, without any delay, let's get started with the remaining 55 problems. So the LeetCode problem we are going to solve now is called swim in rising water. This one is a hard problem, but a very interesting and intriguing problem. So let's try to understand this. We are given an n cross n integer matrix called grid, where every single value inside the grid represents the elevation or height at that particular point in this I and jth location or any particular cell. Now we are told that the rain starts to fall, and at t times, which means rain is falling, let's say from 1 minute, then 1 minute it keeps on falling, like 2 minutes, 3 minutes, 50 minutes, up all the way up until t times. Then the depth of water everywhere is t, which means rain is proportional to the amount of time that has passed linearly. Now we can swim from any particular square to all the 4 adjacent squares if and only if the elevation of both the squares individually are at most t, which means we can swim from one square to any 4 directions as long as, let's say that the current t is, let's say, 15. So any particular square that has the value 15 or less in all these 4 directions, we can swim from this current place. So the amount of t becomes the critical point for us to compare, that are we able to traverse in between any 2 squares or not. Now we need to make sure that we need to reach to the bottom right square, where we are starting from the top left square, and we need to make sure that what is the least amount of time we need to wait before we can reach to the bottom right square. So let's try to understand this with an example. The aim is, we are given a grid like this. Now our objective is to traverse from this particular node to this particular node. We are being told that at every single moment, what is the elevation or what is the height at that particular point. Now the thing is, let's say that we are currently t is equal to 0 point, right? Which means, and we are currently located at this moment. So the thing is, currently only 0 units of rain has fallen, which means this particular portion is entirely filled up with rainwater. So we are able to swim within this cell. But the thing is, this cell has a height of 2, this cell has a height of 7, and this cell has a height of 4. So we cannot traverse in any 4 directions right now. Let's say now enough time has passed, and right now currently t is equal to 3, which means we can assume that, let's say, 3 meters of rain has fallen. So if 3 meters as rain has fallen, then this portion would have filled up completely, because it only requires 2 meters to fill up. But thing is, all the other squares are still not filled up, and because current t is equal to 3 and we are currently initially located at this very first spot, then we can traverse to this particular spot anytime after t is equal to 2. So at t is equal to 3, we can still travel. When t becomes 4, then at t becomes 4, this portion also gets filled up, and we can also swim in this direction as well. So our aim was to reach from this particular square to this particular square, and we can only do that once the t amount of t gets 4. So notice in this case, we are avoiding this path going down, because this path is more expensive. So our answer in this case would be t is equal to 4. Let's try to take one more slightly complicated example. Our aim is to reach from here to here. Now we notice that there are a bunch of different ways for us to we can go from here to here. we can take as many paths as we want. And actually, if we have to calculate mathematically how many paths it's going to take, I think it's going to be n divided by number of ways we can move, and factorial of that. So this is going to be a very expensive operation if we have to manually brute force our way to check every single path. But lucky for us, logical thing is that we need to check only for some t positions. So let's say that initially, if we are at the position of t is equal to 5, so let's see that where up until what point can we reach if t is equal to 5. We know we can swim from here, no issues with this one. Then we cannot swim into this cell because this is a higher t, but this is a lower t value, so we can go over here. Then nextly from this we can also go over here because this is also lower than 5, but we cannot go anywhere further, so we will have to increase the value of our t to t is equal to 6. Still we cannot go anywhere further. If we do t is equal to 7, then we can traverse up until this point, and notice that at t equal to 7 we can also traverse to this point because this is lesser than the current t value we have. So the minimum amount of t we need to complete all the values is not going to be t is equal to 6, even though this value is 6, it is going to be t is equal to 7. So one more way to explain this is to find a path that traverse from this one to the last, like top left to bottom right corner, and in that path find the minimum, like the maximum value of t that is required. So that would be our answer. So now let's try to reverse engineer our way through this one. We already know that, let's say if we are being told that you have this particular example, and for this example you need to make sure that you need to iterate over all the values only and only if for any particular given t. So let's say that we ask you that if the t is equal to 3, are you able to reach to all of these values? So logically what we will do is we will start from here, and then we will see that what are all the cells that has less value than t. So this cell has less value than t, then next this value has less value than t, and then we can say that now we cannot go anywhere further. We can also try to do a backtrack and check for the other possibility, but still we won't be able to do it. So logically we need to do like depth first search or breadth first search in order to find the path we need to take to reach to the end. That is number one fact. The other thing is, after finding the DFS or BFS, we don't know that what should be the optimal value of t in order for us to reach to the very end. So for that there are a bunch of different possibility, but one common way that is for sure is that the minimum value of t can be 0. So whatever the smallest value is, so let's say the smallest value is 0. So let's see, the possible values of t can be 0, or t has to be less than the maximum value we currently have. So in this case the maximum value we have is 24, so t has to be somewhere between 0 and 24. That is a given fact, like less than or equal to. Why? Because all the time if t is equal to 24, then we have access to traverse to every single cell in this given entire architecture. So if we can traverse to all the cells, for sure we can find a path that can lead us from top left to the bottom right corner. But so now we found one condition on where the t should be able to move. This is number one thing, that what could be the potential value of the t. Second thing is, we already know how to calculate that for any particular given value of t, are we able to traverse to all the cells and reach to the bottom right corner or not. We can do this in both the ways. We can use a breadth first search, or we can use a depth first search in order to do this one. And it's a pretty common and standard method that logically we are going to be traversing over all the different paths wherever this condition meets up, and the moment we find out that the condition is currently satisfactory, we can actually move to all four directions to find the value we are looking for. So what I'm suggesting is, instead of checking for all the potential values of t, which is going to be pretty expensive operation, why don't we use binary search in order to find the correct value of t that makes sense. So what I'm suggesting is, let's say that for this particular given value, we know that the t has to be somewhere between 0 and 24. So what we can do is, we can treat this 0 as the left pointer, this 24 as the right pointer. Then we will try to find the mid pointer. Mid pointer is going to be 12. So let's see that if we use the t is equal to 12, are we able to reach to this bottom right corner? So we can go down this path, that's for sure. But now after this 5 we cannot go anywhere because this is 16 and this is 21, so 12 does not work, which means the answer of t has to lie somewhere between 12 and 24. So we update, so sorry, not 12, like 13 and 24. So we update our left pointer and right pointer once again. We try to find the mid pointer. So in this case the mid pointer is going to be I think somewhere between 18. So let's see at 18 are we able to figure out. So yes, we can go down this path. Yeah, for sure at 18 we can take this path, and once again we should be able to complete our answer in this manner. No issues with this one. So yes, 18 works. So once again now we have our left pointer as 13 and right pointer as 18. Once again we will do the binary search. So we will find the middle pointer to be 15. Let's see, at 15 are we able to find the correct value we are looking for? No, right? Because the 16 we would not be able to cross this threshold. So next possible value is going to be 15 and once again 18, sorry, 16 and 18. So the logical step would be 17. 17 would work because we would be able to find out. Then once again from between 16 and 17 we also have to find that are we able to do it. So if we do the mid pointer, once again the value would be 16, and for 16 we should be able to find the answer. So logically we had to do, like, instead of doing 0 to 24 steps, we only did 5 steps to find that value to 16, and that we did it using binary search. So logically in this problem what I'm suggesting is that we use breadth first search or depth first search, whichever one you would like to choose, in order to iterate over all the cells. And we do this with doing the binary search on the different values of t, and the range for t is going to be the smallest element, like 0 less than or equal to t less than or equal to whatever the maximum element we have inside our grid, and somewhere between that we would try to find the value of t. So this solution would work perfectly fine. If we have to calculate time and space complexity, in this case the BFS or DFS would take big O of n square work, because we have n cross n grids and for one iteration, and we will have to do this log n time because we are trying to find different values of t. So it's going to be n square log n in terms of time complexity. In terms of space complexity, depends on how you implement your breadth first search or depth first search. If you are using recursion and if you are using like a stack, recursive stack to store those values, then it might take big O of n square space as well. So just be mindful of that. Now let's quickly see the coding solution for this one. So the very first thing we are going to do is we are going to mark the value of n. Then we are going to initialize our left pointer and right pointer. This is going to be the cell locations. And then we are checking that while our left pointer is less than right pointer, we are going to find the mid pointer that we will have to iterate over. And on top of it, we are also going to check, or we are going to call our helper method call swim. Can swim, and which checks that for any particular given grid, depending on the mid pointer, are we able to reach. If we can, then we shift our right pointer to the mid pointer. If we cannot, then we update our left pointer to go right +1. So this is our binary search method. Now let's understand our can swim method. So in the can swim, we have the given grid as the input and the different values of t we are working with. On top of it, we are checking that first of all, what is the length of the given grid. We are also having a visited boolean hash set that defines that these are the cells we have visited so far, because we don't want to be stuck inside the infinite loop in breadth first search or depth first search. And we are going to call our DFS method in this case, where we are passing in the grid, the nodes that we have currently visited, the I and jth location, and we are also passing in the different values of t. Now this is going to be our recursive DFS method, where first thing we are checking is that what is the given length of n. Then we are checking for the scenarios that if we are going out of bounds, so these 4 conditions are for going out of bounds, or we have already visited that node, or we notice that the location of the grid position is greater than the current t value, then we can return false, that we cannot go to that particular cell. If that is not the case, and we check that the current ith and jth position is at the bottom right, then we can simply return true, saying that yes, we are able to reach to bottom right corner. If that is not the case, then we mark the current node as visited, and then we call the DFS method in all 4 directions, and once again recursively repeat the same process. So this is the coding solution. So basically, after this recursive process ends, we should either receive true or false for any particular t value. And inside our main method, we are trying out bunch of different t values and making these various calls. So this is the whole solution. Now let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats almost 98% of all the other solutions, which is like one of the fastest solutions for this particular hard problem. So I hope you find it useful. Once again, the solution is present on our GitHub repository, so feel free to go ahead and check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do alien dictionary LeetCode problem, and not only it is a very important problem, this problem can actually be asked in multiple ways. It can be asked directly as a graph question, or it can be asked as a follow-up question for the previous question that we solved, verifying an alien dictionary. Because both questions are very similar, and if you want to check that where the solution for this problem is, you can check it out from over here. Also, another reason why this problem is really important is if you just take a list of companies that have asked this problem: Airbnb, Facebook, Google, Amazon, Bloomberg, Microsoft, Uber, they have all asked this question in last 6 months. Also, IT giants like Pinterest, Apple, Twitter, eBay, they all have asked this question in last 6 months to 1 year. And ByteDance, Snapchat, and Flipkart, so they have asked this question not fairly recently, but still it's important. And I will be paying my utmost attention because my aim is to clear any FAANG interview, and I hope you also enjoy the video. This is a LeetCode hard problem, and it justifies this hard tag. So let's understand the problem statement. Essentially, we have identified a new alien language that uses English alphabet. However, the order of those letters is unknown to us. Now we are given a list of strings inside this words, and we are told that they are from this alien languages dictionary. And in that string, the important property these words have is that they are sorted lexicographically. And we need to return a string of unique letters that are present in these words, and we need to return them in lexicographically increasing order. Now also there could be possible that there might be multiple solutions. So if there are multiple solutions, we only need to return any one of them. And there could be some cases where this given string of words is invalid, and if it is invalid, we need to return an empty string. So in order to understand this problem, first of all, we will have to identify that what does this lexicographically increasing order means. The second thing we will have to understand is that what are the cases where this particular input is going to be resulting in falsified information, and what does this string of unique letters with lexicographically increasing order means, because this unique word is actually really important, and I'll come to that later. So suppose if we just talk about what is lexicographically sorted means. If we talk about English language, if we talk about the words A, B, C, D, all the way up to Z, this is plain English language that we use on a day-to-day basis. Now in the English, suppose we are given any 4 letters. Suppose we are given letters like Q, A, E, B, R, C, and Q, E. Suppose we are given letters like this, right? And if we want to sort these 4 in plain English language, how we are going to sort them? Like, of course, the answer is simple. We are only going to check that what is their position in this given order, and based on that particular order, we will sort them. So if we sort them, the sorted result would look something like EA, QA, QE, and RC, something like this, right? And the reason we are able to generate this is because we know that the position of E comes before Q, and in this case there are 2 entries, QA and QE. So which means, like, if we will have to identify that what is the second letter, and second letter A comes before E, and then this R actually comes before Q. So we are able to determine a sequence like this. Now in this given problem, we don't need to generate a sequence like this. Basically we are told that we are not given this information. We don't know that what is the order of words are, and we are directly given this particular sequence that is already sorted in that particular language. So suppose this was to be an alien language, and if we want to identify that what should be the answer we need to return in this case, the few things we can determine from this input is that, okay, over here we are checking first, at any point we are checking any two adjacent words. In those two adjacent words we go letter by letter and we try to see that what is the first differing letter that comes to the existence, and based on the differing letter, whatever the word is presented first should come first in that order rather than second letter. So if we compare these two words EA and QA, we can see that the first differing word comes as E and over here it is Q. So which means we can determine that E will always come before Q in this particular alien language. Now don't forget this, that this is plain English. Just imagine this as an existing scenario. So we know one scenario, okay, that E should come before Q, right? Now over here again, if we compare next two words, the next two words are QA and QE. Okay, so in QA and QE, notice that the first letter is Q, so it is common, which means we cannot identify much information from that. But the second letter is A and E, which means we can determine that at any given scenario A will always come before E. So we can notify that, we can also create a scenario like that, that A will always come before E. And over here I am denoting this relation by an arrow, which indicates that at any given moment E should always come before Q, because it is on the beginning end of the arrow, and the where it is pointing to should comes later. And again we will compare these two words QE and RC. So if we compare these two words, we can identify that, okay, Q should come before R. So we can also denote that relationship, that Q will become will be before R, right? And over here now we have these three relations. So based on these three relations, we can actually establish something over here, that we can establish that A will always come before E, and E will always come before Q, and Q will always come before R. So one of the sequence that we can return over here is that A, E, Q, R. Okay, so this is one of the sequence that we have to maintain at any given cost, because we are given these conditions based on the words that were given. But the thing is, will this be our answer? And actually this will not be our answer. And the reason this will not be our answer is because over here we are given this particular line that we need to return a string of unique letters from this words in the new alien language, that is lexicographically increasing order. But the thing is, over here if we look the original input, in the original input we actually have one more unique character that we are missing, and that particular unique character is, so we already took care of E, we took care of A, we took care of Q, A, Q, E, R, all of this we took care of, but C, the letter C, we did not take care of it. And the thing is, over here, based on whatever the input that we were given originally, we cannot determine the position of C. But the thing is, we know that C is also a unique character. And the only thing we know about the positioning is that for these four characters, we can define some positioning like this. For C, we cannot determine any positioning, but the thing is, it has to be part of the answer as well. And that is why we are told that there could be multiple solutions and we need to return any of them. So in this scenario, this could also be a solution where A, E, Q, R and C we are placed at the end. Or this could also be a solution where A, we put C somewhere in the middle, and E, Q, R is also placed like that. The important thing is that we need to maintain this order. As long as we are maintaining this order, because this C is one of those unique letters where we cannot find the dependency for that. So we will need to take care of it as well, and this is a very important detail that lot of other videos have missed out, and that is why it took me a lot of time to make this video. I want to make sure that I go through it completely. Now let's take one more example from the given input, and we will again try to find that what should be the answer for that. So in the given input, we are given the following words. These are the words that we are given in the alien dictionary, right? And our aim is to find that what should be the answer in this case. Well, the first thing is that what we are going to need in order to generate the solution. In order to generate the solution, we are going to need two things. We are going to need list of all the unique characters that exist, and second thing we are going to need is what are the dependency on all between characters, and based on these two things we will try to generate some sort of order or some sort of pair. And also remember that we will have to consider the scenarios where we could find invalid strings as well. So I'll be explaining that in this example. So over here, if we see the list of unique characters, the unique characters are W, R, T, F, E. Okay, these are all the unique characters that we can find in this particular input. Okay, now let's start making dependencies. Now in order to make dependencies at any given moment, we will have to compare two adjacent words, and we are going to find first differing character, and based on the differing character we are going to establish some dependency. So first of all, the first two words we are going to compare are WRT and WRF. Okay, in this case W is common, R is common, which means that first differing character is T and F, and we already know that these words are sorted. So because they are sorted, we can determine that T should come before F. Okay, we already know that. This is good. Now what are the next two words? Next two words, and we are done with this WRT. The next two words are WRF and ER. Okay, so WRF and ER. Now in this case, what is the first differing word? Well, the first differing word is first letter by itself, W and E, which means we can make another dependency that W should always come before E. Now we can ignore this. Again, we compare next two words. So ER and ETT. So over here, what is the first so EE is common. The first differing letter is R and T, which means that R should come before T. Next one is ETT and RFTT. So over here the first differing character is E and R, so we can also mention that E should always come before R. Okay, now we have these four dependencies for these 5 unique characters. Now let's try to create a dependency tree from this given input. So if we see, we can clearly see that okay, W is dependent on E, and E, so W comes before E, then E comes before R. Okay, then for R comes before T, and T comes before F. So this becomes all the dependencies, and if we notice all the unique characters, they are already part of these dependencies, so we are good. We don't need to do anything more over here. Now if we make that what should be the order of letters, the order of letters in this case would be WERTF, and this would be the correct solution. Now notice that in order to generate the correct solution, what we had to do is we had to find all the unique characters, all the dependencies. Once we had all the dependencies, we actually had to iterate over all the dependencies, see that which dependencies are interconnected. Based on their interconnection, we actually had to generate this order. And in order to do that, we are actually using graph theory. And how we are using graph theory is basically all the unique characters in this case are actually nodes, and all of these dependencies are actually edges between those nodes, and those edges can be represented as in some form of adjacency list in some sort of hash map, and then we will need to iterate over all of the entire graph, and then at any moment we will have to go through the graph and find the solution, that what should be the order in which we are able to iterate over all the unique characters, which means that all the nodes inside the graph, and we need to generate this order of pairs. And if we are able to successfully generate this order of pair, we will return whatever we find, and if for somehow we find out that the input is invalid, we will have to take care of that scenario as well. So first let's take a couple of examples where we can find that the input could be invalid. Now, based on the English language, we know that at any given moment, if there are two words present, W1 and W2, and we know that any single word, so suppose W1 is actually prefix of this W2, if that is the case, then W1 should always come before in the dictionary than W2. Let's take it by an example. Suppose we are given two words like bat and Batman. If we are given two words like this, so if we start comparing these two words and see that what should be their order, we check that okay, B is common, A is common, T is common, right? Now over here, this actually ends. There is actually an empty list. There is nothing over here. While over here, there are still some values. So if that is the case, we can determine that this W1 is actually prefix of this W2, because these three characters are also present over here. And in that scenario, this W1 should always come before W2. At any given moment, we identify that this particular character is not present in correct manner, and suppose we are given an input like this, that Batman and bat. If we at any moment encounter this scenario, we can immediately return false, because, or we can immediately return an empty string, because this is a wrong ordering. So this is one of the failed scenarios where we cannot do anything, right? So this is very important to understand, and we will have to take care of this in our solution. The second thing that will not work is that at any given moment, suppose we are given list of words, suppose the words are like X, A, B, X. Suppose we are given list of words like this, and what this means is that the first letter X should always come before A. Okay, so based on these two, we can establish this dependency. Based on these two, we can also establish that A should always come before B. Okay, and over here, the next thing is that B and X, which means that what this is saying, that B should always come before X. So if you notice over here, that we are actually stuck inside a cycle, that X needs to come before A needs to come before B, and B needs to come before X. So at any moment in our graph, whenever we are traversing over all these unique characters and dependencies, at any moment we encounter that okay, there exists a loop, and if we detect that there is a loop from any particular node, then we can return false immediately, or we can say that okay, this is an invalid case where the string actually doesn't exist, and we will need to break out of the loop. Suppose we are given a custom example like this, words, and we are told that all of these words, they are lexicographically sorted in the alien dictionary, and now we need to return the order of words of all the unique characters that we can find. So what should be the approach? Well, in order to do that, we are going to need two things. First thing we are going to need is all the list of all the unique words or all the unique characters, and we are also going to need the entire dependency between any two letters, that which should come first and which should come later, right? So let's start working on it. So first of all, we have B and A. Okay, so we will just add list of unique letters B and A, and second word is BY, which means that first differing characters A and Y. So we can establish a dependency like this, that A should come always before Y. Okay, now again moving forward with next two values. So over here, the first differing character is B and A, which means that B should always come before A. And also I forgot to add one more unique character Y over here, right? Now this B should come before this A. So we will add that to our dependency list as well, that B should come before A, right? So this is one dependency, and over here we have the unique character D, so we will add the unique character D as well. Now we have this another word, these two words, and in these two words A is common, which means that D and L are differing characters. So first of all we will add the word L over here, and over here we have this D, right? So we know that D at any given location will come before L. Okay, so we'll just mention that. Now over here we have one more unique character T, so I'll also mention that. Now the next two words are these two words. Over here the A is common, L and I are different, and also we have one more unique character I. Now we know that there is a dependency between L to I, so we will also mention that L should come before I. Now the next two words are AI and AIR. Now notice over here that this AI is actually prefix of this AIR, right? Which means that this AI will always come before this word AIR. But we cannot determine anything regarding this R, because this R by itself, it has no other thing to compare its result with. Which means that though we have a unique word, we don't know that what is the intention for that particular word is. And now let's see that in the dependency list that we have created, amongst these unique words, what are all the words that we are able to find a pair for? So one pair we were able to find is for this one, this BAY. Let me just draw everything in same color. So BAY, this is one pair, which means we know that at any given moment this BAY order has to be maintained. Like B always has to come before A and Y. And same goes for this DLI, that D always has to come before L, and L always has to come before I. But in the list of unique characters, we are given this R and T as well, that are not represented by any dependency, which means we can say that this R and this T, they are unique characters by themselves, which does not have any sort of dependency, right? So if we want to see that what could be the potential different pairs we can make over here, well, there could be bunch of different results. Like there can be so many different permutations and combinations. Let me just give you a few of them. Like most simple one would be BAY DLI RT. So this is one combination where notice that we are just maintaining the entire order. Now second combination could be B D A L Y I R T. Now notice over here that at any given moment we need to make sure that these two orders are met up. So B is always coming before A and A is always coming before Y. So that is satisfied. Over here D is always coming before L and L is also coming before I. So that is also satisfied. This RT, they don't have any dependency, so it doesn't matter. We could have some pair like this, that B R T D A Y L I. This is also a valid pair, because notice that this B A and Y, this is maintained, this D L and I, this is also maintained, and this position of R and T doesn't matter. So there can be bunch of different options that we can choose from, and I'm just showing you that these are the different results we can have, right? Because we need to take care of unique characters as well, so don't forget the unique characters, they are really important. Now what should be the approach in this case? Well, one approach is actually quite simple. Because we know that we have unique characters, we have the dependency, we can choose some data structure like hash map. We can iterate over at any point. Whenever we identify the dependency, we can iterate over the entire hash map. We can, from any point, we will try to see that whether it has any dependency or not. If it has dependency, we will go to that dependency, we will try to iterate over those values, and we will try to generate the order list, right? So let's see that how it can work. Suppose we create a hash set like suppose we create a hash map like this. Okay, suppose this is our hash map, and based on these dependencies we know something, that we know that okay, in order for us to put down this B, we know that A has to come after B, which means A has dependency on B, right? We will mention it over here. Now for this A has to come before Y, so A has to come before Y. Now for this y, we don't have any dependency, so we'll just leave this value as blank. Now for this particular d has to come before l, right? So we'll just mention l over here. Now this l has to come before I, so we'll just mention I over here. For this I, we don't have any dependency, so we are good. And same goes for this t and r, that we don't have any dependency, so we are good. Now since we have this dependency tree, let's see that what would be the approach we can take over here. So in this scenario, suppose if we want to calculate that what would be one of those ordering pair, what we can do is we will start traversing through all of these values, all of these unique characters. And remember that this is hash map. So in hash map, we are treating these as key values, and these are actually values. So in the keys, we are mentioning all the unique characters. In the value, we are mentioning all the dependencies. Now over here, we will start iterating at this b. So first I'll just mark b as that we are iterating over it, right? Now from this b, we identify that, okay, we need to have a before b. So again, we go to a, because we will have to check all the dependencies, right? We cannot just put any letter randomly any place, right? Because this b has some dependency, so we will have to go over that. Now this a has actually dependency on y. So again, we'll go to y and we'll just mark a as being as part of being visiting. And over here we reach at this y don't have any dependency, so we are at this y. Now notice that we are actually traversing this graph in DFS manner, depth first search manner, right? And in depth first search, at this y, we identify that, okay, this y does not have any dependency, so we can just put y to our order list. So we can just put y to our order list. Now from this y, we will do a backtrack. We'll again come back to a. Again, we will do a backtrack. Again, we will come back to b, and then we would be done with this b, right? That, okay, we are done with this. Now again, we ignore all of these. Now we start with this second position. Now in the second position, first we determine that whether we have calculated this value already or not. So since a is already calculated over here, so we ignore that. So we can ignore the second case. Again, we check that whether this y we need to calculate it or not, but y we have already calculated, so we can ignore this, right? So we'll ignore this, and now we'll move on towards this d. Now do you see any problem with this one? Well, definitely we are seeing a problem with this one, and the problem is that over here the dependency is like this, that b has to come before a and a has to come before y in order for us to generate the dependency order. But over here, when we started traversing, the actual dependencies we are getting is actually in reverse order. You see that y comes before a and a is coming before b. So one way we can do it is that we can start traversing like this one, that over here we again come to this d. For this d, we find a dependency as l. For this l, we find a dependency at I. For I we don't find anything, so we'll just put I over here. Then we backtrack, so again we put l over here, and then again we backtrack, and then we will put d over here, and then we come to this t, like this I, this l, and this has already been done, so we ignore that. We come to this t does not have any dependency, we put it there. I has already been processed, and we reach at over here at r. Now this order list we got is actually correct, but in reverse order, because the dependency should be like b a y, and this should be d l I, but over here it's d l I in reverse order, and same goes for b a y. So what we'll have to do is when we calculate the answer, we will have to return the reverse of this answer, and that would actually satisfy these dependencies. So that is one way of doing it, right? And there is also another way of doing it, and the better way is that when we are actually creating this hash map, we can actually do something different. Previously in the hash map, what we are doing is that over here we had a key as all the unique characters, and as the value we had these dependencies exactly as they were mentioned, that for this particular b it is dependent on a, for this particular a it is dependent on y. But the thing is, that is not true. The actual true thing is that actually this y, the position of y should be dependent on a, that y cannot be present unless there exists an a value before that. If we start, so if we rather than storing the dependency on value that is taking care of the value that comes after it, if we start taking care in reverse order. So let me show you what I mean by that. So suppose if we have a hash map like this, and over here in the value we actually present at any given value what should be the previous value that has to be present in order for us to reach at that particular value. So what that would do is that if we want to calculate this b, we don't need to basically have any value, right? So over here we will leave this as blank, that for b we don't have any dependency. But for this particular a, we actually have dependency on b, that b has to be there in order for us to process this a. So we will put a dependency over here saying that okay, b needs to be there for us to calculate this value a. Same goes for y, that a needs to be there in order for us to calculate this value y. Again we reach at this d, and for the d we don't have any dependency, so we'll just leave it blank. But for this particular l, again we will have to have a d over here, so we'll put a d over here. For this t we don't have any dependency, so we can leave it blank. For this particular I, we actually have to have an L before that, so we'll put a dependency over here. And for this R, we don't have any dependency, so we'll leave it blank, right? So this is the table this is the hash map that we work with. And over here, now let's try to iterate over this hash map. Essentially our aim is to iterate over this entire hash map. Identify that at any point, if you are inside the DFS function, you are not finding the repeated character. So that is now item number 1. Second thing to make sure is that you go through all the characters and you start building up the order list. So over here we will get, we initially start at B, and at B we don't have any child, so we are good to put B over here. Now next, and we can mark that B is already done. Now we are at this A. So for A, we need to check that whether B is done or not. B, we check over here, B is already done, so we are good, which means that we can put A over here. So we'll put A over here. Again, we will mark A as being done. Again, we are at this Y, we check that okay, Y has dependency on A. So we check okay, A is already done, so we can put Y over here as well. Now we are at this D. So D does not have any dependency, so we can just simply put D over here and we can just mark this as done. Again from L we check for D, D is already marked, so we put L over here. T does not have any dependence and we mark L, T does not have any dependency, so we mark T is done, we can put it over here. Now this I has dependency on L, L we have already marked that it is done, which means we can complete this I as well. And for this particular R, it does not have any dependency, so we can put it over here. Now if you notice this scenario, we are actually fulfilling both of these dependencies, and notice that this B comes before A and comes before Y, so we are good with this dependency. This D comes before L and I, so we are also good with the second dependency as well. And this T and R, they were actually separate values, so it doesn't matter wherever we put them, as long as they are there, it fulfills our purpose. And this is the actual solution that we need to take care of, that where initially we will iterate over all the words, we will create all the unique characters. Based on the unique characters, we will create the dependency list. Based on the dependency list, we can actually create a hash map that we are going to use to traverse as a graph. But the thing is, rather than traversing the original hash map, we can actually create a reverse list of dependencies, and we can iterate over that just once using DFS or BFS, anything, but we are going to use DFS because I want to master DFS for myself, and that would be our solution. So it took me a lot of time to come up with this solution. It took me a lot of time to understand this problem. Okay, let's calculate time and space complexity for this problem. So the time complexity for this one is going to be big O of C, where C is actually total number of characters that are given in this original input words. Because notice that there are actually three parts of this problem. The first part is that we need to find all the unique characters. Like in order for us to generate all the unique characters, we will have to iterate over all the characters that are given in the original input words. So that is one part. Now second part is that we need to create a dependency, and in order to generate the dependency, again we will have to traverse all the words. And the third part is that we will have to so we are generating some sort of hash map, and inside the hash map we will have to iterate over all the values inside the present hash map. So at any given moment, the maximum work we are doing is iterating over the sum of all the characters that are given inside this words. So that is why that would be the time complexity. And if we want to calculate the space complexity would actually depend on the number of unique characters. So suppose that in English language, the number of unique characters maximum we can have is only 26, right? And we are also told that for this alien language, the maximum number of unique characters we can have is also going to be 26. So space complexity actually has a finite number, and there is only so much it can grow. So we can treat space complexity to be big O of 1 or constant space complexity for this one, even for us to creating this additional hash map. The second thing is that suppose if we want to calculate based on the number of unique characters, there is also one equation where the space complexity would actually be big O of u plus whatever the u square or n, whatever the minimum value of this is. And let me know in the comments if you want me to explain the space complexity in a scenario where the number of unique characters are actually not finite and not 26. Like in this case it's 26, so I will just leave it as it is, but let me know if you want me to explain that. First of all, we are going to create our hash map, and we are going to actually create it outside of this alien order method that is given, because we want to use that hash map to our DFS method as well. So, and as a key we are going to use unique characters, and as a value we are going to use the dependency. So it would be list of characters, and we are going to name it reversed list, because essentially we are just reversing the adjacency list. Also we will create another hash map to essentially store the value of any parameter that we are already currently visiting inside our DFS method. And so we'll need to create an output of strings, so we can create a string builder variable. Now the first thing we need to do is find all the unique letters inside our given word string of words. Now this is done. Now we will have to find all the edges, and we will have to add the reverse edges to our reverse list hash map. Now at any given moment we need to check that whether the word 2 is actually prefix of word 1 or not. If that is the case, we can return false immediately, and we have found a terminating case where the given string of words is not valid. Okay, if that's not the case, we will find the first differing character between two words and add it to our hash map. And notice that we are actually adding the value to the second word's differential character. And the moment we find the first differing character, we can actually break out of that particular word. Now we are going to iterate over the reverse list hash map that we have created, and we are going to run our DFS function. Okay, for all the keys present inside the reverse list hash map, we are going to run the DFS function, and we are also going to check that at any given moment have we receiving the result as false. So we are just going to create a boolean variable result, and now we are going to call the DFS function, and we are going to provide the character inside the reverse list. And at any moment, if we identify that the result is for this result character is actually fault, we will return empty list immediately. Okay, now all we need to do is that once this DFS step runs, we should have our output inside the result. So we will have to check that whether all the unique characters have been taken care of or not. So we are going to check that whether the length of output, if that is less than the size of our list, if that is the case, we can return false immediately because we haven't taken care of all the unique values present. And if none of these cases happen, we will return whatever we find inside the output. Now the only thing we need to do is we will have to create the DFS method. Now first of all, we are going to check that whether the current character C we are checking, if we have already visited that or not. If we have already visited that, we are simply going to return false. If that's not the case, which means first we'll add the current character to our scene hash map, and we are going to mark the entry as false. So that way, whenever if we encounter the repeated value, it will always return false. Otherwise, by default, the value would be true. Okay, now for every single character inside the current, for the given character, we will iterate over inside the reverse adjacency list. And at any point, if we encounter the result false, we will return false immediately. If that is not the case, we will remove the entry from the scene hash map. So we'll set the entry as true, and inside our output string we will append the value. And for that particular character, we are going to return true. Okay, so I know this is a very long and too many lines of code. I'm going to put this in the comments. Let's try to run the code. Okay, seems like our solution is working. And also remember, I was talking to you that we will have to take care of all the unique characters. Here, let me show you an example. So suppose we only have two characters, H and P. If we are only given input like this, and we know that H comes before P, right? Which means that in the result we should be getting HP. So let's see that what, okay, so this is accepted, right? But now let's say that we have additional character HA and PB. Now over here we don't have any mechanism to measure this A and this B, so they become unique characters, right? And now let's try to run the code for this particular test case. So if we do that, you are going to see that A and B would be at weird locations. So over here, see, the important thing is in our output we are maintaining the order for this H and P, and that is what it matters. Like A and B over here in our output is actually behind this HP, while over here the A and B are actually at the beginning, and then there comes HP. So it doesn't matter as long as the order that is given in the input is maintained. And now let's try to submit this code, and oh wow, our solution is actually 99% faster than all the other solutions. And I used lot of help from the solutions tab from this LeetCode premium, because it took me a lot of time to understand this problem. So I'll be posting this in the comments, you can check it out from there. And hope you like the video. Hello friends, hope you are having a fantastic day today. So now we are going to solve an awesome lead code problem that has tons of practical use cases. We are going to solve a problem called cheapest flight within K stops, and all the travel companies and airlines uses the logic we are going to solve in this problem. So this is a really important and informative problem with lot of useful properties. So basically in the problem statement we are given n cities that are connected by some flights, and we are given an array called flights where we have three values. We have the source city, we have the destination city, and we have the price it takes to get from like the source city to the destination city, and we are given bunch of entries like this. Now we are also given three additional integer called source, destination, and k that defines that we want our travel to start from the source city, end at the destination city, and k is the maximum number of stops we are allowing ourselves to take. And our aim is to find the cheapest tickets that we can find within the constraint of given k stops from source to destination. And if we can find the cheapest ticket, that's great, we need to return that value. If we cannot find any tickets, then we need to return -1. So let's try to understand this problem with a real life example. So here I have given bunch of different values inside our flights array, and we also have three different values called source, destination, and k. Now we can see that every single entry inside this array contains three values, and we all know that this defines the source city, the destination city, and the price it takes to reach to that particular destination city. We are also being told that we are planning our journey from source city 0 and destination city 3. Now this 0 and 3 can be replaced by any real life values like New York and Paris, France, New Delhi, you name it. And we are saying that we want to take at most one stops, nothing more than that. And now let's try to see that what is the amount or what should be the answer in this case. So I have drawn the whole information that we have provided in this flights array in this beautiful graph like description. And now we can see that we are starting our travel from city number 0, and we need to reach to destination number 3. Now we can see that one route is that we go from 0 to 1, and then once we reach to stop number 1, this would be our first stop. And then from 1 we have to go to 3 because we are only allowing ourselves to only take just one stop. Now from 0 there are no other stops that we can take in order to reach to 3, so this is the only path that we are allowed to take within the given constraint. And the cost to reach to city number 3 in this case is going to be 100 plus 600, so in total 700, and this is what we need to return as the answer. Now say for an example, in the same scenario, instead of k being 1, if we are given the value k being 2 as allowed to be given. Now in this case, let's see the scenario. First stop we can take is that from 0 we can reach to city number 1. This is going to be our first path. Now from the city number 1 we have two options. One option is that we reach to city number 3, that gives us the answer that we can reach to the destination within $700. But the other option is that since we are allowed k to be 2, we can take one more intermediate city as a stop, and we decide to take a stop at city number 2. Now in order to reach to city number 2, it takes $100 plus $100, so $200 to reach to city number 2. And from city number 2 we also have a direct connection to city number 3, and that is also going to be adding the cost of 200. So it takes 200 to reach to city number 2 and plus 200 more to reach to city number 3, so in total it's going to be 400. So in this case the cheapest flight would be 400 that we can return as part of the answer if we are given our k to be 2. So this is what we need to return in this example. Now the first logic that comes to our mind is a very simple brute force approach, where logic is going to be quite straightforward, that we go through every single possibility of all the nodes that we can visit and all the edges that we can visit, and then try to see that what is going to be the cheapest price to reach to the city number 3. In order to do that, we can actually use the graph based representation of this given input flights array, and after converting it into the graph we can actually do like breadth first search or depth first search from any particular node for all the other subsequent nodes. So we are iterating over all the possible edges and recording the values. We can also use backtracking, recursion, you name it, in order to solve this problem. The thing is, that solution would be okay in terms of like coming up with just a solution to have. But the thing is, think of the real life scenario. We are dealing with hundreds or millions of cities, flights, and costs. So that's not a scalable solution. We need to find a better approach. And that's where a beautiful solution or algorithm that comes into the picture, and that is called Bellman-Ford algorithm. So now let's see that how can we utilize this algorithm to solve this problem. So once again, we are going to be using the same example to solve this problem using the Bellman-Ford algorithm. The logic is quite straightforward. We are actually going to be focusing on the only thing that for every single k iteration, how much time it takes to reach to any particular destination city and what is the cost associated with that. And in the end, for all the given k entries, we will keep on running this same process until we reach to the end that we are looking for. And then if we found any particular cost for the associated destination city, in this case we have value number 3, then we can return that. If that is not the case, then we can return -1. So let's try to understand the logic I'm suggesting to solve this problem. For that, we are actually going to be using some sort of placeholder values where we can store that how much time it took or how much money it took to reach to any particular destination city. For that, number one thing we need is to have an array called cost that defines that in order to reach to any particular destination city, what is the cost associated with this. Now the second layer of complexity in this case is value of k, because notice that in our one of the examples we saw, if we only have to make one stop, then we come up with a different cost. But if we are allowed to use two stops, then we are able to come up with a different stop or different cost. So once again, we are going to be using the same logic. And in order to justify the value of k, if we, in order apart from using this one, we will also have to use a temporary array for every single value of k. So now let's try to understand the logic I'm suggesting. Currently I have defined an array called cost, and we are going to be seeing that in order to reach to any particular destination city, what is the cost associated with this one. This is the number one thing. And second one is this temporary array would be reset for every single k value. And once we calculate that how much time and effort and money it took to reach to any particular destination city around any of the k iteration, then we are going to be copying this temporary array to this cost array and repeat the same process for the upcoming subsequent k values. Now in this case, let's say that for first we are going to be calculating that what would be the logic for k is equal to 1. Then we will see that what would be the logic for k is equal to 2. Okay, so let's stay with me. This is going to be pretty interesting to understand and learn the whole process. Now we don't know that how we can define that whether we have a city cost associated that is cheaper or not. In order to do that, what I'm suggesting is that initially I put the cost to the maximum value possible, and after putting the cost to the maximum value possible, whenever we find some value that is smaller than the current value, then we update that value, because it is in our benefit to update that the cost it takes to reach to that destination city. And now let's start our process. Now we know our source city is 0, so by default logically, in order to reach to city number 0, the cost has to be 0 because we are already there, that is our source city. So we are going to be checking first of all updating that value inside our array. So for city number 0, currently it takes maximum value to reach to that particular city, but we are going to be defining it as 0. Okay, and now we are starting our process. So we are going to go through edge by edge for every single array. We are going to be updating the temporary value for that kth element, and then temporary array is going to be flipped over to the cost, and then we are going to repeat the same process. So currently for the temporary array, we are going to take a copy from the cost for this first iteration. So this is 0 and all of these are max in order to reach to any particular city. Now first thing is that in order to reach to city number 1, it takes us $100. So we are going to be updating that information, that in order to reach to city number 1, it takes $100. But the thing is, first we are going to check that the source city that we are traveling from, that already has some value and it is not the maximum value. Because if any particular city has the maximum value, that means that that city is not reachable. So if the source city is not reachable, how can we reach the destination city from that source city? Now in this case, source is 0 and destination is 1 and the price is 100. So we already know that we can reach to the source city because this value is 0 inside the current array. So then we are going to be updating this 1 as 100 because it takes $100 to reach to that particular city. Next thing is, in order to reach to city number 2, it takes $100 from city number 1. But the thing is, in our original cost array, we cannot reach to city number 1. So once again, for this one, we should not be able to reach to city number 2 as well, because city number 1 is not reachable. So notice this is going to be for k is equal to 1, only one city. So we can only make one stop, so that is this stop. And if we, so that's it. So now next thing is, in order to reach to city number 0, the cost is 100 from source city 2. Once again, for 2 source city 2, we cannot reach inside the cost array, so we cannot update any value. And also in this case, this would not be updated because currently in order to reach to city number 0, the cost we have is 0 and this is 100. So why would we pay higher money if we already have a lower value? So this would not be used. Next value is, in order to reach to city number 3, it takes $600. The thing is, we cannot reach to city number 1. So currently, and notice that currently we are iterating over k is equal to 0 and we have maximum value of k is equal to 1. So we are going to be running this iteration twice. So currently for k is equal to 0, this one is from 1 to 3, it takes $600. But the thing is, we cannot reach 1, so we cannot reach 3. Once again, next iteration, we cannot reach any other city because 2 to 3 is 200, but we cannot reach 2, so we cannot reach 3. So these are also going to be blank. Now notice that after the first iteration, we only traveled one city, that was the immediate neighbor of this node number 0. And this is the whole point of this exercise, that every iteration we are going in like breadth manner for all the cities that we can iterate over, and we are updating the cost accordingly. Now for the next k iteration, we also need to update the value of this temporary value inside our current cost array. So first we will update this one. So this is going to be 0, 100, and then these two are going to be max value and max value. And once again, we are going to be starting with a blank temporary array, but we are going to take the copy of this cost array. So this is also going to be 0, 100, and then max value and max value. Now let's see the same iteration again. Now 0 to 1, 100, we already have this value stored, so we don't need to update. 1 to 2, 100. Now in this case, we are able to reach to city number 1 with 100 cost. So in order to reach to city number 2, the cost has to be 200. So we can update this value to be 200. And notice that this time we are iterating over for k is equal to 1. We initially started for k is equal to 0, and now we are going to keep on repeating the same process. Now next thing is 2 to 0, it takes 100, but we don't need to update that because in order to reach to 0, we already have the value as 0. Next one is 1 to 3 as 600. Currently, in order to reach to 1, we have the value 100. So we can reach to city number 3, and 1 to 3 is going to be 700. So we are going to updating the value as 700. And now next thing is 2 to 3 is 200, but we cannot reach 2 in this case because cost array is still showing 2 as maximum value, so we are not able to reach this one, so we are not going to be considering this edge. And next thing is, next would be the k is equal to 2, but the thing is, notice we only have k is equal to 1 as max. So the moment we are done with this one, we will break out of all the loops. And sorry, before this one, we are actually going to updating the temporary array to the cost array as well. So now inside our cost array, we will have a couple of more entries. So in order to reach to city number 2, it's going to be 200, and in order to reach to city number 3, it's going to be 700. Now after this one, once we end our loop, we are going to be checking our cost array. We are going to be seeing that if the destination city is 3, and if this value is not maximum, then whatever value is, we need to return this one. So our answer is going to be 700. And if we cannot return 700, like if the value would have been maximum, then we would have written -1. Now let's take one more example for k is equal to 2, just to solidify your understanding. Once again, 0 to 1 100, we already have updated this value. 1 to 2 100, we also have updated this value as 200. 2 to 0 as 100, we don't need to update this one because we have 0 as 0. 1 to 3 is 600, so this has also been updated. And next value is 2 to 3 is 200. So this value, we can see that we are able to reach to city number 2. That means we can reach to city number 3. The cost is going to be 200 plus 200 400, but the current maximum cost to reach to that particular city is 700. So we need to remove 700 with 400, because now we can reach to city number 3 with 400 cost. And now, since this is k is equal to 2, once we are done with our loop, we will update this value over here. So this becomes 400. And then in the end, if we have to return the answer, we can return 400. That after with k is equal to 2 stops, we can reach to city number 3 in 200 cost. So imagine, see how beautiful the solution is. And now I hope you understood that what we are trying to do over here. If we have to calculate the time and space complexity, it's quite obvious that for k times we will have to iterate over all the given edges that we currently have and all the given nodes that we currently have. So it's going to be k multiplied by the number of nodes and edges, so O multiplied by V. uh, so yeah, and this would be the time complexity. And if we see space complexity, we are using couple of arrays to store the values. This is going to be the temporary storage and this is going to be the constant storage, but both are dependent on the number of cities. So let's say if the number of cities are the number of nodes, so it's going to be big O of n, where n defines the number of nodes. And this is the whole solution. Now let's quickly see the coding solution for this one. So the coding solution is actually quite straightforward. First, we are going to initialize our cost array. Then we are going to be filling the cost array with the maximum value possible. Then we are going to define that in order to reach to source city, it takes us 0 amount. So we are going to mark it as 0. And then we are going to initialize our two loops. First loop is only going to run from 0 to k value, where we are going to be starting a temporary array, where that is going to be the clone of our cost array that we have created so far. Next, we are going to be iterating over every single edge. Now for this edge, first thing we are going to be doing is defining the value of u, v, and the cost to reach to that particular city, where u is the source city, v is the destination city, and cost defines that how much money it takes to reach to the destination city. The values are extracted from our flights input array. Next, first thing we are checking is that in the original cost array, if in order to reach to city u, that is the source city, is maximum value, that means we cannot reach source city in that kth iteration. So we need to continue that operation. If that is not the case and we are able to reach to the source city, then we are checking that in order to reach to the destination city v, what is the current cost we have. And if the current cost is actually greater than the cost we are able to achieve using the cost it takes to reach to city u plus the current cost for the based on the current edge, whichever is the smaller, we are going to be keeping that value inside our temporary array. And once we are done iterating over all the flights for that kth iteration, we are going to be copying the temporary array inside our cost array and repeat the same process for the next kth iteration. In the end, the answer is quite straightforward. We simply need to check that if the cost to reach to that particular destination city, if that is the maximum value possible, then we need to return -1. If that is not the case, whatever the cost value is, we can simply return this one. And this is the whole solution. Look how beautiful it looks. Now let's try to run the solution. Seems like it's working as expected. Let's submit this code. and our code runs beautiful. It beats almost 97% of all the users, which is pretty awesome. And I would be posting this solution inside our GitHub repository, so if you want, you can go ahead and check it out from there. Thank you. The LeetCode problem we are going to solve now is called climbing stairs. We can see that this one is an easy problem and also a very well-liked problem. The statement is quite straightforward, that we are trying to climb a staircase that currently has n steps to reach at the top. Now, each time we have the option to either climb one step at a time or two steps at a time. Now we need to determine that in how many distinct unique ways we can reach to the top of the staircase. So let's try to understand this with an example. Suppose we are only dealing with just one single step. How many distinct ways we can reach to the top? Well, obviously there is just one way we can reach to the top, by taking one step. So in this case we need to return 1 as the answer. Let's say for the same example, instead of 1, what if we have 2 steps and now we are trying to reach to the top? What are the distinct ways? So first is distinct ways, take one step and then again one step, and second distinct way is to take 2 steps directly. So in this case we need to return 2 as the answer, that these we have 2 distinct ways to reach to the top. Same way, if we have 3 distinct 3 steps, how many distinct ways we can reach to the top? Well, we can continue by taking just one step at a time. So that is going to be our path number 1. Second path, we take 2 steps and then we take one step. Or third path, we take one step and then we take 2 steps. So overall now we have 3 distinct ways to reach to the top. So this is what we need to return as part of the answer. Now let's try to understand the most common brute force approach to solve this problem. Well, the idea is quite straightforward. Let's say that we are currently dealing with 5 different stairs. Now at any given moment, starting from position 0, we have 2 options. First option is either we take one step, or the option is we take 2 steps. So let's make a decision tree based on that. Currently we are at step 0. What are the options we have? We can take one step and reach to step number 1, or we can take 2 steps and reach to step number 2. Same way, at 1 we can take one step and reach to step number 2, or we can reach to step number 3. Same way, we can reach to step number 3, or we can reach to step number 4, and over here we can reach to step number 4 and we can reach to step number 5. Now the moment we reach step number 5, this is one of the unique paths. So we will note this path down and keep on iterating with our possible choices. So once again over here we will have 2 choices, 4 and 5, and once again we will have here one more choice. But now notice that there is a big issue with this one. Why? Because at every single position we have 2 different ways to choose from, and whatever path we take, depending on that, we are once again going to be dealing with 2 more positions. So in this case, the time complexity is actually going to be 2 to the power of n, which is a very expensive time complexity, and we will have to find ways to do things smartly. So that's where the most beautiful concept of the entire computer science come into the place, and that is called dynamic programming. Now notice over here that we are doing bunch of repeated work for the same amount of thing that we are calculating. We are calculating that what are all going to be all the different options from 2, and same calculation we are doing it over here. We are calculating that what are going to be all the different options from 3, and same thing we are calculating over here. So why don't we just memorize or store the information that we have already calculated and use it whenever we need to use it sometime in the future? And that is the whole idea of dynamic programming. So in order to do that, or in order to achieve dynamic programming, we will have to understand 2 things. What is going to be the base case scenario, or the minimum starting point for us to understand or start building the solution, and second one is what is going to be the dynamic programming correlation amongst different parties. So first let's understand the base case. Well, base case is quite straightforward. Let's say that if we are given 0 steps, how many different ways we can reach to the 0 steps? So we can only have one distinct way to reach to the 0 step, because where we are not taking any steps. Let's say if we are only given one step, how many different ways we can reach to the top? We only have one way to reach to the top, that is by taking one step. So these 2 are going to be our base case scenario, where dp of 0 is going to be defined as 1, and dp of 1 is also going to be defined as 1. So now these are the most common entries that are always going to be true and that we can calculate very easily. Now let's understand that what is going to be the dynamic programming recurrence relationship between or any given two parties. So for that, let's try to understand the scenario. We are currently dealing with these 5 steps and we are trying to determine how many unique ways we can reach to step number 5. So the most simplest logic you can think of is that whenever you need to reach to step number 5, what are the ways to reach to step number 5? Well, one way is that either we reach to step number 4 and then take one step, or second way is that we either somehow reach to step number 3 and then take 2 steps. Now you must be thinking that there is one more way where we can take one step from step number 3 and then take one more step to step number 4. Well, we already covered this case when we first mentioned that whenever, like, all the different ways you can reach to step number 4 and then take one step. So overall we only have 2 unique ways to reach to step number 5, that is through step number 3 and step number 4. And once we are at either one of these locations, we are guaranteed to reach to step number 5. So all the ways we can reach to step number 3 are all the unique ways we can reach to step number 5. Same way, all the ways we can reach to step number 4 are all the ways we can reach to step number 5. And this is going to be sum of these 2 unique ways. So this is going to be our recurrence relation. Why? Because we have the liberty to choose from 1 or 2 steps, and if we do it like reversely, we can just calculate that, okay, we need to calculate all the ways to reach to step number 3 or step number 4 and do the sum, and that is going to be our recurrence relation. Based on that, we can actually create a mathematical formula that at any given moment dp of I is going to be dp of I minus 1 plus dp of I minus 2. And based on this equation, now we can solve all our problem very easily. Let's say that now we are trying to solve for the answer n is equal to 6. We already know that this is the formula we are going to use to solve this problem. On top of it, we already have the first 2 values being filled out. Why? Because dp of 0, 1, 2, 3, 4, 5, and then this is going to be the value number 6. Now for dp of 0, we already know it's 1, and dp of 1, we already know it's 1. So say based on this equation, dp of 2 is going to be 1 plus 1. So now we can notice that if we have to reach to step number 2, there are 2 unique ways to reach to step number 2, and same way has been proven by this equation as well. Same way for step number 3, the sum is going to be 1 plus 2. So we can do it 3. Same way step number 4, we can do sum of these 2 values, so it is going to be 5. For step number 5, the sum is going to be 5 plus 3, so it is going to be 8. And for step number 6, it's going to be 8 plus 5, so answer is going to be 13. So there are going to be 13 unique ways to reach to step number 6, and the solution becomes quite easy and simple. And notice what we just did is we first establish a base case, then we established that what is going to be the relationship, and then based on that we kept on populating further and further values. So even now if we have to calculate for n is equal to 100, you can do it very easily and very quickly. So logic is quite straightforward. Now we can do one more improvement over here. Because we are only dealing with 2 previous values, instead of using an entire array to store all the values, we can just have 2 variables, previous 1 and previous 2, and for every single value we can just resolve these values and keep on updating for subsequent current values. So we'll see this in code that how this can work, but basically this is the whole idea, and based on this you can solve this problem very easily and very quickly. If we see time complexity, it is going to be big O of n, and for space complexity, well, if you use a full array it would be big O of n, but if you just use couple of variables like this, it is going to be big O of 1. So now let's try to see the coding solution for this one. Now the coding solution is quite straightforward. First we are going to take care of the base cases, that if given n is equal to 0 or 1, we can simply return 1. If that is not the case, we are going to initialize 2 variables to keep track of the previous 2 steps values, and the initial values are going to be 1 and 1 for step 0 and step 1. Then we are going to iterate over the given loop starting from I is equal to 2 or from the 3rd step all the way up to the n. and for any particular current step, the number of ways we can climb up to that step is going to be sum of previous two elements. So we will add that, and then we will simply swap the values between previous two and previous one. So previous one is going to become the current value, and previous two is going to become the previous one value that we had before. And after we keep on updating that, in the end we can simply return previous one as the answer, and that would be the total number of ways to reach any particular nth step. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats 100% of all the other solutions, which is pretty awesome, and that is because this runs in 0 milliseconds. But anyways, this is a beautiful solution and a good introduction towards the dynamic programming. Hello friends, so now we are going to solve a very popular LeetCode problem called minimum cost to climbing stairs. This is the subsequent question to another popular LeetCode problem called just climbing stairs. So let's understand the problem statement. Basically, we are given an integer array called cost, where every single value inside this array represents the cost of to reach to that particular step in a staircase. Now, once you pay the cost, you can either climb one or two steps. The question is that we can either start from the very first step or the second step, or so the 0th index or the first index, and we need to return the minimum cost to reach to the top of the floor. So let's try to understand this with a couple of examples. First example is that let's say that we are given an input array like this that contains three entries, 10, 15 and 20. Now we can see in this case that if we take one jump straight to the 15, now again from this 15 we have two options. We can either take a jump that directly goes to 20, or we can take a jump that directly goes above 20. So basically we are able to reach to the top floor. So in this case, the answer is quite obvious that if we are able to reach to 15, we can reach to the top floor very easily without paying any extra cost. So 15 would be the minimum cost that we need to pay in order to reach to the top floor. Let's take one broader example. Now we can see that this staircase has 10 different entries, and every single step contains a different price. The idea would be, if we decide to take two jumps in this case, which would be the greedy approach, it wouldn't work because we would incur a cost that is 100. Rather than, it would make sense for us to take one jump at this position number 1 with cost 1, and then take two jumps. Now once again, when we are at this position, once again it would take sense to take two jumps, because once again the cost incurred would be 1, and once again taking two jumps. Now after taking two jumps, once again it would not be wise to take two jumps directly because we would be encountering cost 100. Rather than that, we can actually take one jump and incur this cost 1, and through this 1 we can also skip over this 100 and take two jumps and reach to 1. So in total we are only taking 6 jumps, with each jump costing us 1 unit. So in this case, the minimum cost we need to pay in order to reach to top would be 6. So this is what we need to return. So the very first approach that comes to our mind is a very simple brute force approach. The logic is quite straightforward, that we actually calculate every single possibility. So we calculate a possibility like this, then we start to calculate the possibility like this, that taking one jump and then two jumps and three jumps, and then we calculate the possibility like this, and then this, and then this, something like this. So overall, across all the possibilities, eventually we would find a pattern that contains the minimum cost. But this is a very inefficient approach. We can clearly see why, because we are doing repeated work lot of times in order to comprehend the solution. We can solve this problem in n square time using the brute force approach, but this is still very inefficient. So let's try to see a better approach there where we can actually solve this problem. So now to solve this problem, we are actually going to use the most beautiful thing in the computer science and one of my favorite topics, that is dynamic programming. Why we are choosing dynamic programming to solve this problem? Well, first let me give you a very clear logic. If we have to choose any particular value, we will have to make the decision based on the previously calculated values, and based on that we would be able to define that what is going to be the minimum cost to reach to this step. Now currently what I'm suggesting is that we use a bottom up approach. So we go from the very first entry to the very last entry, and at every single step we simply calculate that if we have to include this step, what is going to be the minimum cost associated with this step. And let me show you what I mean. So currently we have no choice but to calculate that what is going to be the minimum cost to reach to these two values, and it's quite straightforward. We can always directly make jump to this very first step or very second step. So we can create a dynamic programming array, and the purpose of this array is going to be that we will calculate that what is the minimum cost it takes to reach to any particular element. And we know that for sure the minimum cost is always going to be these two values for the first two entries, because we can either take one jump or two jump. So let's just mark these two. But now when we come to this position, we have two options. Either we take one jump at this step number 5 and then two jumps directly to step number 3, or we take one jump directly to this step number 1 and then take one jump over here. So if we have to calculate the dynamic programming of this value, so let's say that this is currently index position 2, so this is 0, 1 and 2. Okay, so the dynamic programming equation is going to be quite straightforward. That dynamic programming of 2 is simply going to be cost plus dp of 1, or cost of that this cost defines the current cost of this index. Okay, cost plus dp of 0. So in this case, and whichever is the minimum value, we will pick that. So this equation is going to give us a lot of interesting results and build our dynamic programming array. So let's try to see our solution for the minimum cost it takes to reach to this step with value number 10. One option is that we do cost plus dp of 1. We know that dp of 1, the value is 1, so this is going to be value 11. And second one is cost plus dp of 0, so this is going to be 15, and whichever is the smaller, we are going to pick this. Which means if we have to use this step 10, then the minimum amount of work we will have to do is going to be 11. There is no other option, so we will just fill that value up. Once again, with this value number 2, we are going to repeat the same operation, and basically the logic is once again going to be quite straightforward. That cost at 2 is going to be dependent on these two entries, so 2 plus 11 or 2 plus 1. So 2 plus 1 is 3, so obviously it makes sense for us to give the answer as 3 and not 11. So we'll mark this entry. And once again, this is the top position, so once again the top position, the value is 1. Now if we have to include this one or not to include this one, once again the logic is quite straightforward. We are going to compare the values of the previous two entries which we have already stored, and that is 3 and 11. So once again, if the total is going to be 4, that is the smallest entry we need. Now notice that we have the option to choose the minimum cost amongst these two entries. So whichever is the smaller value amongst these two is the one we are going to pick for the answer, because you can go to the top from this 2 step as well, and you can go to the top from this 1 step as well. So once again, the minimum of these two is going to be 3, so we are going to return 3 as the answer in this case. And this is the whole logic I'm suggesting to solve this problem. Now ideally, I created this dynamic programming array to solve this problem, but you actually don't need to have an entire array dedicated to solve this problem. You can actually just store all the entries in 2 variables, so you can also save so much time, so much space in terms of space complexity as well. Now let's try to calculate that what is going to be the time and space complexity for our optimal approach. Time complexity is going to be big of n, because we are iterating over the given input array just once. And space complexity, well, obviously if you decide to use a dynamic programming array, then it's going to be big of n, but if you just use 2 pointers, it can also be big of 1 as well. So now let's see the coding solution for this one. So the coding solution is quite straightforward. First, we are checking for 2 edge cases, that if the given input only contains 1 or 2 stairs, then we can simply return those values accordingly. If that is not the case, we are just simply using 2 variables, first and second, and we would be updating these 2 variables continuously. Now we are starting our loop starting from the third step, or I is equal to 2, to the very end of the given array. And we are simply doing a very simple calculation. we are checking that what is the current cost for the current step or current ith value we are at. For that we are defining a new value, and we are simply calculating that what is going to be the minimum value of the first or second plus the cost of the current value, cost of I. Then based on that we are updating the values of our first and second. So now our first value is going to become the second value we had, and our second value is going to become the current value we had, which is quite straightforward, quite simple to understand. And after the end of our loop we are simply checking that what is going to be the minimum value amongst first or second, and we can return that as the answer. So let's try to run our code. Seems like our solution is working as expected. Let's submit this code. And this is beautiful. We beat 100% of all the other solutions, and that's because this problem actually runs in 0 milliseconds. So no surprises there. But important thing is that look at the time complexity we are saving, or sorry, space complexity we are saving, where we are beating almost 90% of all the other solutions. So our solution is one of the best solutions on LeetCode. That's because we are using two variables. So once again, the solution of this code is present in our GitHub repository. Feel free to go ahead and check it out. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. The problem we are going to do today is actually asked in a lot of top tier IT companies, and if we look at the recent data, it has been asked in Amazon 20 times, Apple 8 times, Facebook 2 times, Google 6 times. So needless to say that this is a really important problem. So I hope you provide your utmost attention. This is the outline on how we are going to solve this and the things I'm going to cover in this video. So first we'll understand the problem statement. I will be creating a brute force solution. Then we will build an optimal solution with dynamic programming. And at the end, I'm going to show the Java code for this one. Basically, this is a LeetCode medium problem, but in my opinion, it should be a LeetCode easy problem because it's not very difficult to understand. But the thing is, its concept is really important. That helps you build the conceptual knowledge of dynamic programming, which you can use in bunch of different problems. And a lot of FAANG companies loves to ask this kind of questions. So if we understand the problem statement, basically we are a professional robber and we are planning to rob houses in each street. Now the thing is, the way houses are mentioned in the street is that every single house has some amount in that particular house. But the only condition we have is if we rob one house, we cannot rob the house that is exactly adjacent to it. So suppose we decide to rob this house. If we rob this house, which means that we cannot rob this house or this house, and we can again, if we want, we can again rob this one. So that option we have, and our aim is to maximize our profit. So basically we are given an input array nums that shows that for every single house how much amount of money is presented over there, and we need to see that what route can we take which maximizes our input or the amount of money we can steal, and we need to show that in the output. So let's try to understand this with an example. So basically over here we are given the values as 1, 2, 3 and 1. So notice that the maximum amount we can steal is basically if we go down this path. So if we start with the first house, and then notice, then we can't rob the second house, but then we rob the third house, and the sum of these two would actually become 4, and this would be our answer. So for the brute force, we are going to solve the same problem. Basically, one way to understand the brute force approach is that at every single position, initially we are at 0th location. So if we just make all the possible pairs which we can create where we can rob houses, basically that would be our solution. So let me show you how. So initially at 0th position, now we have two options. Either we can select the value number 1 or 2. So either we can select the first value or second value, and these are the subsequent values. Now at this position 1, we again have two options. Either we can rob the third house from here, or we can skip the third house and we can also rob the fourth house if we want. So the two choices we have over here is either we go down this path or we go down this path. And at this house number 2, we only have one option. We can't rob this 1 or we can't rob this 3, so we can only rob this 1. So the only choice over here we have is actually 1. And now we just do the sum of all the values. So for this path, the sum we would get is 4. For this particular path, the sum we would get is 2. I just put it in a box so it's easier to differentiate. And down this path, the maximum sum we can achieve is 3. So if we compare these three elements, we can clearly see that 4 is maximum, so we simply return 4. Now brute force solution works, but the problem with this one is that we need to create every single pair, and in order to generate pair, essentially at every single position we have two options, that whether we need to keep this value or we do not need to keep that value, and that eventually would bring a lot of different values in our graph and on the number of decisions we can make, which means that the time complexity for brute force approach would be, you guessed it correctly, 2 to the power of n, where n is basically whatever the number of inputs given over here. And you guessed it correctly. Also, I already gave it away, but we are going to use dynamic programming over here, and let me show you how we can use dynamic programming to solve this problem. We are going to use a custom example, and I have already mentioned it a bunch of times that it is really important to have your own custom examples. That shows that you can think outside of the box. So over here initially, we are at this position, value number 2. Okay, so what we can determine is that initially at this position, if we were given only one house, what is the maximum amount of value we can steal from this particular house? Of course, the answer is pretty simple. We can only steal whatever we are given, right? Because we are only given just one house. So initially at this point, suppose if we create an additional data structure that keeps the track of what is the maximum amount of money we can steal up for any element, then our decision making will become easier, and we would be able to choose that what path we want to take. So let me show you by an example. So initially at this position, value number 2, the maximum amount we can rob will only going to be 2, because there are no other values before that. So this is the maximum amount we can rob so far. Okay, now this at value number 4, the maximum amount we can rob is actually, up until this point, it's only 4, because we can't use 2 when we are robbing 4. If we choose to rob this second house, if we choose to rob this one, we can't use it. We can't basically use this first house. So we know that for the first two values, these are the maximum amounts we can rob. Now we are at this position number 3. So at this position number 3, we have two options. Choices are pretty simple. Either whatever the value maximum we have so far over here, which means that so far the maximum value we have is 4, or whatever the previous maximum value we had plus whatever value we currently are at. Because remember, if we decide to rob this house number 3, basically we still have the option to rob house number 2. We can't rob house number 4. So up until this value number 5, the maximum we can rob so far is actually 5. Why? Because we check that, okay, up until this point, what is the maximum that previous element has robbed? Basically, like one house before this house has robbed, and that maximum value is 2. So I can do 2 plus 3. So maximum I can rob up until this point is actually 5. So okay, we have this knowledge, and up until this value, the maximum we can rob is 4. Now let's forget about this one for now, because anyways at any given time we are only concerned with the house that are adjacent to each other. Now we are at this position number 9. So what is the maximum value we can rob up until this point 9? Well, the answer is quite simple. We check that, okay, what are the two values before this 9? So this is 5, which means that if we decide not to rob this house, the maximum we have robbed so far in this sub array is actually 5. But how do we decide that whether we want to keep this 9 or not? Well, we just need to apply the same logic. The house that is adjacent to 9, before that, what is the maximum amount we have found? So the maximum for that is 4, and we do 4 plus 9. So 4 plus 9 is 13, which means that up until this point, the maximum we can get, the amount is 13, which is definitely greater than 5. So it is in our interest to keep this pair so far. Now we can forget about this 4 because we already calculated its value over here. And now at this next value number 11, again we have two choices. Do we want to keep 11 or not? So again we do the same thing. We compare 11 with whatever value we have over here. We do, first of all, we do sum of 11 plus this 5. So we do 11 plus 5. Okay, this one is 16. So which is greater than 13, which means it is in our interest to keep the value 11. So again, we are going to have 16 over here. We can forget about this one because we already calculated its value. And yeah, so we are at, now the two choices we have is 16 and 13, and this value number 2, we need to check two items. So value before that, this is 16 and this one is 13. So we do 13 plus 2, 15. So far, if we decide to keep this value number 2 in our list of houses that we are planning to rob, the maximum value we can achieve so far is 15. But the thing is, we have already found a better option than this 15, and which is 16, where if we decide to rob these 3 houses, we will get the optimal answer. And notice that we were able to complete this whole iteration in just single we were able to complete this whole calculation in just a single loop, because we were keeping track of whatever the elements we have calculated so far, which is the exact use of dynamic programming. And we are not using more than one element at any given moment, which means that our solution is actually quite helpful and very perfect. So let's calculate the time and space complexity, and basically this would be the optimal solution. So time complexity, as you have guessed it correctly, it's actually big O of n, because we are completing everything in just one single iteration. We don't need to do multiple rounds of checks. And the space complexity we have is actually big O of 1. It's actually constant time, because notice that at any given moment, the maximum value we were keeping track of is just couple of elements. And we kept on updating our elements, that whatever we are keeping track of, which means that we are not using that much space. We are not creating an additional array to store all the values. Okay, let's create two elements. We'll name it rob1 and initialize it to 0, and we'll create a rob2. We'll also initialize it to 0, and we'll have another variable. We'll just name it max to keep track of maximum element that we have calculated so far. And now let's run a for loop. Inside the loop, first of all, we'll calculate that whether we have achieved the maximum value or not. So max would be whatever value we have at rob1 plus whatever value we are currently at. So this is one option, or whatever the value of rob2 we have, because notice that the rob2 element is actually right adjacent to this ith element. And now we need to update the values of rob1 and rob2. So rob1 will actually become whatever value of rob2 we had, because we are updating it every single iteration, and rob2 will actually become the maximum value we have found so far. And yeah, I think this should be our solution, and at the end we will return the max element. So let's try to run this code. Okay, our solution seems to be working. Let's try to submit it. Oh, okay, yeah, our solution is actually runs in 0 millisecond, and it's 100 times faster than all the other solutions. But the thing is, this is not true, because we are given a limited number of test cases. We are computing everything in just a constant time, so that's why it's showing us 100% faster. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important problem, house robber 2, and this is actually an extension of original house robber problem. I have already solved the house robber problem over here, so you can check out that video, and I highly recommend that you check out that video before coming on to this problem. Typically in any interview, this problem is actually going to be asked as a follow-up question after they have originally asked this house robber problem. And that is why if we see the number of companies that have asked this question recently, it's actually quite small compared to what we are used to seeing for the other companies. But the thing is, still Amazon and Google have asked this recently. Even Microsoft asked this just a little bit sometimes back, and also a few other companies have asked this. So this is a LeetCode medium problem, and basically the problem statement is saying that we are professional robber and we are planning to rob houses along a street. Now the catch over here is that all the houses in this given street are actually arranged in a circular fashion, and also there is one more constraint, that we cannot rob two houses that are adjacent to each other. If we rob two houses that are adjacent to each other, basically police is going to be called and we will be caught. So this is a constraint that we have to look into, and our motive is to collect or gain or rob as much money as possible without being caught. So let's try to see a pictorial representation. So basically all the houses in the street are actually placed like this. So suppose if we consider that this is our first house, actually the first house is also neighbor of the last house in the given street, because all the houses are stored in a circular fashion. And now since the houses are stored in a circular fashion, that is one more thing that we need to consider. And also we cannot rob two adjacent houses. So suppose if we decide to rob this house, we cannot rob this house or we cannot rob this house. So the first example we are given is the houses are placed like this, and these are the amount of money that is at each house. So basically, since there are only three houses, we can only rob one house, and we need to select the house with maximum money. So it's pretty simple over here, that if we select this house, we get the maximum money, and if we rob the house with value number 3, we can't rob these two houses because they are adjacent to each other. In the second example, the houses are stored like this: 1, 2, 3 and 1, and the most amount we can collect over here would be if we rob this house and this house. So in that case, the amount of money we would collect would be 4, and we won't be able to rob these two houses because they would be adjacent to each other. So we already know the brute force approach. Basically the brute force approach is to make every single pair and check out all the possibilities to see how we can find the answer. But the thing is, there is no point in exploring brute force approach over here. I'll directly go to the most optimal solution that we are going to achieve using dynamic programming, because this is an extension of house robber 1. If you want to get more information about the approach, you can check out that video first. So for the optimal solution, we are going to use a custom example, and this is very important to use custom examples because it shows that you can create test cases on your own, and this is a really good skill to have in actual computer world. So suppose the number of houses we are given over here are in this fashion, and let's try to draw them in a circular manner. Now basically we can use the same solution we were using in house robber 1, because remember in house robber 1 what we were doing, we were just simply going through whatever the input we had, and we were just keeping track of what is at any location, what is the maximum amount of money we can rob up until this element by checking the previous values. We are essentially going to do the same thing over here, but just in a little bit different manner, because in the house robber 1 problem we were considering the whole thing because they were all the houses were placed in a straight line, so we were able to consider them like that. The thing is, over here the additional constraint is that whatever the last amount or the last house is actually neighbor of the first house, which we can see over here that these two houses are neighbors of each other, which means that if we at any point decide to rob this house, we cannot rob this house, or vice versa, that if we decide to rob this house, first house, we need to make sure that we do not rob this house. So the answer is actually quite simple. Rather than treating this as a circular street, why don't we just run two functions? So basically during the first loop, during the first iteration, we are going to check the first sub problem, and let me show you what I mean. The additional constraint we have over here is that if we consider this house, it is guaranteed that we cannot use the last house, or if we use the last house, it is guaranteed that we cannot use the first house. So since we know that this condition exists, we are simply going to do calculation twice. In the first calculation, we are going to check between these houses that what is the maximum amount we can rob, and during the second loop we are going to check that amongst these houses what is the maximum amount we can rob, and then we just need to compare that what is the maximum value we have found across both the loops, and whatever the maximum value we find, we just we just submit it as our answer. So let's iterate over the entire problem. Okay, so these are the two loops that we are going to iterate over. So let's calculate the result for the first loop. So at the first position, the maximum amount we can rob so far is only going to be 1. And at the second house, the maximum amount we can rob is only going to be 2, because we cannot rob the first house. Now for the third house, we have two options. Either we keep whatever the value of 2 we have, or we keep the value of 1 plus the third house value, and we see that whatever is the maximum value amongst these two, we are going to keep that. So 1 plus 15 is going to be 16, and of course 16 is greater than 2, so we are going to say that up until this house number 3, the maximum amount we can rob is 16. Now if, we are at the fourth position. Now over here, the maximum amount we can rob is actually 2. We have two options. Either we can rob on 16 units, or we can do 2 plus whatever value at house number 4 we have. So 2 plus 11 is actually 13, which is less than 16. So even up until this point, the maximum amount we can rob is still going to remain 16 and not 13, because definitely 16 is greater value, so it is in our interest to keep this value 16. Now again we are at this position 3, and also notice that at any given location we are only considered with values that are of previous two houses that we have calculated over here. We don't need to consider all the values because we are already adding them up and we are only keeping the maximum values. So this works in our favor. So at value number 3, the maximum we can achieve is either 16 plus 3 or 16 by itself, which is this 16 or 16 plus 3. So of course 16 plus 3 is going to be greater, so we are going to store 19, and we don't care about these values anymore because we already have the latest values so far. Now at value number 6, the maximum we can find is going to be 16 plus 6 or 19. We need to select whatever is greater. So 16 plus 6 is 22. This is the greater value, so we are going to keep this and we don't care about 19. So we can see that at the end of this first loop, the maximum value we have found so far for this particular set of houses is 22. Now let's repeat the same process for the second loop. So in the second loop, for the first position, the maximum we can rob so far is 2. At the second house, the maximum we can rob is 15. Now over here, the maximum we can rob is either 2 plus 11, which is 13, or 15. So of course 15 is greater, so we are going to keep 15 over here. Now at this position number 3, we can either do 15 plus 3 or compare it with 15. So 15 plus 3 is 18, so we are going to keep 18 over here. Now at this position, we consider these two values. So either we do 15 plus 6, which is 21, or we check with 18. So 21 is greater, so of course we are going to keep this one. And now at this last position, we check that whether 21 or 18 plus 10. So of course 18 plus 10 is 28, so we are going to keep that, and we do not consider about 18. So after this entire loop, the maximum value we have found so far is 28, and the maximum value we had found over here was 22. So our job is pretty simple. We just need to see that whichever value is actually greater, we simply return that. And in this case, 28 is greater than 22, so 28 would be our answer, and we just return that value. This is a very good solution. We are building it on top of whatever we have solved for house robber 1, and because we are basically using the same solution, we are just changing the scope of up until what points we are using this solution. So just keep that in mind. And if we calculate the time and space complexity, the time complexity for this one is going to be big O of 2n, because we are running two loops, 0 to n minus 1 and 1 to n. So if we generically mention this, it actually becomes big O of n. And if we calculate the space complexity would be big O of 1, because we are, apart from storing couple of parameters, we are not using any additional space. So that's why we are able to run this in a constant time. Constant space. Okay, let's start creating parameters. So we are going to need two parameters, rob1 and rob2, and we are going to initialize both to 0. We will also need two parameters to store two maximum values, so we'll name them max1 and max2, and max1 will initialize it to the 0th house, and max2 we can actually initialize it to 0, because we are not going to consider the first house, and we are keeping the max1 as 0 because in case we are given the condition where we only have one input, so we can simply return that. Now let's run a for loop starting from the first house, so I equal to 0 to I is less than length minus 1, I plus plus. Okay, over here we are going to calculate max1. So max1 would be maximum value amongst rob1 plus the current number we are at, or the value of rob2. And we also need to update the value of rob1 and rob2. So rob1 would actually become rob2, and rob2 will become the maximum value we have found so far. Now once we are done with this loop, we need to reset the values of rob1 equal to 0 and rob2 equal to 0, because we are going to use them again in the second loop. And we are going to create another for loop, I equal to 1, and we are going to set up I is less than, so nums dot length I'll plus plus. Okay, and essentially we are going to use the same conditions. By the way, this would be max1. We are going to use the same condition, so we can just reuse the code. And we are going to, rather than calculating max 1, we would be calculating max 2. So let's do that. And after the second loop, we simply need to return whatever the maximum value we have found amongst max 1 and max 2. And this should be the solution. Now notice that I am running two loops over here. But the thing is, an efficient way to do this is to create a function, and function would intake the parameters like start and end value, and you can just repeat this process. So that would be an efficient way to do this code as well. Let's try to run this. Okay, seems like our solution is working. Let's try to submit the code. Hello friends, we are not employed by a FAANG company, so let's not stop LeetCode until we get there. Today we are going to do longest palindromic substring LeetCode problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Google, Adobe, Apple, Bloomberg, Goldman Sachs, TikTok, Uber, ByteDance, LinkedIn, Tesla, and eBay. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and also one of the very well-liked problems on LeetCode. Basically, we are given a string S and we need to return the longest palindromic substring that is present inside this original given string S. So in order to understand this problem, first of all, we'll have to identify that what is a palindromic string. And a palindromic string is basically, as the name suggests, any string that forms a palindrome. And we know that palindrome is any string where if you read it from left to right or right to left, the number of sequences is same. So in this case, ABA is actually an example of a palindromic string. Also ABBA is also an example of palindromic string, because in either of these two cases, whatever side you decide to move along, the number of character occurrences remains the same. So that's why they are palindrome. And now our aim is to find the longest palindromic substring inside this given original string S. This is not a very good example to understand, so let me create a custom example. In this case, we need to find that what is the longest palindromic substring. So if we see the string S by itself, it's actually not a palindrome. But if we see these three values A, B, A, and we get rid of this B and D, we can actually create a palindrome, which means in this case, we can return the answer as A, B, A to be longest palindromic substring that is present inside this given string S. And this is exactly what we need to return. So now let's see that what would be the different approaches to solve this problem. In order to understand the brute force way, we'll have to identify that what is the thing we need. We need the longest palindromic substring that is present inside this original given string S. So the aim is that we need to find a substring. So why don't we just use the brute force method and we find every single possible substring that we can make out of this given example S. So we can make bunch of different substrings. Let me just draw some substrings over here. So these are some of the substrings that we are able to generate from this original given string S. Now our aim is to find that what is the palindromic substring. If the substring is palindromic, we will find its length and then we will try to find the longest palindromic substring in that way. So we can clearly see that in this case, this ABA is going to be the answer for this longest palindromic substring, and eventually we would be able to find the solution using the brute force method. But what is the issue with this? Like, issue is actually pretty evident that even for this 4-character string, we actually had to create bunch of different substrings, and out of all of those substrings, we will have to find some effort and resources to find that what is the longest palindromic substring. So that is just waste of time and energy. If we see the time complexity, in this case, the time complexity is actually going to be big O of n cube. Why m cube? Because it takes n square time just to create these substrings. And after doing that, we will also have to identify that whether those given strings are actually palindromic substrings or not, and which is the longest amongst all of them. So that also takes n time. So that's why the overall we can write it as big O of n cube time complexity. So let's see that what would be the better approach to solve this problem. Well, before we come to the optimal solution, first let's build some intuition behind achieving that optimal solution. The idea is that we need to find the longest palindromic substring. Now there are two possibilities. We could have an odd number of string that is a palindrome, or we could have an even number of string that is actually a palindrome. Now in each cases, the middle value is actually providing some interesting results. And the thing is that in both the cases, the palindromes are actually built around these middle values. How? Let me quickly show it to you. Well, if we just take this madam for an example, over here we can actually conclude this D to be a substring in its own, and because this is a single character substring, we can actually conclude this to be a palindrome as well, because if we read from this left direction or right direction, in each cases we are going to get the same result. Now if we add these two A's to this D, we will also get the substring that looks like this A, D, A. Now in each cases this D remains common, but the left value and the right value, because they both are same, we can conclude this string to be a palindrome as well. Now again, if we repeat the same process and we add this M and M, again because they both are same and we are adding at the corners, so if we add them we will get a value that looks like this. Now this D originally was a palindrome. After adding this AA, it remained palindrome because both character had the same value. And again after adding this MM, again the whole thing remained the palindrome because they both had the same value. Now in this case, if I extend and if I add a value that looks like X and Y over here, so this X and Y is actually not same, so this whole thing will not be a palindrome, but this middle portion will actually be a palindrome. And in this case, because we had odd number of characters that are forming a character, we actually have just one value that we can consider as middle value, and all the other values from this middle value are actually just a bunch of set of characters who both have same values. Let's take an example for this even number case. Now in this case, actually we have two middle values, and the two middle values are BB. Now if we were to consider this BB, this is actually a palindrome in itself, because again by definition, even if we go from left or right, in each cases we are reading the same value. Now again this AA, both are same value and they are actually same value that corners our original given middle values. So if we form a value that looks like this BB was already a palindrome, and the two values we added, they are also same. So because they are same, this whole thing actually becomes a palindrome. And again, just like this case, if we add an X and Y over here, this whole thing will not be a palindrome, only this ABBA would remain palindrome. So now after knowing this solution, actually it becomes really easy for us to identify that what would be the optimal solution. Suppose this is the example that we are given and we are trying to find the optimal solution for that. So what we are going to do is we are actually going to expand on the corners, and we are trying to see that whether the left and right value of any middle value, if they are actually same or not. If they are same, we can consider the whole part to be part of any palindrome. If they are not same, then we will move on to the next value and start doing the same process. Now there could be two possibilities. We could have an odd length palindrome where we will only have one middle value, or we could have an even length palindrome where we will actually have two middle values. So in each cases we will have to take care of them. So I'll be showing you the odd example first, and then I'll show you the even example. And basically it's slightly different idea, and I'll just show you when we go there. So first of all, we are going to take this value X. Now we are going to expand upon the corners. So we are going to see that whether this X could be the middle of a longest palindromic substring. If that is the case, then we will expand upon this X. So we will try to see its left value and right value. The left value is actually null and right value is actually M. Now this left and right, they are not same, and also this middle value is actually not same with this right value, and it's also not same with this left value, which means in each cases this X is actually not part of the middle of longest palindromic substring. So we will get rid of it and we will move on to the next value. Now we are at this value number M. Again we try to see the what is the left and right value. Left is actually X, right is actually A. Again they both are not same, and none of them are same with this M. So which means that now we will move on to the next value. Next value is actually A. Again the left value is M, right value is D. Nothing is same, so we will move on to the next value because this is also not a part of the palindrome. Now we are at this position number D. Now if we take the left and right value, the left value is actually A and the right value is also actually A. So because this left and right value is same, this D could be a middle of any palindrome. We don't know if it is the longest palindromic substring or not. Now the longest palindromic substring that we have found so far is actually of length 1. Why length 1? Because any character in itself is also a palindrome, remember that. So that's why now we have this new substring that looks like this ABA. This is also a palindrome, and we will try to see that whether it is longer than whatever the existing palindrome we have, which is true that this ABA is actually longer. So we will have to update the value of this AB over here, saying that this is the longest palindrome we have found so far. We will keep on expanding on its corner. So far the values we have is ABA. Again, we will move on the left and right pointer. So this is M and this is also M. So because they both are same, again we can consider this to be a palindrome. And the previous longest palindromic substring we had was ABA, but this is actually greater than that. So we'll update its value. And now the longest palindromic substring we have found so far is Madam, MADAM. Now again we will go and repeat the same process. Repeat the same process. Over here we will have the value y, and over here we will have the value x. So these two are not same. So because these two are not same, now we are no longer forming a palindrome. So we will have to get out of it. So we will just move on to the next value. And if we move on to the next value is actually a. So again this a, the left value is d and right value is m. So this is not a palindrome. We will go back to m. M is also not part of any middle of any palindrome, and this y is also not part of any middle of the palindrome. So now we are done for our example so far. And in this case, whatever the answer we have found over here for the longest palindromic substring, which is MADAM, we will return this as our answer, and this solution would work as expected. Now this was the case of odd number of palindrome that is being the longest. Let's see the even number of palindrome. So in this case, again we are going to repeat the same process. First of all, we'll take this x, we take the left and right value. Again we don't find anything interesting, so we'll move on to the next value. Now next value is a. Again we check left and again we check right. We don't find anything, right? So we'll move on to the next value. Now again we are at this position number b. Now we are at this position number b. If we check the left value, we find a, but if we check the right value, we actually find another b. So because these two are same, actually the combination of these two b's could be the middle of the longest palindromic substring, and that is going to be true in this case. So we are going to expand on a little bit differently now. Now we are going to have this bb as the middle of the longest palindromic substring we have found so far, and we will repeat the same process. So we will try to find that whether what are the left and right values. So left value is a and right value is also a. So again this is a b b a, because these two are same, and this middle portion we are just consider it to be the middle. So this is also forming a palindrome, and the longest palindromic substring we had so far was only of length 1, and then when we found this bb, it become of length 2, and now we have this ABBA. So this is of length 4. So because this is of length 4, we will have to update the longest palindromic substring we have found so far to be ABBA. Now again we will repeat the same process. So if we again go left and right, this is actually x and this is y. So now these two are not same. Because these two are not same, so now we will just get out of it. We will again check with this a and y. We don't find any palindrome, and we would be done with this one. So in this case, we would return this ABBA as part of our answer, and that would be the final solution. So the time complexity in this case is actually going to be big O of n square. Now why n square? Because we will have to iterate over every single value to see that whether that is the middle of the longest palindromic substring or not. That takes n time, and if we will have to iterate over all the values on the left and right side to see that whether it's the longest palindromic substring or not, which means that in the worst case scenario, we might have to iterate over n square times to find the answer. In terms of space complexity, we might have to keep track of big O of n characters at any given moment, where n is the number of characters present inside the string. Now this is actually a much bigger improvement compared to our brute force approach, which had the time complexity of big O of n cube actually. And now let's move on to the coding. First of all, we are going to check some edge cases. If that is not the case, we are going to run a for loop across the given string. For the any value we are iterating over, we don't know that whether it is the middle of the longest palindromic substring of an even length or of an odd length. So at any given time, we are actually going to have two variables that call a function, where we are going to check that whether the odd length or even length palindromic substring, can it be the middle of any palindrome. And so first I'll create two variables and we'll name it as len1 and len2. And we are going to call a function called check palindrome. Inside this function, we are going to provide the value of given string s, current position of I, and we are considering this to be an odd length, so that's why we are considering I to be the middle element. Also, we are going to create a variable called length2. We are again going to call the check palindrome function. We are providing the value of string s, we are also providing the value of I, and we are also providing the value of I plus 1. Why plus 1? Because remember that in the even length palindrome we actually have two middle entries, and that is how we are going to do it. And also we are going to have a variable called length, where we are going to keep track of the maximum length of palindrome we have found so far. Remember that amongst these len1 and len2, at any given moment, if we identify that there exists some valid palindrome and we have found the maximum value, we might have to update the value of the maximum variable. So we are going to check for that condition as well. For that we actually need two pointers called left and right, and we are going to check that whether the given length we are getting, if that is greater than the left and right length we have already found so far. The thing is, we haven't declared these variables yet. So first of all, let me quickly declare these variables, and we are going to initialize their values as 0. We are going to update the value of the left pointer, and that will be decided based on the value of I. So we are going to do I minus whatever the value of current length we have found. We need to do it divide by 2. The thing is, we don't know that whether that length is odd or even, so we will subtract it by one value and then we will divide it by 2. So in any case we will get the correct result for the left pointer. And for the right pointer, we are actually going to do I plus whatever the length we have found divided by 2, and this should give us left and right pointer to create the desired substring. And after we run out of the loop, we will simply return the substring. So now we are done with most of the logic in the main method. Now we'll just have to create this check palindrome method. So let's assign the value L and R for the ease of our use. Now we are going to run a while loop that until the point when we have a valid palindrome, we will keep on reducing the value of left and updating the value of right, and we will check that whether both values are same or not. We'll also take care of some edge cases. While the existing value is a valid palindrome, we will reduce the value of left pointer and we will update the value of right pointer. This while loop, we will return the whatever the length we have found so far. This should do it. Let's try to run this code. We will have to update the value of this right pointer by 1. Let's try to run the code again. Okay, seems like our solution is working. Let's submit the code. And our code works as expected. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do palindromic substrings lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Facebook, Amazon, Twitter, Google, Microsoft, Uber, Goldman Sachs, Apple, Bloomberg, and LinkedIn. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given a string s and we need to return the number of palindromic substrings that exist inside this given string s. Lucky for us, we are given the definition that what a palindrome is. Basically a palindrome is a string that reads the same from backwards and frontwards. So suppose we are given a string like this GG. If we read it from the backwards or frontwards, in both the cases the answer remains the same. Also one more example, ABA. This is also an example of palindrome because in either case we read it, the answer remains the same. Now a quick question for you guys, that whether this character B, is this an example of a palindrome or not? And the answer is yes, this is also a palindrome. Why? Because if we read it from the left and also read it from the right, we get the same result. But if we are given a string that looks like this AB, this is not a palindrome because if we read it from the left and from the right, the answer is not the same. So these are some of the examples of a palindrome. We are also given the definition of a substring, but I don't think that it is necessary to define. It is actually pretty trivial. Now let's try to understand this problem with an example. Suppose we are given a string S that looks like the CABA. Now in this case, we need to find that what are the number of palindromic substrings that exist. So we can clearly see that we have a palindromic substring that are These four characters are actually palindrome in itself, because as I mentioned earlier over here, that even a single character is also a palindrome in itself. So we already have four palindromic substrings so far. But if we notice over here, we also have one more palindrome, that is this ABA, and that is also a palindromic substrings, which means that in this case we need to return 5 as our answer, that we can actually make 5 palindromic substrings for this given string S, and this is what we need to return. So let's see that what would be the different approaches to solve this problem. Suppose this is the S we are given, and we need to find that what would be the brute force solution for this problem. Well, we have to understand that we need to find all the existing palindromic substrings that are present inside this given string S, which means we need to find the substrings. So what we can do is we will make all the possible substrings that we can make from this given S, and then we will check that whether that substring is a palindrome or not, and simply we will get our desired answer. So if we see that in action for this particular string, we can actually make substrings that looks like these. So these are all the substrings that we can make from this given string S. Now all we have to do is check that whether any given string is a palindrome or not, and in this case we will find that these four strings are palindromes, and also this string is a palindrome. All the other strings are not palindromes, and then in the end we can return 5 as the answer for this problem, and that would be a valid answer for this problem. But what is the issue with the brute force approach? Well, the issue with the brute force approach is that the time complexity in this case is actually going to be big O of n cube. Why n cube? Because it takes n square time just to make these substrings, and then it takes n time to check whether a substring is a palindrome or not. So cumulatively this is a very bad time complexity, and we will have to find a better approach. So before we move for the optimal solution, first of all we will have to build some intuition behind it, that how to identify a palindrome. Well, in the palindrome there could be two possibilities. The palindrome could be of odd length or it could be of even length. First let's see that what would be the scenario in the odd length. So suppose we are given this character O. This is a palindrome in itself. We have already identified that, because if we read it from left or right we get the same result, right? Now if I decide to add two more characters XO, XX at the edges, this still remains the palindrome, which means that because both of these x's were same, and this middle value was a palindrome in itself, this whole thing actually became a palindrome. Again, if I take it even further, if I add two more characters BB, again this whole thing still remains a palindrome. And if I keep on adding same values, as long as they are same, this will always remain the palindrome. But the moment I add a value that likes A and B, now this whole thing is not a palindrome, because these two values are different. But this portion is still a palindrome, and also the smaller portion still remains the palindrome, which means we can define that the palindromes are like an onion, where the middle value remains the same, and because of the middle values, all the other subsequent values where the values are actually same, the palindromic property is sustained. Why I'm giving so much explanation for that is you will see it in the optimal solution. And in the odd cases we only have one value as the middle character, but inside the even character, suppose we are given a value like BB. So this is a palindrome in itself, and both values are same. Because both values are same, this is an even length and this is an even length palindrome. Now again I decide to add two more characters XX. Because they both are same, this still remains the palindrome. Again I add value AA, this is also a palindrome. But the moment I add a value that is different, like X and Y, now this whole thing is not a palindrome, but this middle portion still remains a palindrome. So that is the important property, that in case of odd length we have a middle character of the palindrome that is a single character, and all the other characters has the same value. In case of the even length palindrome, we have two characters that are same. So that is important, two characters, they are both same, and then all the other characters, they are also same as well, and a smaller palindrome is forming a larger palindrome. And let's see that how can we use this property to find an optimal solution. So suppose this is the example we are given, and we need to find the optimal solution for that. The idea is that at any given character, we are actually going to see that whether could this be a middle of any palindrome. And if it is the middle of the palindrome, we are going to keep on expanding our palindromic search, and we are going to keep adding our answer result. First of all, let's see for this character number C, that can this C be part of any middle of the palindromic substring or not. Well, we already know that this C is a substring in itself, because if we read it from left or right we get the same result. And we are also going to have a variable called answer, so initial value was 0. Now because the C is a palindrome in itself, we are going to add the value to our answer as well. Now we are going to see that whether the C is a middle of the palindrome or not, which is not. Why? Because if we see the left of the string and right of the C, this is actually a null value and this is a, which means both are not same. So because both are not same, this is not part of any middle of the substring. Now we are going to have this value a. Again we are going to repeat the same process. Well, a is a palindrome in itself, so we are going to add the value to our answer first of all, so this becomes 2. Now again we are going to check that whether this a is the middle of any palindrome or not. We also have to check for both the cases that could this be of odd length palindrome or an even length palindrome. So for odd length palindrome, like the both left and right value would be same, and for even length palindrome the value would be same with that itself. So first of all we are going to check with this a. So the left value is c and right value is actually b, so both are not same. Also they are not same of this a and b, which means this is not an odd length palindrome and even length palindrome, so we are good to go. Now we will move on to the next value b. Now this next value b is a palindrome in itself, so we will update the value inside our answer to 3. After doing that we are going to check that could this be the middle of any palindrome or not. So we will check the left and right value. Left value is a and right value is also a. So because these two are same, we can define that this b is actually part of the middle of the palindrome, which is of odd length, and we are going to keep on expanding our palindrome. So now this b a b, so sorry, now this a b a is also a palindrome, so we will update our answer immediately. So answer becomes 4 now. Now again we will keep on expanding our palindrome. So if we do a left and right over here, the left value is c and right value is actually null. So these two are not same. Because these two are not same, we no longer have a palindrome, so we will break out of the loop. Now again we still have one more character left to check. So again we will check for this value number a. So a is a palindrome in itself, we will put the answer as 5. Then again we will check that whether this a is that a middle of any palindromic string or not. So we check left and right value. Left value is b and right value is actually null, which means these two are not same and they're not same of this a as well. So immediately we will break out of the loop and we can return, and the next value over here is actually null, which means we don't have anything. We have reached to the end of the string. So this is the answer we need to return in this case, that the 5 would be the answer and we will return that. Let's see one more example s where we will find the even length palindrome. So over here again we are going to repeat the same process. So first of all we'll take this character number c. Can this c be part of the any middle of the substring or not? So this is not part of any middle of the substring and we will have an answer variable. So first of all we'll initialize it to 1 because c is a substring in itself. Now we'll move on to the next value a. So a, where a, if we check the left and right pointer, left is c and right is b. So these two are not same, so immediately a is also not the middle of any new palindrome, but it is a palindrome in itself. So again we will update the value to 2. Now again we are at this position number b. Now at this position number b, if we compare left and right values, so left value is a and right value is b. So these two are not same, but these two are actually same. So we can define this bb to be a middle of a palindrome, and this is the property we are going to use, right? And by the way, for this b, first of all we'll update the value to 3, and now we have this bb, that is a middle of the palindrome. Now immediately we will check the left and right value. So left value is a, right value is also a. Again these two are same, so this is also palindrome, so we'll update our answer again. So this becomes 4. Now again we will check the left and right value over here. So left value is c and right value is actually null. So in this case these two are not same. Because these two are not same, we will break out of the loop and we will say that okay, so far we have found something decent. So right now again we are at this position number b. Now remember that this becomes a little bit tricky, that it becomes easy for us to, if we check over here, this left value is actually b and right value is a. So again these two are same, but we should not fall for this trap because we have already concluded this bb to be a middle of the palindrome, so we will not consider this one. And this is also not a palindrome, which means that the answer we will only update by 1, and that this value by itself is a palindrome. And at the end we will check for this value number a, and a is a palindrome in itself, so we'll update the value to be 6. But in the left and right there is nothing, so we won't do anything with that. And in the end we will return this answer 6 to be the final answer. And this is the solution we are going to use to find all the palindromic substrings inside any given string s. This is the final optimal solution. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n square. Why n square? Because it takes us n time to iterate over all the values, and for any single value we might have to iterate over all the remaining values, so that takes n square time. But this is still a big improvement compared to our brute force approach, which had the n cube. If we see the space complexity, in this case the space complexity is actually going to be big O of n, because at any given point we might have to store all the values of n. First of all, we are going to initialize a variable called answer, and we are going to assign the value as 0. Now we are going to create a for loop and iterate over the given input. Now we have two possibilities. Any single character inside this given string s could be the middle value of any odd length palindrome or an even length palindrome. So we are actually going to make two calls to our check palindrome method, where we are going to return a value that whether this given string is a palindrome or not, and we are going to add that value to our answer variable. And inside this method we are going to pass the value of our string s, and we are also going to pass the character position of the middle variable. So the odd length palindrome would have the same middle value, so we will pass on that, and for even length we are going to pass two values. So over here we will pass I, and we will also pass I plus 1 to be the middle characters. Basically after we get out of this loop, we should have our answer ready, so we can simply return that. Now let's create this check palindrome method, and we will initialize a variable called count to count the number of palindromes we encounter. Now we are going to run a while loop, that while the left and right pointer are in bounds and not out of bounds, and while their character positions are same, so which means they satisfy to be the palindrome. If that is the case, we will keep on updating their values, and we will keep on adding our count variable, and in the end we will return the count variable. So let me quickly type that. So this condition defines that whether this given string is a valid palindrome or not. If that is the case, we will decrement the value of our left pointer, we will increment the value of our right pointer, and we will increment the value of our count variable. And once that is done, once we get out of this loop, we simply need to return the count variable, and that's it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently, and I would be posting this solution in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, Decode ways, and this problem has been asked in a bunch of different FAANG companies like Amazon, Google, Facebook, Microsoft, Uber, Lyft, Apple. So I highly recommend that you focus full attention to this problem. This is the breakdown that we are going to do for this problem. We are simply going to understand the problem first. We are going to see a brute force solution. Based on the brute force solution, we are going to see that how can we create an optimal solution, and eventually we will write the Java code for that. And this is a LeetCode medium problem, and we are given a note that basically a message containing letters can be encoded into numbers using the following method. So A is 1, B is 2, and up until that, if we keep doing that, Z is actually 26. And we are given a string of S that contains digits, and we need to return the number of different ways we can decode it. So let's understand this with an example. Suppose our given input S is equal to 12. We can decode this in two ways. So one way to decode this would be to consider 1 and 2 as separate elements, and 12 by itself as a single digit. So this the value for 1 and 2 would become A and B using this logic, and the value of 12 would become the letter L. So we don't need to return these values, we don't care about them. The thing is, we need to return that how many different ways we are decoding this given input string, and in this case the answer would be 2. Let's take another example. So suppose our given input S is equal to 226. How many times, how many different ways we can decode this one? So one way to decode this one is 2 and 26. So that's one way. The second way to decode this one is 2 and 6. So that is second way. And the third way to decode this one, 22 and 6. And if we check out the values, so this would becomes B Z, this would becomes B B F, and this would become V F. So over here we can see that there are three ways we are decoding this given string. So in the answer we will return the value as 3. Now let's consider one more case. Suppose the value 0 would be a special case, and there could be multiple possibilities where 0 can appear. So suppose our given input s is something like 0 1 1. So in this case we won't be decode it in any manner, because remember that our range starts from this value number 1 up until 26. So 0 is not part of the range, so we cannot begin our string with value 0 at the beginning. So this won't work. Second possibility, that 0 could be somewhere in the middle. So suppose our given input s is equal to 1 0 1, something like this. So in this case we cannot decode this in 1 and 0 1. We can't do this. Why? Because we can't decode this 0 1, because remember that in this scenario if 0 comes at the beginning we can't decode it. The way we can decode this is we can consider this as 10 and this as 1. That value of 0 can appear at the end. So our input string s can be something like 2 0 0. So in this case we can decode this value 20, but we can't decode this 0, so we won't be able to return anything. Or our value s can be 5 2 0. So in this case we can decode this. We can decode this value 5 and we can decode this value 20, because 20 is again between 1 to 26. But if we are given something s is equal to like 5 7 0, we can't decode this, because we can decode this 5 but we can't decode 70, because 70 is not part of this 1 to 26 range. So when value 0 comes in, it becomes a little bit tricky and we have to just take care of it. For brute force approach, let's take a custom example. Suppose our given s is equal to 2 1 2 3, and we need to see that how many different ways we can decode this one. So brute force approach is pretty simple. We just take all the possibilities starting from the first value and keep moving and keep building our solution, and when we reach at the end at any given path we consider it as a one way to decode it. So initially we can decode this as 2 and whatever the remaining value 1 2 3. We can decode this further into 2 1 and whatever value remaining, again same thing, 2 1 2 and this 3, and in the end we can decode this as 2 1 2 3. So this would be one way we would be able to decode this. So where if we treat all the values as separate entities. Now let's go back and see that can we have more possibilities. So over here we cannot have any more possibilities, because this 2 1 and 2 are already being decoded, and this 3 we only have one possibility to decode it by itself. So we don't have any possibility over here. So we go back further up. Do we have any possibility over here? So yes, over here we still have possibility that we can decode this 2 and 1 the same way we have decoded over here, but this 23 we can decode it as a single value. So of course we reach at the end of the loop. So this is one more possibility on how we can decode it. Now let's go back. So for this value 123, of course we still have more possibilities, because over here we are considering this value as 2 and 1 separately. So over here we will consider this as 2 as already being decoded, and rather than considering this as 1 as separate character, we can also consider it as 1 2 and then we can decode 3. So this can also be another way. So we'll just mark it. Okay, now we have exhausted all the possibilities over here. Considering this value, if we start from this value number 2, so we come back at our main point and let's see that what are the more possibilities we can have over here. So we can do, rather than choosing 2, we can choose 2 1 and whatever the remaining stream. So remaining is 23. Okay, now let's see that how many different possibilities we can have over here. So we can have two possibilities now. We can do like 21 2 and 3, so that is one option, or we can do 21 and 23, so that is second option. And yeah, both would be separate ways, and apart from these we cannot make any other possibilities. So essentially we can say that there are 5 different ways to decode this 2123 string. and those 5 ways are mentioned over here. Uh, what is the problem with this brute force approach? Well, the problem with brute force approach is that actually we are doing a lot of repetitive work. How we are doing repetitive work? If you notice over here that we know that we need to calculate that for this 23, how many different ways we can compute this one. But this 23, we have already computed it over here. So since we have already computed it over here, it is not very fruitful to compute the same thing twice. And in brute force we are not doing it, so that is why our path will keep on growing and growing until we reach to our all the possibilities, which means that we are actually doing exponential work for this brute force approach. So of course the time complexity would be big O of 2 to the power n, which is really bad, and we should avoid it in all cases. And actually it can be avoided pretty simply if we just use memoization. If we just create an additional data structure, something like an array or something, where we store the value of calculations that we have already done, and if we at any point come back to the same calculation that we have already computed, we can simply return that value. So we can use something like an array or hash map. I think hash map would be more efficient in this case because we are able to look up things in constant time. And if we only apply that, we can actually implement this solution, this brute force solution, in very effective manner. We can actually use recursion because remember, at every single moment we are repeating a sub problem. So we are repeating a sub problem and we are computing that. So if we just use memoization with recursion, so for this approach, we can actually achieve the answer in time complexity of big O of n rather than this 2 to the power n, and that would be really efficient. Okay, before I go into the optimal solution, I want to show you a few observations. Suppose our given input s is equal to 7. So how many different ways we can decode it? Of course, only one way. We can just use 7. Suppose our input is 7 7. We can still only decode it one way using like 7 7, and that would be the only way we would be able to decode it. Even if our value is 7 7 7 7 7 7 7, whatever the value we have, all of these can only be decoded just one way, because all of these values, they are forming a value where we can only use individual characters. Now, what is the scenario where we can use the characters that are not individual and we can collectively use the pair of elements? Okay, now let's take one more example. S is equal to 2 1 2 3, and now let's try to see that how many different ways we can decode this one. This is the same one we have used in our brute force approach, so we know that there are 5 different ways we can decode this one. The thing is, we are going to do things a little bit differently over here. We are going to decode all of these values. So first we'll start with value number 2. How many different ways to decode this one? Only one way, and that way is 2. Now let's consider the second value, 21. How many different ways to decode this one? Well, of course, two values or two different ways, and those ways are 2 1, so that is one way, and second one is 21 by itself. And let's take the third value, 2 1 2. So there are actually 3 different ways to decode this one. So let's consider the next value as 2 1 2 3. So we know that for this one there are actually 5 different ways to decode this, and the 5 ways are, okay, you must be thinking that why am I writing all these letters? Because the thing is, there is actually a very important relationship that exists whenever we find out whenever we add a new value to our calculation, and if that value that is being added, if the previous value of that with that particular value, if that falls between this 10 to 26, actually something interesting happens. So notice over here that this 21 came in. Okay, we are checking for this value number 21. Now the thing is, just for a second, imagine if this value was actually 27. So how many different ways would we be able to decode this one? Well, only one different way, and that one different way would be 2 and 7. So treating both values as separate values. Same goes for 28, 29, and any value above. But the thing is, because this value falls between this 10 to 26 portion, we are able to do something interesting. So notice that whatever value we append over here, there will only always be one way to decode it. I'm not talking about the value 0. Forget about 0. Apart from 0, if there was any other value, the way to decode it would be to whatever the way we have been decoding the previous value. If we just add that value, then that would be the way to decode it, which is over here. That 2 and 1, we are already decoding it with whatever value we were decoding before, and we were using that way. But the thing is, over here, this 21 by itself falls under this 10 to 26, which means it is a letter by itself. So we are able to add it to our decode list, and that is why we have 2 over here. Okay, but now the interesting part comes in. Okay, now over here we are adding one more 2, and this 2 falls between the values 10 to 26, because the appending value becomes 12. So this 12 falls between this 10 to 26. Now let's see that how many different ways we are creating the pairs. Actually 2, 1 and 2. This is same from whatever the pair we had before, just one iteration before. Okay, now this 2, 1, we already had a 2, 1 over here, and we are just appending this value 2 over here. So that is also okay, because we can append it, right? So whatever the ways we were decoding before, we are still using those ways. But the thing is, over here something interesting happens, because this 1, 2 by itself is a way to decode. We are actually able to create this 2, 1, 2 pair, which we were not able to generate over here. We are not able, I mean, we are using this 2 over here, but the thing is, we are using it for 2, 1, but we can't do anything further than that. We are already also using this 2, 1, 2 over here. And how can we say that we are using this 2, 1, 2 over here? Is because this value is basically 12, falls between 10 to 16. But the thing is, this 2 actually comes from the first value, this one. And why? Because at any given moment we find out that there exists a pair with the new value being added, and that comes between this 10 to 16. We can actually do sum of previous two values that we have calculated so far, and the sum of these two would actually give us the number of different ways we can actually decode this one. If you still don't believe me, let me show you with another example. Let me clean this up a bit. Now over here we are seeing that 5 distinct pairs are being made, and we are adding a value 3 over here, and we know that this pair 23 exists between this 10 to 26. So that is all okay, right? We know all of these stuff. Now let's see that how many different ways we are generating the pair. So one way is 2, 1, 2, and we are just appending 3. This would be the case even if the value was 2129. If the value was 2129, we would still be able to use this way, because apart from this 3, there would be a 9 over here, but that's not the case right now. But the thing is, we would still be do it. And if you look over here, this is the same path we were taking, and we are just adding one more node, so no impact on the number of results. Second pair we are making is actually 21, 2, and we are appending 3 over here. Again, that is the case over here, that we already had a 21, 2, and we can append 3 over here, so that gets taken out over here. If we had the 21, 29, we would be appending 9 over here, so that still remains common. Okay, there are no issues with that. Now next pair over here is 2 and 12. So we also have a 2 and 12 pair, and we are adding a 3 over here, which means that even if we had this 9, we would still be adding 9, and that would be it. We don't care about it. But the thing is, if we had this 9, we won't be able to generate these two pairs, because notice in these two pairs we are actually creating an additional value by the value that has added over here. And if this value was not between this 10 to 26, this value would not be able to be generated. Okay, now the question comes that we have already exhausted all the possibilities over here. So where does these two additional values comes from? Well, actually, if we look above over here, this one is actually 2 1, right? So we are also using 2 1, and we are creating a new decode node 23, and we are appending it over here. Also notice over here that this one is 2 1 and this one is 2 1, so we are appending a node over here 23, which means that at any given location, if we want to see that how many times we can decode it, if we know the information of previous two elements, and if we do sum of those, we can actually generate it. So that's why the value for this 2 1, this can be decoded 2 times. This value 2 1 2, this can be decoded 3 times. So for the value 2 1 2 3, actually this 23 falls between 10 to 26. That is okay, that is perfect. If that is the case, we simply do an addition, and if we do an addition and we just find whatever result we have calculated, and we can simply return this. This is a very effective solution. Now what could be the other case? Well, the other case could be that the new value we are adding, that does not fall between this 10 to 26. So suppose over here the new value we are adding, suppose the new value is 2128, something like this. So after adding this new value, this becomes 28. It does not fall between this 10 to 26. Because it does not fall between this 10 to 26, actually we don't need to do addition over here. We simply need to, whatever the route we can make before this element, that would be the only possibility we would be able to decode this one as well, because that I just showed you over here, that over here I was adding a 9, and because I was adding a 9, I was only able to make the new decode paths for these 3 elements. I won't be able to generate these 2 values, and this becomes our recurrence relationship, and this actually becomes our dynamic programming solution. Now let's try to solve this dynamic programmatically. We know that we care about the 2 previous elements. So suppose our given input is like 2 1 2 3. We initialize 2 values before that as 1 1. Say we have these 2 as 1 1. Now we check at any given location that whether the value we have, does this value with its previous value, does it fall between this 10 to 26? Okay, in this case this 2 does not fall between 10 to 26. If it does not fall between 2 to 26, we just need to take whatever we had from the previous element. So previous element over here we had 1, so we'll just take 1. Okay, now we have this 1. So again we check with its previous element that whether the value falls between this 10 to 26, the value becomes 21. It falls between this 10 to 26. So we do whatever the previous 2 elements were, we do sum of it. So the previous 1 element is 1, and the previous second element, this one is also 1. So we do 1 plus 1, so we can put 2 over here. Now we have new element. This falls between this 10 to 26. That's good. So we do sum of 2 previous elements. Sum of 2 previous elements is actually 2 plus 1. So we can put 3 over here. Now we have this 3. Now it creates the value 23, again falls between this. So we can do sum of 2 plus 3, and that becomes 5. And this 5 would be our result. So this is a very important dynamic programming solution. And at any given moment, if we find out that suppose over here we have an value 8. Now this 38 does not fall between this 10 to 26. So it becomes simple that for this pair, the number of ways we can decode this will still be 5, because we'll just take whatever value we have calculated over here. This solution works perfectly fine, and the time complexity for this case would be big O of n, because we only need to do one iteration across all the strings, and the space complexity would in this case would actually be big O of 1, we would be able to complete this in constant space and time, because remember that at any given location we only need to keep track of just two elements. We don't need to keep track of this whole entire array. We just need two starting elements, and we would keep on iterating them over different values. So this is a very good solution. And okay, first of all, we'll check that whether the first element is 0 or not. If this is the case, we can simply return 0. Okay, so we will create two parameters, 1 and 2, and we will initialize both to value 1. Let's run a for loop. We'll start the loop from first position, and we will go up until the length of the given string. We are running it from I equal to 1 because we already checked for the 0th position. First of all, we create a value current to keep track of the current element, and now we check that if the current if the new character that we are trying to add, if that is not equal to 0, we can assign the value of 1 to current. Now we also need to check that after we are adding the value at ith position, are we getting the 2-digit value between 10 to 26? So first of all, let's create a new variable called value, and we'll try to calculate the 2-digit value. We check the condition. So if value is greater than or equal to 10 and value is less than or equal to 26, which means we need to update the current value is current plus whatever the value of 2 we had, because remember the value at current we are already adding it as 1. Now we need to update the values of 1 and 2. So 2 would become whatever the value of 1 we had, and 1 would become whatever the value of current we had. And yeah, I think this would be our solution. So at the end of the solution, we need to return the value of whatever the current value we had, but since we are initializing current inside, we'll just return the value as 1. And let's try to run the code. Oh, we can initialize the current as 0. Let's try to run the code. Okay, looks like our solution is working. Let's try to submit the code. Okay, our solution works pretty fast and pretty efficiently. So I'll be posting the solution in the comments. You can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to work upon a very important dynamic programming problem, coin change, and which in my opinion everyone should do it at least 2, 3, 4 times until you get a real grasp of the concept on how to solve it. And let's understand the problem statement. We are given an integer array of coins representing coins of different denominations, and we are also given an integer amount that represents the total amount of money that we want to generate. Now we need to return the fewest number of coins that we can use to make up to the amount that has been provided over here, and if the amount of money cannot be reproduced, we need to return -1. Let's try to understand this by an example. So in the given example, the number of coins we are given is 1, 2 and 5, and the amount we are given is 11. So based on the example, we can clearly see that the most optimal way we can create this 11 is by using 5 plus 5 plus 1. So in general, this sums up to 11, and if we see the number of coins, we are actually using 3 number of coins to generate this value. If we look at the second example, basically we are only given one coin, the value number 2, and the amount we are given is actually 3. So no matter how many times we use the number of coins 2, we cannot generate this amount 3. So in that case we need to return -1, while in this case we would be returning 3 because we are using these 3 coins. So once we have this clear, now let's try to understand that what could be the different approaches we can take to solve this problem. The first approach that comes to our mind is actually to use a greedy approach, where whenever we are given the number of coins, so let's take one of our own custom examples, and we also need to keep in mind that whenever you are solving or giving any FAANG interviews, make sure to have your own custom inputs, because FAANG companies really like this kind of stuff, and that shows that you are able to think outside of the box, and you can also create test cases on your own. So suppose we are given an input like this, and the amount we need to create is actually 8. So in our greedy approach, basically we at any given moment, for the given amount, we will take the biggest coin that is smaller than this amount and keep repeating till we reach this amount. Now let me show you that why this approach won't work. Because if we see here, the amount we have is 8, and the biggest denomination of coin we can create that is lesser than 8 is 6. So if we take this, so let's create our answer where we keep track of how many coins we are using. So we use 6 over here, we take 8 to 6, so we subtract 6 minus 8, we get the remaining value is 2. So since the remaining value is 2, we cannot use these 3 coins anymore because they all are greater than 2, and if we were to subtract this coin from 2, our result would actually become negative. So we cannot use that, but we can still use value number 1. So if we do that, and if we use the coin number 1, because this is a greedy approach, so we will add the coin number 1 to our answer as well, and so now the remaining value will be 1. So again we cannot use these 3 values, but we can still use 1, so we will use 1. The remaining amount is 0, which means that we have reached our total amount of 8, and we would add the value number 1 over here. Once we do that, essentially if we calculate in the answer, we are using 3 separate coins to reach the amount 8. So our answer would be 3 in this case, and we would return 3. But notice that this answer is actually not the lowest number of coins we can use. Actually, if we just use the coins 3 and 5, we can simply create this value 8, and our result in this case should actually be 2, not 3. So greedy approach doesn't work at all. Now let's see what could be the next approach we can take over here. We are given an input like this, and we need to reach out to a particular amount 8. So at any given point, if we basically start calculating from 0, and we will keep on making choices based on the number of coins we have until we either reach to this value 8, or our choices actually becomes greater than 8. Until these two things happen, we can keep on making choices given our coin denominations, and based on that we can actually create our own decision tree. And in the decision tree, whenever we reach at value number 8, we will keep track of the value, keep track of the path, and based on that path we can calculate that what are the minimum number of iterations we have to make. So initially we are at 0th position. So from 0th position we have 4 options that we can take. So let's make these 4 decisions: 1, 3, 5 and 6. Now at every single decision we still have 4 more decisions that we can take to reach out to this value 8. So again at value number 1 we still have 4 more decisions we can make. So let's do that. And again at every single iteration we still have 4 more decisions, and with every decisions we come closer to this value number 8. So initially over here complete 8 were remaining. Over here we are only dealt with creating the value 7 because we already used one coin. The remaining value would be 7. So over here the remaining value would be 1. Over here the remaining value would be 2. Over here the remaining value would be 4, and over here the remaining value would be 6. And suppose we continue on this path again, we would still have 4 choices, and notice that the remaining value we wanted to create was 6, which we are able to achieve over here. So the sum for this particular path, 1, again 1, and then again 6, is actually 8, which means that we have found a potential route. And if we see the number of coins we had to use 1, 2 and 3 coins. So current amount, current answer we need to return is actually 3. And since we have found this route, all the other routes, if you see, the values would not reach to 8, and we can cancel out these values. And basically because if we keep going on, we will still have to make more decisions, and the number of route will definitely be greater than 3. So we can start eliminating these routes, and we have one potential route over here. Again, if we keep on going down this path of 3 and keep making more decisions, we would end up with a result that would be greater than 3, or we would not reach 8 at all. So we can ignore this. Again, we can ignore this from 5, and at 6 we would still find a route something like this, where, because notice even at 6 we still have 4 decisions we can make. So we can choose either 1, 3, 5 or 6, and notice that only 1 is remaining over here, and we can select this one. So we would have another potential route starting from 1 going to 6, and then again going to 1, that sums up to 8. But again, for this route as well we need to use 3 coins, so our answer will still remain 3 and it won't be changed. But this is where we find another answer. And now we have exhausted all the possibilities from value number 1, so we can just ignore all of this. Let's get rid of it, so we have something that is more clear and not so much congested. Now let's try to see that what could be the possibilities from this value number 3. So even at value number 3, the remaining amount we have would be 5, and at value number 3 we still have 4 more possibilities that we can choose from: 1, 3, 5 and 6. And notice that in all of these these 3 possibilities we would not reach 8. So we would not reach, basically the remaining value would not be 0, which means, but if we get down over here 5, over here only 5 is remaining, and we directly have a coin 5 present at the decision tree 3. And if we calculate the route would look like 1 and then 2. So basically we are only using one coin over here, and we are using second coin over here. So we are only using 2 coins to reach to this value 8. So we can simply update our answer, that we have found a new minimum value that can come up as our answer, and we can set the value as 2. Now we can continue to search and keep on making more decision trees, and even for those nodes we will continue to making further down decisions to see if we can find a better answer. But we won't be able to find a better answer than 2, and eventually we would have to return this value. So this solution, in a way, it works, and it works as expected. At least we are getting the answer. But the issue with this approach is that time complexity is actually so bad. It's not even in polynomial time, it's simply in exponential time. And the time complexity, suppose the amount we are given, if we consider it as m, essentially until we reach this amount m, we are at every time keep on making multiple decisions based on the number of coins that are given. So we can compute the time complexity as big O of m to the power of n, where m is the given amount and n are the number of coins that are present at any given moment. This is such a bad time complexity that we, even if we ask NASA to run this command, they won't be able to do it more than up to a certain values, and we need to find a better approach. And in the optimal solution, we are simply going to use just two golden words: dynamic programming. And let me show you how we can solve this via dynamic programming programmatically. And we are just like a rational person. We are just going to think it in terms of intuitively, that if we are given this problem just to solve on a pen and paper, how we are going to do it. And one approach is that we can basically start from the value number 0. We can keep on reaching towards the amount we want to reach out to, and for every single element that we have found, we will find that for 1 2 3 4, how many number of coins it took us to generate that particular amount. And once we are sure with this value, whatever value we have generated, the amount for 1 or amount for 2, we would be able to use this later down the road. And let's take an example. Let's continue with our example and see how can we achieve that. So we are given the example 1 3 5 and 6, and the amount we want to generate is 8. So initially we would create an array of amount from 0 all the way up to amount of 8, and we will initialize all the values by any value that is higher than 8. So let's say 8 plus 1, and now we will start with our solution. So far all the values are actually 8 plus 1 in this amount array, and this represents that these are the number of coins that are needed in order for us to generate any particular value. Now if we just want to generate 0 coins, how many number of coins do we need? Well, answer is pretty trivial actually. We simply need 0 coins, and this becomes our base case. So now let's say for the second value, amount of 1, that if we want to generate value number 1, how many distinct coins we need. So whatever value is, we will check first of all in our coins for all the values that are given in the coin, to see if we can directly use, if the given coin is lesser than the value we are trying to achieve, can we use that coin. So since the value is 1, we can clearly see over here that this 1, if we just use one coin, we would be able to generate this value 1. So the answer in this scenario becomes pretty simple, that if we just use one coin, we would be able to generate this value. And notice that for value number 1, we cannot use any of these 3 coins because they are all greater than our value 1. So there is no point in using them. Now let's repeat the process for amount 2. So for amount 2, if we want to generate the value 2, how many minimum number of coins we need? So first of all, let's check with the first value. Okay, so coin is actually less than 2, so we can use this coin. We will use this coin. So if we use that coin, basically we have already used one coin so far, and since we use coin number 1 and we want to achieve value 2, we can say that now the value we are trying to generate is actually 2 minus 1. So again, value number 1. Now we want to generate value number 1, and if we can do either two things. Either we can go back to all these coins, again we try to generate that value, or notice this beautiful thing over here, that we have already calculated that if we want to generate amount 1, how many coins we are going to need. So why are we being so picky, and why are we doing all this extra work, and why are we making our lives miserable, our CPU's life miserable by doing all these additional calculations? Why can't we just store this somewhere? And if we have stored it, we can simply use it over here. So in this case, we can say that we have already used one coin in order for us to generate this one. And now once we have generated this one, we know that the number of coins that are needed to create value 1 is already computed. So we will do 1 plus amount to generate 1 coin, and this would be the answer if we want to generate the value 2 from the given coins, and this would become 1 plus 1, so 2, and this would be our direct answer. And these are the minimum number of coins that we can use to generate value number 2. The reason I'm emphasizing so much on this is because this exactly is the core concept of dynamic programming, and we have just hit a very big hammer to its head. Basically, we have said that, hey, I'm going to take this dynamic programming all the way, I'm gonna chew it, swallow it up, so it becomes a second nature to me. And now let's continue with our example. This is going to be a really long video, and I recommend that if you just understood at any point, I would just suggest you to go ahead and start skipping over. So now the value for amount 2 is actually 2. Now let's calculate for amount 3. If we look at for amount 3, we have two options. Either first of all we can start with this value 1. We'll take value 1, then again the remaining value would be 2, and we have already calculated that what is the amount that is remaining for value number 2 over here. So if let's take that approach just for the sake of understanding. So first of all we use coin number 1. So we use coin number 1, and plus the amount that is remaining is actually 3 minus 2. So we still have amount 2 that needs to be computed in order for us to achieve this value 3. So we can say that for this one, the way we can do it is 1 coin that we already used plus whatever the amount 2 that we need to use. And notice amount 2 has already been computed over here. So we can say that 1 plus 2 equals to 3. So if we choose one of these coins and we try to achieve the value number 3, initially we would be able to find our answer by using minimum of 3 tokens. Now again we notice that now since we have computed this coin, we notice that value number 3 is actually less than or equal to this given coin 3, and we can use it to our advantage. So now we know that we want to achieve value number 3 over here. If we just use this 1 coin, we would be able to achieve this amount number 3, and current minimum amount that we have calculated that is that we need minimum 3 coins in order for us to achieve value number 3. So why are we using 3 coins? Because our aim is to use the minimum number of values. So we can simply just say that if we just use one single coin that is of denomination 3, we would be able to calculate the result as 3 for this amount 3, and we won't be able to do anything with these two because they are already greater than 3, so we can't make 3 with those denominations. Now let's move forward with our with the next value, amount of 4. And if we generate the amount 4, how many number of coins we need? So basically if we just take this first coin, we know that we have already used 1 coin, and plus we have the value remaining as amount 3. Amount 3 is already computed. We are using the best knowledge of computer processing we can, and based on that we can simply determine that, oh, and by the way this would be 1 not 3, my mistake. So we can just simply say that if we want to generate amount 4, we can do 1 plus amount 3 is already 1, so we can use 2, and this would be the minimum solution, that even if we use the first coin as 3, we would use second coin as 1, and still we will get the same answer. So I'm not going to do whole computation, but you get the idea. So for amount 4, we can say that 2 are the minimum number of coins we need in order for us to generate amount 4. If we want to do amount 5, how many coins we need? And the answer is pretty simple. We already have this 5 present over here, so we can just simply write 1. And notice that we are going to check all the coins, and when we get to 5, we will be able to say that this is the minimum number of coins we can use. Next is amount of 6. If you want to generate amount of 6, again the answer is 1, because we are already given a 6 over here, and we are going to check through all the coins that are less in the value of whatever the amount that we are trying to calculate. Now let's calculate for amount of 7. If we are calculating for amount of 7, and if we check for the first coin, the first coin is actually 0. So basically we can just simply say that the first coin is actually 1. So basically we can just simply say that we have already calculated the 1 coin, plus now we need to calculate the amount 6, because 7 minus 1 is equal to 6, and we already have the result for amount 6. So we can just simply write that we need at least 2 coins in order for us to generate the value number 7. And now let's try to calculate our output that we have already given, that we need to calculate the 8. So if we want to calculate amount 8, and based on this table, it becomes pretty simple. Initially, so first of all, we will calculate this with value 1. So basically we would be doing the calculation something like 1 coin that we have already used plus amount of 7, and we know that amount of 7 from our previous computation is actually value number 2. So we will do 1 plus 2 equals to 3 for this amount 8 that we are trying to calculate. But can we do something better? And remember that we are going to check all the coins. So because we are going to check all the coins, when we get to coin number 3, our solution would be that we have used 1 coin, and that is the coin value is 3, and because we have used 3, now we need to generate the amount 8 minus 3 equals to 5. So we can say that we used 1 coin to generate the value 3, and now we need to generate value 5 in order for us to achieve this amount equals to 8. So if we do 1 plus amount of 5, what is the answer? And the amount of 5 is already calculated over here as 1. So we'll just simply use that value, and we'll do 1 plus 1 equals to 2, and we will carry on with our computation with this value 5. Again we will find the answer 2 because we will do 5 plus 3, and when we get to value number 6, we will again find the answer to generate the amount 8 as 3, because we will do like 6 plus amount of 2. So the minimum number of coins that we can find in order for us to generate value number 8 is actually 2, and we can simply return this value 2. Now notice that we also have to take care of the scenario where we cannot create the amount based on the given coins, and if we cannot create the amount at the end of our computation, the value for amount would amount of any given, let's say 8, that we cannot compute in this case, would actually be the value 8 plus 1, so equals to 9. Because notice that at the beginning of our array, this is how we initialize the values to, and if after all the computation we found that the value of amount is actually the original by default value that we set, which is amount plus 1, if that is the case, we know that we are not able to generate this value, and we are not able to make any impact with our solution because the coins cannot generate this value. We will simply return -1, and this solution would work perfectly fine. This is a really beautiful solution, and if you go through with this approach in your interview, you are gonna just be very impressive candidate, and all the FAANG companies would want to hire you. So let's calculate the time and space complexity. So time complexity for this one would be actually big O of n times m. Now why n times n? Because we are running the loop to calculate the value n, and n is actually the value of this amount or whatever is given. So we are going through a loop n times, and m are the number of coins. Because notice that over here for every single element we will have to we'll have to go through all the coins in order to generate the value. So the time complexity would be big O of n times m, and the space complexity would be big O of n, because we are creating an additional data structure array to store all these values, and the values we are storing up to is actually the amount, whatever amount we are given. So we can say that the space complexity would be big O of n. Okay, so let's create an array amount, and its size would be amount plus 1. We fill out all the values inside the amount as amount plus 1. This would help us determine that whether if we cannot create the value, we need to return -1 or not. And now we will set up the initial value for amount of 0 would be 0. Now let's create our loop. So we will start with I equals to 1, because we have already calculated the value for amount 0, and while I is less than or equal to amount. Now notice that for every single value of I, we need to calculate for all the values of coins. So we will have another loop that would iterate over coins. And first of all, we will check that if our present I is actually greater than or equal to whatever value of coin that we are comparing it with. So if this is true, then only we will check that whether what is the amount for any given j, any given I. So we'll do a minimum value of either the value itself, so whatever value we already have, or we will take one coin of any j and we'll do an amount of I minus j. And yep, this is the main logic, because in this logic we are calculating all the amounts, and we are using it further down the road as well. So after this iteration, we just need to check that if for any given amount, so amount of amount, if that is less than the value amount plus 1, which means that we have been able to generate this amount. So in that case, we would return whatever the value we found, else we can simply return -1. Let's try to run this code. We made a silly mistake. Again. Oh, we need to check with coins of j. Yeah, looks like our code works. Let's try to submit this. And yeah, our submission is actually pretty efficient compared to others who have submitted. So I hope you like this video. It took me a lot of time to make it, and I know it was a really long video, but it was, believe me, it's equally informative. Once you master dynamic programming, you are almost guaranteed that you at least have a foot in the door for FAANG. And yeah, we are not gonna stop till we clear FAANG. See you. Today we are going to do maximum product subarray. This is a very popular problem on LeetCode, and if we see some of the companies where I want to get a job who already asked this question, there are companies like Amazon, LinkedIn, Microsoft, Google, Apple, Bloomberg, Facebook, and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. Okay, so this is a LeetCode medium problem, and as mentioned, a very well-liked problem on LeetCode. Basically, we are given an integer array called nums, and we need to find a continuous non-empty subarray that has the largest product, and we need to return the product. We are also given the definition that what a subarray is. That is basically a continuous sequence inside the any given array. And let's try to understand this problem with an example. So I have broadened this example over here, and basically we are trying to find the maximum product subarray. So a subarray that contains the maximum product. In this case, this is a negative value, and that changes the dynamic equation. So in this case, the product of these two elements, that is a subarray, is actually going to be 6. And all the other subarrays, they are always going to have lesser values than 6. So in this case, as the answer, we need to return 6, that is the maximum product subarray we can make for this given input array. And this is what the problem is asking us to do. So first, let's see that what is going to be the brute force way to solve this problem. Well, the brute force way to solve this problem is that we are asked to find the maximum product subarray, right? So if we are asked to find something of a subarray, why don't we check every single subarray, see that what is the product we can make, and find the maximum amongst that? So like do the baby steps. So what we are going to do is we are going to keep on iterating over every single subarray that we can make. We are going to see that we are going to have a variable called answer, and in the answer we are only going to store the maximum value we have found so far, and then we will keep on repeating the same process for all the remaining subarrays, and eventually we would find a pair that contains the maximum product subarray. And in this case, the answer is actually going to be this 6 times 7, that is 42, and we will have 42 populated as the answer eventually. So the brute force way is a very trivial way, but it leads to the correct solution. So if you are only looking for a solution, you will get it using brute force. But what are the issues with this one? Well, the issues clearly we can see over here, that we will have to iterate over every single subarray that is there, and that would lead us to have a time complexity of big O of n square. So which is very bad, because for every single element we will have to iterate over every other elements and then keep on repeating the same process. So the idea is to see that can we find something of a better time complexity. We can actually achieve that using the most important concept inside our computer programming, and that is called dynamic programming. Using the dynamic programming, we are basically going to have 2 pointers to store some critical important results, and that is going to lead us to find the maximum product subarray. So first, let's understand one thing regarding what is being asked. We are trying to find the product. Now we know that for the product, suppose if all the integers are just positive integers, then basically it is the product of all the integers that we need to return, right? The thing is, that is not always the case. We could encounter negative integers, and the negative integers leads to very interesting results. The interesting results are that, first of all, we suppose in this case, these 3 values, if we do product of them, okay, the product of these 2 is 6, and the 6 times minus 3 leads us to minus 18 to be the product over here, right? The thing is, now this value seems very low value because of the negative value. But imagine that over here, rather than this 4 being positive, if we had a negative 4, then that is actually going to lead us to have a very beautiful results, that if we do minus 18 times minus 4, the answer is going to be plus 72, and that is going to be the maximum product subarray. So you see what I'm trying to say? The moment we encountered a negative value, immediately we found it to have the minimum value, but that negative value lead us to have some better consequential results in the future. So we don't know that whenever we encounter a negative value, we don't know whether we should keep it or not. So that is a tricky part. That is why we are going to use dynamic programming, and we are actually going to use 2 pointers. And these 2 pointers are going to be that at any given position we are at inside our array, we are going to see that up until this point, what is the minimum value we have been able to achieve, and what is the maximum value we have been able to achieve. Or basically what I'm trying to say is, what is the minimum product we have been able to achieve, and what is the maximum product we have been able to achieve. And every single value, we could have 3 possibilities. So let me clean this up a bit. At every single value we are at, there could be 3 possibilities. Either this value could be part of a subarray that leads us to have the maximum product, or it could have been a part of a subarray that leads us to have the least value up until this point, or this could be the start of a new subarray that leads us to have a maximum product in the future. The idea is at any given position, we are going to check three things. And the three things we are going to check is that up until this point, whatever the minimum value we had, which we have stored so far, we are going to multiply this value with this minimum value. We are also going to multiply this value with whatever the maximum value we have been able to store so far. And we are also going to compare this value by itself. So we have basically three values at any given position: the value with the previous minimum value, the value with the previous maximum value, and the value by itself. And for all of these three values, we are going to see that what is the minimum value we are able to make, we will store that. What is the maximum value we are able to make amongst these three values, we will store that as well. And eventually we would reach to the end of our loop with the maximum value we have been able to generate, and we will have a parameter called answer, and in the answer parameter, whenever we identify a better maximum value, we would populate that. So this is the approach I am suggesting. Now let me try to go over an example. Okay, so suppose this is the example we have, and now let's try to use dynamic programming in this case with two pointers. So we are going to create two pointers called min and max, and for every single value we are going to compare it with three values that we are going to compare it with, and we are going to populate these results. We are also going to have a variable called answer. We will update it based on the maximum value we have found so far. Okay, so first value is 5. So we for all the three values we only have 5. We can't compare with anything. Okay, so the minimum value we have found so far is going to be 5. Maximum is also going to be 5, and that's it. Now this next value is 3. Okay, so now let's see that what are three values that we have to compare. So first value is 3 by itself. Next value is 3 times the minimum value. So 3 times 5. Next value is 3 times maximum value. So again 3 times 5. So the three values we have is 3, 15 and 15. Okay, so now the minimum value amongst these three is going to be 3. So we are going to populate that, and the maximum value is going to be 15. So we are again going to populate that. The answer so far that the best we have received is 15. So we are going to populate that. Okay, now let's get rid of this one. Now again we are at the next element, that is 1. So now the three values we have is 1 times whatever the minimum value, so that is 3. So the value is going to be 3, and the 1 times the maximum value, that is 15. Okay, now amongst these three values, the minimum value we can able to make is going to be 1. Okay, so let's populate that, and the maximum value is going to be 15. The answer is going to remain the same. Now let's clean this up. Okay, now things become interesting when we reach to this value -2. Okay, now the three values we have is going to be -2 by itself, then -2 times the previous minimum value. So previous minimum value in this case is 1. So -2 times 1 is going to be -2, and the previous maximum value. So previous maximum value in this case is 15. So -2 times 15 is going to be -30. Okay, now these are the three values we have, and now we are going to see that what is the minimum and maximum value we are able to generate, right? So currently the minimum value we are able to generate is going to be -30. So we are going to store that over here. Okay, and the maximum value we are able to generate in this case is going to be -2. So we are going to store that over here. Okay, now we are good up until this point. Now this value is 0. So the three values that we have to compare is going to be 0, 0 times the minimum value. So that is again going to be the 0, and 0 times maximum value, that is again going to be the 0. So all three values are 0. So let's put zeros over here. Now again, we are at this value number -5. So now the three values that we have to compare is going to be -5, and then both of these are 0. So it's going to be 0, 0 again. So currently the maximum value we are able to generate is going to be the 0. So we are again going to populate the value with 0, and the minimum value we are able to generate is -5. So we are going to populate the value with -5. Now the next value is 8. Okay, so now the three values we have to compare is 8. 8 times -5 is going to be -40, and 8 times the 0 is going to be 0. Okay, now the three values that we have, let's compare them and let's find the minimum value. So minimum value in this case is going to be -40. So we are going to put it over here. The maximum value we are going to have is 8. So let's populate that over here. Okay, now we are at this value number -3. So with this -3, we have three options. So -3, and then -3 times this -40, that leads us to +120, and -3 times 8, that leads us to -24. Okay, so now in this case, the minimum value we have so far is going to be -24, which is this one, and the maximum value we are going to have is going to be 120, and this 120 is greater than this value number 15. So we are also going to update that in our answer, And now we have reached to the end of our array, so end of our dynamic programming journey. So we'll stop here, and whatever value we have found in the answer, we are going to return this as the answer. So in this case, answer is 120. That is the correct answer. If we see and if we compare this to our brute force, well, essentially, because we are using the beautiful concept of dynamic programming, we are completely everything in just one single iteration, and all we are doing is just storing couple of variables to store the previously calculated results and comparing different values. That leads us to have the correct answer and find the maximum product subarray in a single iteration, which is wonderful. If we see time complexity, in this case the time complexity is actually going to be big O of n, and the space complexity is actually going to be big O of constant space complexity, because apart from storing couple of variables, we are not storing any other data. So this is a very good time and space complexity to have compared to our brute force approach that had the time complexity of big O of n square, which was very bad. So first let's take care of some edge cases, that if the given number is empty, we can simply return 0. So now we will initialize a min variable, a max variable, and a result variable. Okay, so now let's run a for loop to iterate over our given nums array. Let's initialize a variable called current to keep track of the current variable we are at. Okay, now we will have to calculate max and min value. So first let's calculate max value. So this takes care of comparing three values for our max variable, and we are using math.max function 2 times because that is the way to do it. I think in Python you can do it just without using like two math.max functions. Now let's calculate our min value as well. The thing is, for our min value we will also have to use the max value, but since previously we have already calculated our max value, it makes no sense for us to use that over here. So what I'm going to do is I'm going to create a temporary variable, and this temporary variable I'm going to calculate the max value. Then for the calculation of min value, basically I'm going to use the previous max variable. Now because this is the temporary variable, we will assign this value to max. We will also have to keep on updating our result variable as well. That's it. Basically when the loop ends, we should have our answer populated in the result variable. So let's return that. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions, and I would be posting this solution in the comments so you can check it out from there. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code medium problem, word break. Let's understand the problem statement. So basically we are given a string s, and we are also given a dictionary of string word dict, and we need to return true if s can be segmented by all the words that are given inside the word dict. So if we look at the example, suppose our s is LeetCode, and the word dict we are given is first set is leet and second set is code. We can clearly see that this LeetCode we can generate from whatever the values we are given in this dictionary. So we will return true in this case, and we are also mentioned that we can use the same word multiple times. So suppose if this problem was LeetCode, code, something like this, we would still return true because or whatever words are, we can still make it through this dictionary. But if we were given some wording like this, that LeetCode LEE, so up until this point we have the words that we can make from this dictionary. The thing is, this LEE, there is not a specific word given for that. The word we are given in the word dictionary is leet, so it does not match. So in that scenario we would return false, otherwise we would return true. Okay, let's try to understand that what would be the brute force approach. Suppose we are given s is equal to ESPN, and the dictionary we are given is E, S, P and N. So we can clearly see that all the words are present in the word dictionary, so the answer should be true. And in the brute force solution, we are going to use a bottom up approach. So and in this video I'm going to show bottom up approach all the way, even for the optimal solution. So this can also be solved as a top down approach. So let me know if you want to make a separate video on that. And there is also one more thing to consider. Suppose we are given something like s is equal to null value or empty string, and in the word dictionary we are given some elements like a, b, a b blah blah blah. So this case we can clearly return as true. Why? Because this empty element will always be there, though it might not be showing. But the thing is, if there are no elements in our given string, we can always return true, because the emptiness is also exists in this word dictionary. So we are going to use this logic, and let's see that how we can build our brute force. So we are doing bottom up, so we are starting from the lowest value and eventually we are going to make the whole world. So the first value we need to, so we are at the 0th position. The first value we need to make is simply the word break of a value e, and the word break of value e is very easy to calculate. We only need to check that whether the word break of empty string and the value e exist in this given word dictionary or not. So basically, and we know that if there is an empty string scenario, this will always be true, because I just explained it to you how. So we only need to see that whether this e exists in this word dictionary or not. If this exists, we can clearly say that this is true, and we can denote the value of word break of e as true. Now the second decision we can make over here would be to see the word break of two elements, so e and s. And how can we determine the word break of e and s? Well, again, it's simple. So we need to we have two ways to determine that. Either we can do a word break of empty string, and we can check that whether this es value is present in this word dictionary or not, or we can do a word break of value e, because we know that this is always true. The word break of empty is always true, so we can do a word break of e, and we can check that whether the value s is present in this given word dictionary or not. And word break of e, we already know how to do it. For this word break of e, we need to do word break of empty, and we need to calculate the value of to see that whether this e is present or not. The third option over here we can have is and you guessed it correctly, the word break of three elements, so e s p. And for this three elements, we again have three more possibilities. So word break of empty string, and we need to check that whether ESP, all these three exist in this scenario, or we need to check that whether the word break of this E and SP exist, and the word break of ES and P exist. And yeah, so these are the three ways we can determine that whether the word break of ESP exists. The next option we have is the final scenario, that whether the word break of ESPN exists or not. And to check that, we will have four possibilities. So first one is that we check the empty string, and we check whether the ESPN, the whole word, is present in this word dictionary or not. Or we can check that whether the word break of E is present and SPN, these three values are present or not. Or we can check that word break of ES is present, and we can check for PN. Or we can check word break of ESP, and we can check the value N. So these would be the four cases where we need to calculate all of these, and for every single one of them. So even in order to calculate this word break of E, we will use this method. To calculate this word break of ES, we will calculate this whole method. And yeah, so this would be the brute force solution. Eventually we would find that whether we are able to make this ESPN or not, and whatever result we get, we just need to bring it upwards, and we would be able to find the solution. So this solution works, but it works in a very horrible way, because at every single location we have two possibilities to make, whether we want to keep that element or not, and our decision tree keeps on growing and growing and growing. And though we will come to the correct solution, but it's gonna take us a lot of iterations to achieve that, because over here you can see that we only had these four elements that we need to consider. We generated such a big tree, and over here most of the values we did not even completed the whole sub iteration for them, because I would be running out of space. So the time complexity, as you have guessed correctly, for this approach is actually big O of 2 to the power n, because at every single location we are making two decisions, which is pretty bad. And why it is 2 to the power n? Because we are calculating everything at the same time. So see that, do we have a room where we can save whatever we have calculated before, and can we use it further down the road? Of course we can, because notice over here this w word break of e, we are using it over here, but we have already calculated its value. So why do we need to calculate its value again over here? Same goes with this word break of es. We have already calculated the value over here. So why are we repeating this whole process? There are a lot of repeated effort. This is repeated, this is repeated, this is repeated. We have already calculated all these values. So somehow if we just create a cache, we store that whatever the values we have calculated so far, and keep track of that cache, and whenever we need to encounter that whatever value we are calculating right now, we can simply check that whether that has already been calculated, and using that we can actually come up to a better solution. Since you guessed it correctly, that because we are using something that we have already calculated in past, we are keeping a track of it in some form, and we are using it further down in our next iterations. So basically we are using the most beautiful thing in the computer programming, the dynamic programming approach. In the dynamic programming, we are going to create a single array of size whatever the given input string is, and based on that particular array we will calculate all the values that have been calculated so far. And because this is a bottom up approach, we are going to start filling up array from the 0th position, and we will reach at the end, and in the end, after all the calculation, we will just simply return whatever the value we have calculated over here. So let's see that what would be the optimal solution. Suppose again we are considering the same example. S is equal to ESPN, and the word we are given is ESP and N. And now let's create a new data structure called DP of an array that is of size 4, and there would be, so 0 1 2 3 4. Now we know that this 0th position would always be true. And why it would be true? Because this indicates that for DP of size 0, which means that for string of size 0, does the word dictionary contains this particular element or not? This is what this DP is representing, that at every single location, whether the value of that length of the character, is it present in this word dictionary or not. So DP of 0, we know that that's an empty string, and if it is an empty string, we can determine the value as true. So this would become our base case, and this is very important to identify in a dynamic programming problem, that we need to have a base case. And initially we would set up all the other values as false, and we will run our iteration. So let's see that what each of these values are going to represent. And you guessed it correctly, that this value represents a word break of 0. This represents the word break of 1. So in this case it would be the value E. This represents the word break of value ES. This represents the word break of value ESP. And this one represents the whole word, so word break of the value ESPN. And yeah, so at the end, whatever result we find over here, if we just return that, that would be our perfect solution. So example we are going to take is the same one that we have been discussing. So the S is ESPN, and the value of word is E, SP and N. And we know that our dynamic programming of value 0, this is our base case, that is true. So what we are going to do is, we are going to iterate over, starting from single element, we are going to keep on increasing the size of our element. Depending on the size of our element, we are going to fill up this DP array, and at the end we will just return the value. So initially we will calculate just for value E. So DP of 1 would be calculating the word break for value E. So let's see that whether this value E is present in this word dictionary or not. So the value is present, so we can say that the DP of 1 is true. Okay, this is good. Now let's check for the second element. So for DP of E2, this would be calculating the word break for ES. Now we know that we can break down this word break for ES in two parts. Either we can do like an empty string and we can check for this value ES, or we can do the word break for the value E and we can check for the value S in this given word dictionary. If we go for this one, ES is not present over here, so we are left with the second approach. In the second approach, we know that word break of E, which means this DP of 1. So DP of 1 is already true. So we can say that, okay, this is true. Now we only need to check that whether this S is present or not. So S directly is not present in this word dictionary, which means that this condition is not satisfied, this condition is not satisfied. So we can say that the value for DP of 2 is actually false. So we will just mention it over here that this is false. Okay, let's try to calculate the DP of 3. So DP of 3 means word break of elements ESP. Word break of ESP means three things. First one is that we can directly calculate to see that if ESP is present or not. This is not present, so this condition won't work. Second one is we can check that whether the word break of E is present and the word SP is present or not. And third we can check is whether that word break of ES is true and the P is present. Now the thing is, we already know that this condition is not true. The ESP is not present, which means we need to check these two conditions. Now let's check this bottom condition first. So word break of ES, this word break of ES is actually in the dynamic programming array, it's the second position. So DP of 2, DP of 2 and the value P. Now we know that DP of 2 is already false, which means that this condition will also be false. So we don't even need to calculate, and we don't even need to check for this element P in the word dictionary, because we know that since this DP of 2 is false, we can just ignore this case and let's focus on this one. So word break of E, which means that DP of 1. So DP of 1 is true. If DP of 1 is true, which means that at least this condition is true. Now we need to check that whether SP exists in the word dictionary or not, and SP also exists in the word dictionary, which means that DP of 3 we can consider this as true. Let me also put this one on this side. Now let's calculate the DP of 4, which means word break of ESPN. So again, this will have 4 conditions. Now I'm going to write this in a different manner. So we can also say that this is DP of 2 and PN, because DP of 2 represents this ES. And we can also say this as DP of 3 and N. And yeah, these are the 4 conditions we need to check, and if any of them are true, we need to return true over here. So let's check the first one. Does ESPN exist in over here? No, it does not. So this is false. So WB of E is true. So at least one is true, but SPN does not exist over here, which means this is also false. Now DP of 2, this is already false, which means we don't even need to calculate and check for this PN. Now the last one is DP of 3. DP of 3 is true, so this is good. Now we need to check whether N exists over here or not. So N exists over here, which means this is true. So we find one case that is true, so which means that over here we can mark this value as true. And remember that this given string, this is of length 4. So because this is of length 4, we simply need to return whatever value we find as DP of 4, and that is true. So in this scenario we'll just return the answer as true, and that would be our solution. This is a very good solution. because notice that we are already calculating what we need so far. We are keeping track of it at every single position. Because we have calculated these values, we are able to use it effectively and come up to the result. Let's calculate the time complexity. So we are iterating over all the elements at least once, so that is an n. Then we are also creating substrings. So for every value n, there can be n minus 1 substrings, which means that we need to do additional n work. So the time complexity would be big O of n cube. So this is also pretty high time complexity, but if you compare it with 2 to the power of n, this is actually way lesser. Because this time complexity that can still be calculated, and this is a polynomial time complexity. But the thing is, this one is exponential, and yeah, we need exponential salary but not exponential time complexity. So let's code up the solution. Okay, let's create a boolean array to store our cache, and we'll name it as dp. We'll assign its length to s.length plus 1, and we know the base case where dp of 0 would always be true. Also for this word dictionary, this is a list, so we are going to create a hash set that will store the strings, and we will store this word dictionary over there, so it becomes faster for us to access the word dictionary. We'll just name it word set. Now I think we are all set to start our loop, so we'll create the two loops. Notice we are starting our loop from I equal to 1 because we don't need to we already have the value for I equal to 0, and we are going to start the second loop from 0th position, and while j is less than I, because we only need to go up to ith point. Now inside the loop, first of all we will check that whether the dynamic programming for the jth value exists or not, and this is what I already explained in the solution explanation, that if this is true, then only we check that whether the word set contains the substring. So we'll use a substring method, and we will provide the parameter as j and I, because j is less than I. And if this is true, basically we just need to assign the value of dp of I as true. And yeah, I think that's it, and we don't need to do anything. And at the end of the loop, we can simply return the value of our dp of s.length. And yeah, also when we find this value dp of I is equal to true, which means that we can break out of this inner loop, because there won't be another pair that we need to calculate, because even at any moment if we find a single true, that's sufficient for us. So let's try to run this code. Okay, looks like our solution is working. Let's try to submit this. Yeah, our solution works. It is accepted by LeetCode, but notice that this solution is actually pretty slow. It is taking a lot of time, and it is not as fast as our other solutions. So there is one trick we can do is, rather than going from from j equal to 0 to I, we can actually go in reverse. So we can start the position of j equal to I minus 1, and we can see that whether j is greater than or equal to 0, and we will do j minus minus. That way we would be able to find this a little bit faster. So let's try to run the code first. Yeah, this works. Let's try to submit it and see the significant difference. Now our solution is much faster, and even if you see over here, previously this one was running in 13 milliseconds, and this one is now runs in 4 milliseconds. Basically we are just eliminating and breaking out of this inner loop faster. We are not doing anything special. So yeah, this is just something to keep in mind. And yeah, I hope you liked it, and I will be posting this code in the comments. Now the next problem we are solving is called longest increasing subsequence. This problem actually has two optimal solutions. First optimal solution is a dynamic programming solution that can solve the problem in big O of n square time, and which I'm explaining in the first part of this video. Now for the same problem, there is an even better solution which is very tough to understand, and that is something that is using a patient sort algorithm. So the thing is, if you are only considering and trying to learn dynamic programming, I think part one of the solution should be fine. If you also wants to learn the optimal approach for the same problem, you can also see the part two of the same question. So there are going to be two solutions for the same problem, and now let's start understanding the problem statement. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code medium problem, longest increasing subsequence. And I have decided to break this video in two parts. In the first part, I'm going to discuss the brute force solution and an accepted solution for this problem. And in the second part, I'm going to show the optimal solution. But the thing is, the optimal solution is really difficult to achieve, and it's a little bit tricky to come up with. So let's understand the problem statement. Basically, we are given an array of numbers, and we need to find the length of longest strictly increasing subsequence. So subsequence means that suppose we are given an input like this, 1 2 4 5. So we can say that the value 2 and 5 is actually a subsequence of this given initial problem. Let's try to understand that what is the input given. So we are given over here an 18, and this example, and if we take these numbers 2 3 7 and 101, this would be our longest increasing subsequence. So if we get rid of this value 5, this would be the longest subsequence we can make, where all the values are in increasing order, and the length of all the values would be 4, which is what we need to return as a part of this output. So once we know the problem statement, let's see that what could be the brute force approach. So in the brute force approach, we are simply going to take every single subsequence that we can possibly make, keep a parameter that tracks the length of any subsequence, and eventually at the end we should be able to find a subsequence with the maximum length. So let's take a small example and see that what are the possible subsequences we can make. So suppose our given input is 5, 3 and 8. I'm only taking 3 elements because I need to show that why this approach is bad and what are the possible subsequences we can make out of this. So let's start making all the possible subsequences. The possible subsequence would be 5, 5, 3, 5, 8, 3, 3, 8, 8 and 5, 3, 8. These are the possible subsequences we can make out of only these given three problems. And if we check the length of each of them, and if we find out the property that which one is a strictly increasing order, we found that this is the strictly increasing order, and the maximum length we can achieve is 2. So this solution works, it works fine. The problem is that notice that we are only given 3 elements over here, and based on this 3 elements we were able to make almost 7 subsequences. Mathematically it's actually 2 to the power of 3 minus 1, and for any single given n, this is the number of subsequences we can make. So suppose we are given n values in the given input, the number of subsequences we would be able to make would be 2 to the power of n minus 1. So if we calculate the time complexity, we can just say that the time complexity is actually big O of 2 to the power of n, which is extremely horrendous time complexity, and this is exponential. So even with enough numbers, even NASA won't be able to solve this one. So let's move on to the next approach. Now we want to find the better approach, and we know that the way to do is to use dynamic programming. The thing is, how can we identify that we need to find the solution using dynamic programming? Also, what dynamic programming solution are we going to use? So I'll be discussing both the things in next portion. And first of all, let's take an example. We'll try to see how we are going to solve it. Then I'll show you how we can determine that we are using the dynamic programming, and after that we would be implying the result, and I would be showing you the coding example. Suppose our given input is, suppose this is the input given, and we need to find the longest increasing substring. So just by looking at the given example, we can determine that the longest increasing substring actually exists between 7, 8, 16 and 27. And now let's see that how can we come up with this solution. How do we determine that this is dynamic programming? Suppose we are just given an example like this. We are just given one value, that let's say the value is 7. If we are only given 7, what is the longest increasing substring we can make? Well, the answer is quite simple. We can simply make just one substring of length 1. So this actually becomes our base case, that if we are only given one value, we are guaranteed to have at least one substring that would be the longest increasing substring that we can make. So now let's see that how can we use this logic. Say that for all the given elements, basically there exists one substring at least that is the longest increasing substring. Let's just mark all the values as 1. We know that if we are only given the value 10, the longest increasing substring we can make would only be 1. But when it comes to the second value, now we have something to compare to. Suppose the 7 value, if this was greater than 10 and we only had 2 values, we can say that at the second position, the longest increasing substring that we would be able to make would actually be whatever we have made so far plus 1. So we would have been made 2, but over here that's not the case, and over here the value 7 is actually less than whatever we are given the value before that, which means that the longest substring we have at the value 7 would also be 1. So this would be true in this case. But now when we come to 8, we have two possibilities. What are the total substrings we can make up until this point, up until 8? Okay, so for this value 8, what is the one thing that we can determine? We can basically determine that there are 3 possibilities of the substrings we can have and we can compute. One possibility is we could have a substring like 10 and 8. Second one is we could have substring 7 and 8, and third one is we could have a substring 8 by itself in case if all the values before 8 are actually greater than 8. So in this scenario, from 10 to 8, we know that 10 is already greater than 8, so we cannot create a substring over here. So let's ignore this scenario. For the second scenario, 7 to 8, actually this is a valid increasing substring because 7 is less than 8 and it comes after it. So what we can determine is that the longest increasing substring we can make at value number 8 would be whatever the longest increasing substring we have made up until this point. So whatever the longest increasing substring we have made for the value number 7 plus 1, because 8 is coming after 7 and 8 is just one step after it. So we can say that longest increasing substring at value number 8 would actually be whatever we have found up until longest for the longest increasing substring of 7 plus 1. And this is how we can determine that this should be solved as a dynamic programming problem, because in dynamic programming, basically whatever calculations we make in the past, we keep track of them in some way, either through an array or storing them in variable somehow, and based on those results we actually use it in upcoming future calculations. so that we don't have to calculate everything from the scratch. So this is one way we can determine that this problem should be solved using dynamic programming, because if we just look at the problem, we understand that we need to find the longest increasing substring, which means that we need to keep track of whatever we have calculated so far in the past, and using those results we would make decisions that whether we want to keep this current value or we want to ignore this current value. So this is a very important thing to keep in mind, and this is basically the core concept of finding the pattern whenever you are given that whether the problem is dynamic problem or dynamic programming problem or not. Because in the interview, the interviewer is not going to tell you that hey, this is a dynamic programming problem and just go and solve in that manner. So now let's again continue with our example. So we can determine that currently the value at 8, the longest increasing substring we could make at value number 8 is 1, but we just found that from 7 to 8 we can actually make a substring as well. So this bit would become actually 2, and we can say that up until the point of 8 the longest increasing substring we can make is actually 2 and not 1. Now let's move forward. Now let's consider for value number 5. At value number 5, let's again compare from 10 to 5. We cannot do anything because 10 is already greater than 5, so there is no point of doing this conversation. Let's compare 7 to 5. From 7 to 5 we cannot do anything because 7 is greater than 5 and also 8 is greater than 5. So at value number 5 there are no values that are less than 5, so at value number 5 the longest increasing substring we can make is actually size 1, because there does not exist a smaller number before 5 in our given input. So we'll keep this 1 as it is because we have already made all the calculations. Now let's calculate for this value number 16. And actually for value number 16, if you notice that all the values are smaller, so this would be a very good point for us to understand that how everything works. So from 10 to 16 we notice that 10 is smaller than 16, so there is a possibility. And basically we can say that whatever the longest increasing substring we have found at 10, if we do it plus 1, that would become 16. So the longest increasing substring for 10 we have found is actually 1, so 1 plus 1 equals to 2. So let's just update the value 2 over here, and now let's move on with our calculation. So we are done with this 10. Let's calculate with 7. So if we do 7 to 16, actually again we will do 1 plus 1 because LIS of 7. So 1 plus 1 is again 2. We already have 2, so there is no point in updating the value. Let's ignore this. Let's do again with the value 8. So from 8 to 16 we know that the value of 8 is actually 2. So over here at value number 16 we can say that increasing substring at value number 8 plus 1, so it becomes 2 plus 1, and 2 plus 1, okay, I made a mistake. I think this is 1 that represents 5, and the value for 16 is actually over here, so I'll just write it down. So LIS of 8 plus 1 is actually 2 plus 1, which is 3, which is greater than whatever the longest increasing substring we have so far. So which means we can update this value. So over here the longest we have found so far is actually 3, and now we can also create one more substring from 5 to 16. If we calculate from 5 to 16, we found that the value is actually 1 plus 1 would be 2, which is not greater than whatever we have at 16. So we can say that up until this point 16, the longest substring out of all of these values we can make is actually 3 for the values up until the point of 16. And let's move forward with our calculation. So again the next value is 27. 27 is greater than all the other values. So if we do 10 plus 20, 10 to 27, we would find the value as 2. We'll do 7 to 27, we will find the value as 1 plus 1, again 2. We will do 8 to 27, we would find the value 2 plus 1 as 3. Again we will do 5 to 27, the value we would find would be 2, and at the end we would do 16 to 27, and we know that the value at 16 is 3, so we would be able to find the value as 3 plus 1. And because we have calculated all these results, we don't have to do calculations all the way from beginning, and we are just able to use the results we have stored so far. So we know that the maximum value we can find is 3 plus 1. So we would update the value at longest increasing substring at value number 27 to 4, and then we come to our last value 9. So, and again we will do the whole thing for 9. So 10 is greater than 9, so we cannot do anything. 7 is less than 9, so we can for this one we can have the value as 2. 8 is also less than 9, so from 8 to 9 value we can have would be 3. 5 is also less than 9, so from 5 to 9 the value we would have would be 1 plus 2, 2. From 16 to 9 we cannot do anything because 16 is greater than 9, and from 27 to 9 we cannot do anything because 27 is definitely greater than 9, which means that the maximum value we could have find so far over here for 9 is actually 3, and that comes from the 8 plus 1. So we will update the value over here as 3, and now we just need to find that what is the maximum value we have found in this array that we have created based on the calculation. So basically clearly we can see that this value 4 is the maximum value we have found, and that would be our answer. That is what we would be returning as longest increasing substring. The thing is, we actually don't need to iterate over the entire array again. We could have actually done this when we are calculating, or when we are making this array. We could have just keep track of one parameter called max, and we would compare it with whatever the value we calculate at each location. So whenever we find a new maximum value, we'll just store it in this value, and at the end of our loop, in this max parameter should have our final solution, and we can definitely return this, and this solution would work perfectly fine. Now let's calculate the time complexity. So basically the time complexity for this one would be big O of n square, and it's pretty simple to understand that, because for every single element we are basically taking all the elements before that and comparing it with whatever the element we have. We did the same for every single element. So for n element n, we might have to compare it with n minus 1 values, so the time complexity becomes big O of n square. And if we calculate the space complexity is also big O of n, because we need to create this additional array to store all the values, and this is a good time complexity and good space complexity compared to our brute force approach. Remember our brute force approach, the value we had was actually 2 to the power of n, which was way higher. This was almost exponential time complexity, and we have done significant improvements from this one, and we have actually moved to n square. So this solution would work perfectly fine in any interview, and I'll move on to coding. But the thing is, I would be making another video to explain that how can we solve the same problem using n log n complexity, and this is actually pretty ideal. And if you can achieve this in any interview, if you can come up with this time complexity right then and there in an interview, you can be guaranteed that you would be placed in any company you want. So let's move on to coding now. So first of all, we will create a new array called lis, and we would create the array of size, whatever the size we are given for the input nums. And we will initialize the array with value 1. We will also create a parameter called max that will keep track of the maximum longest increasing subsequence inside the loop, and we will initialize the value as 1. So now let's create our two loops. So first of all, we will create a loop that is starting at position number 1, not 0, because we need something to compare to, otherwise all the values would be just 1 before that. And we will run it till the length of the given array. Well, now this would be our inner loop, and we would start it from position 0 and we will run it all the way up to the position I. Now inside the loop, first we need to determine that whether our current I that is on the right side of the array is actually is actually greater value than whatever our j is. If that is the case, then only we would move forward with the calculation. So if I is greater than j, now we will do our calculation for the dynamic programming. So the value of I would actually be the maximum value we can achieve for whatever LIS of I we already have, or 1 plus whatever LIS of j we have achieved. And this would be our recurrence relation. I guess that is what it is called in dynamic programming. So this is just to keep in mind that yeah, if you mention that this is the recurrence relation, it sounds really good impression. It sounds cool as well. And also we check that whether the current LIS value is our max or not. So we'll just check the existing max value with the new LIS that we just created. And yeah, I think that's pretty much it. After this loop runs, we can simply return whatever we have found for the value max, and this should be our answer. Let's try to run the code. I think we made some silly mistake. Yeah, looks like our code is working. Let's try to submit it. And our submission works, but if you notice that our submission is not actually the best submission, it's only faster than 55.54% of the online submissions, and that is because our this solution is actually work in big O of n square times, so n to the power 2. But there is another solution that actually runs in big O of n log n time, and I would be creating a new video explaining that solution. And this is actually a pretty interesting solution. It's actually a sorting algorithm that we are going to use to achieve this. So hope you like the video. Let me know what you think, and if you have any suggestions, just feel free to reach out to me. Our goal is to get employed in any FAANG company, and until we get there, we are not gonna stop. So hope you like it. Thank you. So basically the previously when I solved this problem, I mentioned in that video that I was solving it in big O of n square time, and this would be perfectly good and reasonable to expect from any candidate in an interview. But the thing is, if you want to be an exceptional candidate, if you want to make sure that you don't leave any gaps in your FAANG journey and your so you need to know these things. So that's why I'm creating this video, and in this video we are going to solve this problem in actually big O of n log n time. And the way we are going to do is something called as patience sort. So let's take our custom example. And as I have mentioned previously, that it is very important to make custom examples, because using those custom examples you can determine that you have the ability to think and make sure that how can you create your own test cases. So this is our example, and it's quite a long one, but the thing is I need to make sure that I go through all the possible aspects in the given example, and that's why I took so many integers. So it becomes absolutely clear in your mind that how we are going to achieve it. So basically, at any given location, we can either have a null string, so a subsequence that has no entries, a subsequence that has just one entry, a subsequence that has two entries. So this is null, one entry, two entries, subsequence that has three entries, subsequence that has four entries, and so on. So, and our aim is to find out a longest increasing subsequence that we can achieve. So for this one, we are going to use a couple of arrays. We are going to put them in a different manner, and as you would have guessed that because the time complexity we get is actually n log n, somehow we are going to use binary sort over here. So let's start the problem. First of all, we are going to create two arrays. First array is to keep track of the longest increasing subsequence that we have found. So whether it's value 1, of value 2, of value 3, whatnot. And second thing is we are going to store the last digit for any given longest increasing subsequence. So what I mean by this last digit is that suppose we find an increasing subsequence over here, that the values 5, 16 and 27 is an increasing subsequence. So in the longest increasing subsequence array, we are going to note an entry as 3, where because the length of values are 3, and the last entry we have in this subsequence is 27, and the combination of these two is going to allow us to create some pretty interesting things. So let me go over the example, and I would be explaining every single time what we are doing and how we are finding it. And at the end, I'm going to show you that what could be the intuition behind this. So at first location 10, basically we don't have any substring so far. So the current substring we have found up until this point 10 is just a single value 10. And in this single value 10, in our LIS, we can create an entry like 1, and the last digit we have for this entry 1 is 10. So we are good so far. Now let's move on to the next one. Now next entry is, currently we only have a substring 10. Next entry we have is 7. Now we cannot create an increasing subsequence just by these two pairs, because obviously 10 is greater than 7. But the thing is, we can replace this 10 with this 7, and how we can replace it is because up until this point 10 is a substring of length 1 and 7 is also a substring of length 1. So both of us are just same. But the thing is, whenever we move forward, all the values that are greater than 10 will also be greater than 7, which means that suppose we have value over here 11, 15, 18, something like this, and if we take it with 10, we would be able to create a longest increasing substring like 10, 11, 15, 18. But the thing is, same thing can be done for 7 as well. So it makes no difference that which entry we keep. But if we have a value that is between 7 and 10, 10 won't be able to do anything in that case. Suppose we have an entry like 8, 9, 11. So in this case, if we would have just considered 10, the longest substring we would be able to make is 10 to 11. That's it. But from 7, we can actually make 7 to 8, 8 to 9, and 9 to 11. This would be of size 4 and this would be only of size 2. So it is in our interest to keep 7 as our longest increasing substring and not 10, because value of 7 is actually less than it. So we will replace this 10 in this array we have created. So currently the last element we have becomes 7, and this 7 is also of just length 1. So we have only kept this one entry, and we have basically just discarded it. We have went over it and we didn't find anything good. Now at this point we only have a substring of 7. Now comes the value 8. Now 8 is greater than 7 and 8 is in itself a higher value. So we have two possibilities. Either we can keep 7 as it is as a longest increasing subsequence, or we can have a subsequence like 7 and 8, and we are not appending 8 behind this 7. We are creating that the longest increasing subsequence we have so far of value of size 1 is still 7, but this one is, we are creating a new subsequence that is of size 2, and we are appending this 7 behind 8. So which means we would be creating a new entry over here in our longest increasing subsequence of value 2, and the last element of this value is actually 8. But the thing is, meanwhile the first element is still 7, because we only up until this point, if we consider a substring that is of only value that is to be only of size 1, the best element to choose for size 1 would be 7 because it is the smallest. And this is the main logic behind the patient sort. So let's move on to the next element. Again we go to value 5 now, and the substrings we have so far are 7 and 8, and now we have this 5. So we cannot append this 5 over here, we cannot do anything with this. But the thing is, if we consider these 4 elements and if we consider the substring of size 1, 5 would be the most ideal candidate and not 7, because 5 is actually less than 7. So it is in our interest to replace this entry 7 with the entry 5, and we will update in our array with entry 5. Let's clean this up a bit. Now due to space constraints, we are going to write down our subsequences over here. So far we have found 2 subsequences. One is just 5, that is of size 1, and second one is 7 and 8 that we have stored over here, and we are keeping track of the last digit that we have appended. Again let's consider 16. So now for this 16, and if we consider the last 2 elements, 16 is definitely greater than 5, but there is no point in appending 16 at 5. It is in our best interest to append 16 behind this 8. So our algorithm is basically, what we are doing is we are taking the value from the input, we are checking in our last array to see that what is the best position to fit that value, and the best position to fit that value is to keep the increasing order intact, because notice that previously the value we had was 7 and 8, that was increasing order. Now the value we have is 5 and 8, that is also increasing order, and now the next value 16 comes, we can actually append it behind 8. So after 8 we can create a new entry, and we would do that. So we would create a new entry called 3, and why we were able to do a new entry is because this 7 and 8, we are not going to replace 8 by 16. We are actually going to leverage this 7 and 8 because they are already a subsequence, and our aim is to find the longest increasing subsequence. So why would we replace 8 with 16? It's actually in our favor to keep this 7 and 8 and create a new subsequence 7, 8 and 16, so that we can use, because suppose if all the values that come after 16 are like 9, 10, 11, 12, 13, and if we have created a subsequence called 7 and 16, so these all values we would not be able to consider them as our longest increasing subsequence because we don't have this 8. But if we have this 7 and 8 over here, and if these values comes after 16 and we have created a separate entry like this one, 7, 8 and 16, so this is separate in itself, we can actually append all these 9, 10, 11, 12, 13 values behind this 7 and 8, and this would be our longest increasing subsequence. So I hope that this makes things more clear that why we are choosing to have a new 7, 8 and 16 as substring, and we would create a new entry in our array as well. So now these are the three substrings we have. Next value is 27. So 27 is again greater than this 16. So now we are going to create a new entry 7, 8, 16 and 27, and we are going to have a new entry in our LIS with value number 4, and we are going to add the last digit as 27 over here. I hope that what I'm doing is understandable, that why we are actually creating this new entry from the given input. The next value we have is 9. So let's see that where is the best place we can fit this 9. The best place we can fit this 9 is actually after 7 and 8. So like this 9. The thing is, we are not going to replace this 7 and 8 with 9, because up until this point, up until 9, if we see the best pair with 2 entries only, that with the least value is actually 7 and 8. There are multiple pairs that create the that are creating the longest increasing subsequence of length 2, like 5 and 16, 16 and 27, 5 and 27. The thing is, they're all greater values. If we see the last element over here, 7 and 8, the last element is the perfect fit. So that is why we are going to keep the 7 and 8, and we would be creating a new entry at this place. So we are going to replace the 16 with value number 9. So let's update this in our array as well. So for the value 3, the best we can find is 9, and that would be the subsequence 7, 8 and 9. So far we are keeping track of all the subsequences that we have found with the values 1, 2, 3 and 4, and we are also keeping track of the last digit that we have calculated so far. And because all the values are in an increasing order, it becomes very easy for us that whenever we find any new value like this, it becomes pretty easy for us that where we are going to add it in this array, and which value we are going to update it. So this is the main logic behind patient sort. Now the next value is value number 1. So where in this array we can store value number 1? It's pretty simple. We can only store it at position 1. No other position we can store. And based on this, we can say that up until this point, if we only have to create a subsequence of length 1, it would be the most ideal to have the last digit as 1, because all the values after that would actually be in an increasing order, and we can replace this 5. In our list of subsequence, we will have entry 1 over here. Now let's consider this value number 13, where over here we can add this value number 13 so that it would give us the most value. And actually we should not be replacing this 9 with value number 13, because we are not trying to achieve a substring like this. Rather than having 7, 8 and 9, we are not trying to get 7, 8 and 13, because that is not in our favor. Because notice that this is already existing and 13 can be appended next to it. So what we can do is, actually we can replace this 4, the subsequence with 4 entries, with this 7, 8, 9 and 13. So our new subsequence would become 7, 8, 9 and the 7, 8, 9 and 13. And why we are able to replace the 7, 8, 9 and 13 with previously 7, 8, 16 and 27? The reason is quite simple, because both generate the value 4, so that is okay. But the thing is, with this 9 and 13, we have higher odds of making longest increasing subsequences for the upcoming values, and which we are going to see right for with the next value. So we will update the value 13 over here, and so far these are the 4 subsequences we have. Now the next value is actually 15, and imagine that if we had kept this value as the substring of 4 values, we won't be able to insert 15 over here, because though both of these were same, 15 is easier to be appended over here, but it cannot be appended over here. So that is why in the previous step we actually replaced this value 4 with 13. So I hope this makes it more understandable. Now let's see that what we can do for this value number 15. So the logic is quite simple. We are simply going to append this value number 15 behind this 13. So the new substring, and we are going to keep the value number 7, 8, 9 and 13 as a 4 substring, as a substring of length 4, and we are going to create a new substring 7, 8, 9, 13 and 15, and this would be a new entry in our array. So we will have a substring of length 5, and the last digit for that would actually be 15, and this would be the end of our array. And since we have reached to the end, we just need to iterate over this one and find out that what is the biggest length we were able to find, and we just simply return this value. So this is as simple as it can be. And why we are able to achieve it? Because at every single location, for every single element, we are trying to see that where we can fit that element that best represents that position, and based on it we were keeping track of the longest increasing subsequence. So basically we were intellectually choosing our own longest increasing subsequence, and we are also keeping track of whatever we have calculated in the past, because if we were to choose a value of 3, that what is the longest increasing subsequence up to the point of 3, we can easily say that hey, it's this one, and the last digit is actually 9. So if we find some better digit, it becomes pretty easy for us to calculate that where we are going to append that value. And I hope this makes things more understandable. Now let's calculate the time and space complexity for this one, and it's pretty simple, that at any given location we are iterating over the entire array, and for any single position we are checking that where we can store that position in this given new array that we are trying to create. But the thing is, this new array is already sorted, so because it is sorted, we can actually achieve that in log n time, and initially we have to iterate over this entire actual input once, so that will take n time. So basically we are calculating this whole approach in big O of n log n time, which is a very good time complexity, because if you remember correctly, originally for the brute force approach, our time complexity was 2 to the power of n. For the second accepted approach that I completed in last video, our time complexity is actually n square. The thing is, n log n, this is a thing of beauty. Now let's move on to coding. And if you still don't understand the concept, I again ask you kindly to go over this example again, because if you can master this, sky's the limit for you. So let's do the coding now. Let's create a new array list. We can start by adding the first element, because the first element would actually be the first list of size 1. And then we will initialize our loop to iterate over the entire input array, and again we will start the loop from second position, I equal to 1. Inside the loop we need to find that whether the given number is it actually greater than whatever the last value we have in the subsequence? If it is, we need to append it to the subsequence. So and we can just add it to the subsequence. If not, we'll need to run the binary search. So, and over here we can just create a new function for to run our binary search, and in input we will provide the substring and current ith value we have. And now let's create method for that. Inside the loop, first of all, we'll create a left and right variable. So left would be of size 0 and right would be of whatever the size we have for the integer for the given in substring. Now we will just run a condition that while left is less than right, we are going to calculate the mid pointer, and then if the mid pointer is already existing, we simply return that value. If not, we either move on the left side or right side. So we'll do left is equal to mid plus 1, else we can simply do right is equal to mid, and after the loop we can return the value of left. Now over here in the J we are receiving whatever the value of left we got, so we add the subset to our existing subsequence. That should be the logic. So after the return we after the end of the loop, we just need to return the size of the list, and this should provide the longest increasing subsequence. Let's try to run this code. Looks like we put the values out of order. Yeah, looks like our solution is working. Let's try to submit it. And yeah, see, our solution is actually faster than a lot of other submissions, and that is because our runtime is actually n log n. And I'll be posting this solution in the comments, and I hope you like the video. Thank you. Hello friends, hope you are having a fantastic day today. So now we are going to solve an awesome LeetCode problem called partition equals subset sum. Now we can see that this one is a LeetCode medium problem and also an extremely well-liked problem. So let's understand the problem statement. Basically, we are given an integer array called nums. Now we need to return true if there can be a partition in the array such that the two subsets that we make with that partition has the sum that is equal of the sum of the elements in both the subsets, and if that is not the case, then we need to return false. Now I know that the wording of this problem is actually not the best way to put the problem statement, but let's try to understand in simple terms. We are given an integer array. Now we need to, if we can create two partitions such that sum of all the elements in this partition and sum of all the elements in this partition, if both are equal, then we need to return true. If that is not the case, then we need to return false. Now let's try to see some examples. If we see this first problem, we can see that there are 4 elements and we can create a sum like this, that is sum of 5 plus 5 plus 5. So this can be one partition, and second partition can be this value 11. And if we check the sum of both of them, they turn out to be 11. So in this case, we can return true, that we can create a partition such that the sum of all the elements in both the partitions are equal to each other. Let's try to take one more scenario, 4 3 6. Now in this case, we cannot create a partition where the sum is going to become even. If we create a partition like 4 and 3 and second partition is 6, then it doesn't work, because this is going to be 7 and this is 6, and there are no other partitions that you can make. So in this case, you will need to return false, because no such partition can be made. Next, let's see one more example. So in this case, we can create a partition like this, 1 2 and 3 as first partition, and second partition is 6. If we do sum of like either partition, eventually we would get the value 6 as the answer, and this is what we need to return. Because we are seeing 6 partition being made, we need to return true in this case. Now if we see the brute force approach for this problem, it is quite straightforward. Brute force, or the most simple way to solve this problem, would be to check for every single possible partition. So we can start from the first element, and we can try to start every single possible partition. So we can create a partition where one value only contains 5 and the other value contains these 3 values. Then we create a partition like this, then we can create a partition like this, and so on and so forth. So every single time we would try to create all the possible partitions, and then we will see that whether that approach works or not. But the thing is, this is not the most optimal approach. Why? Because we can clearly see that with the given number of elements, we can create multiple partitions. So this basically becomes like an exponential time complexity, because now we are dealing with all the permutations and combinations. So this is not a good way to move forward with this approach. We will have to find a better way to deal with this problem. So the brute force solution would not work. Let's try to see that what the optimal solution would look like. Now, before we start understanding optimal solution, let's make 2 or 3 very quick assumption that will help us eliminate lot of bad cases. Number one thing is, whenever we are able to make like 2 equal partitions, there has to be the total number of all the sum has to be even number. What do I mean by that? Well, if the sum is even, then only we can create 2 partitions that are going to be equal to each other. And we can understand it with this example. We have 3 values, 1 plus 2 plus 3. So total sum is going to be 6. And because this total sum is 6, we have the possibility of creating 2 partitions that becomes equal in value, that is going to be 3 and 3. If we had the total sum to become even number, let's say that this value is 1 2 and 4, something like this. If we have an input array like this, if we do total sum, this becomes 7. With 7, we can never create 2 partitions that are going to be equal to each other. Why? Because 7 divided by 2 is going to be 3.5, and we are only dealing with integer numbers. So we cannot have a partition that sums up to 3.5, which means we cannot generate the answer. This is the first assumption we can make, that the total sum of all the elements has to be an even number. Okay, after determining the even number, next assumption is that once again for the same example, we can see that the total sum is 6. Now the total sum is 6. We know for a fact we need to create 2 partitions, and both partitions has to be even. So both partitions has to be value 3 and 3 in nature. So in this given input array, if we can find a partition that sums up to only value 3, then we don't have to find another partition. It has to exist inside the array. Why? Because we know that the total of all of these elements are 6, and if we already find a partition, let's say with these 2 values, that sums up to 3, then we must have another partition that is going to be 6 minus 3. So this is also going to be 3. So we can also find that answer. So basically we need to first check that whether the sum is even number, and second thing we need to check is that are we able to find a partition that can actually sum up to the total sum. So total sum divided by 2. If we are able to fulfill these 2 conditions, then we can return true immediately. And if we cannot fulfill these 2 conditions, then we can return false in the end or immediately. Okay. Now let's try to see the solution I'm proposing. And for that, remember one thing, that The input we are currently given, we are actually depending on the previously calculated values that we already have so far, which means let's say that if this is the example we are given, we know that we can make a partition with these two values as partition 3, but this is useless information if we don't know that what other values are or what is the total sum. We know in this case that the total sum is going to be 14. So because total sum is going to be 14, we are striving to create a partition that sums up to value number 7, but with these two we can only create 3. So should we discard them from the partition? Yes, but we can have another partition like these three values that sums up to 7. But the thing is, creating partition depends on the previous elements that we already have calculated and the next future elements that might come into the picture. So our current calculation that we are doing for the current value is actually dependent on previously calculated values that we already have, on whether to include that inside our solution or not to include that. So we are going to use the most beautiful thing in the entire computer science, that is dynamic programming. And for dynamic programming, what is the approach I'm suggesting? Number one, we are going to create a new dynamic programming array, but for this array we are not going to go to the full length of the total sum that we currently have. We are only going to go up until the total part, like the half of the total sum. So currently half of the total sum is value 7. So we are only going to have 7 entries inside our dynamic programming array. We can create a partition array like this. Now initially all of the values are currently going to be false because we cannot create any single partition so far, because we haven't checked for all the values except value 0. Why value 0? Because we can always create a partition that equals to 0 if we don't have any value in that partition. So the purpose of this dynamic programming array is that for every single element we will only mark it true if we can create a partition that sums up to this value. So let me just mark the initial value as 0 as true, because we can always create a partition with 0 entries in it. So now this one is currently true, and our aim is to check that by the end we are done with all the current numbers that we have. We simply have to check that whether the dp of 7 is true or not. If this is true, then we can always have a partition that sums up to 7, which means we can create two equal partitions that sums up to 7 because the total is 14. So I hope my explanation made sense. Now let's see the walkthrough of this problem. So first thing we are going to do is, now we currently have value number 1. The idea is we are going to be starting from value number 7 and we are going to go back to the value number 1. And currently our I value that we are dealing is going to be the current I that we are using to iterate over all of these values. And next thing is that for the number that we are currently using, so we are actually using value number 1 to go over. So all we need to do is that dynamic programming value of any particular number depends on the total number of position, like so I position I have minus the number value I have. So let me explain what I mean. So currently I minus num that we are going to check for any particular value. So let's say when initially the I is going to be 7. So if I have to update the value of 7, currently I have a dp of I minus num is going to be dp of 6. So dp of 6 is false, so I'm going to leave this false. Same way for dp of 6, I'm going to be checking dp of 5. This is also false. Then for this one, because currently the number is 1 that we are dealing with, same way this is false, this is false, this is false, except when we reach to this very first element, we can see that dynamic programming for 1 is going to be the value of I minus num. So the value of I is currently 1 and the value of num is also currently 1. So this is going to be dp of 0. So dp of 0 we know is true, which means we can also create a partition with that sums up to value number 1 and we can mark this as true. So let's just quickly do this one, and this is going to be turned into true. Now you understood what I did. I check for all the possible values and I check that whether there can be a partition being made where I can include value number 1, and then I can make those partitions. So currently I don't have any values, so I can not check any other value apart from creating a partition that is 1. Now let's start to work with value number 2. Once again we are going to be repeating the same formula, that we are going to be checking of dp of I minus the current number that we are dealing with, and current number is 2. So for value number 7 I will have to check dp of 5. so this is false, so I'm going to leave it as it is. For 6 I'm going to check 4, this is also false. For 5 I'm going to check 3, this is also false. But now for 4 I'm going to check 2, this is also false. But for value number 3 I'm going to check dp of 1. I now notice that dp of 1 is true, so I can also mark this as true, because I can create a partition using value number 2 that sums up to value number 3. So I'm going to be marking this as true. Now for dp of 2 I'll have to check value of dp of 0, so this also becomes true, so I can also mark this one as true as well, because I can create a partition that sums up to 2 which only contains one value. Now you must have gotten the grip of what we are trying to do in this problem. So now let's just quickly walk through the remaining solution. For dp of 4, for value number 7 I will have to check the dp of 3. dp of 3 is true, so which means we can also create dp of 7 is equal to true as well. So I'm going to mark this one as true. Same way, for dp of 6 we will have to check dp of 2, so this is also true, so we are going to be marking this as true as well. And now you understood, for dp of 5 this is also going to become true, and dp of 4 is also going to become true. So this entire array eventually became true, and we haven't checked the value 7, but we can also check for value 7 as well, no worries with this one. And this is also going to become true. So now logically all we need to check is the dp of 7, if that is true or not. Since this is true, so in the answer we can also return true, saying that we can create a partition that sums up to value number 7 using this dynamic programming approach, and this is what we need to return. So basically this is such a beautiful solution, and rewatch again if you did not understood, and let me know in the comments on how do you feel about my explanation. Now let's try to understand the time and space complexity. In this case, time complexity is going to be big of n, because we are simply iterating the entire array, but we are doing it in total number of elements that are currently present inside the array. And if we see space complexity, so space complexity is going to be big O of n, because we are using an additional array to store this information. Now let's quickly see the coding solution for this one. So the coding solution is quite straightforward. First, we are going to initialize a variable called total sum, and we are going to iterate over the given input array nums and add all the elements inside the total sum. First thing we are checking is that if the given total sum is odd, then it is not possible to create equal partition, so we can simply return false. If that is not the case, we will first of all create the target value of which the partition number we are trying to achieve. Then we are going to initialize a boolean array called dynamic programming, and we are going to be marking the first value inside the dynamic programming array is true. Now notice that I added the value to be target plus 1, because if the target is 7, we need total 8 elements inside the array, where first element is going to be dp of 0. I hope you understood that. Now next thing is that we are going to have a for loop that is going to iterate over every single number that we have in the nums array. For each of the number, we are going to be checking that we are going to be starting from the target value, and we are going to go down to that particular number, and we are going to be reducing one element at a time. And every single location we are going to check inside the dynamic programming array that what is the value of j minus num. And if that value is true, then we can also define the dynamic programming of j to be true as well. And in the end, we simply need to return dynamic programming of the target value, or the very last element inside the given array. So this is the whole solution. Let's try to run the code. Seems like our solution is working beautifully. Let's try to submit this code. And our code beats 94% of all the other solutions in terms of time complexity, and 87% of all the solution in terms of space complexity. This is one of the most accurate and beautiful solutions out there. So I would be posting this inside our GitHub repository. Feel free to go ahead and check it out. Thank you. Hello friends, we are still not employed by FAANG company, so let's not stop late coding till we get there. Today we are going to do a very important LeetCode problem, unique paths, and as you can see that this question has been asked in Google, Facebook, Amazon, Apple, Microsoft, Bloomberg, all huge gigantic IT companies. So I highly urge you not to miss this video and try to understand the problem as thoroughly as possible. This is going to be the framework for the video. We are going to understand the problem. We are also going to find a primitive approach. We are going to find the optimal solution, and we will write a Java code for the optimal solution. This is a LeetCode medium problem. We are given that there is a robot in an m cross n grid, and robot is initially located on the top left corner. Now robot tries to go to the bottom right corner. So this is the last place where robot wants to reach. And at any given moment, robot can only make one move. It can either go down or it can go right at any point in time. No other ways it can make. So in the problem, we are given this m and n, and we need to find that how many distinct unique paths can robot take to reach to the bottom right corner or its final destination. So suppose our given m is equal to 2 and n is equal to 3. If suppose our m is equal to 3 and n is equal to 2, this is one of the test cases. So if we draw it on the board, it would look like this. This is where the robot is initially, so I'll just mark it as R, and this is the destination that robot wants to reach, the bottom right corner. Now we know we need to find that how many unique paths exist. So let's see that how many unique paths can we make. And at any given moment, robot can either go on the right side or down. It cannot make any other steps. So let's see that what are the possibilities. So this is one possibility. So this is one path. I'll just mark it somewhere. Now this is second path. I'll also mark it somewhere. So this is second path. So have we exhausted all possibilities? No, there still exists a third path, and the third path is like this. 1, 2, 1. And apart from these, we cannot make any more paths. So essentially, we are exhausting all the possibilities, and we can return that for this given m and n, the number of unique paths can be 3. Now I hope that this makes problem statement more understandable. Over here, initially we are given an example of m is equal to 3 and n is equal to 7. And the number of unique paths they get is 28. But the thing is, this would be such a long example, so I'm not going over it. Okay, let's understand this with a custom example. So suppose our m is equal to 3 and n is equal to 3. So we would have a grid that looks like this. Here, this is our robot, this is our destination. Now we are going to calculate that in order to reach to any element, how many unique paths we can take. So suppose if we want to reach to this element, how many unique paths we can take? We can only take one unique path, and that would be to take this right step from here. We cannot take any other step. Same goes for this element, that we can only have one unique path, and that would be to take 2 right steps from here. We cannot reach to this point any other ways. Same happens for these two elements as well, that we can only take 1 step down or 2 steps down in order to reach to these two elements. The thing is, there cannot be any other unique path if we want to get here. But the thing is, when we get to this middle points, something interesting happens. And the interesting thing is, suppose we want to reach to this point, how many unique paths we can take? Well, we can take 2 unique paths. We can take one unique path to reach over here and then over here, or we can take one unique path to reach over here and then again reach over here. So we can say over here we took 2 unique paths. But the thing is, if we just see that what are the entry points to get to this point, actually there are only 2 entry points to get to this point. One entry point is that we can, if we somehow get to this point, we just take 1 step downwards, we come over here. Or if we somehow get to this endpoint, if we take 1 step on the side, we reach over here. Which means that whatever the unique paths we have at these 2 locations, if we just sum these 2 up, it will give us the number of unique paths we can take to get to this point. So let me show you by another example. Now again, let's consider this element. So in order to reach to this element, there are only 2 ways we can reach to this element. We can either take 1 step from here, or we can take 1 step from here. Which means that whatever the number of possibilities we have over here, that once we get to this point, we will be able to come to this unique path. Okay, so that is a given. Same goes over here, that no matter how many number of possibilities we have to come to this point, if once we are at here, we are guaranteed that we can come to this point. So in order to reach to this point, the only possible ways are this one and this one. So if we sum these two, we will find the number of unique ways we can reach to this element, and in this case it would be 3. If we continue down the same path for this point, we can take 3 distinct paths to reach over here, and in order to reach to this destination D, we can take 3 plus 3 6 unique paths to get to here, and this actually becomes our answer. Okay, so based on our previous explanation, we know these things. So if we see, now we need to see that how can we use dynamic programming to solve this problem. And the reason we are choosing dynamic programming is because at any single location we are computing that whatever the previous two results that we have already calculated, and we are using them to calculate the next values. So that pretty much indicates that we need to use dynamic programming over here. Now let's take a 2 by 2 matrix, and we'll just provide the index values. So index values would be 0 1 2 0 1 2, and we would name this matrix as DP to refer dynamic programming. Now the thing is, if we want to find out the value at this position, we know that it would be sum of these two elements. So mathematically we can write them like this, that DP of 1 1, because this is 1 and this is 1, is actually equal to dp of 0 1 that we have already calculated, which is this value, plus dp of 1 0, which is this value, and sum of these two will give us this value. So generically we can actually write them like this, that at any given location dp of m and n would actually become dp of m minus 1 n plus dp of n and n minus 1, and this would be our recurrence relation for dynamic programming. And I already explained that why are we choosing dynamic programming, and our aim is to find that how many distinct ways we can reach to this destination. So this destination would actually become dp of 2 2 over here, and if we compare it with whatever m and n is given, this actually becomes the value over here. This would become the dp of m minus 1 and n minus 1. So we start our calculation like this, and eventually we would reach to this point, and we just need to return whatever we have found over here, and this would be our solution. So we can just create two loops. One loop iterate over the column, one loop iterates over the rows, and eventually we will reach to this endpoint. We return this. This becomes our solution, and this is a very efficient dynamic programming solution. Any FAANG companies, Facebook, Google, Amazon, whatever, they would be happy to hire you immediately. So now let's see that what would be the time and space complexity. So time complexity would be big O of m times n, because we need to iterate over this entire grid, so that's why it's big O of m times n. And space complexity, remember that we are creating this additional dp array, which is 2 by 2 matrix, and we are giving the size as m and n, so space complexity would also be big O of m times n, and this would be our solution. Now let's move on to coding. Okay, first of all we'll create a two-dimensional array, and we'll name it as dp, and we'll provide the length as m and n. Now we'll have to create our base case, so we'll fill our two-dimensional array, and this is the way to fill a two-dimensional array. And over here now we'll create two for loops, and we'll start with I is equal to 1 and j is equal to 1, because we already have cases for 0. While I is less than m, I plus plus, j is equal to 1, j is less than n, okay. Now we will provide our recurrence relation. So dp of I and j at any location is equal to dp of I minus 1 j plus dp of I j minus 1. And yeah, this is pretty much it. This should be working. So now let's return dp of m minus 1 and j n minus 1. Let's try to run this code. Oh, it should be arrays.fill, small error. Looks like our solution is working. Let's try to submit the code. Okay, our solution is actually runs in 0 millisecond. It's 100% faster than all the other submissions, which is pretty good. And I'll be posting this in the comments. You can check it out from there. Thank you. So the LeetCode problem we are going to solve now is called longest common subsequence. Now we can see that this one is a LeetCode medium problem and also one of the most liked problems on LeetCode. So I'm going to pay my utmost attention. Now let's understand the statement. We are given two strings called text1 and text2. Now we need to return the longest common subsequence. And if there is no common subsequence that exists, then we need to return 0. Now we are given the definition of a subsequence is a string, that is a new string that can be generated from the original string with some characters that can be deleted without changing the relative order of the characteristics. So without getting too much into the details of the definition, let's try to understand what we are being asked to solve. Basically, we are given two strings text1 and text2. Now we can notice that text1 currently has 5 characters A, B, C, D, E, and text 2 has currently 3 characters A, C and E. Now the thing is, if say for an example from text 1 we decide to eliminate this characters B and D, we can also create A, C and E, and this is going to be the exact same manner, or the sequence of relative order remains the same between both the strings. So we can say that for this given example, we actually have a longest common subsequence that we can make that follows the relative order, and that is of size 3. So we need to return 3 as part of the answer for in this case. Now let's try to understand it with one more example for this one. Now we can see that currently the characters we have is x, y, z, and the characters we have for this text 2 is y, a, b. So now we can only find one character that is common between both of them and that follows the relative order, and that is this y. Apart from that, we don't see anything common. So in this case, we can only create a longest common subsequence that only consists one character. So we need to return 1 as the answer. Now if we take a look at this example text1 and text2, we see that there are no characters that are same between both the text. So in this case we will have to return 0. But in the same example, say for some reason, if we are given the values like a, b, c and d, e, f over here, and then we are also given d, e over here, then we will need to return 2 as the answer, because the relative order of d and e remains the same even if this string had 3 additional characters. So we will have to solve this problem, and definitely this is going to yield to some very interesting results. Now let's understand the brute force approach to solve this problem. The logic is quite straightforward. Let's say that we are currently given two strings in this particular fashion. Then what we can do is we can go through every single possible combination of any particular string and try to match it with the other string. So what I'm suggesting is that for this text one, we start taking permutation of all the other substrings that we can make out of this one. And we know in terms of making permutations, we can actually make 2 to the power of n permutations for any given value. Why? Because at every single character we will have to make the decision that whether we need to include this character or not to include this character in order to generate the permutation. So this would eventually yield us the correct result, because what we'll do is we'll try to create all the different permutations and combination, compare it with this given another string, and we'll try to see that what is the longest common subsequence that we are able to make. But this is very inefficient approach, and also the time complexity goes in some sort of exponential form, so I'll not go into the depths of this one, and we'll try to do something smart in order to solve this problem. Now let me come to the optimal way to solve this problem, and for that we are going to use one of the most beautiful concepts in computer science, and that is dynamic programming. Now let's take a quick recap. Let's understand that why do we actually have to use dynamic programming in this problem. Well, the answer is actually quite straightforward, because let's say that we are currently given the two strings as a, b, c, d, e, and then once again a, c, and e. Now notice that if we start comparing the two strings at any given moment, character by character, it would not be very much fruitful. Why? Because okay, let's say that we define that this a is common between both of the subsequence. Now we are at this character b, and we don't know that next character b is not present over here. So we don't know that whether b is going to be present somewhere down the road or not. So do you think that we should compare b with every other character that is currently present inside the t2 string? Well, we could do that, and we are going to do that, but in order to do that we'll also have to remember that what was the relative order of sequence that we have been able to identify beforehand. And it could be possible that if we are dealing with multiple sequences, which subsequent to consider. So let me give you one example like this. Let's say that we are given currently strings like a, b, c, d, e, okay, and we are given the t2 string to be a, b, then x, y, z, and then once again we are given the string to be, let's say, b, c, d, e. So do you think that from this particular point forward, if we see, the longest common subsequence we can make is going to be 2? But the moment we start identifying these characters, we can, if we just drop this b, we can actually create the longest common subsequence of size 5. But we have to drop one b that was already part of one of our relative subsequence, which means the result that we are going to make later down the road is actually going to be dependent on the previously calculations that has been made, and also future calculations that we are yet to be make. And when we are at the last position, we should make the best judgment on which path to take. So that's why this is a good candidate for dynamic programming. Now the question is how we are going to use dynamic programming to solve this problem. And for that, what I'm suggesting is, number one, we have to check every single character for all the other characters, and same way for any particular character we will have to compare it with all the remaining characters. So there is no getting away from that in this problem. We will have to do n square work, or m multiplied by n work, where m is the length of text 1 and n is the length of text 2. Okay, so this has to run in big O of n square time complexity. But how we are going to do that? Number one thing I'm suggesting is that we actually create an m cross n grid, just like the one that I have shown over here. And for this particular grid, we'll need two things for our dynamic programming. We'll need a base case scenario. So base case is quite straightforward, that if any particular character is not matching with the other character, then we simply define it as 0. And notice that we actually have created an extra space at the beginning. So there is an extra row and extra column, which means this is not strictly an m cross n matrix. This is actually an m plus 1 multiplied by n plus 1 matrix. So we are adding one more extra line, and that is to consider our base case. Now at any given moment, what we are going to do is, if we identify that there exists a combination, there exists a value that is common. Let's say that over here the c and c is going to be common for this particular cell, which means what we can definitely say in this case is that this cell is going to be an addition to the previously calculated longest common subsequence. Now where is going to be that information for the longest common subsequence? To the diagonal value. Why it would be at the diagonal value? Well, let's take a simple example. Let's say that currently the values are a, b, c, and this value is a, b, and c. So notice that for this particular square, the logic is going to be quite straightforward. We are going to have a and a common at this place, then we are going to have b and b common at this place, and then we are going to have c and c common at this place, which means longest common subsequence is directly represented towards the diagonal value in the best case scenario, and this is the fact that we are going to exploit. So whenever we identify that at this particular location there was a common subsequence, then we had to add one value to the previously found longest common subsequence, but we haven't found any subsequence because this value is 0. So definitely the longest common subsequence at this 8th location is going to be 1, so we are going to mark it by 1. Same way, the longest common subsequence at this location is actually now 2, because we are comparing AB with AB, and that's why this is going to be an addition to the diagonal, so we are going to mark value 2, and same way this is going to be value 3, one more addition. So same logic we are going to apply over here, that whenever we identify any particular common characters, we will check the diagonal value. That is number one thing. Next thing is that let's say we identify any particular character that does not have any common values, so both characters are different than each other. Then it becomes the question that what is the longest common subsequence we have found so far, and there can be two possibilities. Why? Because let's say that I'm currently at this bth position, so on one side I'm checking against AB, but for AB I have checked with A, I have checked with AC, and I have checked with ACE, because I'm trying to fill up this row. Same way for any particular cth character, I'm also comparing it against A, against AB, against ABC and whatnot. So the answer for the longest common subsequence where the characters do not match is actually going to reside on the adjacent cells for any particular cell. So let's say I'm trying to consider the values for this cell. Now we know that B and C don't match, so in this case we'll have to check that what is the longest common subsequence we found either way, because we are not only comparing text 1 with text 1 or text 2 with text 2, we are comparing them with each other. So we'll have to take the maximum value amongst the adjacent cells, and this is going to yield us the correct result. So now let's recap our rules. Number one, if we find equal characters, so let's say that if an I and j value are equal, then we are going to do the +1 operation compared to its diagonal value. So diagonal value is going to be I minus 1 and j minus 1, this cell. Okay, and if that is not the case, if we find that I and j character do not match, then we will have to find the maximum value from its adjacent values or subsequent neighbors. So now let's try to do the solution right now. Okay, let's start filling up this particular whole matrix. Now very first value we find A and A, there is a match. If there is a match, we are going to compare it with its diagonal value and add 1. So diagonal value is 0, so we are going to add value number 1 over here. Now next thing is that we will also have to check, let's go row by row. So now we are checking this A with this value B. A and B do not match. So if they do not match, we'll have to, for this cell we'll have to check its neighbors. So we'll check this neighbor and this neighbor, and whichever is the maximum value we add this one. So what we are saying is that up until this point inside our input, we have calculated A B with A. So in this text 1 and text 2, we can see that the longest common subsequence we find was of size 1, and this is what we are defining it over here. Next we are comparing A with C. Once again, A with C, once again there is no commonality, so we'll add value 1. A with D, once again no commonality, so we'll add the maximum value 1. And A with E, once again the maximum value is going to be 1. Now let's repeat the same operation once again, but now this time we are going to be doing it for value C. Now C and A do not match, so we'll try to find the maximum amongst these two values, and once again the maximum value amongst these two is still going to be 1, so let's just mark it as 1. Same way this is going to be 1 as well. Now we are at this position of C matches C, so we'll have to do an increment with the diagonal value, and we are going to be adding +1 over here, so we can mark this as 2. Now for this D with C, we'll have to compare the maximum amongst these two, and the maximum value is 2, so we'll mark the value as 2 as the answer, and same way 2 as the answer over here. Now we are comparing E with this A, so once again the maximum amongst these two values is going to be 1, and notice we found 2 over here, but why we are marking 1? Because notice what we are calculating or comparing so far. We are comparing A with value ACE. So in this case, the longest common subsequence is going to be of size 1, and that's why we are marking 1 over here. Same way, this is going to be 1 because we are comparing the maximum amongst these two. Same way with C, we are now the value is going to be 2 because this value was 2. And why it was 2? Because notice we are comparing the values A, B, C versus value A, C, E. And amongst this comparison, we can see that there exists the longest common subsequence of size 2, that is, which is represented over here. This is the beauty of dynamic programming solution. Now for this D comparing with this E, once again we'll choose the maximum, so answer should be 2. And now we have E common for this last cell, so we'll have to do +1 with the diagonal. So 2 plus 1 is going to be 3, so we'll mark it as 3. In the end, we simply need to return whatever we find in the very last cell as part of the answer, and that is going to be 3 in this case, so we can return this with confidence. See how beautiful this solution looks. All we need to do is just fill up this matrix and things work out beautifully for us. Now if we have to calculate the time and space complexity for this one, time complexity is going to be big O of n square or m multiplied by n, and space complexity is also going to be big O of m plus 1 multiplied by n plus 1. So we can say m cross n for simplicity, but anyways, this is a beautiful time and space complexity and very awesome approach. Now let's see the coding solution for this problem. Basically, we are going to define two characters m and n to define the length of both of the given strings text1 and text2. Then we are going to initialize our new array dp array. Now notice that we are defining it as an length of m plus 1 and n plus 1 to take care of the 0 case scenario that is going to be our base case for our dynamic programming table. Now for this matrix, we are going to fill in all the details. So we are going to use two for loops to iterate over every single row and every single column. Notice that we are starting the values from 1 and 1 because for ith value of 0 and jth value of 0, we have already defined the values as 0. Now first thing we are checking is that at any given moment we identify that the character at I minus 1 and character at j minus 1 location are equal to each other. Then for the current ith and jth value, we are going to add 1 to the existing diagonal value, that is I minus 1 and j minus 1 value inside the DP array. If that is not the case, then we are simply going to pick whichever is the maximum value for any particular ith and jth element from its adjacent neighbors. So whether the top value or the left value of any given cell. And in the end, we should have completed all the values for the longest common subsequence, and the very last element inside our DP array is going to represent that. So we are simply going to represent that value that should give us our correct longest common subsequence. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code beats almost 90% of all the other solutions. That is excellent in terms of time complexity. Now for the memory, we can improve on some aspects, but we are using like an m cross n grid, and that is also a fine enough solution. But overall, this is a beautiful solution, and once again, it is available on our GitHub repository, so feel free to go ahead and check it out from there. Thank you. So the LeetCode problem we are going to solve now is one of the most popular LeetCode problems, that is called best time to buy and sell stocks with cooldown. This one is a medium problem, but in my opinion, this can be categorized as hard in some scenarios, and this is a very well-liked problem. So let's understand the problem statement. We are given an array called prices that represents the price of any particular stock on any particular given ith day. Now we need to find the maximum profit that we can achieve, and we have the luxury to complete as many transactions as we like, and the only restrictions is that after we sell our stock, we cannot buy the stock for the very next day, which means we'll have to cool down for 1 day. Now let's try to understand this with an example. Say here are the price of any particular stock is given for 5 consecutive days, and our aim is quite simple: maximize the profit. Now let's try to first understand that what is going to be the answer in this case. Let's say if we decide to buy stock on this particular day, then our buying price is going to be 1, and then we decide to sell the stock on this day, so then our selling price is 2. So what is the profit we made during this duration is going to be of value 1. Then remember, after selling we'll have to wait one more day for the cool down. So let's say that we decide to cool down on this day, then we buy again when the price is 0, and then we sell again when the price is 2. So we make profit of $2 or 2 units over here. So in total amongst these prices, the maximum profit we can make is going to be 3. Now notice that we did not use the greedy approach and try to maximize our profit in one single transaction. Why? Because logically it would make sense that if we have values like this, then if we have already bought the stock on this day, then instead of selling over here, if we decide to sell on this particular day, then our profit for this region would have been 2, but this would not yield us to the maximum profit. Why? Because then we cannot buy stock on this day because of the cool down condition that we have, and then we are at the last day. So even if we buy the stock, then we are just diminishing our profit. Let's say that we don't do anything on this day, still the maximum profit we can achieve is going to be 2 in this case. So this is a very tricky problem, and first let's try to understand a very simple brute force approach in this case to solve this problem. Now notice the brute force approach is quite straightforward. We, for any particular day, simply try out all the different combinations and permutations and combinations, and do all sorts of calculation. So we can check that what if we buy on this day, then we decide to sell on this day, then we decide to sell on this day, then we decide to sell on this day, and then we decide to sell on this day. Once again repeat the same scenario where we are buying on this day and then selling on this particular day, and based on that also consider it for the cool down scenario as well. So logically, for any particular ith day, we can have 3 different states that we can think about, whether either we are buying, we are selling, or we are resting. And for each one of the 3 possibilities, we'll have to do this ith times, and we are calculating all the permutations, which means now we are talking about the time complexity that yields in big of n factorial time, because we are dealing with all the permutations. So this is a very expensive brute force approach to find the maximum profit. We'll have to optimize the things, but the thing is there is no way for us to get away from maintaining the states for any particular ith day, that what if we buy the stock, what if we sell the stock, or what if we rest for that particular day, and what is going to be the maximum profit in that regard. And once we have this information, it becomes much easy for us to find the appropriate result that we are looking for. Now let's talk about the optimal way that we are going to solve this problem, and we are going to use the most beautiful concept in the computer science, that is dynamic programming. Now let's just do a quick recap. Why do we need to do dynamic programming in this case in order to solve this problem? Well, logically, we cannot use just any single approach to find the maximum profit. We just saw it with this example, that if we decide to use greedy approach, where we are trying to buy at the smallest price and sell at the highest price, this does not yield the correct result. Also, the decision we make at any particular day on whether we need to buy the stock, sell the stock, or go into the cool down mode would depend on the all the previous values we had and all the future calculations that we might have, which means all we can do is that for any particular day we can simply say that if, let's say, on this particular day, if I decide to buy the stock, what is going to be the maximum profit I can make. If I decide to sell the stock, what is going to be the maximum profit, and if I decide to go for the cool down, what is going to be the maximum profit. And keep this calculation doing for every single one of these days, and just based on the previous calculations of the previous day, we should be able to calculate the maximum profit of the subsequent day. So I know what I just said might confuse you, but let me explain it with an example. So let's say that for the same example that we were talking about, let's define each of the scenarios for maximum profit that we need to calculate in each of the 3 scenarios, for buying, selling, and for holding or resting, or if we are in the cool down mode. How do we define that what is the maximum profit we can generate if we decide to buy on any particular day. Let's say that on this particular day, if I decide to buy a stock, then what are the different considerations that I'll have to make? Number one consideration is we can only buy any stock after we are coming out from the cooldown, which means on the previous day we must have been in the cooldown state. So number one thing is, we'll in order to check the maximum profit for buy on any particular day, we will have to compare two values. Number one value is that what was the maximum profit we were achieving on the previous day for this buy operation, and compare it with that what if we did a cool down yesterday and now we are trying to buy. So the cool down maximum profit for the previous day minus the current ith value we have, so price on this particular day. So now let's try to generate the mathematical equation for any particular value of buy. But the thing is, we'll have to remember that what was the maximum profit achieved on the day before, and not on the current day. So for that, we'll need to have some data structure that stores that information, and we can use an array to store that information. We can create an array of the same size. So let's say that I create an array of size 5. Where for any particular day I'm defining that what is going to be the maximum profit I can achieve if I decide to buy on that particular day. So that calculation is going to be dependent on the maximum profit I was able to achieve if I had already bought before and not buy today, or maximum profit I can achieve if I'm coming out of the cooldown and I decide to buy today. So what the mathematical equation is going to be that maximum profit on if I decide to buy on ith day would be, I'll need to compare two elements. So max between what was the buy of I minus 1. So what was the maximum profit on the previous day, and compare it with the cool down profit on previous day plus sorry, not plus but minus the current prices that we are dealing with. So price on the current day. So this is going to be our mathematical equation for our buy formula. Same way for our selling, let's say that if we want to calculate the maximum profit we can make if I decide to sell on any particular ith day. Once again, I'll have to do the calculation with the previously calculated values. But now in this case, the calculation comes off a bit different. Number one thing is, if I decide to sell today and on any particular day, then the profit I'll be comparing it with is that what is the profit I was making if I sold yesterday. So if I sold yesterday and I made more profit, it does not make sense for me to sell it today. So that is number one thing we are comparing. And we are comparing that what was the buy profit that we made yesterday. So if I bought yesterday, what was the maximum profit I was making plus the price of the current particular day. So same way for the buy we made this equation, same way we can make another equation for sell, where we are comparing the maximum value amongst the two values. So what was the previous profit if I sold on yesterday instead of selling it today, and comparing it with what if the maximum profit I made on buy of I minus 1. So previous day if I bought the stock plus whatever the price of I today is, because the price increased, so there is higher potential that I can gain more profit by selling the stock today. And next thing is, if I decide to rest on this particular day, so let's say that instead of selling on any particular day, I decide that I'm not going to do anything and I'm just going to rest, then what is going to be the implication? So we simply need to compare that what was the previous day's profit we were making, that is for sure. So for rest, we are going to compare the previous day's profit, so rest of I minus 1, and we are going to compare it with what if we sold yesterday. So if we sold yesterday, then we are resting today. So what is going to be the profit if we sell yesterday, and whichever value is maximum, we are going to store that as the answer. Okay, so based on our explanation, these are the three different equations that we made. Now I just wrote them roughly to have a brief idea on what we are talking about. And then we have initialized three different arrays that we are going to play around to keep track of the maximum profit on that particular day based on whether we can buy, sell or rest on any particular day. So now let's first initialize the value, and this is the prices array that we are given, that we are dealing with. Now on first day we cannot sell anything or we cannot rest, so we can mark these values as 0. And the maximum profit we can make on very first day is if we decide to buy something. And let's say if we buy something, we haven't made any profit, we are actually losing money or putting money on the table. So the maximum profit we can make if we buy something is going to be -1 or the negative of the price of that particular day. Okay, now we can start our calculation. So let's say that for second day, if we have to calculate that if we decide to buy something, what is the maximum profit we can make. So for that, for buying, we need to compare the buy price on the previous day, so maximum profit being made on the previous day. And what if we decided to rest on the previous day, so what was the maximum profit we were making then, minus the price of the current day. So if we compare that, we are comparing the value of -1, that is the maximum profit being made on the previous day. And what if we rested on the previous day, so that was 0 minus the price on the current day, so 0 minus 2. So we are comparing the values of -1 and -2. So what is the maximum profit we can make? Well, of course, maximum profit is going to be -1, so we can simply mark -1 at the buy array. Same way for the sell array, if we decide to sell on this particular day, what is the maximum profit we can make? Once again, we are comparing the previous selling profit, previous maximum profit from the previous day, or what if the previous maximum profit we are making if we bought a day earlier plus the prices of the day today. So of course this is quite obvious that if we decide to compare, then first value we are comparing is 0 because that is the maximum profit we are making on the previous day, and we are comparing it with the buy maximum profit on the previous day, so that was -1 plus the price is today, so the price is today is 2, so -1 plus 2. So we are comparing the values 0 and 1, so obviously 1 is greater, so maximum profit we can make if we decide to sell is going to be 1, so we'll mark 1. Same way, if we decide to rest today, then we are comparing two values, the previous profit being made on rest and previous profit being made on sell. Both of these are previous because we are simply not doing any transactions, we are just resting, so both are 0. So since this maximum profit we can make by resting today is also going to be 0. Next thing is that what is the maximum profit we can make when the price is 3. So once again, for buying we are comparing the maximum profit, so -1 versus what if we rested, so resting is 0, so 0 minus 3 is going to be -3. So -1 and -3 we are comparing, so -1 is the maximum profit, so we'll just mark -1 so far. Okay, now for selling, if we decide to sell when the prices are 3, we are comparing two values. First value we are comparing is the previous day's profit, so that is 1, and second value we are comparing is the previous day, so this is -1, so -1 plus 3, so that is going to be +2. So once again, and by the way, this it would not be this -1 but this -1, I just did not included that, but I hope you understood what I mean. So this profit is going to be 2, that if we decide to sell today, maximum profit would be 2, which would be great. And for the resting over here, we will have to compare the previous day's resting value versus selling value. So this is 1 because we are comparing these two values basically. Once again, when the prices are 0, what is the maximum profit we can make? So now the values we are comparing is going to be -1 with what if we decide to rest yesterday. So if we rested yesterday, then we would have made so it would be 1 minus the current day's price 0. So 1 minus 0 is going to be 1, so we are comparing values -1 and 1. So over here obviously the judgment is quite obvious that it would be in our favor to buy today, so we'll just mark as value number 1. Same way, if we decide to sell today, what is going to be the maximum values we are comparing? Number 1 value is previous day's profit, so we'll mark 2, and second value we are comparing is that what if we bought yesterday, so that is going to be -1 plus the prices of today, so -1 plus 0 is going to be -1. So answer is quite obvious that we are just going to leave 2 as it is. This is the maximum profit we can achieve if we decide to sell today. And for the resting phase, if we decide to rest, we are comparing these two values, so maximum profit we can make is going to be 2. Now for the very last day, the value is 1. So if the value is 1, we are comparing these two values. So first value is 1 and second value we are comparing is 2 minus 1. So both values are 1, so we can make maximum profit as 1, so we'll just leave 1 as it is. Next value is for in terms of selling, what is the maximum profit we can make? So one option we have is 2, because this is what we have. Second option is that the buying profit from the previous day, so this is going to be value 1 plus the price of the stock today. So okay, and this value should not have been 1, this should have been 2. So let me just mark it clear. Okay, so 1 plus 2, so 1 plus 2 is going to be 3. So we are comparing values 2 and 3. So it would be in our favor to sell today if we bought yesterday. So now the answer is going to be 3. This is the maximum profit we can make. And for the very last element, if we decide to rest today, which means we must have sold all of our stocks yesterday, so we are comparing these two values, and the values are 2 and 2, so this is going to be 2. Now this is what our table looks like basically, where we can see that in the end we simply need to check that what is the maximum profit we are making if we are selling on the last day or if we are resting on the last day, because if we buy on the last day, we are always going to lose money. So whatever value is higher amongst these two value has to be our profit, and in this case our profit is going to be 3. So this is what we can return as it is. So this is the whole solution. I know it looks messy, but it's beautiful in my opinion, because we are, imagine what we are doing. For every single day we are maintaining 3 different states. We are calculating that what is the maximum profit we are achieving on each day, and we are taking into the consideration of the previous task being done for any particular day's solution. So that is in itself pretty awesome that we are able to do it, and dynamic programming is actually giving up a huge contribution in this program. So if we see time complexity now, then it is going to be big O of n, because we are simply iterating over the given input array once to solve the whole thing. If we see space complexity, well, this is going to be big O of 3 times n, because we are initializing 3 new arrays to store all of these states. So this is a beautiful time and space complexity, and also an excellent question in my opinion. So I hope the explanation made sense. Now let's see the coding solution. Now the coding solution for this problem is quite straightforward. First of all, we are checking that if the given prices is equal to null, or the given length of the price array is less than or equal to 1, then we can simply return 0. If that is not the case, we have a variable n that is defined to calculate the length of the given prices array. Based on that, we are going to initiate 3 different arrays to check out the state of the profit on every single possible outcome. So first one is for buy, second one is for sell, and third one is for rest. Now we are going to initialize all of these 3 arrays for the very first position. Now for sell and rest, the value is going to be 0, because it's quite straightforward. We cannot sell on the first day, and if there is no sell happening the day before, then we should not be resting, or this should not be a cool down day. But for buying, because if we decide to go and buy on the very first day, then definitely we are going to be at a loss. So the maximum profit would be the negative price of that stock and on that particular day. Now we are simply going to run a for loop to iterate over the given input array. We are starting iterating from the very first day, and now we have our condition set up for buy, sell, and rest. In order to make the judgment call that what is going to be the maximum profit if we decide to buy a stock on any particular day, then we will have to compare that what was the maximum profit if we bought the stock the day before, and we need to compare it with, let's say that if we decide to rest the day before minus the current prices on this particular day. Same way, the maximum profit for sell is going to be calculated, where we are comparing the profit from the previous day by selling or by buying whatever we bought on the day before plus the current prices of this day. So we'll compare these two values, whichever is higher we are going to keep that as the profit. And in order to make the judgment that whether we should rest or not today, we will compare the maximum profit achievable on any particular ith day, and for that we are comparing that what if we decide to, what was the profit we made if we rested the day before, comparing with what was the profit we made if we decided to sell the day before. Whichever is higher, we are going to keep it as it is. Now for the maximum profit, we simply need to compare that what was the value if we decide to sell on the very last day, or if we decide to rest on the very last day. Whichever one value is higher, we are going to return that as the answer. So this is the whole solution. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully. It beats almost 80% of all the other users, which is pretty significant. And once again, the solution of this code is present in our GitHub repository. So feel free to go ahead and check it out from there. Thank you. So the LeetCode problem we are going to solve now is called coin change 2. This is the additional version of the original coin change problem. Now we can see that this one is a medium problem and also a very well-liked problem. The statement is quite straightforward, that we are given an integer array called coins that represents the coins of different denominations, and we are also given an integer amount called amount. So that represents the total number of money that we are trying to make. Now we need to return the number of combinations that make up to that amount, and if we cannot make any particular such combination, then we need to return 0. Now let's try to understand this with an example. Suppose we are given an input where the coins we are given are currently 1, 2 and 5, and we are given the amount to be value number 5. Now the ask of this problem is to see that using these coins, how many different ways we can generate the total amount to be 5. So let's start marking each of the ways. Well, one way is quite straightforward. If we use all 5 1 coins, then we can actually make up to the value number 5. Second way is if we use coin number 2 plus we use 3 1 coins. So this is also a good way and we can generate value number 5. Same way we can use 2 coins of 2 and then we can use 1 coin of 1. And the lastly is that we don't use 1 or 2 coin and we simply use coin number 5, and that also gives us value number 5. So in total there are 4 distinct ways for us to generate value number 5. So in this case we will return 4 as the answer. First and most common approach that comes to our mind is a brute force solution, where we are given coins and we are trying to find different ways to make any particular amount. So let's say that in this case the amount is 5. What is the most common thing that we can do to solve this problem? That is that we will take every single coin and try to make every single possibilities. So one possibility is we will take this coin number 1 5 times to generate amount number 5. Then one possibility is that we will take this coin number 1 4 times and then we will add this coin. Then we will take this one coin 3 times and then we will add this coin 1. Same way we will keep on repeating this again and again and again for every single possible combination. And you can see that eventually we would receive the correct result of 4, but this brute force approach is going to get out of hand really quickly, because now we are dealing with exponential time complexity and we are working in the realm of factorial and exponential time and space complexity. So this is a very bad approach. Now in order to generate the optimal solution, we are going to use the most beautiful concept in the computer science, and that is called dynamic programming. Now first let's understand that what is the core logic to finding solution for any particular coin in this problem. Let's say that currently we are only given the coin of size 2 and we wants to find out that how many distinct ways we can generate amount number 8. Well, for sure in your mind you must be saying that there is only one distinct way to generate amount number 8. But let me take a different approach. Let's try to see that if starting from 1, how many different ways we can generate each of these amounts, and we will try to make some important assumptions based on the findings that we are going to make. So let's say that currently we have all of these values. Now we know that currently if we only have the coin number 2, we cannot generate amount number 1. So let's say that currently we cannot generate amount number 1, so we can mark this as 0. Also, no, remember one thing, that we are at the beginning of our input, so we don't have any way to generate each of these amounts. So initially I'm going to initialize all of these values with zeros. Now I know for a fact that if I have coin number 2, I can always make value number 2. So I can simply mark this value as 1. So let me just mark this as 1. Now I also know for a fact that I can also generate amount number 4 using coin number 2. So let me also mark this value as 1 as well. And now let's do a recap. Why was I able to mark this value as 1? Because one logic is that I can do 2 plus 2. But other logic is that if I already know I need to do 2 plus 2, Why am I bothering to doing all of these computation when I already know that how many distinct ways I can generate amount number 2? Because whatever the number of distinct ways I can generate amount number 2, I just need to add the total number of distinct ways for the amount number 4 that I'm currently doing. I know it sounds confusing, but let me give you an example. Let's say that currently, in order to generate amount number 6, I only have 0 distinct way to do it. But now I know that currently I'm dealing with coin that is of value 2. I also know that the current amount I am trying to make is amount number 6. So I can simply check that if I do 6 minus 2, so in this case, the value is going to be 4. I simply need to check that whatever the distinct ways I can make value number 4, I just need to add it to the current amount number of distinct ways I can generate value number 6, and that is going to be the number of distinct ways I should be able to generate value number 6. So in this case, this value is going to be 1. Same way, currently I can not generate value number 8, but I know I have a coin of size 2. So instead of doing all of these computation like this, I can simply check that 8 minus the value of amount of coin is going to be 6. I can generate 6 one distinct way. I can generate 8 0 distinct ways. So why not just do 6 plus 8, like whatever the sum of these two values, and whatever the value is, that is going to be the new value for 8. And this becomes our dynamic programming solution to solving this problem. And we are going to do this for every single coin, because in our initial example we only had one coin of value number 2, but now we are going to have a coin of 2 and 1 and 5. If we have scenarios like this, how would this operate? So this is the core logic we are basing our solution based on. Now let's make some considerations for the optimal solution. Number one, we are going to be using a dynamic programming array to store the result from the starting value of 0 all the way up to the current amount that we are given. Now the first question is, what is going to be our base case? And that is quite straightforward, that if we have to generate amount 0, we know for a fact that there are 0 distinct ways to generate there is one distinct way to generate amount number 0. So we can mark this as 1. Next thing is that in order to generate any particular dynamic programming of I value, the answer is that we are simply going to check that what is the current distinct way to generate any particular I, plus we are going to be doing dp of I minus the current coin that we are iterating over, and that is also we are going to be adding into the number of distinct ways. Using this one solution, we should be able to find the result of this problem and all the different possible ways to generate the answer. So let's take it with one example and it would make things more clear. So let's say the given coins are 1 2 and 5 and the currently amount we are trying to make is 5. So now we are going to initialize our dynamic programming array, and now we also have our base case that there is one distinct way to generate amount number 0. Now we are dealing with coin number 1. So for coin number 1, we are going to be using the same logic, and we will start iterating for value number 1, because whatever the coin size is, we will start iterating from there. So now currently all of these values are 0 because there are 0 distinct ways to generate value number 1. What is going to be the equation of dynamic programming of 1 in this case using this logic? This is going to be dynamic programming of 1. So currently this is 0 plus dynamic programming of 1 minus the current coin value, that is 1. So dynamic programming of 0. So this value is 1. So remember from over here. So we can just take it from here and this value becomes 1. So we will mark this initial value as 1. Now same way we are going to be repeating the same operation for dp of 2. So dp of 2 is going to be dp of 2 plus dp of 1. So this value is also going to be 1, and same way subsequently all of these values are going to be 1 for our coin number 1. So let's just mark all of these values as 1. Now again, now we are dealing with another equation and another coin. Next coin in our category is coin number 2. So let's say that we are dealing with coin number 2. So for coin number 2, we will start iterating from coin number like amount number 2, because it does not make sense to iterate from amount number 1. What is going to be equation for dp of 2 in this case? This is going to be dp of 2. So current distinct ways to generate amount number 2 plus dp of 2 minus the amount, the current coin value, that is 2 minus 2, so that this is going to be 0. So this value is already 1 because we already have one distinct way to generate amount number 2. Plus we will also check it over here. So now we have 1. So notice now we have two distinct ways to generate value number 2, and we are dealing with coins 1 and 2 possibilities. So in this case this value is going to become 2. Same way, we are going to be, this 3 is going to remain as it is because 3 minus, remember, 3 minus 1 is going to be 1. 3 minus 2 is going to be 1, but the thing is this value is also 1 and this value is also 1. So this is also now going to become 2 because now there are two distinct ways to generate amount number 3. For value number 4, this is we are going to be doing sum of these two values. So now once again 4 is going to become 3 because there are three distinct ways to generate amount number 4. And same way for value number 5, now we are going to be doing the sum of 5 plus 3. So this total is going to be 1 plus 2. So now there are three distinct ways to generate amount number 5 as well. Now we are bringing in the value number 5 into the equation. Now for the value number 5 would not impact all of these results up until this point because we cannot add 5 for anything, but we can add 5 for this value. So for what is going to be the equation for dp of 5, this is going to be current dp of 5 plus dp of 5 minus the value of current coin. So current coin value is 5, so 5 minus 5 is going to be 0. So this is going to be, there are three distinct ways that we took from here, plus there is going to be one distinct way that we can make amount number 5, and that is going to be over here. So the answer is going to be 4. So in this case we can just mark this value as 4, and this is going to be the whole solution. Now see how beautiful this solution is, and all we have to do is just come up with this equation and try to understand that how generating a new value based on the previous value using the current coin size can make all the difference. And this is the whole solution basically. So now let's move on. Now let's understand the time and space complexity first. Time complexity is going to be big O of n square, and not n square, big O of n. So where n is the given number of coins multiplied by the amount that we are trying to calculate. So overall we can consider it as n square because it's like multiplication of two different variables, but one variable is the number of coins and the other variable is the amount that we are trying to generate. And in terms of space complexity, it is going to be big O of n because we are using an additional array to store all the results. Now let's move on to the coding solution. So for the coding, the idea is quite straightforward. First, we are going to initialize our dynamic programming array to the value of amount plus 1 because we need to encounter for the value 0. Now we will set up the base case for our dynamic programming, where if you have to create amount 0, there is exactly one way to make amount 0 using no coins. And then we will keep on updating our dynamic programming array for every single coin. Logic is quite straightforward. First, we will take in the current coin that we are iterating over. Then we are going to start iterating from the value of coin to the value of amount, and for every single value for that particular instance of j, we are going to add it based on j minus coin. So whatever the current value is, we will add it with the j minus 1 location, and in the end we should only return the amount that we are being asked to return. So whatever value we find for the dynamic programming amount, we can simply return that. So such a small coding solution, but such a beautiful approach using dynamic programming. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats 100% of all the other solutions, which means this is the most optimal solution that we have provided. And also this is one of the most efficient in terms of space complexity as well. So once again, this coding solution for this problem is available on our GitHub repository. Feel free to go ahead and check it out from there. Thank you. So the LeetCode problem we are going to solve now is called target sum, and we can see that this one is a LeetCode medium problem and also an extremely well-liked problem on LeetCode. We are basically given an integer array called nums, and we are also given an additional integer called target. Now we need to build an expression out of these given numbers such that by adding one of the plus and minus syllables before each of the integer in numbers and concatenating this expression to basically create this target value. So here is an example. Let's say that if we are given values 2 and 1, then we can add plus before this 2 and we can add a minus before this 1 and combine them to build an expression such that minus 2 plus 1, which is going to result in the value 1. So now we can basically create bunch of different expressions like this using plus and minus sign. Now we need to return the different expressions that we can build inside the given nums array, there where the total sum becomes the target, and we need to return every single possible combination that can have such values. So let's say if we are given an example like this, where we are given nums array that contains 5 elements and all the values are 1, and we are also given a target value that sums up to 3. Now in this case, we can use plus and minus symbol to create bunch of different expressions that I have noted down over here, and we can see that all of these are unique operations that all sums up to value number 3. And in total we can define that there are exactly 5 different ways for us to generate value number 3 from using this given nums array and using plus and minus equation, and in the end we need to return 5 as the answer in this case. Now first let's try to understand the very preliminary brute force approach. The logic is quite straightforward, that for any particular given number of input, all we need to do is just test out every single possible plus and minus symbols and make the subset sum of every single possible permutations and combinations. Let's say in this case we are given target to be 3 and we are given these 4 values. So what we'll do is first we will use all the plus values and we will try to see that if we are able to reach target. If not, then we will try to go reverse and we will try to add one minus over here and then leave all of the values are plus. Then we will make these two as minus, then we will make these three as minus, then we will make all four as minus, and so on and so forth. We will keep on checking bunch of different permutations and combinations. Whenever we hit target value, we will mark that as an correct answer, and in the end we simply need to return that variable. This solution works, it gives the answer, but it is extremely inefficient, and you can understand why, because we are testing every single potential permutation and combinations, and majority of time we are going to be not targeting value number 3, we will have some other answer, so we are not focused on that. So we'll have to do things smartly. So before we come to the optimal approach, let's make few things or few mathematical equations correctly. Let's say that we are currently given bunch of different values inside our nums array, right? Now we know that all of these values, they can have some any particular meaning. But the thing is, we can add all of these values and we can mark these values, so sum of all the values inside a variable called sum. So let sum be the sum of a plus b plus c. Now we are also given for a fact that we need to create partition amongst these a, b and c in such a manner that there are two partitions. First partition is s1 and second partition is s2, and the difference of these two partition becomes the target value. So this is one equation we can make. Second equation is sum of s1 plus sum of s2 is actually going to be this sum value as well. So now we have two mathematical quadratic equations for two different variables, and we know the value of target, we know the value of sum. So it should make sense for us to get the quantifiable value for s1 and s2, and let's combine them. So if we do combination of these two plus this two, we can create a new equation where the values are, we did nothing special, we just did sum of these two values. Okay, now in this scenario, this s2 and s2 are going to cancel out each other, so we can say that 2 of s1 is going to be target plus sum. So we know that we need to find a partition such that the value s1 exists, and the value of s1 is going to be simple, that is going to be target plus sum divided by 2, and we have the value of s1. Now if we can identify s1, then we should be able to identify s2. So s2 would be basically all the remaining values, and we will just add minus sign before them. Now the thing is, lucky for us, we are not being asked to calculate that what are all the different expressions. We simply need to provide the number of different expressions. So for that, we actually don't need to calculate every single possible pairs. We simply need to know that what are different ways we can generate s1, and this would be true for s2 as well, and then we can simply return that as the answer. Okay, so now we have established all of these things. Now let's try to also consider some edge cases and some scenarios that for sure we can say that they are never going to make anything. So let's say that if we identify that sum of all the values are less than 0, in this case it would be impossible for us to generate the target value. So in this case we can simply return 0 as the answer. Same way, if we identify that the value of s1 is not modulo by 2, it's not possible to modulo by 2, then also we can return 0. Next thing is that in any scenario we identify that s1 value becomes negative, is a negative value, then also we cannot find subsequent s2 value, because in front of s2 we are putting all the negative values, so we can return 0 as well. These are going to be our edge cases, so we can get rid of them. Now let's come to the meat of the solution. The aim is that we are currently given a nums array that contains bunch of different values. Let's say a1, b1, c1, all of these are some integer values. Now we need to create the combination amongst these values such that the sum of them, so a plus b, could become s1, or a plus c could become s1, so on and so forth. We are not focused on adding plus or minus and all of these things. We are only focused on finding a subset sum amongst the given values that sums up to that value. And this is the critical moment of the entire problem, to understand that why are we trying to find this one. Okay, now we know what we need. Let's see how we can achieve this, and how is actually going to be solved by the most beautiful concept in the entire computer science, and that is called dynamic programming. Now why dynamic programming is a good candidate in this case? Well, reason is quite straightforward. Let's say that we are currently only given just one value, 1, and we are given some arbitrary target value. So in that case we can simply say that whether this makes the target or not, does not make the target. Let's say the target is also 1, then we can say that there is exactly one way to generate target. We can clearly see. But if we are given values 1, 1 and 1, now in this case the number of ways we can generate target actually increases with the increment of every single value. Let's say next value is 2, let's say next value is 4, so on and so forth. Whenever new values gets added to the equation, the way for us to generate that particular target becomes increasingly more. On top of it, our s1 also changes. So what I'm suggesting is that instead of focusing that how many different ways we can generate s1, why don't we just generate the entire sequence that starting from 0 all the way up to s1, that how many different ways we are able to generate that particular element, and that we can calculate very easily using every single numbers that we are given. And we are going to keep into the consideration that how many different ways we were able to generate some previous element, and based on that we would add that value to our s1. So that's why this is a good candidate for dynamic programming. On top of it, let's see that how does dynamic programming is actually going to work. So we explained that we are going to create a dynamic programming array. We also know that how can we generate our s1. Basically the formula for s1 is the target plus total sum divided by 2, and we simply need to generate this value. Now for our dynamic programming, we are going to have an array that starts from 0 and goes all the way up to our s1. Now what is going to be the value of dp of 0? Now notice that this 0 indicates that how many different ways can we generate value 0. And in this case we know that there is exactly one way we can generate value 0, and that is by not using any values inside our subset sum problem. So there is one way, and this is going to be our base case that we can use as like a stopping point. Now let's say for an example, I'm giving scenario. Let's say that the given number only contains value 3, and the target we are given, let's say that this target is also 3, right? Now we know for a fact that if this number is 3, then we can make two numbers plus 3, and we can also make minus 3, because we can use two signs plus and minus. So in that case, if this number is 3, does it make sense for us to check that how many different ways we can generate value 1 and 2? No, of course not. We cannot generate value 1 or 2 using this value 3. We can only generate value 3 and above values. So we are always going to be considering this value 3. So what is going to be our dynamic programming equation? Dynamic programming equation is quite straightforward. Let's say that if we are trying to find that what is going to be the dynamic programming of 3, because current the given number is 3, then this is going to be that how many number of different ways we are able to generate 3 plus the total number of difference between dynamic programming of 3 minus the current num value. So current 3 that we have, so basically 3 minus num, and this would be the formula that we are going to be using in order to populate our dynamic programming array. Let me explain the solution once again, that at any given moment dynamic programming of ith number is going to be depending on dynamic programming of ith, which already says that these are the different ways you can generate value number I plus dp of I minus the current num value that we are iterating over. Because remember, if we can generate 3, we can also generate 6, like if we are given one more 3, so on and so forth. So if we are at 6 location and we know that there are two different ways we are able to generate 3, then there is going to be 3 different ways we can generate 6. Basically that's the way how it works. Let's say assuming that original value of 6 was 1. Now coming back to our problem, let's try to populate our dp array for the given case. Let's say that current given values are 1 1 1 1 and 1. So in this case all of these values are 1, and the target value we are currently given is going to be 3. Now for this scenario we are going to be using our equation that dp of I is going to be dp of I plus dp of I minus num's value, and we need to calculate our s1. So s1 is going to be target plus sum. So in this case target is 3 and the sum is going to be 5. So let me just mark sum is equal to 5. So s1 is going to be 5 plus 3, 8 divided by 2. So s1 is going to be 4. So we are going to initialize our dynamic programming array that is going to be extending from value 0 all the way up to 4. So let's just mark this value. Okay, now let's start making our base case. So dynamic programming of value 0 is 1, so that is obvious. We can't do anything about it. Now let's start populating all of these values one by one. Now the current value we are dealing with is value number 1. Now notice that we are actually going to start traversing in the reverse order, not in this order. And why are we going in the reverse order is to make sure that whenever we calculate the results or the number of subset sum, we calculate that only once, not two times. Because let's say that if in this case currently all of these values are 0 0 0 0. Now if I apply this equation and if I start with this 1, so position 1 we are going to be starting with, then this value becomes 1, this value becomes, now this value would become 2. Why? Because we are doing the sum of this value with this value, and so on and so forth. So the value would keep on increasing and we would count the same value multiple times. So that's why we will start counting in the reverse and we will come up until this particular number value that we have. So let's start with value number 4. Currently the value of value number 4 is 0, and currently so this value is going to be 0 and dp of I minus none. So 4 minus 1 is going to be 3. This is also 0. So we are not bothered to check or update this value number 4, because there are no ways we can generate value number 4 using just 1 1. Now next, once again we are at dp of 3. So for that, and we are considering this very first one so far. Now once again equation is going to be 0 plus dp of 3 minus dp of 2. So 0 plus this, so this value is also going to be 0, so this will remain 0. Same way dp of 2 will also remain 0 because this is 0 plus 0. But for dp of 1, dp of 1 is 0, but dp of 1 minus num is going to be 1. So this value becomes 1 at the end of this equation. And notice that what we have done so far is nothing but just saying that if we are only given an input array that contains value 1, then we can only generate value or target sum to be 1 one time. That's it. Now we are considering our scope and we are including the second one into the equation. Let's repeat the same operation. So dp of 4 is still going to remain 0, and same way dp of 3 is also going to remain 0 because of this equation. But for dp of 2, now this value would become 1 as well. Why? Because now we have one way to generate value number 2, that is by using 1 plus 1. And for dp of 1, this value will become 2. Why? Because remember that we are following this equation, so this is going to become 1 plus dp of I minus num is also going to be 0, and that value is also 1, so this value would become 2. Okay, after this, now we are considering this third one. So once again, the value of dp of 4 is going to remain 0, so let's just leave it as it is. But for this dp of 3, this value is going to become 1, so let's just mark this one as 1. Now dp of 2 is going to become current value of 1 plus 2, so this value is going to become 3, so let's just mark this as 3. And this value is going to become 2 plus 1, so this is also going to become 3, so let's just mark 3 as well. Now we are considering this one. So for this particular one, now once again we are starting from position number 4, and this value is actually going to become 1 because the previous value is 1. Now this value is going to become 1 plus 3, so because previous value is 4, so let's just mark this one. This value is going to become 6, so let's just mark this one, and this value is going to become 4, so let's just mark this one as well. Okay, cool. Now we are at the final one. So for the final one, we are going to be doing the sum of these two values, so this value would become 5, which means we are saying that if we have to generate 4 using these values, then we have 5 different ways to generate 4. Same way, this value is going to become 10, so let's just mark this as 10, and let's just mark this as 10 as well. And in this case, 1 would become 5, and this one is going to remain 1 as it is. And now we have reached to the end of all the nums, so basically we are simply going to return this value as it is. This is the whole solution. Now look how beautiful this looks. Basically, this dynamic programming array tells us that if we are given the input numbers as 1 1 1 1 1, then if we are given the target value to be 4, then we can generate it in 5 different ways. If we are given target value or s1 value, not target value, if s1 value to be 3, then we can generate it 10 different way, and so on and so forth. So we are calculating for all the possibilities, and I hope my solution made sense. Now let's understand the time and space complexity. Time complexity is going to be simply big O of n multiplied by big total number of s1, because we will have to do every single iteration this time for all the values that are currently present inside our given input nums. In terms of space complexity, because we are using an additional array, it is going to be big O of n, but that is a reasonable and acceptable solution. It's not that bad, and it's actually pretty good because we are using memoization to solve this problem. So now let's see the coding solution for this one. So first we are going to create a variable called sum, and then we are going to iterate over the given nums array to include the total sum of all the elements, and that we are going to populate inside our sum variable. Now we are checking that if it is possible to make partition, which means we are checking few edge cases and scenarios. That is, the first one is that if the sum of target plus sum becomes an odd number, then we can simply return 0. If that is not the case, then if the sum is actually total sum is actually less than the absolute value of target, in that case we can also return 0 as well. If that is not the case, we are going to define our s1, that is defined by target plus sum divided by 2, based on the explanation we had during our solution. Now we are checking that if the s1 is less than 0, then also we can return 0. This is to make sure that we are preventing negative array size. If that is not the case, then we are going to initialize our dynamic programming array, where we are initializing it with s plus 1 value, and we are going to have our initial base case for our dp array, where dp of 0 is 1, because there is exactly one way to sum up to 0 by using no elements. Then we are going to iterate over every single nums that is currently present inside our nums array, and for each of the number we are actually starting from s1 and we are coming down all the way up to nums and we are reducing one value. So there is a loop inside the loop where we are simply following the equation where the value of dynamic programming of j is going to be the sum of dynamic programming of j plus j minus num, and we are coming in reverse order in the second loop is to make sure that we are not counting the same element twice. If we go from num to s1, then there is a very high likelihood that we are going to keep on counting the same element multiple times, and that would give us all kinds of weird results. So in the end we simply need to return dp of s1, and this should give us the total number of distinct ways we can sum up to that particular target element. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code, and our code beats almost 99.78% of all the other solutions, which is our solution is one of the most popular solution on the entire LeetCode, which is pretty awesome. And we are also extremely efficient in terms of space complexity as well. So once again, the solution for this code is present in our GitHub repository. Feel free to go ahead and check it out from there. Thank you. The LeetCode problem we are going to solve now is called interleaving string. Now this one is a LeetCode medium problem, a very well-liked problem. The thing is, this problem statement is extremely complicated to understand. We are given string s1, s2 and s3. Now we need to check that whether string s3 is formed by interleaving strings s1 and s2. If you want, you can go ahead and read all of this description. If not, let me give you a quick simple example. We can notice that currently the entire s3 can be created using the characters in the same sequence that they are present in s1 and s2. So let's take it one by one. We have this character a, so we can take a from s1, so we use this one. Same way we use a, so we also use this one. Now we have a d, so currently this character is b and this is d, so once again we can use this one. Same way, now we have b, b and c, so we can use b, you can use b, and we can use c. So same way we use all of these characters, and then once again we have characters b and c, and same way we have character a, so we can take a from here, and then once again we have one more c, and then we can take c from here, and this ends all the characters inside s1 and s2 and all the characters inside the s3. We can say that we can interleave string s3 from the given string s1 and s2. This is what we need to prove for any given input. If we are able to do that, awesome, we need to return true. If we cannot do that, we need to return false. Well, the most basic brute force approach comes to our mind is to check for every single permutation and combination of s1 and s2 to see that how can we form all the characters in such a way that we are able to generate s3. So let's say that we are checking for the first character a, then we need to either choose the first character over here or first character over here. We cannot choose both. So lucky for us, we can choose a over here, so we get rid of this character. Now we are at second character on b, and we are still at first character at b. Now the thing is, next character we are trying to find is b. Let's say that by sheer chance we decided to choose this b character. If we choose this b character, immediately the very next element is x. Thing is, we check, okay, this one is b and this one is c, so x does not match b or c. So we can say that because this does not match either one, we can simply return false, saying that we cannot interleave string. But thing is, this would be a wrong assumption, because we did not consider the scenario where instead of picking this b, we could have picked this b, and then we would be still in a position where we are comparing the values between this b and this x, and then this x would have make perfect clear sense. So in the simplest term, we are actually making a decision tree where the very first character option choices we have is amongst a and b. which is the very first these two characters. And for that we have in the S3 we have a character A that we compared. So now we get rid of this one. Now in the next choice we have the characters B and then once again B, and in the S3 once again the character we have is B. The thing is we don't know which B are we going to choose from. So we can choose from B that is located over here, and then we would have the choices C and B, or we could have chosen this B and then once again the choices we would have is going to be B and X. So depending on that we can have many different decision trees, and now you will start to notice the problem that could arise, because at every given moment we have the option to select something from between two different tasks or two different paths, and that is the time complexity of 2 to the power n, which is extremely bad time complexity. And that's why solving this problem in brute force would yield the correct result, but this is not going to be a good approach. We are trying to deal a scenario such that any particular result that we are currently calculating is actually going to have an impact on the previously calculated results, and depending on that we will have to make further decisions that which path are we going to take. And this is why this becomes a perfect candidate for the most beautiful concept in the computer science, that is called dynamic programming. Because number one, we will have to keep track that what was the previously calculated result. Number two, what is the current result. And number three, store these values in such a format or such a fashion where we can access them immediately and we can make judgment calls based on that. So let's start understanding with very small examples. Let's say S1 is an empty string, S2 is an empty string, and S3 is an empty string. Once again, yes, from using this example we can create string S1 from S2 and S3. This is always going to be true. Let's take one more complicated example. Let's say the values are going to be A, B, and this value is going to be C. And currently for S3 we are comparing the values A, C and B. We know we can make this one, but how it is going to work? The idea is, first we are going to compare the very first element compared to S1 and S2 and the value S3. And for that let me just make a very small table. Okay, this is going to say that if I am at 0 and 0th position, then even for the S3 I'm going to check for the 0th value. If I am at first and 0th position, then for the S3 I am going to check for the first value. If I am at second and 0th position, then 2 plus 0, so I'm going to check for the second value inside the S3, and so on and so forth. We will keep on repeating and compare the values. So let's compare. We know if we are at 0 position and 0 position in S1 and S2, and the cell inside the S3 is also 0, so currently we are starting at 1. 0 means that S1 is empty, S2 is empty, and S3 is empty. In that case, this is always going to be true, because we can always interleave string S3 from S1 and S2 if both characters are 0. Okay, that's a given fact. Now let's take this scenario. Currently we are at position A. So let's say that if we are only given S1 is equal to A, we are only given S2 is equal to nothing, because we are marking it as 0, and 0 we don't have any value for S2. And for S3 we currently have we are only comparing the 1 plus 0, so we are only comparing the first value inside the S1. So currently S3 also contains just A, one value. So if this is the case, are we able to interleave string S3 from S1 and S2? Yes, we can interleave string S3. We can just use this string. So because these two values are same, we can say that this is going to be true. Now let's add one more scenario. Let's add this 2 over here. So if we are given a string such that A, B, S2 is still empty because we are comparing against this cell. And for S3, because this has two characters, we are going to mark 2 characters. So this is going to be A and C. Now in this case, are we able to interleave string S3 as AC if the given string S1 is AB and S2 is empty? No, because B and C does not match. So in this case, we can mark, because they do not match, we will mark this result as false. Okay, if that is, now let's come back. Now we are at this position. So we are checking for this particular cell. So what is the position of this cell? Currently this one is empty. So the value inside the S1 is going to be empty, and the value inside the S2 is only going to be C. and we are comparing the S3 to be so let's do the sum of these characters, because this is 0 and this is 1, so we are only comparing one value from the S3, and that is going to be A. So if we are given three strings S1, S2 and S3 like this, are we able to interleave? No, because this one is A and this one is C, so they do not match, so we are going to mark false over here. Now once again let's repeat the same operation. Now we are checking in for this particular cell. So what are going to be the configurations for the cells S1, S2 and S3? Well, S2 is going to contain character C, S1 is going to contain character A, and for the combination of this one, so this is 1 and this is 1, so 1 plus 1 is 2, so we are going to consider two characters from S3, and that is going to be AC. In this case, we know we are able to generate this pair completely, so we know for sure that this needs to be true. The thing is, how are we able to say for certainty that these pair matches? Well, because notice, and this particular position, we have the value, this value as A, this value as C, and the combination of these two values becomes AC. Let's see that what is matching with what. We can see that very first value A, we already have a match because of this particular value, and currently we have a match with C that is coming in. So whenever we have any value on, like this is going to be Y axis, so whenever we have any match on, let's say that this is going to be our ith row and this is going to be our jth row, if we have a match on jth row, because C is matching with this current C, so if we have a match on jth row, we will have to compare that are we able to generate A and C in order to make sure that if this C is valid or not. If you get confused, just look at this example and it would make sense, because we can, this character C is only good if we already have a previously matching character. If we did not have a previously matching character, let's say over here, instead of this S3 being ABC, if we had values XCB, then this would have been XC. So even if these two characters match, because we are at this particular cell, still this should not have been true. Why? Because this character did not match, and if this character did not match, this value would have been false. So in this case, because this value was true, so using that, because this value was not X and this value was actually A, then only we can say that there is any fruitfulness in this C currently matching with the subsequent value inside S3. So the result of this character is actually dependent on its previous character, because the string was from S2. So whenever any particular cell from S2 we are trying to compare, we are going to check it with the previous element on top of it. So in this case, we can mark this one as true as well, because this character was true. Same way, now we are at this position where if we notice, this is going to be A, B, C, and since the sum is going to be 2 plus 1, so 2 plus 1 is 3, so we are going to compare all of these three characters, so this is going to be A, C, B as well. Now notice that the matching pair in this case is actually going to be this B. So we are matching with the character from S1. If we are matching for this particular cell for a character from S1, then we need to check that whether the very previous value for all the other remaining S1 characters, are we facing the value to be true. And in this case, because remember, same way for this character, we check that whether this previous element was true or not. And because this element was true, then only we can say for certainty that this has to be true as well. But in this case, now the matching pair is from this region, the top region, then we will have to check that whether for this cell, whether its previous element on the left for S2 was true or not. Why? Because let's say, once again repeating the same example, let's say that if this S3, instead of being ACB, if this value was once again, let's say XCB or XYB, something like this one, then even if this B matches, the previous values did not match, so this value must have been false, so then we would have to mark this false. But since this was not false and we found out a correct match, so we can also mark this as true. Now we iterated every single possibility inside this cell And same way we simply need to return whatever the value we have at the very last element inside this character, and then we can return true it as true or false. Now let's take one more quick example to understand that how does this thing is going to work completely. So for this example, we know that this value is always going to be true, so let's just mark this as true. Now we are going to iterate over the first column. Okay, so we will compare the only s1 values with s3 values. So for this first value we have a matching, so because it's s1, we are comparing it with its previous value, so currently this matches, so we can also mark this a as true. Same way, next value is b. Once again, ab and ab are still matching, so and the previous value is true, so we can also mark this one as true. Next value is x and this value is c. Because of this, they do not match, so we are going to mark this as false. We don't need to check any other value. Next value is once again b and this value is d, so once again they do not match, so we can simply return false. And even if they did match, we would still mark them as false because the previous value was false. Same way, we are going to check the column value where we are only comparing this s2 with this given s3. So currently the very first value should have been a, but over here the value is b, so we can mark this as false. Same way, now this value is b, but this value is x, so once again we can mark this as false. And same way, this value is y, but this value is x, so once again we can mark this one as x. Now we are at position 1 and 1. So because values are 1 and 1, we are comparing the value number 2. So value number 2 is going to be b. So we can see that yes, there is a potential match b over here. Now notice, whenever there is a match on this side, we will need to compare for this cell, it's above cell above it. So since this value was true, we are going to mark this value as true as well. Now we are comparing once again this particular cell. So for this cell, the value should be 2 plus 1. So we will need to compare the third value. So third value is x over here, and over here both values are b and b, so this value needs to be false. Same way, next we are going to compare 3 plus 1, fourth value. So fourth value is b. So we notice that over here we do find a potential match b with this b, fourth value that we are trying to compare. But the thing is, once again, same way, yes, we have a potential match over here, but the value above this was false. So because of that, we are also going to mark this one as false. And same way, now we have this value c over here, and we have this value comparing between d and b, so it does not match, so we are going to return false over here. Same way, now once again we are comparing this particular cell. So now the value is 2 plus 1, so 3. So third value is x. Yes, because third value is x, we can notice that this x matches. It matches with the value on once again j axis, so we will have to compare the value above it. This value is true, so because of that, this is also going to be true. Then we are going to compare this b and x with this b. So once again, this value is b, that is correct. Now this b matches with the value over here. In this case, because it matches with the value on the y-axis, we, for this particular cell, instead of covering the value above it, we are going to check for the value right before it, and this is true, so that's why this is also going to be true. Next, we are going to compare the values between c and x, and this value is 3 plus 2, 5. So fifth value is going to be the c. So once again, this c is true. So if this, because it matches with over here with the ith value, so we are going to compare the value before this one, that is true, so we are going to mark this one as true as well. Same way, the next value we are comparing is going to be d and x, and over here the value is also d, so we are also going to mark this one as true because it matched over here. Now we are at once again this position, the value is y, so the value is 3 plus 1. So 3 plus 1, 4. 4 is not y, so we can y, or 4 is not a, so we can simply return false over here. Same way, this value we are comparing is going to be b with y. So and this is going to be 2 plus 3, 5. So fifth value is actually c over here, so we can return false over here. Same way, now this is going to be 3 plus 3, so sixth value is d, and over here the values we are comparing are going to be y and c. So once again, it does not match, so we can return false. And the very next value is y, and because this is the seventh value and we are comparing 4 plus 3 seventh value over here, so we have a potential match y. The moment we see a potential match y on this jth axis, then we will have to compare the value above, and the value above is t. So this value is also going to be true, and in the end we need to return whatever the value we found for the very last element. Since this was true, we are going to return true, and this is the whole solution. See how beautiful the solution is, because for every single possible pair we keep on checking that whether we can interleave string s3 with given subsequent string s1 and s2. So this is pretty awesome. And the time complexity in this case is going to be big O of m multiplied by n, where m is the length of s1 and n is the length of s2. Space complexity is also going to be big O of m multiplied by n, and it is quite obvious because we are using a dynamic programming 2D array to store this answer. So now let's quickly see the coding solution. The coding solution is quite straightforward. First, we are going to define three different variables m, n and l to define respective lengths of s1, s2 and s3 strings. We will check for an edge case that if the given string length m plus n is not equal to l, we can return false immediately. If that is not the case, we will initialize our dynamic programming array, and notice that as part of the length, we are keeping it as m plus 1 and n plus 1. This is to take care of that extra row and extra column where we are only considering s1 or s2 string. Then we are going to have our base case that dp of 0, 0 would be true, as in we can always create or interleave a string with 0 characters if both s1 and s2 has 0 and s3 also has 0 characters. If that is not the case, then we are going to fill in the first row where we are simply going to check the values for the s1 row, and same way we are going to fill in our first column using s2. Where we are simply comparing the characters s1 and s2, s1 with s3 and s2 with s3, and we are going to pick the previous row value or column value in the place of the current ith or jth position. Then we will fill in the rest of the DP table where we are going to use two for loops starting with I equal to 1 and j equal to 1, and for every single cell we will compare that whether that cell matches with S1 and S3 or it matches with S2 and S3. If it matches with S1 and S3, then we can simply mark the value of the previous row position. If it matches with S2 and S3, the character value, then we will mark it with the previous column position, and based on that we will keep on filling our DP table or dynamic programming table. In the end, we can simply return the value for DP of m and DP of n. So if this is true, it's great. If it is not true, then we can simply return false. And this is the coding solution. Let's try to run our code. Seems like our solution works as expected. Let's submit this code. And our code beats good chunk of other solutions in terms of time complexity, and it is excellent in terms of space complexity. We beat nearly 96.46% of all the cases, which is pretty awesome. And once again, the coding solution is present in our GitHub repository, so feel free to go ahead and check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. So the question we are going to do today is called longest increasing path in a matrix. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Apple, DoorDash, Google, Facebook, TikTok, Nvidia, Amazon, Uber, Microsoft, Snapchat, ByteDance and bunch of more. So I'm going to pay my utmost attention. I hope you also find this useful. So this is a LeetCode hard problem and also a very well-liked problem, which is a rare combination to find. Basically, we are given an m cross an integer matrix and we need to return the length of the longest increasing path in this given matrix. Now, how do we build this longest increasing path that we need to return the length of? Essentially, we are told that from every single cell, we can move in 4 directions: left, right, up or down. And based on that, we need to calculate that what is going to be the longest increasing path. We are also explicitly told that we don't have to care about diagonally moving or values outside the boundary. So let's try to understand this with an example. Suppose in this case, this is the example that we are given. Now our aim is to find the longest increasing path. Now we know that from any single cell how to define an increasing path. Let's say that we are currently located at this cell number 4. Now we have the option to go in 4 direction, up, down, left and right. Now from this 4 direction we only need to go to the direction of the cell that is actually increasing order. So we need to maintain this increasing property. So from this value number 4, what are the places we can go? We can go to 9 and we can go to 8. We cannot go to 6 because this would be a diagonal and we cannot go anywhere outside the boundary. Now in both the cases we have the option that the values are currently in the increasing order for this 8 and 9, which means both are legitimate scenario, but our aim is to find the longest increasing path. So from 8, do we have any other option to go to that increases in the path? No. From 9, do we have any other option to go to in any next cell that increases? Again no. So in this case from 4, the longest increasing path we can make is going to be 2. But is this the longest inside the given entire matrix? The answer is no. We need to find the cell that has the longest increasing path. So if we take one more example, let's take an example for this value number 1. Again, at this location value number 1, we have the option to go into 4 direction. But let's say that for the ease of convenience, we decide to go into the direction of this 1 to 2. Currently, the increasing path length is 1. Again from this 2, we have one more neighboring cell that is higher than the value, that is this value number 6. So this time the increasing path value will increase by 1. And again from the 6, we can go to one more neighbor that increases in the value, and that is value number 1. And originally we started with this value number 1 and we moved one hop. So basically we will add one more over here. So essentially we can create a path that looks like this, 1, 2, 6 and 9, and this would be the longest increasing path in our matrix, and the length of this matrix is going to be value number 4. That is what we need to return in the answer. And the first approach comes to our mind is the brute force approach, the very basic approach that we can take to solve this problem. Now let's try to understand that what would be the brute force approach in this manner. Well, of course, the answer is quite simple. From every single cell, we start iterating in all 4 directions, and from all 4 directions we will see that where we can find the increasing path, and the moment we find the increasing path, we keep on adding the value to our answer variable, and we will keep on adding 1 over here. And same way for our increasing path, we will go to its neighbor, and again we will keep on repeating the same process. So let's try to see the solution I'm proposing in action. Okay, so let's say that for the ease of convenience, we start at value number 1 or this value number 9. Again from 9, what would be the increasing path we are able to make, and what is the maximum answer we have found so far? These are the 2 variables we are going to keep track of. So 9 does not have any neighbors that are in the increasing order, because 9 is the biggest value amongst all. So in this case we won't be able to find anything. Let's go to this another 9. Again same thing will happen, we won't be able to find anything. So these 2 are the values that we took care of. Now we are at value number 4. Since value number 4 we already calculated that there are only 2 paths we can take. So currently the increasing path maximum we can make is going to be 2. So answer currently we have found so far is value number 2, that this is the maximum path we are able to make. But let's keep on increasing with next subsequent values. So currently the values we took care of is going to be the first row. So I'm just going to mark them as X, that we already took care of this. Now we are at this value number 6. From 6, what are the options we have? We cannot go here because this is not increasing, this is same. We can go here to 9, so this is good. So from 6 we can again create a path of increasing path of size 2, and then that's it. So again our answer will remain same. We also took care of 6. Same goes for this 6. This 6 we have the option to go to value number 9, and we have the option to go to value number 8, but that won't lead to any further results. So again we cannot move anywhere forward. So we also took care of these 5 variables. Now let's move on to value number 8. Again from this value number 8, we do not actually have any path to go to, so we don't even bother updating any of the variables. Now we are at value number 2, And now things will start to get a little bit interesting. So what are the options for the increasing path we have at value number 2? So first increasing path option is over here. So from 2 to 6, that is good. Again from 6, do we have the option to go for the increasing path? And the answer is yes. That is 6 to 9. So in this case, from this value number 2, the maximum increasing path we can achieve is going to be value number 3. So we are going to update our result, and so far the longest increasing path we have found so far is going to be value number 3. So again we are going to update our answer as well. Now we are at value number 1. So what are the options we have so far? Can we go to this? No. Can we go to this 6? Yes. So currently we go to this 6. From this 6, what are the options we have? We can either go to 9 or we can either go to 8. So let's just first go to 8. Okay, now we went to the 8. From 8, can we go anywhere else? No. So in this case, for this particular path, the answer we found is 3. But we still have one more option, that from 6 we can still go to this 9. So even if we go from 6 to 9, we don't have anywhere else to go. So once again the answer is going to be 3 as well. Now after taking care of both of these paths, now let's explore more options. And that option is that from this 1 we can go to this value number 2. Okay, from this 2 we still have option to go to value number 6. From this 6 we still have option to go to value number 9. So in this case we created a path that is 1 to 2 to 6 and then to 9. So in this case we created a path with a path length of 4. That is going to be the maximum path we have found so far. So we are again going to update our values. So this is going to be the current increasing path we found for the cell number 1, and the maximum path we have been able to find is also going to be 4. So we are going to update our answer because we need to enter the longest increasing path. And now we still have one more value that we need to go to. So again from this value number 1, we have the option to go to 1 to 8. And then from 8 we won't be able to go anywhere else. So in this case the maximum path we are able to achieve is going to be 2. After completing or after iterating every single value, we found out that the maximum longest increasing path we can create is going to be value number 4. So our brute force approach gave us the appropriate answer that we were looking for. But was it the most optimal answer? Well, the answer you already know, that of course not. And why? Because there are a few things we can actually make changes to. So first thing we can make change to is going to be regarding that for every single cell we were actually doing a lot of repeated computation. And how we were doing that, let me give you a quick example. So again, let's clean this up a bit. Initially when we were traversing our answer, when we reached to this value number 6, we already knew that from this 6 there is only one path we can go, and that is going to yield us the higher result, and that is from 6 to 9. So the longest increasing path or the longest path we can make at value number 6 was going to be 2. Now when we came back to this value number 1 originally, from 1 what we did was we went from 1 to 2, from 2 to 6, and 6 to 9, every single place repeating the computation we have already completed, and that is a bad approach. What if we already knew that at value number 6 the longest we can do is going to be 2? Same way this value number 2, the longest we can make is going to be value number 3. So based on this information, if we are at value number 1 and we need to go back to this value number 2, we can clearly see that from 1 we already know that there is an increasing path that leads to 2, but from 2 we already know that the maximum amount of value it can generate in terms of longest increasing path is going to be of value number 3. So rather than doing all of this computation, we could have actually just done from 1 we reach to 2 and see that we already have the computation result for 2. So we could have done 1 plus 3 and the answer would have been immediately available to us as the value 4. So this is one of the major significant improvement we can make. And what this improvement is, this is actually we are storing the results that we have already calculated. So what we are doing is one of my favorite things and one of the most beautiful things that is available in the computer science, that is we are actually using dynamic programming in this case. But on top of using dynamic programming, we are also doing something more interesting, and that is that we are actually rather than treating this as the matrix or 3 by 3 matrix, we can actually treat this as individual nodes, and this individual nodes would have some way of connection with them. How connection? Because we are trying to find a path. Now for this path we are actually given the definition that if only from this current cell, let's say the value of current cell is a, if there is a path from a to b where b is greater than a, then only we can connect a to b and consider it for our path. So rather than treating this as just 2 by 2 matrix or m cross n matrix, we can actually consider every single cell in this matrix is equal to node and the path that we are trying to connect actually as the vertices. And once we do this, after seeing these two words, immediately in your mind it's gonna click that essentially we are treating this as a graph solution, and we are in the graph we are trying to find the longest increasing path. We already know how to build a path, and that is using the greater than or less than relation between any two cells. So essentially we already have a directed graph, and we already know that there won't be any cycles in this graph, because let's say that how does the cycle occur in a single graph? Let's say we go from 3 to 5 up in the same position 3, then we can see that there is a cycle. But in this case it is not possible to have a cycle. Why? Because the relation of this edge is actually based on the property that 3 is less than 5. That's why there is an edge that exists over here. If 3 was not less than 5, then there won't be any edge over here. So which means from 5 to 3 there is an edge, there is an impossible way to create an edge. So essentially this is also going to be an acyclic graph, and we already know that this is a director acyclic graph, and in the DAG or directed acyclic graph we are trying to find the longest path. Basically, rather than treating it as longest increasing path, we are just trying to find the longest path. So essentially now our life becomes much easier. On top of that, we are already going to use the dynamic programming properties. So we are going to know that how we are going to take care of every single value. So we are not going to repeat the computations that we have already created. Now let's see that what would be the solution look like in action. Okay, so now what we are going to do is we are actually going to create a dynamic programming to m cross n grid, and in this case we are going to use this to store that every single element, how many increasing path we can make, maximum amount of increasing path we can make. So this would be a great help for in terms of memorization. On top of that, for every single node, we are treating it as a graph, and we are going to build the graph upon them. So we are not actually creating a separate graph. We can actually use the same matrix. For the visual representation, I'm going to make some circles and some arrows, but you would be able to imagine that what we are actually trying to do. So first, let's say that we are at value number 9. So we are at a graph node like 9. From 9, do we have any edges extending out? No, because this is the same as 9 and this is less than 9. So there is no edges, which means the longest path we can make at value number 9 is going to be of value number 1. Okay, we are good with this result. Now at this second cell 9, again same thing is going to happen, that we are going to have a single cell that is not able to branch out or connect with anything else. So once again the longest path we are going to make is going to be value number 1. Now we are at this value number 4. What are the options we have? So let me just clean this up a bit, and from this value number 4 we actually have a couple of options. We can either grow from 4 to 9, or we can go from 4 to 8. So let's say if we decide to go from 4 to 9, do we need to calculate that from 9 how many values we can go to? No. Why? Because we already know this result. So from this 4, let's say if we decide to go to 9, we are actually going to create a path like this, that initially we are going to have a node 4, and from 4 we have the option to go to 9, or from this value number 4 we have the option to go to value number 8. So currently we have two options. From this 8 we don't know how many options we have because we haven't calculated, but we already calculated the result for this value number 9, which means if we decide to go from 4 to 9, we are for sure guaranteed to have an increasing path of 2, because from 9 it does not lead anywhere else. So we are good with this so far, which means and from this 4 to 8, let's say if we decide that from 4 we are going to go to 8, what are the options we have? From 8 we cannot go here or here, So again from 8 there are no possible nodes that we can calculate, which means we are again going to be able to create a maximum path of 2. So in this case, rather than doing all of this computation, we can actually store our answer, and we can just put down the value 2 over here, that this is the longest path 4 can take. Now we are at position number 6. From 6, what are the options here? It has, well, 6, as you can clearly see that 6 is not able to go over here. It is only able to go over here, and this we have already calculated from. So that means that from 6 we only have 2 options, and that is the longest path we can make is of value number 2. Again from this 6 we have 2 options. We can go to this value number 8, or we can go to this value number 9. In either case, the maximum path we are going to make is going to be of size 2. Reasons you already know. From this 8 we cannot actually go anywhere else, so the longest path we will be able to make is going to be 1. Now from this value number 2 we actually have just one option that where we can go, and that is to go to this value number 6. But from this 6 we already calculated the results, and that is going to be 2. So in this case we can clearly write the answer as 3. Now from this 1 we actually have multiple options to go to. So this I'm going to draw in the answer, and you would be able to understand what I mean. So initially we are located at this value number 1. From this 1 we have the option to go to value number 6. From this 1 we also have the option to go to value number 2, and from this 6 we have the option to go to value number 8, and we also have the option to go to value number 9. From this 2 we have the option to go to value number 6, and then 6 we have the option to go to value number 9, and currently we are located at this position. So these are the possibilities, or these are the options we can have. Let's assess each path. So in this case, if we go from 1 to 6, then from 6 we can either go to 8, or we can either go to 9. In either case, the answer for this portion is going to be value number 3. But in this case, if we decide from 1 to 2, 2 to 6, and 6 to 9, we are going to get the answer to be of value number 4. So in this case, 4 is the maximum answer we can get, but we don't actually have to do all of this computation. Why? Because we are using dynamic programming. That is the most important concept so far. So from this value number 1, the moment we see that this is where we can go, our mind should click that if we take this path, then what we would do is from here if we take this path, then the sum is going to be 3. But from here, if we take this path, then the sum is going to be 4. So obviously we are trying to find the maximum value, so we are going to store the value 4 rather than storing the value 3, and 4 is here. Now we are again located at this value number 1. From this 1, can we go over here? No. Can we go over here? Yes. So what is the maximum path we can make? We can do one jump like this, and we already know that there is only one single entity path we can choose over here. So maximum value we can get is going to be 2. So this is going to be our dynamic programming graph combination matrix combination solution, and that is why this is treated as a hard problem. But in my opinion, if you already knew these concepts, then it won't be so difficult for you. And after watching this video, I can guarantee that this is definitely not going to be hard for you. So we can clearly see that in the end we only need to return the maximum value that is present inside the dynamic programming graph, and that we can return quite easily, and this is going to be the whole solution. Now this is a very beautiful solution. If we see time and space complexity in this case, essentially the time complexity is going to be big O of 2 times m cross n. So overall we can write the time complexity to be big O of m multiplied by n, which is a very good time complexity. And if we see space complexity, well, this is a little bit more expensive because we are using an additional 2 by 2 or m cross n matrix over here. So this is also going to be big O of m multiplied by n, but this is also reasonably acceptable. This is not very complicated. So in my opinion, this is a very good problem to understand 3 major concepts, and that is graph, dynamic programming, and also matrix. So everyone should do this problem at least once. Now let's go to the coding part that is not so difficult. So basically, first of all, we are going to create a 2D array to store all the directions that we are going to traverse over. We are also going to have some private integers that we are going to use. Now the first idea is to create or to find the longest increasing path. As an input, we are using the matrix that we are given in the input, and we are simply going to iterate over the given matrix. We are also going to create a cache or a dynamic programming m cross n array, and we are simply going to have our answer stored initially as value number 0. Then with using two for loops, we are going to iterate our n cross n array, and we are going to check that whether at any single cell position are we finding the maximum longest increasing path or not. And for to do that, we are actually going to call another helper method called dfx, where in the dfs as an input we are going to provide matrix, the current ith and jth position, so to identify that which cell we are talking about, and the current array that we or the current dynamic programming matrix that we have created and populated. Now inside our dfs method, we are first of all going to check that for any particular value, are we or have we already checked that particular cell value or not, and we are going to initialize the dynamic programming array as 0. So if the value is not equal to 0, then we need to find the value for that, and we are now going to iterate in all four directions from that particular cell. Then we are going to check that we are going out of bounds or not using these four conditions. If not, then we are only selecting the path where the adjacent values are going to be in the increasing order, and if that is the case, then we are going to update the value of our current cache with whatever the maximum value we can find for that existing cache, or recursively calling the dfs method again. And in the end, we are going to add one more value to our cache because we found an additional path that exists. And let's say if we don't find any additional path, still the initial value of cache is going to be 0. So if we increase it by 1, it is going to be added by 1. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code, and our code runs pretty efficiently compared to a lot of other solutions. I would be posting this code in our GitHub repository, and that link for our GitHub repository is actually posted in the description, so you would be able to check it out from there. Thank you. Hello friends, so the LeetCode problem we are going to solve now is called distinct subsequences. We can see that this one is a LeetCode hard problem and also a very well-liked problem. Now basically we are given two strings s and t in the input. Now we need to return the number of distinct subsequences of s which equals to basically t. So how many different ways we are able to generate string t from the given string s, and that is what we need to return. So let's try to understand it with a couple of examples. Let's say that we are given the string as a b b and the given string is a and b. Now in this case, notice that we can generate t in two distinct ways. First one is if we use just this first two ab, or second one is if we delete this ab and we use the first and last ab. So that is what we need to return as the answer. Second scenario is that let's say if we are given the word rabbit, rabbit, and in the subsequence that we are trying to generate is rabbit. So in this case, we are dealing with 3 b's over here, and over here we only need 2 b's. So basically, once again, we can generate it using 3 distinct ways. First way would be where we are eliminating or not considering this b, so that forms rabbit. Second scenario would be where we delete this b, and third scenario where we would not consider this b. And in either case, we would be able to generate t, so we can return the answer. Now, as always, let's try to understand the brute force solution first. Well, we know that at any given character s, we need to define that will that character help us generate value that is currently present in t. So for a smaller example, let's say the given values a, b, b, the current t that we are trying to generate is a and b. Now notice that at any given location of s, we are making two decisions, whether to include this a or exclude this a in order to generate the t. If the characters match, we include it for our subsequent answer. If they do not match, we could have excluded it and then try to see whether some other sequence makes sense or not. Same way, after doing this, even for the other two characters, we still have the same two possibilities on whether to include this character or not. And very quickly we realize that this leads to basically exponential time complexity, where we are dealing with somewhere between, like, I guess 2 to the power of n time complexity where n defines all the characters that are currently present inside the given s, and 2 because we are making two decisions at any given interval, which is a very expensive time complexity if you plan to solve this. So we'll have to find a better way to compute. Now just try to understand that the optimal approach in this case is going to involve the most beautiful approach in the entire computer science, and that is going to be dynamic programming. But the thing is, let's first understand that why do we need to use dynamic programming in this case. Well, because all the values that we have currently calculated so far are going to help us make future decisions. Let me give you an example. Let's say the given values are a, b, b, c, and the value we are trying to generate is going to be a, b, and c. Now notice in this case, if we have already computed that in order to generate this character a, there is only one way we could do it, why don't we just keep that information handy? So next time when we encounter a character ab, we don't have to look the entire ways to generate ab from the given input. We already know for a fact that this are, like, let's say there is only one way to generate a, we know for a fact, and then we found like 2 or 3 occurrences of b, then in either case for each of the occurrence we can recompute that result. So let's say that since we are given 3 b's over here, we know for a fact that there are going to be 3 distinct ways for us to generate a b no matter what. And now when we are dealing with c and we realize that there is only one c over here, which means there is only one way we could do it, which means it does not add to us being able to generate this value. So overall the answer is going to be 3. But let's say over here if we are also dealing with 2 c's and a d, then also the answer might change. So at any given instance in the character that is currently present at t, we define that whether that character matches the subsequent character inside the s or not, and based on that we are trying to check that what has been the previously calculated results for each one of the characters, and then we are able to make that decision on whether to include that character or not. Now notice in this case the number of subsequences only increase when the characters match, and basically when we have already calculated all the values that we have calculated so far. Because over here if this was abc and abc, we know that there is only one distinct character, but if this was a, b, b, c, then we have a match at b and one time and a match at b at the another time. So basically we can take whichever b path we want and the answer would still yield the same result. So that's why we are dealing with two possibilities over here. First possibility is if there is a match. If there is a match, basically we include both the possibilities of calculating or both the paths that would yield us in a subsequent. If they do not match, then we simply do not need to include that, and we can keep the same subsequence number that we have even if we did not included that character from the given subsequent s, because it wouldn't change the total number of result that we are trying to generate. And we would understand this if when we start using a DP matrix in order to solve this problem. Now the question becomes, why do we need to use a DP matrix? Because the characters present in s and the characters present in t, they both are of value to us, and we will have to calculate for every single possible permutation combination. And in the very last result that we find in the matrix, that is going to be the total number of distinct subsequences we can make. So I have currently drawn a big matrix like this. Now notice that all the characters we have in the T are currently present over here, and all the characters in S are currently present over here as part of this. So this is going to be basically our jth value, and this is going to be basically our ith value. Now we know that this is going to be a dynamic programming solution. Also, for any DP solution, we need two things. We need a base case. So base case is going to be quite straightforward. It would be as if the given S is not present, or if the given T is not present, what is going to be the value? We know that if, let's say, that T is not going to be present, which means there is only way for us to generate T from the given S is not to include any characters, because that is also a subsequence of given S. So all of these numbers would only mean value number 1. So we can just mark them as 1, because if the character in S is present but subsequent T is not present, we can only make one subsequence out of it. Let's understand vice versa. If the given S is equal to null, but we still have some value present inside the given T, which means we would never be able to generate t based on the given s because the given s is empty. So because that is the case, then all of this results are going to be 0 because we are not able to generate t, or we are not there does not exist any subsequence that would be able to form t from the given s. Okay, now we know that what needs to be the recurrence relation. So recurrence relation is going to be quite straightforward. For any particular ith and jth value we are trying to calculate, we would see that if they match or not. If they basically match, we will have to do the sum of both the subsequence, which means we would need to consider that what does the diagonal value for any particular character is. So that is going to be, let's say for I and j, if they match, then the diagonal would be I minus 1 and j minus 1 plus what the previous subsequence has been with respect to s, and that would be the value I minus 1 and the current jth value. We'll have to do the sum of both of these two characters. So let's say that for an example, we notice that this a matches this particular a. So because this cell has a match, then we'll need to combine the subsequence we are able to generate over here plus the subsequence that we have been able to generate over here, because we can take both the paths from here. And notice that only the values of I differ, j would remain constant because we are trying to build t from the given s. Now I know it sounds confusing, but we'll understand it when we move to building our matrix. Now the second scenario is that if they do not match, then simply that does not add any value for us to build a subsequence. Let's say over here this a and this b do not match. So because they do not match, they are going to have the same number of distinct subsequence value that we calculated even for the previous result of I, that is going to be the cell above it. So we'll just replicate that value. So if they do not match, basically we will just take whatever the value of I minus 1 and j was as it is, and we will store that in the result. So now based on this two recurrence relation, let's see that what does our distinct subsequence that we are able to find. We notice that there is a match over here, r and r, they do match. So because they do match, we are going to take the sum of the diagonal value and the top value. Now notice diagonal is also going to be 0 for the first value, so we'll just mark it as 0, and sum of this two is going to be 1, so we'll mark it as 1. Same way for this r and a do not match. Because they do not match, we are going to carry forward the value from the top, so this would become 0. Same way r and b do not match, so this would become 0, r and b do not match, so on and so forth. So all of this are going to be 0. Okay, now a and r, once again they do not match, so we will take the value from the top. Now over here in this case, a and a actually match. So for this cell, because they match, we are going to do the sum of this character plus sum of this character. So let's just mark these value as 1 as well. Once again, a and b do not match, so this is going to be value from top, and so on and so forth. We will just mark all of these values as 0. Now for b and r, they do not match. So because they do not match, value from the top 1. B and a do not match, so once again value from the top as 1. B and B do match, so because they do match, we are going to do sum of these two values, so the answer is going to be 1. Okay, once again B and B once again match, so sum of these two are going to be 0, and once again B and B do match, so sum of these two are still going to be once again B and I do not match, so value from the top, and then B and T do not match, so value from the top. Now b, once again, so this is going to be value 1 1 so far, but now this, notice that this b also matches this b, so in this case we are going to do sum, so this would become value 2. Now once again this b also matches this b, so once again the sum is going to be value number 1, and now so on and so forth. These are going to be 0 0 as it is. Now for this third b, once again this is going to be 1, this is going to be 1. There is a match with this b, so because there is a match, I'm going to do sum of previous two elements, so this is going to be 3. Once again for the subsequent b, once again there is the sum, so this is going to be 3. So I'll add those values, and now this value is I, so they do not match, so value from the top is 0, and once again t do not match, so value from the top 0. Okay, now I'll change colors again, so better visibility. For I, basically all of these values do not match. So up until that point we can just carry whatever value we had from the top, but now this I matches this I, so we are going to do sum of these two values, so total is going to be 3. Once again this t do not match this I, so once again the total is going to be 0. And lastly for this t, last time we are changing the colors, and basically the value is going to be same that we have been able to identify all up to this, but this last t matches this last t, so basically the sum is going to be these two and the answer is going to be 3, and this is what we need to return as the answer. So basically you understand that how using dynamic programming we were able to shrink our solution from 2 to the power of n to basically time complexity of big O of m multiplied by n, where m is the length of s and n is the length of t. So which is a very good time and space complexity. We cannot go any more optimal than this. Now in terms of space complexity, because we are using an extra matrix, this is also going to be big O of m multiplied by n. That is a reasonable cost to pay. So now let's understand the coding solution for this. The coding solution is going to be quite straightforward. First, we are going to define two variables m and n to take care of the length of the given subsequent s and t strings. Then we are going to initialize a 2D dynamic programming array, and basically we are taking it as m plus 1 and n plus 1. This is to take care of the base case. Okay, after that we will initialize for basically when the given I and I is equal to 1 and j is equal to basically 0. So for the first column, all of those values are going to be 1 and all the jth column is going to be 0. We haven't mentioned it over here, but that would be like an intuitive thought that we can understand. Now we will start filling in the dynamic programming array. We will check that for the given dynamic programming array, if the characters match, then we are taking in the value from the diagonal and the value from the top and summing it up. That is going to be our subsequences. If they do not match, we'll just directly inherit the value from the top of the DP matrix that we have calculated so far. In the end, we will simply return the result or the very last cell in the DP matrix. Coding is not that much, but concept is quite important. Let's try to run this code. Okay, seems like our solution is working beautifully. Let's submit this code. And our code beats nearly 65% of all the other solutions, which is pretty awesome. In terms of space complexity, we could have done things slightly better, but anyways, this is also a reasonably good space complexity. Once again, the coding solution is present in our GitHub repository, so feel free to go and check it out from there. Thank you. The LeetCode problem we are going to solve now is called edit distance. We can see that this one is a LeetCode medium problem and also extremely well-liked problem on LeetCode. Basically, we are given two strings, word1 and word2, and we need to return the minimum number of operations that we need to do in order to convert word1 into word2 completely. Now we have three operations that we are allowed to do. We can insert a character, delete a character, or replace a character at any single moment, and we can come up with the solution. So let's try to understand some of the examples on how long will it take. So let's say that if the given word1 is horse and word2 is Ross. In this case, we'll need to do three operations basically to convert this word1 into word2. First, we will convert this H into R. So now we are left with two words, basically RORSE and then ROS. Then we will keep O as it is and R as it is. Now we can delete this R. So notice that now we have the two words as ROSE and ROS, and then lastly we can also delete this E. So basically we have both the words same. So notice we did three operations. First one was the replace operation between these two values. Then we simply go ahead and deleted this R and then deleted this E, and that's all the problem. Same way, if we are given three words like A, B, C and XYZ, in this case, the only thing we can do is we can replace each of the character one by one. So in this case, we also need to complete or take three operations to come up with this solution. Let's say if we are given two words that are exactly same. So in this case, we don't need to do any operation and we can simply return 0 as the answer. So basically, the idea is that we have the ability to either insert, delete or replace a character, but we'll have to convert word1 to word 2 basically. So now let's try to understand that what would be the brute force approach to solve this problem. So in this case, as a brute force, at every single character we have the 3 probabilities that we can choose for, and we can replace the character with whatever character we have over here. We can delete this character, and we can create an or we can insert a new character. So we can take each of this subsequent path, and then over there we will also have 3 more possibilities, and we would continue to keep on going down each of the path until we find word 2, and we will find all the possibilities of generating word 2, and whichever has the smallest distance we will pick that. Now notice that this is a very expensive brute force solution. Why? Because at every single node we have possibilities to go down to 3 other nodes, and even for those 3 nodes we have subsequent more possibilities. So basically we are running into issues of exponential time complexity, and that would directly be dependent on the total number of words present for word and word 2, which is very expensive. So we'll have to find a smarter and clever way to come up with the solution. Now logically, the only thing that makes sense in this case would be that because we are dealing with word 1 and word 2, and we are dealing with all the values that we currently have. Now notice that whatever the result that we have computed so far would impact on the subsequent result we are trying to generate. I'll repeat what I just said. Basically, currently if we have to generate like a, b and a, x and z from this given a, b, then what possibilities we have? Like we know that first character is a, so we can keep it as it is. Now we are dealing with generating this b with this remaining x and z, and for that what we can do, so with the b we will have basically a character, so we can just replace it with x, and then we can insert z over here, so we can generate an answer like this. But the thing is, notice that we don't know subsequently in word if this value was to a b y z. If it was something like this, then we would have our choices differ. If we had some other values where we are trying to come up with a solution where let's say that this is a b z, and the next value we are trying to build is a x b y z. So even in this case, every single moment we are trying to make the decision, we will have to compute that what was done for the previous values and take that into consideration. And I am giving all of this explanation just to explain that we will be using the most beautiful approach to solve this problem, that is using dynamic programming, where we will compute every single possibilities. So we'll compute that if we have to generate this word and the only word given is currently a, what would be the answer? A b, then what would be the answer? A b z, then what would be the answer? And so on and so forth. If we try out every single permutation combination and have a 2D matrix to keep track of all of these values, then we'll be able to solve this problem very efficiently. Now what are the possibilities we have at any given location? Remember, we can do 3 operations. We can do an insert operation, we can do a delete operation, we can do a replace operation. And for each of the 3 operation, if we only do this operation if the current characters that we are dealing with for the word 1 and word 2 do not match. So let's say if they do not match, we need to do these 3 operations, but we are only going to be selective, and we will look at the previously computed results from our dynamic programming array. And for that we would be able to determine that if we do insert, if we do delete, or if we do replace, what is going to be the cheapest operation. And we will do +1 because we are adding one more operation, and then compute the result. Now let's try to understand this with an example, and it would make much more sense on what I'm talking about. We are going to take into the consideration for the same input that we were originally dealing with, where word 1 is horse and word 2 is Ross. Now notice that I have created one additional row and additional column on the each side, and that is to take care of the scenario of what if word 1 is completely empty and what if word 2 is completely empty. And based on that we will build our solution, because remember, for dynamic programming we need 2 things. We need a base case and we need a recurrence relation. So base case is what if the word is completely empty, then we know that we will have to only insert the character and build the solution. and recurrence relation is the three subsequent neighboring cells that we have already computed for any particular cell that we are trying to compute. So let's see a scenario like this, where presumably word 1 currently is null, and we know that, let's say that given word 1 is null, and for the word 2 that value we are given is also null, then we basically do zero operations, because we can't do anything to, because they both are exactly same. Now if word 1 is still null, that is what this row defines, but word 2 contains the value only r. Now if word 1 is null and word 2 is r, if we want to generate r from word 1, what will we do? Basically we would insert a character, so we would do one operation, insert operation, where we are inserting a value, and that is what we are doing over here. So in order to generate only r subsequent with the given current empty word 1, we would need to do it with one operation. Same way, if we have to generate ro and this word 1 is null, we basically insert two characters, so we are going to do two operations. Now notice in this case we don't need it to compute for this full value, because we already know that in order to generate r we only needed to do one operation. If we have to generate o, we know for a fact that for to generate r there is only one operation needed. So for ro we only need to consider the maximum number of operation needed to generate r plus 1, because we are inserting a new character, and that is supposed to be 2. Same way for ros, we are not going to compute the full thing, but we know for in order to generate ro it takes two operations, and then if we have to add s to it, it adds one more operation, so this is going to be 3. Same way, let's imagine that for this particular first column, if the given word 2 is, let's say, null, and the given word 1 is, let's say, all of this horse, horse, then what we would do in order to generate this value? Well, if it's going to be null, we can add it as 0 because both values are same. But if this word, same way, if this word 2 is equal to, let's say, null and word 1 is currently h, then basically we will have to delete h, because we are trying to build word 2 from word 1. So in that case, we will have to do one operation. Same way, if we have to basically given word 1 as ho and word 2 as null, once again we will have to delete h and delete o. But we don't need to calculate how much time it takes in order to do both of this. We already know that it takes one operation to delete h. Same way it's going to take 1 plus 1 operation to delete ho. So this is going to be 2. Same way this is going to be 3, 4 and 5 subsequently. Now notice that at every single character that we are trying to build, we basically have three possibilities. Let's say that currently word 1 we have is, so for this case this is going to contain value h, and word 2 we have is only going to contain value r. Now in this case, for both basically h and r, if we want to generate this, what are the options we have? For word 1 we can either replace, delete or insert a character. And if we were to replace a character, basically we simply take whatever the previous value we had over here and we just replace it. We do the replace operation. That is option number 1. Second option is, if we have to delete the current character, if we have to basically, if we are trying to delete this h, then this is the scenario where h does not exist, only r exists. So we take whatever the value we have over here and do plus 1 over here, because we did a delete operation. So that would be the subsequent value over here. Or if we have to insert a character, basically in that case r does not exist. So in this case, once again we take whatever the value we had over here and do plus 1. So now notice that in order to build this cell, we have three corresponding relations with each of these three subsequent cells. We can do whatever operation we want to, but basically in each of the cases, our number of operations we are doing relies on the subsequent neighboring cells. So if we do plus 1 amongst these three, then basically we can generate that value. But the thing is that plus 1, we are going to pick the minimum cost it takes to build this cell amongst these three. So for these three values, we will do plus 1 and we will see that what is going to be the minimum value, and whichever the minimum value is, we are going to insert that value over here. So I hope that logic is understood to you why we are picking this value. But basically in this case, notice that if we do +1 over here, the value becomes 2. This also value becomes 2. But in this case, this would turn value to be 1. So we are going to keep value as 1. Now notice same way, this character is H, this character is O. Once again, they do not match. And because they do not match, we have the option to do all of these three operations. They depend on the neighboring cells. The neighboring cells we already know. So once again, we will do the minimum amongst these three. So the total is going to be 2, and basically +1 with the minimum. Same way for this one, the minimum +1. So the total is going to be 3. So what does this 3 defines? This defines that if we have given word 1 as H and word 2 as basically ROS, in order to do that, if we have to do that, it takes 3 operations to build that this word ROS from this word 1 H. Same way we are going to be doing for every single possibility and combination. Once again, now notice O and R do not match. So we will do the minimum operation. So minimum is going to be 2. Once again, now in this case, because this O and because this O match for this particular cell, if there is a match, we don't need to do anything, and we can just take previous subsequent diagonal value we had, where basically we are not doing anything, we are just keeping the value as it is. So this is going to be 1. Same way, if we have to do this now, because the values do not match, so it's going to be 1 plus 1, so this is going to be 2. Same way for this R and R, because these values match, we will take the diagonal value 2. Once again over here, the sum is going to be 2, and once again for here, the sum is going to be 2, and that is this diagonal sum. Okay, same way for this S and R, the values do not match, so this will become 3. S and O, once again values do not match, so this would become 3. Now S and S do match, so because they match, we will take the diagonal value and keep 2 as it is. Now same way for this particular cell, the value is going to be 4. For this particular cell, the value is going to be once again 4, and for this particular cell, the value is going to be 3. And whatever the last value we have on this 2D array, that would basically define that if the word 1 was the full value, so HORSE, and if the word 2 was the full value ROS, then it would take 3 operations to build word 2 from word 1. And we can return 3 as the answer. So this is going to be the whole solution. Now if we see time and space complexity, in this case the time complexity is going to be big O of m multiplied by n, because we will have to iterate over every single value that is currently present. And in terms of space complexity, well, because we are using an additional 2D array, this is also going to be big O of n multiplied by n. But overall, this is much better than our brute force approach, and this is a beautiful example on how dynamic programming can be powerful for us to solve any problem, especially like the recurrence relation problems. Okay, so let's try to see the coding solution for this now. So the coding solution is quite straightforward. Basically, we are going to define two variables m and n to capture the length of word 1 and word 2. Then we are going to initialize our 2D dynamic programming array that is going to be of size m plus 1 and m plus 1, where we will need to create a scenario where m and n are defined as 0, and then we will find values for those as well. Then we will initialize our value for basically each of the words. So like for word 1 and word 2, if they were given alone, and then we will try to fill in the values for both word 1 and word 2 in subsequent first row and first column. After doing that, we will fill in the rest of the dynamic programming array, where we are iterating over every single cell that are not filled, where we are checking that if the given subsequent word 1 and word 2 are same, then we will just choose whatever the previous value was from the diagonal value. If that is not the case, we will check all the 3 adjacent neighboring cells plus 1 and try to find the minimum value for each one of them. So basically we will try to replicate the scenario on if we have to delete a character, replace a character, or insert a character, and whatever is going to be the least cost, we would put that in the current I and jth value. In the end, we simply return the result or the very last element inside our dynamic programming array, and that should provide us the distance it takes to generate word 1 from word 2 or vice versa. So let's try to run this code. Okay, seems like our solution is working beautifully. Let's submit this. And our code works well and beats most of the other solutions in terms of time complexity, so which is pretty good. And once again, the coding solution would be present on our GitHub repository, so feel free to go and check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So the LeetCode problem we are going to solve now has to be one of the most difficult problems that I have solved so far. It's called burst balloons. We can see that this one is a LeetCode hard problem and very justifiably also a very well-liked problem. So basically we are given n balloons that are under indexed from 0 to n minus 1. So they can be placed in an array. Now for each balloon is painted with a number on it. That number is represented in an array called nums, and we are being asked to burst all of these balloons. Now the number that is currently written on that particular balloon represents like some sort of coin values. But the thing is, when we burst a balloon, we actually get coins in by multiplying its neighboring cells with that particular number. And then neighbors basically change because we already burst a balloon from in between, and then we keep on repeating the same process. Our aim is to make sure that we can receive maximum number of coins by bursting as many balloons wisely. So this is the key phrase. Now we are being told that let's say that we run into an issue where there is a neighboring cell that is at the edge of the given nums array. Then basically just imagine that there is one neighboring cell with one painted on it, so that we don't run into an issue of array being out of bounds. So let's say that we are given an example of two balloons. The values are 1 and 5. Now notice for these two balloons, basically we can treat them as following, where the middle two balloons are still going to be values 1 and 5 as represented over here, but it is going to have two neighboring balloons that are valued 1 and 1 that we are not going to burst. We will only consider these two balloons, but they are there for us to our support. Now what is the maximum value we can achieve? Now let's say that we decide to pop balloon number 5. If we pop balloon number 5, basically we get value such as multiplication of its neighboring values. So it would be 1 multiplied by 5 multiplied by 1 because of these three values. Now notice this would yield us the result 5. Plus we still have one more balloon because we already popped balloon number 5. We would have one more balloon 1 that needs to be popped, and now its neighboring cells would become 1 and 1 and with 1. So this would become 1 and this would total out to 6. But the thing is, this is not a wise approach. Why? Because in the same example, if we notice that instead of bursting balloon number 5 at the beginning, if we decide to burst balloon number 1 in the beginning instead, then basically our values would be, so we burst this balloon number 1, so that would yield us the value of 5 multiplied by 1 multiplied by 1, so total would be 5. Plus now this balloon no longer exists, but we still have this 5 left, and its neighboring balloons are 1 and 1, so this is also going to be 5 plus 5, so total is going to be 10, so we need to return 10 in the answer. Let's say same way we are given the values 3, 1, 5, 8. Now in once again for this example as well, we can choose wisely, and the most logical way to pop balloons would be that if we decide to pop balloon number 1, we would get values 3 multiplied by 1 multiplied by 5, and the remaining balloon would be 3, 5 and 8. Okay, so let's sum up this value. So this is going to be 15. So 15 plus these three values. Now once again in this case, and remember, imagine that there are going to be two neighboring ones present at all the times. Okay, now once again we would decide to pop balloon number 5. If we do that, we will be doing 3 multiplied by 5 multiplied by 8, and the remaining balloon is going to be value 1, 3, 8 and 1. Okay, now once again in this case, this is going to be 15 plus this is going to be 120 plus this is, now in this case the ideal thing would be to pop balloon number 3. If we pop balloon number 3, then we get value 1 multiplied by 3 multiplied by 8, so 24, and then we would no longer have 3 existing, so last value would be 8 remaining with 2 adjacent ones, and that would be plus 8. And if we do total of all of these values, the maximum number we can achieve is going to be 167, and this is what we need to return in the answer. So I hope this long explanation makes sense that what is being asked for us to solve this problem. Now, very first approach comes to our mind is a typical brute force approach, that if we are given n number of inputs, let's say values 1, 2, 3, 4, right? Why don't at every given position we have the 3 option of choosing whether to pop that balloon or not to pop that balloon. So if we decide to pop balloon number 1, then we are going to be left with the value that we received from balloon number 1. So that is going, let's say that the value is x, plus we have the possibility of dealing with the remaining 2, 3 and 4 values. And once again in this path, once again we will have the option to take this x, plus amongst 2, 3 and 4 we can pick a number. So let's say we decide to pick balloon number 2, so that value becomes y, and then once again we are going to be left with values 3 and 4, and once again we would be making a decision. Same way for every single value we can make a decision based on the sequence of balloon we pop, and same way we are going to have different choices, and subsequently it will grow over period to basically all of the different permutations and combination of choices we can make. So that is going to be a very huge decision tree that we can make. Now in this case the answer is going to be 2 to the power of n, where n is the total number of characters present, because at every single instance we are deciding whether to include that or not to include that. So that's a very expensive time complexity. That doesn't work. Let's try to become greedy in our approach. So greedy approach works something like that. Basically we can take an input and we will try to pick the smallest value. So let's say that we saw in the example of 3158 that we would pick the 1 first because it was the smallest value, so it would not bring any like long-term benefits to us if we just keep it around. So why don't we burst balloons with the smallest value possible? So in that case, if we decided to burst this balloon number 1, let's say being greedy, okay, so we get the value as 15, okay, plus now we are left with three values, 3, 5 and 8. Once again logically we would be bursting balloon number 3. So if we do that, once again we would be generating the value as 3 multiplied by 5 multiplied by 1. So this would become 15. Plus same way we would be left with value 5 and 8. If we do that, we will be bursting value number 5, so the value would be 40, and plus lastly there would be value number 8, so this would become 8. So if we do sum of all of this, it's going to be 30 plus 40, 70 plus 8, 78. So greedy approach also doesn't work, because we know that if we can do it wisely, we can solve this problem and gain 167 coins amongst this input. So this is also a second choice that would not work. So now the solution would become pretty obvious to you. So in this case, we are actually going to be using the most powerful and beautiful concept of the entire computer science, and that is called dynamic programming. Now, how we are going to be using dynamic programming is that, remember in the brute force approach, basically when we had 4 inputs, we would take certain paths. So we would pick what if we burst balloon number A, and then we are left with whatever the value we generated from balloon number A plus whatever value we can generate from B, C, D. Same way, once again we have two choices of A plus B plus whatever value we generated from CD. Same way over here we could have decided to burst balloon number balloon number B, and then once again generate the value that would be gained from A, C and D. And once again we could have burst balloon number A, and then once again the values would have been C and D. Now notice that both in this case we are left with value A plus B plus CD and A plus B plus A plus CD, basically in just reverse sequence. So we need to keep track that at every given moment, whatever the balloon we burst, depending on whatever the range, what is the value we are generating. Now important phrase over here is going to be range, that we need to know that between every single combination of values, what maximum coins that we are able to generate. Now in this case we'll need to do we'll require a 2 by 2 matrix. Now notice in 2 by 2 matrix I'm using the same example we used 3158, but we have added one at each of the end. They are just denoted by different color, and they are to make sure that we have a neighboring cells present, but we are always going to be iterating amongst these 4 values. Okay, so when I talk about keep track of the values of bursting balloons, that would be amongst this set of values. Now one more thing is, let's say that I only give you value number 3 and ask you that what is the maximum balloon I can generate. You must be saying that hey, it's pretty straightforward. We would do like 1 multiplied by 3 multiplied by 1, and total is going to be 3 for sure. Now let's say that I give you value 3 and 5. Now what is the maximum possibility? Well, we have two possibilities. One possibility is that we actually take 3 first, so basically that would become 15 plus 5, or we could have taken 5 first and that would have become 15 plus 3. So greater total is 20. So we can say for a fact that if we are dealing with only two balloons with value 3 and 5, maximum value we can generate is going to be 20. Now in this case, let's say that we add one more possibility, that 3, 5 and 8. Now for this fact, we can say for with certainty that with this 8, the maximum value amongst this 3 and 5 we can generate is going to be 20. So we can leverage that fact and we can use it to our advantage. In this case, there is also possibility that instead of taking 8 at last, we can take 8 somewhere in middle. So we'll need to keep track that what would be the value being generated with the value 3 and 8, and we'll have to keep track of all of these different permutations and combinations of values. So that's why we need a 2D matrix and a sequence of range that we are going to be determining. Now in this case, let's just try to do it one by one, starting with the smallest range possible, and that is going to be of interval 1. So let's say if we are only dealing with interval 1 ranges, what are the different values that we are trying to compute for? First value would be 1 1, second value would be 2 2, third value would be 3 3, and fourth value would be 4 4. Okay, now for 1 1 we are thinking that if for 1 1, if this were to last value that we are going to be bursting, what is going to be the result? So basically because range is 1, remember, so we are only incrementing the neighboring cell by 1. So in this case 3 multiplied by 1 multiplied by 1, so the maximum value we can generate is going to be 3, so we will mark it over here. Same way in this case, let's say that for some reason we decide that instead for 2 2, so for 2 2, this is the value that we are talking about. What is going to be the maximum value we can generate? The neighboring cell, so remember that we have decided that we have burst all the neighbors in that range, but because this range does not have any value other than that, these are going to be the neighbors. So this is going to be 3 multiplied by 1 multiplied by 3, so that is going to be 15. So we can mark 15 as it is. Same way for value number 5, once again there are no neighbors, so 1 multiplied by 5 multiplied by 8, so that is going to be 40. And same way for value number 8, once again 5 multiplied by 8 multiplied by 1, so that is going to be 40. So we can mark all of these values as it is. That's cool. Now let's up the ante and let's update our total number of range that we are currently trying to build out. So first range would be of size 2. Now comes the interesting part. Now what are the ranges we can generate? So range would be 1 to 2, second range would be 2 to 3, and third range would be 3 to 4. Now let's talk about just range 1 to 2 for a moment. Now in the range 1 to 2, we are talking about basically these two values 3 and 1. Okay, now 3 and 1 amongst the grand scheme of total 3 1 5 and 8 amongst these four values. So now notice that we have the two choices. First choice is that 3 would be the balloon that we would pop last, or 1 would be the balloon that we would pop last. What if we decide that 3 would be the balloon that we are going to be bursting last? Then in that case, what is going to be the neighbor of 3 that we would multiply 3 with? Because we have already popped 1, so that would be value number 5. So that would be 1 multiplied by 3 multiplied by 5. This 1 we got from the neighboring 1, that is this over here, and 5 we got, that is the end of the range, that is the over here. Plus we must have received whatever compensation we got by bursting just balloon number 1, and that is going to be dp of basically 2 and 2. So this is that is this value. So the maximum value we can generate is 15. So in this case it's going to be 15 plus 15, so maximum value we can get is 20 for range 1 to 2 by bursting balloon number 3 last. So one possible value is 20, so let's just mark 20 as it is right now. Let's just come back once again, do our calculation. Now for the same scenario, we are considering that what if we decide to burst balloon number 1 last. So okay, so 3 and 1, we are bursting this balloon number 1 last, which means we have already burst this balloon. So what is going to be the neighboring cell? 1 and 1 and 5. Now what is going to be the value? So bursting balloon number 3 would give us maximum value of 3. So let's mark 3 plus bursting this balloon number 1 now would be 5 multiplied by 1 multiplied by 1. So that is going to be 8. So 5 and 8. Yeah, so basically 5 plus 3. So total is going to be 8. So in this case, because the higher value is going to be the maximum value that we can generate, that would be amongst this. Oh sorry, this value was supposed to be 30 not 20, because remember we did 15 plus 15. Okay, so now the maximum coins that we can generate at between range 1 to 2 would be amongst the maximum between 30 and 8, and we know that maximum value is going to be 30, so we will just mark 30 over here. This defines that this is the maximum number of coins we can generate for this particular range. Now let's just come to the next range in our set of sequence, and now I'll just start moving quickly because I don't want to spend this much time for each of the things. Okay, next range would be value 2 to 3. So now 2 to 3, the values are going to be 1 and 5. Okay, now for this one, what if we decide to burst balloon number 1 first? Sorry, balloon number 1 last. If we burst balloon number 1 last, basically it's going to be value number 3 multiplied by 1 multiplied by 8. So that is going to be 3 multiplied by 1 multiplied by 8. So that would be 24 plus whatever the value we get from DP at value 5 and 5. Sorry, value 3 and 3. So that is value 3 and 3 is going to be 40. So the sum is going to be 64. Okay, now what if we decide to burst balloon number 5 at last? So in that case, well, it's going to be 5 multiplied by 8 multiplied by once again 3. So plus whatever value we get by bursting this balloon, so that is going to be 15. So the total is going to be 135. So logically it makes sense that at range 2 to 3, the maximum value we are able to generate would be value 135. So we will just mark 135 as it is. Okay, now the last range we have is going to be range 3 to 4. Now once again, at the values range 3 to 4, what are the basically two balloons that we are able to pop? The values are 5 and 8. So we can either pop value number 5 in the last. If we decide to pop value number 5 in the last, basically we would be gaining the value 45. If we decide to burst value number 8 in the last, we would be gaining the value 48. Now why did we get 48? I'll just quickly explain. Basically we are doing 1 multiplied by 8 multiplied by 1. So this is 1 and this is the second one, because remember we are talking about this range, and plus whatever value we get by bursting this balloon, so that would be 40. So basically 8 plus 40, so that sums up to 48. Okay, so maximum value is going to be 48 between the range 3 to 4. So we'll just mark it over here as 48. Okay, now same way, now we took care of all the intervals of size 2. What about all the intervals of size 3? So once again, for this one, the complication now becomes even more critical, because now the first range we are talking about would be 1 to 3. So we have the 3 candidates. 1 2 3 would be 1 2 and 3. So now we have 3 candidates, basically 3 1 and 5, to solve this answer. And for each of the one, so we have, what if we decide to go each of the one in the end? So I'll just do calculation for one of the values, for value number 3. So basically this would, what if we decide to go with this value at last? Now remember, 3 would be multiplied by 8 and it would be multiplied by 1. So it would be 1 multiplied by 3 multiplied by 8, because we took care of the entire range. Okay, plus now because this is the first value in the range that we are talking about, we would also need to do the dynamic programming of range between this value 2 and 3. So 2 and 3 we already have the answer, and that is 135. So this would become 135 plus 24. So the total is going to be 159. Okay, now what if we decide to burst balloon number 1 in the end? Once again, that value is going to be 51. And what if we decide to burst balloon number 5 in the end? The value is going to be 70. So 159 is the obvious choice. So between the ranges 1 to 3, the maximum value we can generate is going to be 159. So we'll just mark 159 as it is. Same way for the range 2 to 4, the maximum value that we are able to generate would be once again value 159 as well by the same logic. And so we'll just from 2 to 4 the value would be 159 as well, so we'll just mark it as it is over here. And now comes our final range, that is of range size 4. And for the range size 4, the only possibility in this case we are going to have would be basically just one value. So the range would be from 1 to 4. We have the possibility of bursting 3, 1, 5 and 8, all 4 balloons at the last. What if we decide to burst balloon number 3 last? If we decide to burst balloon number 3 last, basically the coins we would be generating would be 3 plus whatever the range we can get. So basically 2, 3 and 4. So dp of 2 to 4. So dp of 2 to 4 we already know that value is 159 and plus value number 3. So that is going to become value 162. Okay. Now let's do the calculation for value number 1. So basically once again for value number 1 the total would be 159 plus the total sum would be for value number 1 the total would be only 52. And why it would be 52? Because remember this value the range would be so for this one value number 1 the range would be basically we would do multiplication. So that is 1 multiplied by 1 multiplied by 1, so that would be 1 plus, remember we have two ranges. First range is dp of 1 to 2, so dp of 1 to 2, and second range would be dp of 2 to 4, and dp of 3 to 4 because we already took care of dp of 2. So this dp of 1 to 2 is going to be 30 plus dp of 3 to 4 is going to be 48. So 48 plus 30 plus 1, so whatever the value that would come up to. So on and so forth. If we keep on doing, basically the maximum value we are going to be getting would be for value number 8, because remember for value number 8 the multiplication would have been 8. Okay, let me just clean this up a bit, and I know that this video is getting super longer, but it is what it is. Okay, for value number 8 basically the multiplication is going to be 1 multiplied by 8 multiplied by 1 by ignoring all of these values, plus dp of range 1 to 3. So range 1 to 3 the value is 159. So 159 plus 8, so this would become 167. That we would store over here, and this is what we are looking for, that what is the maximum value we can generate between range 1 to 4. That would be 167, so we can return that as the answer. I know this was a super long video, perhaps the longest one that I did for dynamic programming, but it's an important one. Now let's analyze the time complexity. We'll have to iterate over n by n matrix basically, so that would become big of n square work, and for each of the ranges we will have to do it, so that would be multiplied by n, so that total time complexity would be big of n cube. There is no other way to do it faster than this, even with using the dynamic programming. And space complexity is going to be big O of n square, so which is a reasonably good time complexity given how complex this problem is. So now let's quickly see the coding solution for this one. Now the coding solution is slightly straightforward. So basically we are given total length n. Based on that we are going to be generating our extended array that is going to be of size n plus 2, and we are going to be adding the last values as 1, that is to take care of the neighbors. Then we are going to be iterating over the original nums array and add values to our extended nums array. That would be for simplicity for us to update all of the values. Now we will generate our dynamic programming array, that is, notice that the values is n plus 2 and n plus 2, that is to take care of the two neighboring cells. Now we'll start filling in our dynamic programming table and iterating over all the values. On top of it, we'll have to define a range for every single different position, and that is what this right length defines, that this is the range we are talking about. And at every given range, for every single range that is possible, we will calculate that what is the maximum coin we can achieve on that particular value. That would be by doing the multiplication of extended nums left minus 1 multiplied by extended nums of that particular value multiplied by extended nums right plus 1. Notice that we are taking the values that would be out of the range for every single value, and we are updating the value plus by doing the coins of dynamically programmed ranges that we have already found so far. So for any ith range, the value would be dp of left to I minus 1 plus dp of I plus 1 to the right, and we already have the values being calculated by bursting that particular balloon. And the range value at any particular location would be the maximum value that we currently have, or the new maximum value that we just found. Whatever is greater, we'll just store it in the result. So these are the 3 for loops that would take care of all the entire logic that we just explained, and then we can simply return the value for the range 1 to n. That is the range that we are given in the input. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats nearly 80%, like 74% of all the other solutions, which is pretty awesome. I would be posting this in the comments and in our GitHub repository, so feel free to go and check it out from there. Thank you. Hello friends, I'm a cloud solutions architect at Microsoft, and my aim is to create free resources that will empower every single engineer in this world so that they can do better with their technical interviews. Now continuing in that direction, today we are going to solve a very important problem called regular expression matching. So let's get started with the problem. So if we see some of the popular companies who have already asked this question, there are companies like Microsoft, Amazon, Facebook, Google, Bloomberg, Adobe, Apple, Uber, Snapchat, Tesla, Goldman Sachs, and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also a very well-liked problem. Basically, we are given two input strings. One is string S and the other one is pattern P. Now we need to implement a regular expression matching function that can support a dot character and a star character inside this pattern P as well. Now we are given the definition that what does a dot and a star represent. Basically, a dot can represent that it can match any single character, and the star represents that it can match 0 or more preceding elements. Now first let's try to understand both of these with examples. So suppose we are given a pattern P that looks like A, B and dot. Now dot by definition it can support any single character. Now inside our given string S, suppose we are given the values to be A, B, C. Now can we conclude these two to be matching strings? The answer is yes. Why? Because for this particular dot we can consider it to be C because it can match any character. Suppose if we are given an S that looks like A, B, X, is it true? Yes, this is also matching with this pattern P because for this time for this dot we are actually considering it to be X. But if we are given S that looks like A, X, is this matching? No. Why? Because the second character over here, this is A. Meanwhile, the second character inside our pattern is B. These two are not matching, so this is not a matching sequence. So basically, this is what does a dot represents. Now let's try to see one example of what does a star represent. So basically, suppose we are given a pattern P that looks like this, where the values are again A, B, star. Now what does the star is saying by definition? The star is saying that it can match 0 or more preceding elements. Now what is a preceding element of this X? The preceding element is B. So which means that now this particular pattern can match bunch of different other strings. So strings such as A, B, 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 B. Does this match this particular pattern? Yes. Why? Because if we see, okay, first character A is matching each other. Now for the second character B, we can have multiple B's over here because of this star value, because that is what is given in the definition. So based on the definition, we are now in this case considering the star to be all of these B's. Suppose we are given a string S that is only A. Is this matching with this pattern P? Yes, this is also matching. Why? Because this star can represent that we have 0 or more preceding elements. So in this case, we are considering that we have 0 B's in the pattern, which means that our given S is actually matching. And in this case, since both of these are matching, now let's try to take one more example. Suppose our given S is equal to like A, B, X. Is this matching? No, this is not matching. Why this is not matching? Because this AB portion, this is matching, that is good. But we do not have an X over here, and that is why this is not a match. Does this match? And pause the video for a second. Try to guess that whether this matches or not. Let me come up with the answer. The answer in this case is that this is actually a match. Believe it or not, this is a match. Why this is a match? Well, okay. First, F is matching. This is good up until this point. Now, because we have a star with dot, which means we can have n number of occurrences of dot. And we know by definition that dot can represent any single character. So in this case, what we are going to have is, we are actually going to have 7 different dots. And these 7 different dots, they are going to represent each character that is missing in the remaining string. And then eventually when we reach to the end, we are going to declare this as a match, and we will be able to return true in each of the cases. So I hope after so many examples, things would make sense and you would get the idea that what this problem is asking us to do. Basically, we need to return a Boolean answer, whether true or not, that whether any given 2 strings, do they match or not match. Okay, now before we come up with the solution, first let's see that what could be the different possibilities for our problem and what could be the different things we can do in the solution. Now I have drawn a table over here where I'm representing different like string values and pattern values, and we'll try to see that what happens in every single scenario and what are the actions we can take. Now I have noted that there could be like a C mentioned over here in this column file, and this means that it could be any character from A to Z, because in the string we can only strictly have A to Z characters. Meanwhile, for the pattern we could have definitely C, or we could also have a dot and a star. So that means different things, and if they are present, we might have to do things a little bit differently. So first let's see the first scenario. In the first scenario, basically both the values we are given is like a simple character. So for S and P, suppose we are given the values like A, B, C and X, Y, Z. This is pretty simple to match that whether the string matches the pattern or not. We simply need to judge character by character. In this case, we can simply see that whether they are matching or they are not matching. This is a very simple binary operation. Second option we can have is the most beautiful option, that whether we are given one character and we are given a dot value. This is also very straightforward. If there is a dot present, definitely it matches the character. We can simply return that there is a match for that particular character. Second scenario is that we could be given bunch of different characters, and we could be given like some characters at the beginning, and then we might be given like a dot and a star. In this possibility, basically what we need to check is that whether like a single character like this first character, and whether this first character, I mean this could this could represent like more characters. These could represent something like a and like a dot star, something like that, right? There could be like different matching things. I'm just noting down C. But this means that if like the before portion matches, everything at this position is definitely going to match. So in this case, if like the values before the dot and star matches, then everything is a match, right? If we take a look at this example, basically we are simply given dot and star. In this case, 100% there is going to be a match. Why? Because all the values that are present over here, we can take like 0, 1 or bunch of different dots, and all of these dots can represent all the characters that we have. Now comes the interesting part where we are dealing with a star. What could be different possibilities? So let me give you like one possibility. Suppose for this our string and P value, we are given the values like A, B, and over here we are given the values as A, B star. Question is this a match? Yes, this is a match. Why? Because this is the first value. This is a match in itself. And over here we only have one value of B. Now over here we have B star. So this B star could represent that we don't have any values, or we have one value of B, or we have two values of B, or we have infinite values of B all across like the board, whatever we want to choose. In this case, we are definitely going to choose one value of b, which means this is a match. So in this case, what are we considering? Value before the like preceding value of star. So value before preceding value of star. If that is a match, definitely we can find a match, right? There could be another possibility. We could be given a string, we could be given a p, we could be given a bunch of different values like a, b, x, y, z, a, b, x, y, z. So far everything is the match over here. And then over here we are given something like 2, 3, 4, 5 z's, right? And over here we are given like just a star value. In this case, how would you define that whether this is a match or not? Well, definitely this is a match, but the way you are going to define is that the values that this z and star that we are considering, like these values, before that we are checking that whether all the values that are present before that, are they a match? If all of these values are match, definitely we can create this to be a match. So again, we are considering like all the values before the preceding value of star. I know I'm using a lot of abbreviations, but you just have to be with me. I'm not going to write all of them. And if that is a match, we can consider this to be a match. There is also one more possibility where we actually do not need to consider this like preceding value at all. What could be a scenario? Suppose we are given string as is equal to like a, b, c, d, and over here we are given some p is equal to a, y star, and then b, c, d. In this scenario, this is definitely a match. Why? Because for this y star, we are considering this to be 0. If this is being considered as 0 values, which means that this is a match, and then all the other values, they are match. So we will find a potential match over here. So again, we are considering like if the value before the preceding star, if that is a match, then we can consider this to be a match. So now we are just like dealing with lot of possibilities where every single time for value inside the pattern, we will have to keep track of the value, like two value before that whether that is a match or not. And in order to calculate any single calculation, we are always checking that whether the values before us, are they matching or not. So this is a very good candidate for a dynamic programming solution. Why a dynamic programming solution? Because first scenario, we are definitely like using whatever the results we have calculated to check that whether the current result we are at, if that is a good or not. Second, already calculated results are going to give us the ability to decide that what do we do in the current position, because we are not only dealing with like simple characters, we are also dealing with like a dot, and we are also dealing with a star. So this is going to be really helpful. And we can use something like recursion to solve this problem, but that is going to complicate things. We are actually going to use recursion with DP, and that is going to make things much more easier. So let's try to take one example over here. And the question is, for a dynamic programming, we are not only going, because we are dealing with two different like string and pattern, it would be better to create a 2D matrix, and inside the 2D matrix, for every single like string and every single pattern, we will try to see that whether the characters match or not, and based on their true and false values, we would be able to calculate some interesting results. So let's see that in action with an example, and that would make things more clear. Okay, so currently we have created an example for a string and a pattern, and we need to check that whether they match or not. Now also for this pattern, I have created a 2 by 2 matrix where inside every single row represents the string value we have, and every single column represents a character inside the pattern we have, and we will try to see that whether there is a match or not. Now remember, for the first row and column, I have kept it as empty. Why? Because these we are going to use to create our base case. Now our base case is that currently for the string, the first character we have is empty character, and also for the pattern, the first character we have is empty character. Now, because these two are empty characters, definitely empty characters are going to match for sure. So in this case, this value is always going to be true. Now we will try to see that whether there is a match over here or not. So in this case, because this is an empty character and we have some character over here, there is not going to be a match. So definitely we would always be able to like have all these values as false. So currently we are at this first position. This value is f, this value is f. Both of them are characters, both are same. And when both are same, we will also have to check that all the values before that, if they are also match or not. So currently the only values before that were two empty strings, and that represents this diagonal corner. So because this diagonal corner was true and we have matching set of characters, we are going to take the value that is diagonally present and put it at this position for this 1 1 box. Again, I'm repeating myself that because these two characters are same. So first we check, okay, these two characters are same. Then we check its diagonal value, because what this diagonal value is going to do is it is going to check that whether all the values before these two values are they a match or not. And this will come in handy when we are at some position like this, because if over here we find this AA to be matching, which means this value is a true, but do we need to keep it as true? Because if this is false, which means if we are, say for an example, we have string to be FA and we have patent to be PA. So in this case, though these two match, but this is not a match. Why? Because this F and P does not match. So we can break out immediately. And that is what we need to keep track of every single time. And that is why this is a dynamic programming problem. So in this case, as explained, this is going to be true. Okay, now again let's start filling up this all of these files. And what we are going to do is, okay, this one is true. Now we will have to check that, okay, currently we have FA and the value we are comparing it against is F. Is this a match? No, this is not a match. So this is going to be false. Again, currently the value is FA star and the only value we have is F. Is this a match? Yes, this is a match. Why? Because for this A star, we can actually consider this to be an empty string or zero values of A. And if we do that, then we will have no values over here. So in this case, this F and this F is match. And why this happened? Because we had a star value over here and we were dealing with the star value. So now again the new theorem comes that whenever we are dealing with a star value, we will have to check the value before its preceding value. Again, whenever we are dealing with a star value, we will have to check the value before its preceding value. And if that is true, then we can directly mark true over here. So we check, okay, this was true. So definitely we are going to put true over here. Awesome. Now we are at this position number n. Now currently what is the scenario we are comparing? We are comparing the values of F, A star, N, and we are comparing it with F. So N and F, there is no match. So definitely we can mark false over here. Now we add a dot over here. Again, there is a no match. So we can mark false over here. And same way, this is also going to be false. Okay, now we are at this position. So now we actually have two values, FA. Now for this FA, if we only compare it with this value F, is this a match? No, this is not a match. So we can mark false over here. Okay, now after marking false over here, currently we add this positions. Okay, so FA, definitely there is a match. So because these AA matches, we will compare its diagonal value, and the diagonal value we get this result, and we will mark the value over here. So this is going to be true. Awesome. Now currently we are at this FA star. So FA star, is this a match with this FA? Again, now we have the star value. So we will have to check. First thing we will have to check is whether we can consider this to be just like an F and empty string, or we can consider this to be an FA, or we can consider this to be an FAA. I'm talking about this value, right? And if we see this FA is a perfect match. So now because we have a star value again over here, we are going to mark this as true. But this true, we are getting it from the value before. Because remember, in this case, you must be wondering that, hey, for this particular position, this value is actually empty. Then why are we marking this to be true? We are marking this to be true because this one is true. because we found a match of FA, and because this value is true, we will mark this as true. So let's do that. Awesome. Now currently the next value we have is like FAN, and this value we have is FA. So definitely there is no match. We will mark this as false, and all of, if we add dot, we will again mark this as false, and blah blah blah. Right? These are all the values going to be false. Now currently we are at the position of FAA. Let me clean this up a bit. So currently we have FAA over here, and currently we only have F over here, so definitely this is going to be false. Again, this FA is also going to be false. Now again we are at the critical juncture. We have a star value. Now because we have a star value, you must be wondering that what will be the possibility. Well, the possibility is, again, over here for this FA star, we can consider it to be like only F or FA or FAA. This case we are going to consider it to be FAA. Now you must be asking that, hey, previously when we were at this position, you mentioned that because this is true, we are marking this to be true. Then when we were at this position, you mentioned that though this was false, but because this was true, we were marking this to be true. Now we are at this position. This is also true. This is also false. This is also false. Then how come we are marking this as true? We are marking this as true because this value is true. Mind blown. Yes, this is like the most important point for this problem, that whenever there is a star present, we will have to check 3 different values. So whenever there is a star present, we were checking that whether the value before the preceding value, if that is true, we can mark this as true. If there is a star present, we will check that whether the value before this, if that is true, then also we can mark it true. And if there is a star present, we can check that whether the value above it, if that is true, then also we can mark it as true. Which means whenever we were at this position, if we don't want to get into all of these like calculations, all we need to do is that currently we are at this box, then we will have to check 3 different boxes. First box is the right, like before box. Second box is this one, like the box before box, and third box is a box above that box. So for this particular box, if either this or this, if any one of the value is true, we will need to mark that value over here. If all 3 are false, then only we will mark it as false. And why this happens? Because this was a star value and there could be bunch of different possibilities we can use over here. And this was the most difficult part of this problem. And congratulations, you understood it perfectly. And now because this was true, now currently we have this FAA, and now we have this like F. Now we are at the next value. So next value is FA star N, and this N is not a match, so this is going to be false, and then all the subsequent values are also going to be the false. Now this is a very easy problem to tackle, because now we are at this position N, so this is not a match, so this is going to be false, this is also going to be false, this is also going to be false. And now we are at this N and N, because both of these are characters, so there is a match. Because there is a match, we are going to consider it's like diagonal value, so diagonal value is true, so this is also going to be true. Now this is a dot value, and we only have values up until this point, so which means we are going to mark this one as false, and we are also going to mark this one as false. Now again we are at this value number G, so all of these are going to be false up until this point. Now there is a dot over here and there is a G over here, which means there is a match. So if there is a match, we are going to compare its diagonal value. The diagonal value is T, so that is true. So because this one is true, this is also going to be true, and the last value is going to be false, because we only have value up until G up till this point, and we have this M over here. Now the last value is, okay, this is going to be false, 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 and this is also going to be false. Now we are at this last position. This M is a match with this M, so because this is a match, we are going to take its diagonal value, and the diagonal value in this case is true, so we are going to take this value as true. Now our dynamic programming table is complete, and all we need to do is we need to check this diagonal file, and we need to check this last value. Because this last value was true, we can return true in this case, and this would be the answer we need to return. And that is the whole logic behind this problem. and this was a very beautiful problem. If we were only dealing with the dot values, this would be much easy to solve, but because we were also dealing with the star value, it added a layer of complexity. Now if we see time complexity, in this case the time complexity is actually going to be big O of m cross n, where m is the length of a string and n is the length of the pattern. And if we see space complexity, because we are creating a 2 by 2 matrix, basically the space complexity is also going to be big O of m cross n. And this is a beautiful solution, like one of the best dynamic programming solutions I have seen so far. So I hope you would have enjoyed it. Now let's move on to the coding. First, we will check for an edge case that if both the values are null, we can simply return null. If that is not the case, we are going to initialize our dynamic programming 2D array. And for this 2D array, let's name it as dp. And we are going to assign the length of whatever the length of s is plus 1 and also length of p plus 1. And we are going to assign the base value of the 0, 0 to be true. And now let's populate the first row. So this should take care of the first column. Now let's start our loop. So we are going to iterate over I and j, which means we are going to do 2 for loops. Inside the loop, we are going to check for all 3 different possibilities. So first possibility is that the given characters, the p is actually a dot. If that is the case, which means it would be able to match any single character, we are marking like the dp of I plus 1 and j plus 1 to its diagonal value. Now you must be wondering, why am I dealing with like I plus 1 and j plus 1? Because for the first row and first column, remember, we mark their values as 0 and we actually started the value of s and p on the first position. So that is why every single time I'm going to updating like I plus 1 and j plus 1 values, because the ith and jth value is actually located at like 0, 0 position. They don't have any values. So if there is a dot present, we simply check the diagonal value. Now the second possibility is that both of them are characters, and if both are characters and they both match, we can also mark their value as same as their diagonal value. Now we are at the third possibility, and the third possibility is that if the given character, if that is in the pattern a star, if that is a star, then we will have to do some additional calculations. So now for first we are at the value star. So there could be two possibility. We could have some value as like character and a star, or we could have some value as like a dot and a star. So if there is a dot and a star, we only need to check that whether all the values before that, if they are match or not. And if that is the case, we would be good. We can mark it as true. And so first let's take care of the scenario that if the given value is actually a dot star. So now we have done that check, and then we will check all of those 3 boxes I mentioned, that if either one of them is true, we will simply add that value over here. With this value, we are actually comparing all of those 3 boxes. So if any one of them is true, we can mark it as true. And in the end, this concludes all the possibilities we can do inside our loop. So basically we are done with our calculation. Now simply in the end, we need to return that what was the last value inside our dynamic programming diagonal. That should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's try to run this code. And our code runs pretty fast compared to a lot of other solutions, and which is really good. And it's great in terms of time complexity and also in terms of space complexity. And I would be posting this solution in the comments so you can check it out from there. Thank you. Today we are going to do maximum subarray LeetCode problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Apple, Microsoft, Google, Adobe, Facebook, Bloomberg, Uber, ByteDance, Yahoo, eBay, and Splunk. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and very well like problem on LeetCode. Basically, we are given an array called nums, and we need to find a continuous sub array which has the largest sum and then return the sum value. We are also told that a sub array is a continuous part of any array, so we are given the definition of it. Now let's try to understand this with an example. So suppose this is the example we are given. Well, I have actually drawn this example in much bigger format over here. So for this example, what we are going to do is we are going to see different sub arrays, and then we are going to see that what is the maximum sum we are able to find so far, and then in the end we will return whatever the maximum sum we have found. So first of all, this value is actually -2. So because this value is -2, even if all the remaining values they are positive, it makes no sense for us to keep this value. So we are going to ignore this value and we are not going to keep it in our current sub array. Now this value is +1, so that is good. But again, combination of these two is actually -2. So again, we cannot keep this in the our continuous sub array. Well, now this value is actually +4, and which is good sign. Now these two values, this is again still +3, which is also a good sign, and the combination of these three is again 5, and then we add this value, so this becomes 6, and we are going to keep on updating the max value as well. So max value so far we have found so far is 6. That we can say that up until this point, the sub array there where we have found the maximum value to be is 6. Now this is again -5. So if we do 6 plus -5, we still get +1 value, which is again positive. So we are keeping this as a sub array, and then again this value is +4. So +4 plus 1 becomes +5. So this is also positive. The thing is, in the end, up until this point, the maximum value we were able to find is 6. So because it was 6, we are going to return 6 as the answer. This is what the problem is asking us to do. We need to find the sum of maximum sub array and then return that value. So let's see what would be different approaches to solve this problem. Basically, we need to find the maximum sub array. What we can do is we will try to find every single possible sub array, try to see the sum of all of those characters, and whichever possess the maximum sum, we simply return that sum. So let's see that in action. So first of all, what we are going to do is we are going to take some of this character, then we are going to take some of these two characters, then we are going to take some of these three characters, and so on and so forth. We are keep on repeating the process with the first element. After we are done with this, essentially we are going to get rid of this first element, and now whatever the remaining elements are, we are going to start taking some of those values. So in this case, what again we are going to do is we will take this element, then again we will take these two elements, and again we will take these three elements, and overall we will keep on making the sum, and eventually we would find the answer. And the answer in this case is going to be the sum of these three characters, and whatever the answer is, we can simply return that. So this approach would work as expected, but the issue with this brute force solution is actually that we are doing a lot of repetitive work. If we see the time complexity in this case, the time complexity is actually going to be big O of n square. So let's see that what would be the better way to solve this. Before we come up with the optimal solution, first of all, let's make a couple of things very clear. What is our aim and what is the thing that we are trying to find? Well, basically we are trying to find that what is the maximum sum sub array. At any given moment, there can be any current subarray that we are iterating over, which could be the maximum subarray or could not be the maximum subarray. We don't know. But at any given moment, we will need to have the ability to keep track of some of all the characters that are present in that particular subarray. So which means that we are going to have a variable called current or current subarray, where we are going to keep track of the sum of all the current variables that we have iterated over and we are keeping track of. Well, second thing is that we need to find the maximum subarray, and amongst any of the subarrays, anyone could be the maximum subarray. So we are also going to keep track of another variable called maximum subarray, where we are going to keep track of maximum current sum we have found so far. So well, these two things are understandable, right? They are from programming perspective. But there is also one more thing that is actually rational, and the rational thing is that at any given moment, suppose this value is actually -3. So current sum or current sub array we have found is actually -3. So if this value is -3, because this value is negative, so if this value is negative, even though all the remaining values they are positive and they keep on increasing the value in size, this -3 is always going to have to cause them to have a lesser value. So if that is the case, why are we even bothering to keeping this value at our bay or at our disposal? So the idea is at any given moment for our current subarray, the moment we would identify that the current value or some set of current values, they are causing it to have a negative value, If that is the case, we are going to immediately update our current subarray, and then we will keep on moving towards the next values. And based on these two logics, all we are going to do is we are going to iterate over our given array and keep on going to updating the current subarray, and then keep on updating the maximum subarray we have found so far, and in the end we should be able to find the answer. So let's see that traversal in action. Before we start iterating over this array, we are going to define some default values for this current and maximum variable. The default value for current is going to be the 0, and for maximum it's going to be whatever the first element of this given array is, which is -3. That is to cover an edge case where we are only given one element. Now let's start iterating over. Okay, so now the sum of these two elements is actually going to be -3 plus 2. So -3 plus 2 is actually going to be -1, which is still less than 0. So because this is less than 0, we are not going to update our current max variable, and the maximum sum we are actually able to find so far is going to be 0, which is definitely greater than -3. Now again, for these three variables, again the sum is going to be negative, so we are not going to do anything, and we are going to ignore all three of these cases. Now this value is actually positive, so because this value is positive, the current sum we have is going to be 8, so which means we will have to update the maximum sum we have found so far to be the value 8 as well. Now again we add the sum of these two values, so 8 plus -1, so 8 plus -1 actually becomes 7. So this becomes 7, which is less than whatever the maximum value we have found so far, so we don't need to update the max variable. Now we again add this value to our current sum, so 7 plus 2, 7 plus 2 is 9. 9 is greater than whatever the maximum value we had, so this becomes 9. Okay, now again this is also a positive value 3, so we can do 9 plus 3, which becomes 12. So we are again going to add the value 12 to our maximum sum that we have been able to find so far, and then this value is actually -5, so we can do 12 plus -5. So 12 plus -5 is going to be 7, and again because this value is still positive, we are keeping this current subarray going on, because we don't know, future values might be positive values, and this can also go up pretty quickly. Now we have actually reached to the end of this array, and we don't have any more elements to go over, so the maximum sum we have found so far is 12, and this is what we need to return as the answer in this case. And so this is the most optimal approach to solve this problem. If we see time and space complexity, in this case the time complexity is actually going to be big O of n. Why big O of n? Because we will have to iterate over every single array or every single value that is present inside this given array, which takes big O of n time. If we see space complexity, in this case the space complexity is actually big O of 1 or constant space, because apart from storing these couple of variables, we are not using any additional space, so that's why space complexity is very minimal. First of all, we are going to initialize two variables called current sum and maximum sum. For current sum, we are going to initialize the value to be 0, and for maximum sum, we are going to initialize the value to be the first value inside this given nums array. We are going to create a for loop to iterate over this given array. Now we are going to check that whether the current sum, if that is less than 0 or not. If that is less than 0, we are going to update the value of current sum to 0. That is not the case. We are going to calculate the value for current sum and maximum sum. So current sum is going to be current sum plus whatever the current value inside this given nums array we have. And we will have to check that whether the current sum we have created, if that is the maximum sum or not. And after loop ends, we simply have to return maximum sum. Let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do jump game problem. Recently this problem has been asked in Amazon, Facebook, Apple, Google, Oracle, TikTok, all these gigantic companies, and they are some of my dream companies. So I'm going to do my utmost focus for this video, and I hope that you find it enjoyable. This is going to be the framework for the video. First we are going to understand the problem, then we will come up with a brute force approach. We'll improve our brute force approach. We'll find the optimal solution, and then we'll write the Java code for the optimal solution. This is a medium problem, and we are given an integer array nums, and we are initially positioned at the first index, so 0th index. Each element in the array represents that is the maximum jump we can take, and if that is true, can we reach to the last position? So if we are able to reach to the last position, we would return true. If we cannot reach, we will return false. So let's understand this with an example. Suppose our given input is like 2, 3, 1, 1 and 4, and initially we are located at this position. This is the same example over here. So we can see that if we over here, we can take maximum 2 jumps. So either we can take 1 jump and reach over here, or we can take 2 jumps and reach over here. Let's get the greedy approach, and we'll take the maximum amount of jumps. So over here, if we take 2 jumps, we end up over here. Over here, the maximum jump we can take is only 1, so we'll reach over here. Again, the maximum jump we can take is just 1, so we'll reach over here. And this is our last position. So since we have reached over here, which means that we can conclude that we can solve this jump game, and we can reach to this end position. So we'll return true in this case. Now let's take one more example. So suppose we are given input like this: 3, 2, 1, 0 and 4. And if we check for the possibility, so over here the maximum number of jumps we can take is 3 jumps. So if we take 3 jumps, we reach at 0. From 0 we can't move anywhere forward. So let's, rather than taking 3 jumps, we'll try to take 2 jumps. So if we take 2 jumps, we end up over here, and over here the maximum we can take is just 1 jump. So again we end up at 0. And lastly, rather than taking 2 jumps from here, we'll just take 1 jump. So we'll end up over here at this position number 2. Now at this 2, the maximum jumps we can take is 2. So again we end up at the 0, which means that in any circumstances, if we start at this position number 1, we cannot reach to this last position. So over here we would return false. This is basically the problem statement. I have given a custom example that we are at any position. We are going to first of all see that what is the maximum jump we can take. We'll try to make that jump. We'll try to see that using that jump, if we can reach to this end index. If we cannot reach to the end index somehow, we will backtrack. We will go back to the position where we initially took the jump from, and we'll try some other possibilities. So let's see that in action. So over here, we are initially at this position number 2. The maximum jump we can take is at value number 2. So that jump will bring us over here. Now over here, the maximum jump we can take is at this position 0, which means that we can't move any further. So we will backtrack. We will come back over here. Now again, we are at this second position. Now let's, rather than taking the 2 jump, we will reduce our jumping possibility, and we will just take jump of 1 step. So now we reach at this value number 3. And over here with this value number 3, we can take maximum jump of 3 steps, which means that we can, if we take 3 steps, we will end up over here. So 1, 2, 3. And at this position 2, the maximum number of steps we can take is 2, which means that even if we take 2 steps, we will cross our last entry, which means that in any case, we would be able to reach to this last element, and we would return true in this scenario. Now this approach seems sensible on pen and paper, because we are dealing with a small number of things, small number of input, and we are able to clearly see that how the pattern is going on. So let's take another example. So these are the values. Let me also denote the index values for these. Now with every single iteration, I'm going to note down the index value transition we are making. Okay, so initially we are at this position number 5. The maximum jump we can take is a 5 step, which means that we would end up over here. So initially we would do something like this. So 0 to 5. This is one step we take. We are at 0 position, which means we can't go forward, which means we have to backtrack, which means that again from 5 we will come back to this 0th index. Now from 5, rather than making a jump of 5 steps, we will make jump of 4 steps, and we would end up at this position 4. So from 0 we would end up at this position 4. Now from this 4, the maximum jump we can make is 1. So again we will take 1 step jump, and we would end up at this position 5. Again, we are at 0, we can't do anything, so we will have to backtrack. So in order to backtrack, we will go back to this position number 4. Again, we have to backtrack from this position 4, so we will end up at 0. Again, we will, rather than making a jump of 4 step, we'll make a jump of 3 step and we'll end up over here. So we end up over here, and so on and so forth. So you can see that this in this approach, all we are doing is just we are going someplace, we are coming back. Again we are going, and then again we are coming back. Again we are going to some next element, we are going to some next element, and we are coming back. And suppose this keeps repeating multiple times, you are essentially depleting your resources, because if you see the time complexity at any single iteration or at any single value, we have two possibilities: whether we want to keep this value in our current transition, or we do not want to keep our value, keep this value in our current path that we are calculating. Which means that the input, if we make decision tree, the decision tree would keep on growing and growing with addition of every single value, which means that we are basically making a lot of decisions, and the time complexity in this scenario would actually be big O of 2 to the power n, because at every single position we are making two possibilities. This is a very bad exponential time complexity which we cannot allow in any scenario. Okay, so the issue in the brute force approach we had is that we were doing a lot of repetitive work, because at any point we found out that we are not able to make any progress from this point. We are still ending up at that point. So let's see that how can we counter that with a better approach. Suppose we create an additional data structure over here. So we create a dynamic programmatically additional data structure over here. Let's create an array, and in that array we are going to define that at any position can we reach to this endpoint. And if we identify that yes, we can reach to this endpoint, we would basically fill that position as true. And let's see that how it can help us. So if at any point in time we are at this final position, we know that this is the main terminating case, which means that we can put true over here. So this final element we can always put true, and this would actually become our base case. Now we have a base case. We are going to start iterating on from right to left manner, and we are going to start filling up our DP array to see. And in the DP array, the only thing we are mentioning is that at any given location, if we are able to reach to this endpoint or not. If we can, we'll just mark it as true, otherwise we'll mark it as false. Okay, so now one step over here, this is this value has potential to make two jumps, and it only takes one jump to get to this last point, which means that if we end up at this 4th position, we can reach to this 5th position, which is what we want. So over here we can also fill this as true. Now we are at this 0th position. From the 0th position, can we reach to this 5th position? No, because we basically can't make any jumps. So we'll just fill this as false. Okay, now from this one, can we end up at this 5th position? So we are going to, now the interesting part comes. Now we are going to check that, okay, this has possibility of only doing one jump, right? So with one jump, we can only end up at this 3rd index. Now we only need to check that in this DP array for this 3rd index, if the value is true or false. So in this case, this is already false, which means that the maximum we can get to is this 3rd place. From this 3rd place, we can't go anywhere. So we don't even need to check these values. We can only check this DP table, and we can conclude that no, we can't go anywhere forward. So we will put a false over here as well. Now we are at this 3rd position. Now from this 3rd position, we will again do the same check. But the thing is, this has potential to do 3 jumps. Okay, so let's do one jump at a time. So first we take a jump. If we take a jump of 1 step, we end up over here. We check over here that this is false, which means that this is false, right? Now we take second jump. With the second jump, we end up at this 3rd position. We check in this DP array. This is also false, which means that we can't do anything. Now from this 3rd position, we still have one more possibility, that we can take a jump of 3 values. So if we take a jump of 3 values, we end up at this position, value number, this index number 4. So for this index number 4, we see that the value is true. If we find any true, which means that we can say that from this second this index number 1, we can reach to this last endpoint. And now for this position, we need to check that it has potential to do 2 jumps. We will only check for 1 jump. So with 1 jump, we will end up at this first index. That one is true, which means that we can fill true over here as well. And in the end, we just need to return whatever of dp of 0 we found. So in this case, we can determine that this is true, which means that we are able to come to final endpoint. So this solution is very good. It works perfectly fine. Okay, so the time and space complexity for this approach would be, so the time complexity would be big O of n square, because notice that we need to do one iteration to go on for every single element, and sometimes for any given element we might have to do multiple jumps like we did in this case of 3. So in the worst case, we might have to solve this in big O of n square time, and the space complexity would also be big O of n because we are creating this additional DP array. Now this is still much better than our brute force approach, but our aim is to go into companies like Google, Facebook, Amazon, Apple, and whatnot. So those companies expect the best out of the best solutions. And is this the best out of the best solutions we can do? Actually, no, there is still a better optimal solution, and let me show you how we can get there. Okay, and this optimal solution is actually based on the dynamic programming solution that we just saw. So in dynamic programming, what we are doing is we are creating an additional DP array, and we are storing that whether we can reach to this last element or not. But the thing is, what if rather than storing this value at any position, when we find out that suppose from this position we found out that yes, we are able to reach to this last position. So why do we need to check that whether we can reach to this last position or not? If at any point amongst these values, if we end up at this position, we would still be able to guarantee that we can reach the last element because we have already checked this condition. So rather than checking for this whole thing, if we just check that okay, from here if we can reach to this element or not, and if this is true, we can simply return true at that moment also. And let's see that in action. So let me clean this up a bit. Let's mark all the index values. Okay, initially we create an element called final, and this final element represents the last value in the given input, and initially we set it up to this index number 5, right? Now our aim is that at any point we found out that amongst these values, if anyone can reach this final element, then that element by itself becomes this final. So rather than storing all the values of at any given location, we are actually shrinking down our boundary of search. Initially the final is at this 5th position. Now we are at this 2nd position. So all we need to do is to check that whether our current index our current index and this current value, if sum of these two is actually greater than whatever final we have. So currently the final we have is this 5. So this is the final we have. Current sum of these two values becomes 4 plus 2 is equal to 6, which is greater than 5, which means that we can update the final value of our final. So now this becomes our new final, and we basically don't care about this value anymore. Now we are at this 3rd location, and we try to see that the index plus its value. So this becomes 3 plus 0. Is it greater than our final? No, this is not greater than our final because this is 3 and this is 4, which means that we can't do anything over here. So we drop this calculation and we check with the next element. So over here we have this 2 and we have the value 1. So 2 plus 1, is this greater than 4? So greater than final? No, this is also not true, which means we can't do anything over here. We again go back. Now this is 1 and this is 3. Now 1 plus 3, is this greater than or equal to value 4? Yes, this is greater. This is actually equal to 4, which means that we from this point we can come to this point. This is what this concludes, and which is what we want, right? So now we know this information, which means that we can update the value of our final again. So now the value of our final would become 1, so at this value. And now at this 0th position we need to check that whether we can reach to this 1 or not. So over here the sum of these two value becomes 0 plus this is 2. So 2 is definitely greater than the final amount we have is 1, which means that we can reach over here. So the final element would be shifted to this point, and our at the end of our iteration the final would be 0. So now the final is 0. After the end of the iteration we only need to check that what is the value of final. If final is 0 we return true. If final is anything other than 0 we return false. And this is a very good solution. The whole thing runs in the time complexity of big O of n, and if we see the space complexity, we are only storing one additional parameter. So we are essentially using constant space and we are solving this problem. So this is a very efficient solution. Let's create a variable called final. Oh, it's Java, I can't use final. Let's call it final with an extra L, and we'll assign its value as nums.length -1. And now we will run a for loop, and we'll start it from I is equal to number of length nums.length -2, because we already know the result for the array length. And we will run it up until we reach to this 0th position. We'll do I minus minus, and inside the loop we are only going to check one condition, that if the current value of I plus nums of I, if they are greater than or equal to whatever the final value we have, we can update the value of this final parameter to whatever the ith value we have. And yeah, that should be pretty much it. Now we only need to check that if the value of this final character is 0 or not. So if it is equal to 0 we can return true, else we can will return false. Okay, let's try to run the code. Seems like our solution is working. Let's try to submit the code. Okay, our solution works 100% faster than all the other solutions. This is really good sign, and this is not constant time, but because we are basically shifting our boundary, we are essentially reducing the number of work we can do. And also if you see the memory usage, we are actually better than 86% of all the other solutions. So this was a very small line of code, but this small line of code actually requires huge set of understanding. So see you in the next video. Thank you. Hello friends, I am a cloud solutions architect at Microsoft who like making LeetCode videos, and today we are going to solve an awesome problem called Jump Game 2. If we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Goldman Sachs, Bloomberg, DoorDash, Uber, Microsoft, Apple, Tesla, TikTok, Snapchat and ByteDance. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also very well like problem on LeetCode. Basically in this problem we are given an array of integer called nums as an input, and we are told that we are initially positioned at the first position inside this given array. Now our aim in this problem is to return the minimum number of jumps required to reach to the last position. Now you must ask that how are we going to make these jumps? What are the criteria for that? So the criteria for any jump is that any given value that is presented inside this given array represents the number of values it can jump. So basically if this one is represented 2, we can say that it can reach, it can either take like one jump or it can take two jumps and reach to these positions. and our aim is to reach this last position, and basically we need to do this in the minimum number of jumps that is required. Now if you are confused, don't be. I'm actually going to show you a couple of examples to understand that how things work. So basically over here we are given 5 different values, and for these 5 different values, as I mentioned earlier, every single value represents the maximum number of jumps it can take. So this value number 2 has two possibilities. It can either take one jump and reach to this position number 3, or it can take 2 jumps and reach to this position number 1. Same goes with value number 3. It has 3 options. It can take like 1 jump, 2 jump, or 3 jumps, and then do that. And our aim is to reach the last position from the first position in the minimum number of jumps possible. So if we see in this example, the answer is actually quite evident. We start our position at this value number 2, and if we just take like first jump to reach to this value number 3, okay, so currently the number of jumps we have taken is 1. Now from this value number 3, if we take another jump of the size 3, basically we would be able to reach to the end position, and in total we are only taking 2 jumps to reach to the end. So basically we need to return 2 as the answer in this case. If we try to understand the second example, things are a little bit different. So in this case we can only take 1 jump. So okay, so currently the number of jumps we have taken is 1. Now from this 1 we need to take one more jump to reach to this position. So again the number of jumps we have taken so far is 2. Now from this 2 we have two options. Either we can take one jump and reach over here, but that is not the most optimal way. Most optimal way is we take a jump of 2 steps and reach to directly to this end point. So basically the answer in this case is going to be 3, that we need minimum 3 jumps to reach to this last position, and in this case we need minimum 2 jumps to reach to this last position. So this is what the problem is asking us to find, and I know it can look tricky, but it's really simple to do it. And let me show you a couple of different approaches to solve this problem. Okay, so the first approach that comes to our mind is a brute force approach, and in the brute force approach basically we are just going to use the simple logic. The logic is that at any single position we will try to see that how many jumps it can take, and try to explore all the possibilities and try to find that how many jumps it takes to reach to the end element, and also have like a minimum variable in mind that whenever we find minimum number of jumps we will keep on adding it over here, and eventually when we compute all the calculations we should have a result. So in this case what we are going to do is that okay, this value is 2. So first we will consider the possibility of just taking one jump. So in this case, okay, if we take one jump we reach over here. Again we have 3 possibilities over here, but we are only going to take one jump. So again we reach over here. Again this only has one possibility, so we reach over here and then we reach to the end. So in this case we took in total 5 jumps to reach to the end. Now secondly we are going to take like different things. So first we will take 2 jumps. So we took 2 jumps, and now we take 1 jump every single time and try to see how when we reach to the end, and so on and so forth. We keep on repeating the same process with different combinations. Now just by the explanation you can imagine that how complicated it's gonna make things, because for every single time you will have to calculate different permutations and combinations of sums, and eventually it's gonna lead to very disastrous results. Like if we see time complexity in this case, it's gonna be in the order of n factorial, because for every single element we will have to compute the process for all the other elements, and that is going to be in the order of big of n factorial, which is really bad. So we will have to find a better solution, and the better solution is actually quite simple. So let me just directly go to the optimal solution. And now for the optimal solution we are actually going to use a very interesting concept called greedy concept, and basically we are going to try to make the biggest jump possible every single time and try to see that where does that leads us. Now being greedy is not good in real life, but in computer science it is like the must thing, so you have to do it. Now for the greedy approach we are actually going to keep track of 4 different variables. So first variable we are going to keep track of is the index value we are currently at. So let's just name it as index. Again we will also have to keep track of the number of jumps we have made so far. Also we will need a variable to keep track of current maximum variable that we have been able to reach, or current maximum value we have been able to reach. And also from the current index we will have to keep track of that what is the current end value we can reach at. So there are 4 variables. Let me go over them again. First one is the index value, second one is the number of jumps we have made so far. These two are sensible. Third one is to keep track of that what is the current maximum value we have achieved so far, and we will only update it when we find like a better maximum value. When we go through the example, everything will make more sense. And the current end defines it is in correlation with the index value, that where does the current end lies, and if we are at the index value, then we will have to make some changes. So now let's look at the example, and currently let's initially assign the values. So initially the number of jumps are 0, current maximum is also 0, and current end is also 0. Now we start our journey. So first we come up at this first index. So whenever we are at the first index, okay, the index value currently is 0. Now the index value is 0. Now let's just keep on updating these values, right? So currently this has value number 1. So if this has value number 1, which means that this 0th index has the potential to reach maximum at the first index, which means the current maximum value we can achieve is that, okay, this current value is 0. Now over here it says that it has maximum potential to reach index value number 1. So 1 is definitely greater than 0. So because it is greater than 0, we will update the value of current maximum to 1, that okay, this is the maximum value we have been able to achieve. Now the interesting part comes. The current end we were at, the current end was 0 because we were at the 0th position, and also the index value we were at was also 0. So because both of these values were same, which means that in order to get ahead to the next index, which is not the last index, again remember I am repeating, in order to get ahead from the current index, which is not the last index, we will have to update the current end, because currently the current end was also here and the maximum value was also here, but this has the value 1, so we have the ability to go to the next, which means the current end needs to be updated. And whenever both of these are at the same place, that means if we are updating the current end value, we will only update the current end value in the condition when we are making the jump. So again, let's just go back to our analysis. Because the index value and the current end both were same, so because these two values were same, we can define that we need to update their values, which means we are taking a jump. So okay, so we made a jump, so we will do jump plus plus, so currently this value becomes 1. But the thing is, where do we update this current end to? We will always go this current end to the whatever the maximum value we have been able to find so far. So current maximum we found is 1. So again, we are going to include this value number 1 over here. Now let me clean this up a bit. So now we are at index position number 1. So we will update our index value. So our current index value is 1. Now at this position, what is the maximum it can travel? Maximum it can travel 3 points. So 3 is going to be 1 plus 3, so that is 4. So now this is the current maximum we can achieve, that is 4. So we will compare 4 with the current maximum we had. Current maximum is 1, so 4 is definitely greater than 1, which means it is sensible for us to update the current maximum. So current maximum becomes 4. Now we will also have to check that what is the current end. Now current end is still same as the index value, because this was the current end, so which means that anyways we will have to make a jump. So because we are making a jump, we will update the value over here. So currently the number of jumps we have made so far is 2, and we will also have to update the value of the current end. So current end we can reach is position number 4, because we already established that that is where the maximum number of jumps we can take. So okay, we are good up until this point. Now again, let's make the changes. So now we are at index number 2. So let's see that what story happens at index number 2. Now index number 2, the maximum we can take jump is 1. So if we take 1 jump, we reach at index number 3. But the thing is, if we check the current max is already 4, and the maximum we can reach is 3. So 3 is actually less than 4. So in this case, we don't need to update the current max. Okay, awesome, we are not updating the current max. And now we check, okay, current end is 4 and the index value is 2. So these two are not same. Because these two are not same, we don't need to update the current end or the number of jumps that we are taking. Now okay, now our index value keeps on updating, because we are checking this for every single index value. So now we are at position number 3. So now at position number 3, we have maximum 3 possibilities, right? So if we go to 3 steps, we reach to the index number 6. So our current maximum will become 6, because definitely 6 is greater than 4. Now we updated our current maximum. Now we also need to check few other things. Okay, so current end and index value, these two are not same, so we are not going to do any changes for now. So now our index value becomes 4. So let's update this. Okay, so this becomes 4. Now we are at this fourth position. This only has possibility of 1, so this will reach to the maximum of 5, but 5 is actually less than 6. So in this case we will not update the current maximum. Now in this case the index value and current end is both of them are same. So because both of them are same, we will have to do the update. So now when we do the update, okay, we are going to mark the current end as 6 because that is what the current maximum we have been able to achieve, and also the number of jumps we are going to take is going to become 3. Okay, now again we keep on repeating the same process. So again our index value becomes 5. Now because with the 5 index value, the maximum we can take is 1, so that is going to lead up to 6, because but we already have current maximum at 6, so we don't need to do anything, and these two values are not same, so we know we are not going to do anything. Now the index value is at position number 6. Now at position number 6 we are actually able to reach to the end with just a single jump. So we are going to do that. Okay, now we reach to the end of this jump, but the thing is we are just going to, for the sake of simplicity, go ahead with this calculation. So the current maximum we have been able to achieve is going to be 7. That is the end. Now current end and the index value, both of these are same. So because both of these are same, we will have to update our number of jumps that we need to take, and also we need to update the current end. So current end in this case is going to be 7, and we are going to check that if the current end reaches to the last position or the size of the array, that means that is the answer, and we can break out of the loop, and whatever the answer we have been able to find, we can simply return this. So in this case, for this example, the answer is going to be 4, that we can return simply. And this is the most beautiful approach of the greedy solution that I have seen so far. Now if we see time and space complexity, in this case the time complexity is so good because we are only going through every single values and calculating, keeping track of 4 different variables. So time complexity is actually going to be big O of n. So notice that from big O of n factorial we were able to bring it down to big O of n, and all due to the greedy approach that we took. If we see space complexity, in this case the space complexity is actually going to be big O of 1 or constant space. Why? Because we are not using anything else apart from like these 4 values. So that is also a wonderful news. Okay, so let's initialize 3 variables that we need. That is going to be jump, current end, and current maximum, and initially all the values are going to be 0. Now notice that I am not using the index value over here, and that is because we can actually use it from our loop directly. Now let's run a for loop to iterate over the given input array. So now every single time we will check that what is the current maximum we have been able to achieve. So we are basically going to compare the maximum value amongst the existing current maximum value or the value of I plus whatever the value of nums of I for that particular I is, and whichever is maximum we are going to put it in the current maximum. Now we are also going to check one very critical condition, that if the given I is actually equal to the current end we are at. If that is the case, which means we will have to update the value of the jump. So we will do jump plus plus, and we will also have to update the value of the current end. So current end is in this case going to become the current maximum that we have been able to achieve. And believe it or not, but this concludes the whole solution. After we get out of the loop, we can simply return the jump that we have been able to find, and this should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And if we submit it, this is beating like almost 99.99% of the solutions in terms of time complexity, and in terms of space complexity, this is also very efficient. So this is a very good solution. And if you see, we are just only using a single loop and just like few lines of code to solve this problem. And I would be posting this in the comments, so you can check it out from there. Thank you. The LeetCode problem we are going to solve now is called gas station, and we can see that this one is a LeetCode medium problem and also a very well-liked problem. The statement is quite straightforward, that there are n gas stations along a circular route where the amount of gas at any particular station is defined in the array gas of I. And then we are told that we have a car with unlimited gas tank that cost of I gas to travel from ith station to the next I plus 1 station. Let's do a quick recap. Basically we are given two arrays. First array is called gas and second array is called cost. Basically gas, any particular value inside the gas array defines how much oil or how much gas we can fill in the tank at that particular location. Cost at that station defines that if we have to move to the next stop, what is going to be the cost in terms of gas amount. So based on distance, you can understand it that way. Now we begin our journey with an empty tank at one of the gas stations. Okay, now we have basically need to make sure that given these two arrays, we can start from any particular gas station's index, and we need to check that if from that gas station's index are we able to travel around the entire circuit once in a clockwise direction. If that is the case, then we need to return the location of that index. If that is not the case, we need to return -1, and we are guaranteed that we would be able to find a solution. So if there exists a station, there has to be only one station that can fulfill that property, otherwise it would be -1. There would not be any duplicated answers. So let's try to understand this with an example. Currently we are given a variable called gas and we are also given variable called cost. At any particular index position, this is the amount of gas we can fill in the tank, but if we need to go to the next stop, then this is going to be the cost associated with that, and so on and so forth. So let's try to see that what would be the answer in this case. Let's say that suppose we start our journey from index position 0, which means currently our car has so let's just mention that what is going to be the tank amount of gas in the tank. Okay, so currently tank has empty, so no gas at all. At position number 1, we would be able to fill in one amount of gas. So currently tank has only one amount of gas. Now let's say that if we need to reach to next position, index position number 1, then we will have to pay this cost. If we were to pay this cost, it would be 1 minus 3. So basically our tank would go in negative, so we would not be able to reach to this position number 2 from tank number 1. So we can clearly say that option 0, it does not work. Same way we can also check that from option number 1, currently our tank would be initially 0. Okay, let's just repeat the calculation. So this is going to be 0, but now we can fill in plus 2, so now the gas would be 2. But if we have to get to option number 3, then we would have to spend 4 units or 4 liters of gas, which means 2 minus 4 would become -2. Once again, we would not be able to reach to item number 4, so that would also not work. So let's just start our iteration from this third index position. Once again repeating the same logic. Currently tank is going to be 0, but we can add tank as 3, so 3. And but if we have to reach to next station, the cost is 5, so 3 minus 5, once again this would also not work. So now we are at this index position number 3. So currently our tank is going to be 0, so we can add value number 4. So now tank has 4 liters of gas. If we have to reach to value number 5, then we need to spend 1 liter of gas. So once again this is also going to be 4 minus 1. So basically when we reach to this index position number 5, our tank would have 3 units of gas. Once again at this position we would fill in 5 units of gas, so this is going to be 3 plus 5. But now from this, in the clockwise direction, basically we will need to reach to station number 1, but we will have to pay cost of 2, so 3 plus 5 minus 2. So overall this is going to become once again 6. So we are going to have 6 units of gas when we reach to this position number 1. Once again over here we will add 1 unit of gas, but in order to reach to next element we will have to spend 3 units of gas. So now when we reach to this index position number 2, our gas is going to be 6 plus 1 minus 3, so 7 minus 3, so basically this is going to be 4. Once again from this position number 2, we need to reach to position number 3, so 4 plus 2 minus, we will have to spend 4 units of gas, so basically this is going to become 2. And at this position once again we get 3 units of gas, so 2 plus 3 minus, if we have to reach to next, which is from where we started, then basically it's going to be 5. So 2 plus 3 minus 5 is going to become 0. So basically we would be able to reach to unit number 4, and this is going to be the starting point if we were to complete the whole circuit. So we'll need to return the index position, so we can return 3 as the answer over here. And I know the explanation took a lot of time to understand what this problem statement is, but basically this is actually the whole solution as well. Because in order to solve this problem, we don't need to use any special data structure or any special architecture. Basically, if we just follow the most simple basic rule, that we are going to start our iteration from the very first index, and from this very first index position we are going to check that are we going in a scenario where our current tank goes negative. If the current tank goes negative, we can simply choose the starting point as the next element, and once again if it goes negative, we can choose the starting point as next element, and we will keep on repeating the same process. And the moment the tank goes into negative, we will just update the tank value to become 0, and that is the whole logic of this problem to solve this problem. Now let's talk about some of the critical possibilities. Number one scenario is the only way we are not able to complete the whole circuit is a very simple logic, that is that if the given gas is going to be less than the total number of cost. If that is the case, cost is higher, so we would not be able to complete the full circuit, and we can calculate this immediately, basically by summing up all the values that are currently present in both gas and cost arrays, and we can just compare those values. So if that is the case, we can simply return -1 immediately, saying that this problem cannot be solved. If that is not the case, then we will simply follow the most common, most logical thing that humans are really good at, and that is called greedy approach. That we are simply going to take the first value, try the solution. If solution works, great. If we at any given moment find the tank goes into negative, then we will just pick the next value. So over here, for the same problem, I have just presented it in a different manner. Currently, we have our index position stored inside. So 0, 1, 2, 3 and 4. Now this second circle defines that how much amount of gas can we get at any particular location, and the values located at these gates define that if we have to jump from gate number 1 to gate number 2, then we will have to spend 3 units of gas, and which we can subtract. So basically the solution is that we will start our greedy approach by iterating at value number 1 with initially the tank is going to be 0, and then we will just repeat the same exercise we did. So we will check, okay, over here we can add 1 unit of tank, but this is going to be 3 units of tank to reach to value number 2, so tank would go into negative. So basically we would choose our starting point over here by resetting the tank to be 0. Once again 2, and this is 4, so tank goes into negative. So once again we would choose our starting value to be index position number 2. Once again tank goes into negative, so once again we would choose our starting index to be this. The moment we find a starting index where the tank does not go negative, we would try to iterate over and see if we are able to complete the whole journey or whole transaction, and basically we should be able to do it in this case, because we know that we have a starting point where the tank does not go negative from to when we start iterating. And secondly, the total cost of basically total cost is basically not greater than the total number of gas. So that's why we know that the answer should not be -1, and just that's it. So in this case we would return 3 as the answer. If we have to calculate time and space complexity, it is quite straightforward. For time complexity, basically this can be done in big of n time if we apply the greedy approach and we do some slight tweaks with the code. So the tweaks with the code I'm going to explain you when we actually get to the coding portion. And for the space complexity, well, we are not using any additional space to solve this problem, so basically this is going to be big of 1, so which is quite beautiful. Now let's just quickly see the coding solution. So the solution is quite straightforward. First, we are going to have a few variables. They are going to be initialized as 0. First one is total gas and total cost. Both are initialized at 0. Then we have tank, and then we have starting index. Then we are going to have a simple for loop that is going to iterate over every single starting point in the given input. We are going to have two variables, total gas and total cost, that is going to be continuously adding the total amount of gas and total amount of cost we have. For the current proportion of gas that can live inside the tank is going to be calculated by adding the current gas with the current tank value and reducing or removing the cost of the current ith position. Then we are checking for a simple condition that if the tank goes into negative, then the starting index that was originally at 0 now needs to be at I plus 1th position, because we identify that the current ith position does not work, and then the current value of the total amount of gas inside the tank is also going to be 0. Then we are going to check at if at any given moment the total amount of gas becomes less than the total amount of cost after the running of whole for loop. Then if that is the case, we can simply return -1, and if that is not the case, we simply return the starting index. And this is the whole solution. Let's try to run the code. Okay, seems like our solution is working beautifully. Let's submit this code. And our code beats 99.29% of all the other solutions, which is exceptionally fast, so pretty good. And once again, I would be posting this solution in our GitHub repository, so feel free to go ahead and check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So now we are going to solve an awesome LeetCode problem called hand of straights. Now we can see that this one is a medium problem and also a very well-liked problem on LeetCode. Let's understand the problem statement. We have a girl named Alice who has some number of cards, and she wants to rearrange these cards into a groups such that each group of the size group size consists of group size consecutive cards. So let's try to understand what this means. Basically, we are given an integer array called hand that defines bunch of different values inside a deck of cards, and at any given integer I is the value returned for that particular hand. Now we are also given another variable called group size. Now we need to check that whether we can divide all of these hands in a group sizes, like groups of these group sizes, such that all of the rearranged groups contains consecutive cards and we can rearrange all the groups. So let's try to understand this with an example, and then it would make much more sense. Let's say that we are currently given the hand or deck of hands like this, and we are given the group size to be 3. So let's see that can we create the different 3 size groups. So first group we can create is going to be cards 1 2 3. Now notice that there is a condition when we are trying to create the groups, that every single card inside the group has to be consecutive. So we can create this one group. Second group we can create is using these 3 characters, and that is 2 3 and 4. And third group we can create is using 6 7 and 8. So now notice that in this case, we use all of the cards that were currently given to us, and we divided them into the size of 3, and each group contains the cards that were coming in consecutively. So in this case we can say that we can create the hand of straights using this, so we will return true in this case. Let's take one more example. Suppose the given hand is values 1 2 3 4 and 5, and in this case we are given the group size to be 4. So in this case we can create a group of size 4 with these 4 characters or with these 4 characters, both of which are going to have consecutive values. So values would be 1 2 3 and 4. The thing is, we would still have one more value left that is going to be left out, that we cannot use. So in this case we can return false, because we are not able to create or use every single card inside our hands array. Let's take just one more example. Let's say that currently the values given are 1 2 3 and 5 6 and 8, and in this case the group that we are trying to create is of size 3. So we can see that we can create a group 1 2 3 like this, no issues with this. We can also create a group of 3 cards using 5 6 and 8, but the thing is, this is not going to be a correct group, because we need to create a group that only contains consecutive elements, and 5 6 and 8 are not consecutive cards. If this were to be 5 6 and 7, then it would have worked. So because of that, for this particular example we will have to return false. So that's it. This completes my explanation on what the problem statement is actually asking us to solve. Let's see that what is going to be the optimal approach to solve this problem. Well, the idea is quite straightforward. What I'm suggesting is that we are given currently the hands, and we are also given group sizes. Now we know that for this particular given group sizes, we will have to create groups. The values inside the group has to be consecutive. So first thing that comes to our mind is that if we are dealing with consecutive or subsequent values, why don't we just simply sort the given input of hands and then try to start creating groups according to that? Do you think that approach would work? Let's try to see that approach in action. Let's say that this is the current hand that we are given. Now we are trying to use our first approach where we are going to sort every single value inside our hand array and try to create groups of size 3. So the sorted hand is going to look something like this. Now notice in this problem, if we try to create groups of 3, we would not be able to make consecutive groups. We would run into this issue. If we create a group of 3, we would have a group that looks like 1, 2 and 2. And based on this, we can just say that this is a false group and we cannot make sense of it. But this would not be the correct assumption. Correct assumption would be that if we identify two values that are same in frequency, then we only need to consider the first value for the partition of first group. So the idea in this case would be that we would create a group that is going to be 1, 2, then we found a repeated character, so we would ignore this one and add value number 3 into a group. After creating this group, we will check that whether there has been any values that are currently left. So yes, this 2 has been left. So let's use the same operation. So now we are going to create one more group using this 2. Now notice that we have already used this 3 in the first group, so we are going to be eliminating that, and then we will have values 3 and 4 in this case. So we can also repeat the same operation, and then after all the values that we have currently used, we will keep on trying to make partition and trying to check that whether they follow the property of them being consecutive or not. So in this case, based on this approach, we can actually find the solution, which means number one, there are few assumptions we can make based on this. Number one, sorting is going to be greatly helpful. Second thing is, we come into the issue of duplicated numbers. So we will need to know that what is the frequency of every single character. And if we can combine these two values, store that information that have the sorted values of all the unique values that are present and have the frequency that how many times they are currently present, it would be easy for us to make these groups. And if we are able to make subsequent groups that follow all the property and we are able to use every single value inside the hand, we can return true or we can return false. So using this, what I'm suggesting is that we actually use something smartly. We use a hash map and we use a sorting approach. Now the thing is, why am I suggesting to use the hash map? Because we are dealing with unique entries, and for each of the unique entry we have different frequency, and this is what I'm suggesting that we store as part of the hash map, where as a key we are going to store that what is the current value of the hand, and as its subsequent value we are going to store that how many times that hand has been repeated in any particular iteration. Next, after storing this information, we will have to sort all of these given keys because we are trying to generate consecutive values one by one. So logically, why don't we just combine hash map and sorting at the same time, where we can simply use a tree map that is going to have best of both worlds, that can access and fetch all the elements in big O of one time, and it can insert all the elements in big O of log n time for the frequency and stuff like that, because based on the key value. So this is going to be an efficient approach. So now what I'm suggesting is that we are currently given our hand that we are going to be dealing with. For this particular hand, what we are going to do is we are going to create a tree map. This tree map is going to contain the unique value plus their frequencies, and for these two, using these two values, we will start creating groups of bunch of different numbers, and we will need to make sure that if the starting value of group is, let's say, 5, and the group has to be of size 3, then next value has to be 6 and next value has to be 7. If we can find 6 over here, that's great. If we cannot find 6 at any given moment, we can directly return false, saying that this group is not being able to make. So let's try to see my solution in action. So now based on the hand, we have our tree map ready. Notice in the tree map, we have every single key or the hand value is currently sorted, and we also have the frequency that how many times this is present. Now we need to create the group size 3 for every single value. So the idea would be that for very first group, we are going to take the smallest value out, and we are going to reduce its frequency, and this is going to give us the starting point for that particular group. So starting point is going to be 1, which means this has to be a group of size 3. So next subsequent element that should be in the group has to be value number 2. But thing is, we are not sure if 2 is present or not, and lucky for us, we can check that immediately, that whether 2 is present or not. By the way, when we took this 1 out, we would have reduced its frequency, so we can reduce the frequency to 0. The moment frequency becomes 0, it would make sense to completely eliminate that element rather than just storing it. So we can eliminate 3. Now we are looking for 2, we found 2, and which means we can also reduce the frequency of 2. So now the frequency is going to be 1. Next thing should be 3. So we are trying to find a 3, and we also found a 3 over here. We are also going to reduce its frequency from 2 to 1. So now this is also going to be 1, and we created our first group. Now for the second group, once again we will check inside our hash map or tree map that what is the smallest element, and this is going to be the very first value inside our tree map, that is starting point is value number 2. So now we are going to use value number 2 over here, which means its frequency is going to become 0. If the frequency becomes 0, we can mark it as 0, and then next element should be 3. So we will check that whether 3 is present. Yes, 3 is present. So we are also going to mark its frequency to 0. Once this becomes 0, we can also eliminate this value, and we can also now we are looking for next element to be 4. 4 is also present, and we can mark 4 as counted, so we can remove that element and close this group. Now after closing this group, we have basically deleted all the elements before that. Now once again we will have to create a new group, then that group starting point has to be 6. So we'll going to mark 6 over here, and then which means now we are looking for 7 and 8, and lucky for us 7 and 8 are also present, so we can just mark these as visited. And then in the end, notice that now we currently don't have any value inside our tree map, and because we did not find any place where we could not find an element, so in this case we can return true. Now let's say that in the same example, instead of this being 7, let's say that this value would have been 9. So in this case, what would have happened? That we would have values such as 6, and the frequency of the value is going to be that 6 is present one time, 8 is present one time, and 9 is going to be present one time. Over here we find that the starting point has to be 6. Now for this this group to exist, we will have to find value number 7, but 7 would not have been present over here. The moment we identify such thing like this, we could have written false immediately. So this is just for you to understand that under which scenario we would return false, and basically this is the whole solution. Now you can see how beautiful we are doing things. If we calculate time and space complexity, in this case the time complexity is going to be big of n log n. Why n log n? Because it takes us log n time to add all the entries inside our tree map. In terms of space complexity, because we are using an additional tree map, it is going to be big of n, but we can manage that. Now on top of it, we can also do one more optimization, that if let's say the given number of hands is currently 10, and if the given group is equal to 3, so if the total cards are 10, do we even need to check that can we make all the groups of size 3? No. Why? Because 3, we can only create like the group for 9 cards, and there is still going to be one more left out card. So initially we can always check that whatever the size of the given currently h is, if that is going to be divisible by the given group size or not, and this value the remainder has to be 0. If that is the case, then only we will move forward. So this would be a way for us to eliminate few like bad and edge cases. And now let's see the coding approach. Now for the coding solution, first thing we are going to check is to see that whether the given length of all the hands, so all the cards that we currently have, if that is divisible by group of 0. If that is not the case, then we can directly return false, because for sure we would not be able to make the group of that particular group sizes if this is not divisible by 0. If that is not the case, we are going to initialize a tree map where we are using hash map in combination with tree map, because we want to access the keys in a particular order. And now we are going to be counting every single card. So we are going to iterate over each of the card that is currently present inside our hand array, and we are going to be adding that to our tree map, where we are going to define that if that card is present as the key, then we simply update its frequency. If that is not the case, we create a new entry. Then we attempt to form groups, where we are first of all in the outer loop checking that while the we still have present cards inside our key tree map, we are going to do the following, where first we are going to initialize the first key or the first starting point of the first group with the smallest key. And notice that because we are using tree map, we can actually just keep on accessing the keys directly because they would be stored in a sorted manner. Then we are going to iterate over the for loop, focusing on each particular group sizes, where we are checking that what is the current card, that is going to be first plus I. Then we are going to check if we have that current card inside our tree map or not. If we do not have that value inside the tree map, we can simply return false immediately because we cannot make consecutive groups. If that is not the case, we are simply going to add that value. Then we are going to reduce the value or the decrease the count because we are removing the card. And then we are checking that if the given count is equal to 1, then we can simply remove that card completely from our tree map. If that is not the case, we simply reduce its frequency and repeat the same operation. If we do get out of this loop, which means we are able to get out of every single card and use every single card to create the appropriate group sizes, and which means we need to return true in the end. So this is the whole solution. Let's try to run our approach. Seems like our solution works beautifully. Let's submit this code. And our code beats good chunk of solutions. It is not the best and there are still improvements can be made, but given the time frame, this is a good approach. And the solution is present inside our GitHub repository, so feel free to go ahead and check it out from there. Thank you. The LeetCode problem we are going to solve now is called merge triplets to form target triplet. Now we can see that this one is a medium problem and also not very well like problem, but a really important one. Basically, a triplet is an integer array of 3 integers. Okay, that's fine. And we are given a 2D integer array called triplets with bunch of different values that contains the pieces of triplets, which means like values like A, B, and C. Okay. Now we are being told that there is a target triplet X, Y, and Z. Now we need to make sure that in this given triplets, are we able to generate this target by doing the following operation on any number. So basically we can pick any two triplets from our given triplet array, and if we pick any two triplet, basically we can combine them to create a separate new triplet that is only going to contain 3 values, but that is going to be the maximum value at each position amongst these two triplets. So let me give you an example. Suppose we have a triplet 1, 2, and 3, and we have a triplet, let's say 4, 5, and 6. So in this case, we know that amongst these two, the higher value is 4. Then amongst these two, the higher value is 5, and amongst these two, the higher value is 6. So if we merge these two triplets, basically we can form an operation like this. So based on this, we are being told that we can do as many number of operations as we need amongst all the triplets that are given, but we are trying to make this target number. If we can make the target number, awesome, we need to return true. If we are not able to make the target number, then we need to return false. So let's try to see one example, and we'll try to figure out different examples from that. So first one is that let's say that in any given case we are given these three triplets, right? For these three triplets we need to form a number 2, 7, and 5. Now notice that we have the option to do the operation between any two triplets. So let's say that we do that max operation between these two triplets, which means we have value 2, 5, and 3 at one position, and second value is 1, 7, and 5. By doing the operation like the merge operation, basically we can pick the maximum amongst the all of these values, and we will form a new triplet that is going to be maximum of these two values. So the value is going to be 2, this is going to be maximum, so value is going to be 7, and this is going to be the maximum, so once again value is going to be 5. And notice that this exactly matches the given input target that we have. So in this case we can return true, saying that yes, based on the given input we are able to generate the target value and hence we can make the triplet by merging two triplets. So let's see that what is going to be the brute force approach to solve this problem. Well, it is quite straightforward that for any given triplets that we currently have, let's say that we are given in total 5 triplets, and I'm just marking them as A, B, C, D and E. And for each of these 5 triplets we have the option to do the merge operation. So if the brute force ways that we do merge operation amongst these two triplets, we do merge operation amongst these two triplets, and so on and so forth, we keep on repeating, and every single time we compare it with the target value to see if we are able to generate the target value or not. And eventually if we can, we would find the correct answer, but this would yield in big O of n square time, where n is the number of triplets that we currently have, which is an inefficient approach. We'll need to find a better approach, and the optimal solution in this case comes from doing things in the most simplest manner optimally, and that is to use a greedy approach. So let's say that this is the example that we are currently given. Now notice that whenever we are iterating over any particular triplet, we should always compare it with the target to determine that is this a triplet of interest or not. And the comparison should only contain two items. First thing is that whether if each of these three values, if all of these are lesser than the target value, then and then only it is a triplet of interest for us. Otherwise we need to move on to the next triplet. And why? Let's try to understand. Let's say that currently we are given a triplet 2, 6 and 5, and we are given the target to be 4, 6, 6. Okay, so in this case we can notice that every single value, so 2, 6 and 5 comparing with 4, 6 and 6, notice that every single value inside this triplet is actually less than or equal to the target triplet that we have, which means this can be a potential candidate that we can use in future for the merge operation. Now the thing is, if we are going to use this for the merge operation, then we should just put this on a side, and noting that we found a triplet which can be of potential use to us. At the same time, we should also have to keep track of a variable that what if we already found a triplet that we are all anyways going to find the optimal solution with. And in order to do that, we will have to basically compare the given triplet with the target triplet and keep track of the maximum value that we are able to generate from both of these triplets and just store that information. So let's say in this case we can notice that because this is a triplet of interest, then we are going to store the maximum value amongst these two and these two. And notice we are having a condition that this has to be smaller or equal to the target, which means either we can have all the values that are going to be smaller than target, or it is equal to target, which means we would never exceed target in this approach. So in the maximum variable we are going to compare the max values. So we are going to, this is going to be 4, this is going to be 6, and once again this is going to be 6. Okay, so we took care of this triplet. Now let's move on to the next triplet. Once again in the next triplet we have a value called 7, 4 and 6. Now notice that for this one, for 7, 4 and 6, we did found a triplet that we currently have over here that is of potential interest could to target or not. So notice that the very first value 7 and 4, so 7 is greater than 4, which means if we do merge operation with this triplet, then we are always going to have first value that is going to be greater than the target value, which means this would not be a use for us. So we should just simply skip over this triplet because we should not use this triplet to merge with anyone else. Okay, next we have this value 4, 4 and 6. So let's try to see that if we use this value, what is going to be the expected range or expected triplets we are going to be find. So in this case, basically once again we compare 4 with 4, so this is equal, 4 with 6, so this is lesser, and 6 with 6, so this is equal. So once again this can be a potential triplet that we can use. So now let's try to do the max operation in this case. So the current values are 4, 4 and 6. So we are doing 4, 4 and 6, and we are comparing it with the target, which is 4, 6 and 4. So now notice that maximum amongst these two is going to be 4. So we add 4 over here. Maximum amongst these two once again is going to be 6, and maximum amongst these two is going to be 6. And now in the end we are going to have a maximum variable that is going to contain values 4, 6 and 6 over here. And meanwhile we are going to have another target value that we were trying to achieve, and that was also 4, 6 and 6. So notice that because both of these values match, we can simply say that yes, there exists a triplet that we can generate by merging other triplets. And if we cannot find this maximum value, which means there does not exist a triplet that is of good use to us, so in that case we would have returned false. So if you see approach for this solution, then we can simply run it in big O of n, where n defines the number of triplets, and in terms of space complexity we are not adding any additional space, so this is going to be big O of 1 as well. So I hope this solution makes sense. Now let's quickly see the coding approach. The coding solution is quite straightforward. First, we are going to initialize an array with size 3, naming it as max values. Then we are going to iterate over every single triplet that we are given inside our triplets 2D array. And for each of the pair, we are going to check that if the current triplet that we have, will it be contributing towards making the target or not. So we are checking that if the given triplet position, the first value is less than the target, less than or equal to target, second value is less than or equal to target, and third value is less than or equal to target. If that is the case, then we are going to simply update the maximum values we have been able to achieve based on the given current triplet and the target values. Now remember, because we are considering triplet values to be less than or equal, which means if the only case where we have the target value set as it is if the given triplet value is also same as target value, that subsequent value. So we are going to store the values for all three parameters and keep on repeating the same process for every single given triplets in a greedy fashion. In the end, we simply have to check that whether the three values present inside our array match the target values that are present. If that is the case, we can return true, otherwise we can return false. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, and it is pretty fast. So I will be posting the solution in the comments, so you can check it out from there. Thank you. So the LeetCode problem we are going to solve today is called partition labels, and we can see that this one is a pretty popular LeetCode problem. Basically, we are given a string that we want to partition into as many parts as possible so that every single letter in each of the partition appears at most at one and not in any other partition. Now note that the partition is done such that after concatenating all the parts in order, the resulting string would be string S. So we cannot just partition randomly from the middle of the string. It has to be sequential. Now let's try to understand it with some examples. Let's say that we are given a scenario like this. Now we want to create maximum partition where every single character only appears in just one partition. So in this case, we can create a partition with this A, B, A, because remember A appears over here and A appears over here. So they both has to be in the same partition. And then we can create one more partition called D, and notice that if we combine this ABAD, then we would get the resulting string S. Same way for this one, we can create a partition AA because that would fulfill that all the characters of A are present. Then we can create a partition called BCDB because B is present over here and here, so it has to be part of the same partition. Now for this third one, we can create a partition AA. We can also create a partition CC, and then we would be creating an individual partition called B, and then there would be a partition called D. And this is what we need to return. So basically in the answer, we don't need to return something like this, the exact partitions, but we only need to return the size of those partitions. So for this example, we would return answers such as 2 and then 2 and then 1 and 1. So these are going to be the sizes. Now the brute force solution is actually quite straightforward. We simply take a character, We iterate over every single remaining values. We see that what is the last point where the character occurs, and then tries to create a partition of that size, and we keep on repeating the same process again and again for every single remaining characters, and so on and so forth. Eventually we would get all the necessary partitions. But the thing is, this is not the most optimal approach, and we can see that this one would run in big O of n square time, so we can do something better. And let's try to find an easy and simplest solution that we can derive from originally brainstorming our brute force approach, and that is to use the greedy way to solve this problem. We are going to be very efficient in picking and choosing how we are going to go forward by selecting the partition. Now the first rule to select any particular partition is to identify that for any particular character the starting value doesn't matter, but what is going to be the last occurrence for that particular character matters the most. Because once we identify that a character is part of any partition, then we will have to figure out that what is going to be the last place this character is going to be placed at. That is number one thing. Second thing is, apart from being like finding the last position, we would also have to figure out that this partition makes sense if all the characters present in this particular partition has the last point either being this value or before that. I repeat that this can only be a partition if every single unique character that there are present, their last point or the last occurrence would either be less than the index value that we are currently at. So based on using these two values and some additional variables like the partition end time and the partition starting variable, we can actually solve this problem very easily and very efficiently. So let's first identify our first approach, that is to find the last occurrence for every single unique character. So let's say that for A the last occurrence is going to be index number 2. For B the last occurrence is going to be index position number 1. Okay, so now we have our list of last occurrences for every single character. After that we can start iterating over any particular given character in this simple fashion in this given string, and all we will have to compare is that what is going to be the last occurrence compared to its current ith position, and whichever is going to be the greater value, we are going to put it as part of our partition end, because that has to be the partition end, and whenever we find a greater value we would update the partition end that we are currently at. On top of it, if we are at a position where the given ith value is equal to the partition end, which means we found out a correct partition, so no other character exists that has a greater last occurrence compared to our current value, and we can mark it as a partition, so we can just add it to our result list. So let's say that we are also creating a result list to store all the results. Okay, and let's just follow our approach. So first we identified value number A. So for value number A, the last occurrence is located at position number 2, so the partition end has to be at least value 2, so we'll mark it over here. Okay, and then the partition start initially is going to be 0. Then we are going to iterate over value number B. What is the partition end? Partition end is 1. 1 is lesser than value number 2, so which means we don't need to update the partition end. Next current ith value we are at is value number A, that is located at position number 2. So in this case, because I is equal to 2 and the partition end is also going to be 2, we can actually mark these values inside the result. So currently in the result we are going to have 3 characters, so that we can determine by finding out position start minus position end minus position start plus 1. We'll have to add plus 1 because we are starting with a 0 index. So in this case, first result is going to be value number 3. After that we are going to update the position start value to the partition 3 number 3, and we are going to reset the value of partition end. Okay, so currently the partition end would be dependent on this particular value C. Okay, so C for the current C value, the last occurrence is 6 and previous value was 2, but 6 is greater, so we are going to mark 6 as the current partition end. Now for this D, the partition end is going to be 4, so 4 is lesser than 6, so we don't need to do anything over here. Same way 5 is lesser than 6, so we don't need to do anything over here. Now we are at I is equal to 6 and current partition end ends at 6 as well. So in this case, once again we are going to do partition end minus partition start plus 1, so we will have 4 characters in this second partition as well, which are these 4 characters. Now we are at value, now the new partition end is going to be value number 7. Okay, so we mark partition value number 7, and lucky for us, the value we are iterating over for y is also valued at value number 7. And by the way, the partition start would also be updated to value number 7. So since we found I is equal to 7 and the partition ending position is also 7, so we can mark this as a new partition, and this is only going to contain one element, and same way this is also going to contain one more element, and we can mark it as the answer. And this is the whole solution basically. Let's do a quick recap. First, we created an array that is going to store the last occurrences of every single character. Once we have that, then we can simply go over all of these characters one by one, comparing with the last occurrence, the current position end date and position start value, and we can maintain a result array. And if you see the coding solution, this would become much more sense that how does all of this operates. Now if we calculate the time and space complexity, in this case the time complexity is going to be big O of n, because we will have to iterate over the given input string couple of times, but overall it's just a linear update or the linear traversal. And the space complexity is also going to be big O of n, or this can be big O of 1 depending on how you perceive it, because if we are only talking about the lower case English letters, then there are only 26 possibilities, and we can use a constant amount of space to solve this problem. So you can debate this with your interviewer that on how they wants to perceive it, but basically both the approaches would be correct. So the coding solution is going to be quite straightforward. First, we are going to check that what is the last occurrence of every single character, and since there are only 26 characters that could be in string s, we can use a simple array instead of using a hash map. We can iterate over every single characters and then just mark their position with the appropriate ith position and just store it in our array called last occurrence. Step 2 is to iterate through the string and determine the partition. For that, we will need to have a variable to store the answer, and we are going to initialize our array list called result. We also need a couple of variables to keep track of the partition end and partition start pointers. So once we have everything set, we are simply going to iterate over the given integer, and we are going to mark the current partition end as the maximum value between the current partition end that we have been able to find and the maximum value of the last occurrence of the current character we are at. Then if at any given point we identify that the given I is actually equal to partition end, then we can simply find we have simply found a partition where there does not exist any more characters further than that point. So we can add that value to the result, and then we can start working with our next partition. So we can just update the value of the partition start, and then we can keep on repeating the same process, and in the end we can simply return our result array list. So let's try to run this code. So the solution is working as expected. Let's submit this code. And our code beats 91% of all the other solutions, which is excellent. And I would be posting this in the comments, so you can go and check it out from there. Thank you. So the LeetCode problem we are going to solve now is called valid parentheses string. We can see that this one is a LeetCode medium problem and also a very well-liked problem. Basically, we are given a string s that contains only 3 types of characters: open parentheses, closed parentheses, and a star. Now we need to return true if the given string is valid, and there are some definitions given on what is valid. Basically, any left parentheses must have a corresponding right parentheses. That's fair. Same way, any right parentheses must have a corresponding left parentheses. Next point is that left parentheses means opening parentheses must go before the corresponding closing parentheses. So this is valid, but if we have like this, then this is not valid. Okay. And last one is that if we are given star at any moment, then we can consider star to be whatever we want. So we can treat it as a right parentheses or a closing parentheses or an open parentheses, or we can also consider it as an empty string, so that makes no difference. So let's try to see some examples. Suppose we are given a parentheses like this one is a valid. If we are given a parentheses like this, once again this is a valid. If we are given a parentheses that contains star, once again this is a valid. In this case, we are treating the star to be an empty string, which means we are basically left with this. We can also say that this is also a valid string, and so on and so forth. So the only scenarios where it is not valid is if we are dealing with number of like out of order parentheses, or we are dealing with multiple parentheses of being like this and only one parenthesis like this. So this is also not valid. So let's try to understand the most common logic on how we can pursue solving this problem. Now we know that if we are only dealing with working with problems that only contains parentheses, we can simply use a stack and solve this problem very easily, very efficiently. There are like a lot of different examples of that. I would not go in depth in this case, because the important thing for this problem is this asterisk. So whenever we are dealing with an asterisk, we have three possibilities. We can either consider it to be an open parenthesis, we can consider it to be an empty string, or we can consider it to be a closed parenthesis. So in each of the cases, let's say that if we are dealing with multiple stars, there can be many possible combinations and permutations that we should be able to make. But that adds more and more complexity to our problem, because let's say that we are given a string like this. Now in this case, we need to basically have option over here to choose three different entries for each three different options. We have another way to choose three more different options, and so on and so forth. So we can make many different possible combinations. So we'll have to do things smartly. So one solution I'm suggesting in this case is that we use greedy approach, and basically we iterate over the given input in just a single fashion, and we keep track of the number of open parentheses. And we also define that what is the maximum number of open parentheses that we currently can have depending on the star value, and what is going to be the minimum number of open parentheses we can have depending on the given star value. Now there are two possibilities. One possibility is that for any particular star, if we treat it as an open parenthesis, which means there is one more open parenthesis left for us to deal with. So in that case, we can add basically that value to the max pair character, or we can treat this star as an empty string or a closed parenthesis. In this case, we have one less open parenthesis that we need to deal with. So in this case, we would update the value for the minimum character. So let me just walk you through the solution I'm suggesting. Let's say that we are currently given an input like this. So in this case, we are going to simply have a few rules for two variables that I'm suggesting. First variable, the variable's name is maximum open, okay, and second one is minimum open. Now for each of this, we are keeping track that what are the maximum number of untouched open parentheses we have, and what is the minimum number of untouched open parentheses we have. The logic is quite straightforward. We are simply going to follow few rules. If the given input character is an open parenthesis, then we will have to increment at both the places. So we are going to increment at max and min. If it is a closed parenthesis, which means there is one less open parenthesis for us to deal with. So in this case, we would decrement at both minimum open and maximum open variables. And we are going to initialize these with value 0. And if the given value is star, in this case, we have two possibilities. So there is one possibility, we treat this as an open parenthesis, or we treat this as an closed parenthesis or an empty string. So if we are treating it as an open parenthesis, which means there is one more open parenthesis left for us to check. So we are going to increment at our max open. So for max open, we are going to update the value whenever we encounter a star. And whenever we encounter a star, we can also treat it as a closing bracket. So we will decrement the value at the minimum variable that we have stored. And these are the rules that we are going to follow. Now there are a couple of conditions that would allow us to solve this problem. Basically find the loose cases. So first case is that if at any given point we identify that given number of maximum open parentheses go into negative, which means that there are too few open parentheses and too many unopened parentheses. Because remember, when this can go into negative, whenever we have a closed parentheses, then we decrement the value. So let's say that if for the given example, if the first character in itself is a closed parentheses, then we would have decremented the value for maximum open and minimum open. So in this case, the maximum open would have become negative. So we can say that now, even if this is like the most valid string, this is always going to be not valid, because it has an open parenthesis where we don't have a corresponding closed parenthesis. So this is one scenario that we can keep track of. Second scenario is that at the end, our goal is to ensure that there are no untouched or there are no left open parentheses. So let's say that we iterate over the entire given input using these three rules, and we find that there are no open parentheses, which means the min open is 0. Then we can simply return 0 as the answer. Now next thing is we have a possibility where if we are encountering a star, we are basically reducing the value of the min parameter. So min parameter can still go into negative, but the thing is this would not directly say that we are dealing with an invalid string. So in this case, if for some reason the minimum variable goes negative, then we are simply going to just start it back to 0, treating that there are no open parentheses left for us to check. And I know that there are a lot of rules that I just talked about, but the thing is, if you just understood what we are trying to do with the example, then it would make perfect sense. So let's say that this is our minimum variable, this is going to be our maximum variable, and we are going to start iterating in this fashion. So first we identify an open parentheses, which means we are going to increment the value for both in min and max. So currently both values are going to be 1. Once again open parentheses, so both values are going to be 2, and once again open parentheses, both values are going to be 3. Now notice what these values define is that what is the minimum number of open parentheses that we will have to deal with, and what is the maximum number of open parentheses that we have to deal with. So far we haven't encountered any star, so that's why the numbers are same amongst both of them. Now we encountered a star. So we can treat the star as either an open parentheses or a dot or a close parentheses. If it's a one more open parentheses, then we would have 4 open parentheses that we will need to deal with. And if we treat this as a closed parentheses, then we will only have to basically deal with one less open parentheses, because we can basically close these two parentheses. So in this case, this value would become 2. And let's try to see this by different examples. So first 3 values we have as open. Then we have a star over here. So what are the 2 possibilities? First possibility is that we create a close parentheses. So in this case, this becomes a close parentheses. So how many number of open parentheses that we are left to deal with? 2, which we are representing over here. If we treat this as an open parentheses, in this case, how many number of maximum open parentheses that we will have to deal with? 4, and that we are capturing over here. And this is the whole logic of the entire solution. So now let's continue moving forward. So once again, we identified one more star. So once again, the minimum variable is going to be decreased by 1. So this would become 1, and maximum variable would be increased by 1. So this would become 5. And now we encounter a closing parenthesis. So whenever we encounter a closing parenthesis, basically we are reducing the values at both minimum and maximum values. So this would become 0 and this would become 4. Now, because we reach to the end of the loop, we don't care about this maximum variable. This maximum variable is only there to keep track of if this goes into negative or not. If it does goes into the negative, which means we can stop immediately and return false. If that is not the case, we check the value of this minimum variable, and if because this is 0, so in this case we can return true for this one, and that this is a valid string. So this is the whole idea behind the solution. Now if we see time and space complexity, time complexity is going to be big O of n because it's quite straightforward. Space complexity is going to be big O of 1 because apart from using couple of variables, we are not using any extra space. So this is a wonderful solution. And now let's quickly see the coding solution for this one. So the coding solution is quite straightforward. First, we are going to initialize a couple of variables called minimum open and maximum open. This is to keep track of the minimum possible open parentheses and maximum possible open parentheses. Now we are going to start iterating over character by character inside our given input string s. And for every single character, we are going to check that if there is an open parenthesis, then we need to increment both min open and max open. Otherwise, if it is a closing parentheses, then we need to decrement both min open and max open. And if that is not the case, which means we have identified a star value, in this case we will need to decrement the minimum open because we are treating it as a closing bracket or an empty string, or we need to increment the maximum open because we are treating it as open left parentheses. Now at any given moment we realize that the max open is less than 0, which means we can return false immediately because there are just way too many closing parentheses compared to the subsequent open parentheses. Now if that is not the case, then we are going to check that at any given point, if the min open becomes negative, then we are simply going to initialize the value starting from 0. So min open can go into negative, but we don't care about that. Now in the end, we simply need to check that if the given min open is equal to 0, which means that there are no minimum possible left open parentheses. So in this case, we can return true, saying that the given parentheses string is valid. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And code beats 100% of all the other solutions, which is exceptional. So once again, I would be posting this solution in the GitHub repository that we have created, so you can find it from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCode until we get there. Today we are going to do a very interesting LeetCode problem, interest interval. And if you see the number of companies that have asked this question, it's really amazing. The companies like Google, LinkedIn, Amazon, Robinhood, Facebook, Uber, Apple, Twitter, Microsoft, ServiceNow, Bloomberg, and Goldman Sachs. Like these are, if you see the description of my channel, these are my dream companies that I want to get a job of. So that's why I'm doing these questions and I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and essentially we are given an array of non-overlapping intervals. This is a multi-dimensional array. It's a 2D array, and at any given cell, essentially we are given the value like start and end, which indicates that there exists an interval between those times. Now our aim is that we need to insert a new interval into the list, into the array of intervals that we are already given, and we need to maintain this non-overlapping quality of the intervals. So if we try to understand this with an example, suppose over here we are given a set of intervals like 1, 3, 6, 9. So we are given an interval like this 1, 2, 3. This is already given, and we are also given another interval like 6 to 9, and we need to insert a new interval called 2 to 5. So if I draw it on paper, it would be something like this. So 2 would fall over here and 5 would fall over here, and this is the new interval that we are trying to insert in this original existing interval. So how can we insert this new interval? Well, the answer is actually simple. Essentially what we are going to create a new interval is that we will start an interval at position number 1. Then from 1 we will have an interval all the way up until the position number 5, and then we will have another interval from position number 6 and all the way to position number 9, and this would be the two intervals that we will have to take care of. Now the thing is, in this problem we can clearly identify that why did we come up with this approach, because we wanted to make sure that we do not have any overlapping intervals. So that is why when we found out that this is the existing interval and this is the new interval that we are trying to achieve, if we wanted to insert this one, there exists an overlap between these positions, between this 2 and 3. So that's why, because there was an overlap, we actually chose to merge these two intervals, and we created a new interval like this. And for this one, this had no concern with the existing with the coming of new interval, so that's why we left it as it is. So let's see that what could be the different approaches we can take, what could be the different scenarios, and how we need to behave in any single scenario of them. And essentially that would be our solution. So first of all, if suppose we are given a number series like this, and we are given a list of intervals like this, that there exists an interval between this value 2 to 4, there exists another interval between this value 8 to 10, and 13 to 15. Now let's see that where different set of intervals can be entered. So suppose first of all we are given an interval like this that is not overlapping with, or that is not in conflict with any existing interval. So let's see that what would be the scenario in that case. Suppose we are given an interval like this, that from 0 to 1 we are given an interval like this. Now if we see this new interval, it has no sort of conflict with any of the existing intervals. If we wanted to add this to our array of intervals, it would be just pretty simple. We simply create a new interval like this, 0 to 1, and then return whatever all these values are, and this would be our answer. So we would be done in this case. There won't be any issue. But suppose if this is not at the first or at the beginning of the intervals, if this is at the end of an intervals, so suppose this particular new interval that we are trying to enter, suppose we are given some interval like this, that from 16 to 17 we are given an interval. So suppose we are given an interval from 16 to 17, something like this. Now in this case, what would be the approach? Essentially we would be doing the same thing. What we would be doing is we would be transferring this interval on top of whatever the existing intervals we got. And how we are going to do it, basically we are going to start traversing towards the original given input. We are going to see that, okay, where is the starting point of this new interval, and where this new interval can fit inside the existing set of intervals that we have. Now in order to check that, essentially what would be helpful? It would be helpful if we had a sorted set of intervals, and in this scenario all the intervals that we are given, they are already sorted. So that is why which works in our favor. So which means it becomes really easy for understand that where this new interval we wanted to shift into. And in this case, so we will start traversing. We will first see that, okay, this is the value 2, this is 16, we don't care, so we move forward. Again we are done with this interval. Now what is the next start point of this interval? This is 8 and this is 10 and this is 16. So again it doesn't matter, there is no overlap, so we can put this in the answer. Again this is 15, this is 13, this is 15 and this is 16. So again there is no overlap, so we can put this in the answer as well. And then we find out that after 15 there are no intervals, and we need to enter this new interval 16 and 17. So we simply add it over here from 16 to 17, and we add this to our array of answers as well, and we return these 4 as a new set of intervals. Now suppose somewhere in the middle, rather than this one, these are like easy scenarios where we are given at the beginning or at the end. Suppose we are given something somewhere in the middle. So suppose we are given a new interval that we have to take care of, something like this, that it is from 5 to 7. This is the new interval that we are trying to insert. What should be the approach in this case? Again we are going to repeat the same case over here. This is the value 5 and 7. And now what we are going to do is we will start iterating over this given input. We will see that, okay, first value is 2 and the end of this interval is at 4. So this is 2 and 4, and the new interval starting point is 5, which means there is no conflict so far. So we would add this to our set of answers. Now from this 4 we reach at this 5, and at this 5 is the starting point of this new interval. So we check in our original set of intervals that from 5 to 7 does there exist any conflict. So from 5 to 7 actually there is no conflict in our original interval. So if there is no conflict, we simply add a new interval over here from 5 to 7, add it to our list of answers. And because we have reached the end of our new interval, right? We have reached the end of our new interval, which means what this dictates is that from this point forward, there cannot be any existing interval that could be causing any sort of overlap with this, with the arrival of this new interval. So whatever the answer or whatever the list of intervals we are given beyond this point, once we have already entered this new interval, we can simply add these to our answer array, and this would be our solution. So this would make our lives very easy, and that is how we would be able to handle this scenario as well, right? Now so far all the 3 scenarios we saw, we entered the value at the beginning, at the end, or somewhere in the middle, but in all the cases there was no conflict between existing intervals with the arrival of new intervals. Now suppose the new interval that we are trying to enter, that new interval is something like 3 to 8. Suppose it's something like this, that now we need to take care of this scenario where we are handling this new interval, and which is from 3 to 8. So what should be the approach in this case? Well, the approach is actually quite simple. We will start iterating over our input. We will find all the intervals. So first we find that what is the start point of this interval. So the start point of this interval is 2. And what is the end point of this interval? The end point of this interval is 4. Now what is and every time with the end interval, we are going to compare the start interval of the new interval that we are trying to insert. So the start interval of this one is 3 and this one is 4, which means that we know that we will have to enter this 3 over here, and there exists a conflict. Now since we have identified a conflicting scenario, what should be our approach? Well, our approach should be simple, that we are going to take a look at this particular interval and we are going to take a look at this particular interval. Now there exists a conflict. Because there exists a conflict, we are going to check the starting points of both the intervals. Now in terms of starting points of both intervals, this one is smaller than this one. So whatever is the smaller, we are going to treat this as the starting point of this new interval that we are trying to enter, because there exists an overlap amongst these values. So we are taking care of the overlap. So that's why this would be our starting point. This would be the start of this new interval, and we are going to drag this new interval up until the end of this point. So up until the end of this point, when we come, we find out that it comes up until all the way to value number 8. Now in this scenario, we did not had anything in the middle, but if we did had anything in the middle, that would have been merged by this new interval, right? But the thing is, even when we come at this position number 8, we see that actually the position number 8 is start of another interval. So which is this one. So if it is start of this interval, we cannot just treat this as a separate interval. I mean, what I'm trying to say is we cannot have an interval like from 2 to 8 is one interval, and from 8 to 10 another interval, because this 8 is actually a conflicting point, and it is because it is a connecting point, these two intervals also needs to be merged. So because this 8 is a connecting point, we are going to merge this interval with this new interval that we are trying to create, and essentially this interval from 8 to 10 will also be dissolved by this new interval, and we would have an answer like this in this scenario, that we would have a newly created interval from 2 to 10. This would be for one interval where we have, and this would be another interval, because remember, now we have already entered this one, which means all the values beyond this point are not part of our concern. We can simply add it to our list. And in this scenario, the second interval would be from 13 to 15, and this would be our answer that we are going to return. So this is one conflicting scenario, and I mentioned that how we are going to tackle it. So essentially the different test cases in this case we can have is that we can either have a scenario where the item lies somewhere between beginning or at the end, where it is not conflicting with anyone, or it can be existing somewhere in the middle where it is not overlapping with any other interval, or it can be a case where it conflicts with some intervals, with one interval or more than one intervals. In either scenario, what we are going to do is, the moment we find that there exists a conflict, we are going to see that what is the start point, what is the lower value amongst these two. So because the lower value is 2, we are going to start this new interval starting from the position number 2. Okay, now for the end position, again we are going to do the same thing. We are going to check that what is the end position of this existing interval and what is the end position of this new interval, and in the end position we will have to check the maximum value, because the interval we are trying to create should be the size of biggest interval that we could create, which is not overlapping with any other interval. So that's why we would have an interval that is maximum amongst these two ending values. So these two ending values, the value is 8. So we would have an interval from 2 to 8 so far. But the thing is, this is not the end yet, because when we come at this 8, we will still have to check for the conflicting scenario. So over here we would have the starting, we would have two intervals like this, and in the two intervals we have the 8 value as the value number 8 as common. So we are going to merge these two as well, and in this case we are going to choose the biggest value we can find as 10, and we are actually, rather than having an interval from 2 to 8, we would actually have an interval from 2 to 10, and this is the critical part to understand. And this is basically our solution. Essentially we are using the greedy approach, but this is all. We don't need to do anything else. And if we calculate the time and space complexity, the time complexity in this case would be actually big O of n, because at any point for this new interval we would need to find that what should be the entry point of this new interval, and then we will check for the conflicting scenario. If there exists a conflict scenario, we will find a way to put it there. If there does not exist any conflicting scenario, well, good for us. In terms of space complexity, well, for the space complexity it would also be big O of n, because we will have to create a new array of list of intervals that we are going to return. So we will have to create a new two-dimensional array, something like this in this scenario, from where the answer would be 2 to 10 and 13 to 15. So this would be our new array that we are creating, and we would be returning that. So that's why that explains the space complexity. And yeah, this would be the solution. Now the question is, where can you use these kinds of approaches? Like, what is the point of having this question at the first place? And actually this is a very interesting question. It has a lot of practical applications. Practical applications is like, suppose you are trying to design an app where you need to maintain some sort of calendar, or you need to maintain scheduling. So these are very practical, very real life applications. Google Mail, Outlook, all the companies, they all use this mechanism. So if we know that where we need to insert an interval where we are not creating any conflict, it could be a conflict between shifts of two employees working for a factory, or it could be the interval between two trains going through a station. So like, yeah, these are real life practical examples, and that's why that justifies the number of companies that are asking this question. So first of all, we are going to initialize some variables, and we are going to create a new start and new end for the given new interval. We are also going to create two pointers, left and right, and left would be at the 0th position inside the given intervals, and right would be the size of the given intervals. We are also going to create a linked list to store all the output, and then we are going to convert it into the array. So now first of all, we are going to add all the non-overlapping intervals that come before the new start. So we are going to create a while loop. Okay, now inside our given list, we will need to add the new interval. So in order to add the new interval, we will have to check two conditions. There could be two possibilities. There might be an overlap, or there could not be an overlap. So we'll have to take care of both of them. So first we are going to create a parameter called interval, and we are going to store all the value inside this parameter. Now we are going to check the condition that if the current position where we need to insert the new interval, does there exist an overlap or not. So if there is no overlap, we can just simply add the new interval. So if that's the case, we can just simply add the new interval. If that is not the case, which means there exists an overlap. So if there is an overlap, we will have to first of all check that what entry what should be the starting point and ending point of the overlapping character, and that we can define by choosing the minimum out of the starting values or the maximum out of ending values. So first of all, we are going to add the last value we have in our linked list inside this new interval variable that we created. And now we are going to check that what should be the endpoint, and we would add the new entry to our linked list. Okay, now we might have to merge all the elements that are after that came because we added this new interval. So we will take care of the merge scenario. And if there exists an interval, we will do the same thing that we did before. So essentially we can just repeat this process. Yeah, after this loop runs, we should have everything stored inside the linked list, so we can return the linked list, but we will have to convert the linked list to an array. This should be our answer. Let's try to run the code. It seems like our solution is working. Let's try to submit this code. Oh, we will have to check for this end variable here, so that's why. Okay, looks like our solution is working, and it's actually pretty fast compared to a lot of other solutions. And even in terms of space complexity, we are also saving a lot of time, a lot of space as well. So I would be posting this in the comments. You can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCode until we get there. If there is any question that can get you in the FAANG, it's this one that we are going to solve today. Because if you just see that the number of companies that have asked this question, it's just out of this world. This question has been asked by hundreds of companies, literally hundreds of times. You can see over here that like Facebook and Amazon, they both have asked this question recently over 100 times in their interviews. So you can imagine the severity and the importance of this problem that we are going to solve. So apart from Facebook and Amazon, if we look at the number of companies that have asked this question, there are companies like Google, Salesforce, Microsoft, Bloomberg, Apple, Uber, LinkedIn, IBM, VMware, Walmart, TikTok, Adobe, Twitter, ByteDance, and then there are companies like Yahoo, PayPal, Wish, Goldman Sachs, Robinhood, and also Plantier, Square, and Netflix. So these are all one of my dream companies where I want to get a job. That's why I'm making these videos, and that's why I made this channel. So I would be paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem, and it is one of the most liked problems on LeetCode, and that's why a lot of companies likes to ask this problem. So essentially we are given an array of intervals where every single entry inside the interval mentions that there exists a start point and an end point of that particular interval. Now we need to iterate over all of the intervals, and then we will need to merge all the overlapping intervals. And we need to return an array of non-overlapping intervals from this given input, and that would be our solution. So if we try to understand this with an example, suppose we are given some set of intervals like this. Now let's try to mention them on this number sequence that we have drawn out. Now over here, our aim is to return all the non-overlapping intervals, and if there exists an overlap, we will need to merge those two intervals. So first of all, we will have to identify that what are those two intervals where we can see an overlap. So essentially, if we look at the start values of this interval, so the start value over here is 1 and 3. And if we look at the start value of this second interval, the start value is actually 2 and 6. And over here, we can clearly see that there exists an interval amongst these values. And these are the two intervals that are causing an overlap, and we will have to merge them. Now the question is, first of all, we need to know that why we were able to calculate that there exists an overlap over here based on the given input. Like this is a pictorial representation, we can clearly see that why there is an overlap, but in terms of computer we will need to dictate some sort of mechanism. So essentially we can say over here is that at any point, if we start iterating over any number of intervals, and if we identify that for those particular intervals, if the starting value, so in this case the starting value is actually 2, if this starting value falls between any interval, so because this 2 currently falls in between this 1 2 3, this first interval is 1 2 3, and over here the starting value of this new interval actually falls between those places. And the moment we identify that okay, this 2 falls between this 1 and 3 interval, so we know that okay, this interval that starts at 2, so this 2 to 6 is also causing an overlap between this given input interval, and we'll need to merge them. So this would be our condition to identify that at any moment, at any interval, we are trying to see that whether it intersects with some other interval or not. What we are going to check is we are going to see that suppose this value is the start value. So we are going to see that this start value, if that meets, if that is greater than whatever the interval start we are checking and whatever the interval end we are checking for. If this condition is true, we can determine that there exists an overlap. And now since we have already identified that there is an overlap, we'll need to resolve that. So in order to resolve that, how we will resolve that is, we will create an interval from this value number 1 to value number 6. So essentially we are merging both of these intervals. And what is the condition we are using to merge these two intervals is that we are going to check that, okay, for the starting point of the new interval, what is the minimum value amongst both the start values. So in this case over here, the first start value is 1 and second start value is 2. So the minimum value is actually 1. So we create an interval that starts at position number 1, and for the end value there is this 3 and 6. So we compare this value 3 and we compare the value 6, and we identify that, okay, 6 is greater in this case. So for the end value we are going to pick the maximum value amongst two values. So we are going to create a new interval like this, that is from 1 to 6, and then essentially we have taken care of these two overlapping intervals. And for this one, this 8 to 10 and this 15 to 18, these two intervals, they are not causing any kind of overlap, so we can just directly put them as it is inside our answer. So in this case, if we try to calculate that what would be our answer, the answer is actually quite simple. Our answer in this case is going to be an interval from 1 to 6, and this is the merge interval. Second interval is going to be 8 to 10, and the third interval is going to be 15 to 18. So this would be our solution, and we can simply return this one. Let's try to understand the same problem with another example that is given over here. So in the second example, we are only given two intervals, 1 to 4. So this is one interval, 1 to 4. So the question comes that, are they overlapping integers? And the answer is yes. Why? Because if we see at this value number 4, actually 4 is connecting point for both the intervals. So 4 is the ending point for the interval 1, and it is the starting point for the interval number 2. So in this case, we actually need to merge these two intervals, and we will have to create an interval like this, that is from value number 1 to 5. And again, we are going to use the same logic. The logic is going to be that over here the values were 1 to 4, and over here the values were 4 to 5. So for the starting values, we are going to choose the lesser value, and for the ending values, we are going to pick the maximum value. So maximum value in the lesser value in this case is going to be 1, and maximum value is going to be 5. So this would be our intervals, and these are all the scenarios that we need to take care of. So suppose we are given a custom example like this. Let's see that what should be the solution. And always remember that it is really important for any programming interview that you come up with your own custom examples. It shows that you have the ability to think about all the different kinds of test cases, and you can come up with some unit test on your own. So over here our aim is to find that all the non-overlapping integers. Now to find all the non-overlapping integers, we already know that what is the condition, that how can we determine that any particular value is actually causing an overlap. And the way we can do it is that by checking the start value and comparing it with that whether it exists somewhere in between any given interval. The question is, previous two examples we saw, they were already sorted. So all the starting values were already in a sorted manner. So that's why it was really easy for us to identify that whether there exists an overlap or not. But nowhere in the sequence we are told that all the input should be sorted. So that's why that makes things a little bit more complicated, and let's see that how it does so. So over here, suppose we are given an input 4 to 6. So we can create a line over here that, okay, there exists an interval like this from 4 to 6. Now second one is 11 to 15. So again, there is an input like this, 11 to 15. Next one is 7 to 9. So there exists an input from 7 to 9. And this next input is 2 to 5. So we know that there is an overlap, but we are going to just draw it over here. And the next one is 13 to 16. So over here we can clearly see that there are two places where there exists an in overlap, but we don't know that yet, right? Because the input is not sorted, and we will have to identify it by ourselves. So how we are going to actually identify? Well, essentially we are going to use the same logic. We are going to check that whether the start value falls in between any of the interval. If it does, we are going to determine that, okay, that so if it does, so we know that this particular interval is in conflict with that interval, and then we are going to have to merge it. So let's try to do that. So over here we are comparing this value number 4, that is the starting value, First of all, we are going to check that whether 4 falls between 11 to 15. Well, it does not, so we are good with this. Whether 4 falls between 7 to 9, it does not, so we are good. But over here 4 actually falls between 2 to 5, because 2 is actually less than 4 and 4 is actually less than the 5. So we know that 4 actually exists over here, which means there exists a conflict between this and these two intervals. So we will have to resolve this conflict. How we are going to resolve this conflict? Well, of course, we are going to create a new interval. So starting value is going to be the lesser of both of them. So we are going to have a starting value that is at 2, and for the ending value it's going to be greater of both of them. So the ending value is going to be 6. So we are going to create a new interval like this, that is from this value number 2 to value number 6, and we are good with this one. So essentially we have merged these two intervals, so we can just simply mention that okay, these two are merged or these two are taken care of, so we don't have to worry about them anymore. And now we are done with essentially these two intervals, right? And we have in our answer we already have this this new interval stored. Now let's see that how can we move forward. So again, for this 11 to 15, again we will have to repeat the same process. So we check that whether this 11 falls in between some interval. So first of all, we compare this 11 with this 4 and 6. So it does not fall in between. And also remember that because we are done over here doesn't mean that there could not be any more overlaps that we cannot take care of. So we might have to do it. So that's why we are going to compare again all the values. So 11 does not fall between 4 to 6, 11 does not fall between 7 to 9, 11 does not fall between this 2 to 5, and 11 does not fall between 13 to 16. So far we are good that okay, this 11 to 15, that is okay, we don't have any issue with that. Now we again check for the 7 to 9. So we check that whether this 7 falls in between somewhere. So 7 does not fall over here, it does not fall over here, it does not fall over here, and it does not fall over here. So this 7 to 9 is also good. 2 to 5 we have already checked. Okay, so this value number 2 does not fall anywhere, so we are good with this interval as well. Now again we are at this interval number 13. So for this interval number 13, it does not fall here, but it falls in this place. So we again have a conflict between this these two intervals. So 13 to 16, that is one interval, and second one interval is 11 to 15. There exists a conflict. So because there exists a conflict, we will have to resolve that, and we can mark these two as done. So we are going to create a new interval that is 11 and 16, which means lesser values of the starting values and greater values of the ending values, and this would be our new interval. So we can add this to our answer as well. So this would be 11 and 16. This is also our answer. And now we need to check that amongst these intervals, which were the ones that were not part of any overlapping series. So we know that this particular value 4 and 6 was part of an overlap, 2 and 5 was also part of an overlap, 11, 15 and 13, 16, they all were part of overlap, which we have taken care of with these two values. So this 7 and 9 was not part of any overlap, so we will have to add that to our answer as well, and we will add the 7 and 9 to our answer, and this would be our final answer in this case. Now the thing is, we are able to resolve this quite easily, right? We are able to generate the answer, we know all the logic and blah blah blah, we are able to identify the overlapping condition. If we calculate the time and space complexity in this case, the time complexity is actually big O of n square. Why n square? Because remember that for every single entity we are going to have to check all the remaining elements. Same goes for this one, that for every single entities we are going to have to check for all the other remaining values. So that causes n square work. The question is, can we do something better over here, and that rather than using this n square, can we bring down the time complexity? And the answer is yes. Okay, let's sort this given input. So the sorted result would be, now this is the sorted result. Now we need to identify that whether there exists a conflict or not. So it becomes really simple. What we are going to do is, we are always going to check the first value, and we are going to compare that whether the starting point of any value, if that is actually less than the ending point of the previous element. If that is the case, we would be able to identify that there exists a conflict. And always we are going to start checking from the second value, because for the first value we know that the first element is already the smallest value. So even if there exists a conflict between first two entities, this first one would always act as a starting point of the new merged variable. or the new merge interval. So let's try to do that. And over here we will start with the second position. We know that okay, this one is 4. We compare it with the last element of the previous interval. So last element of previous interval is 5. So we know that actually 4 is less than 5. In this case we know that there exists an overlap between these two values. Because there is an overlap, we can see that we need to take the minimum value amongst these two. So minimum value is actually 2. So we create a new interval starting at 2, and for the ending values we will have to check the last values. So the ending value in this case would be 6. So we will have a new interval like this. So let's draw a new interval like this on this number system. Now we are already done with these two values. Now we take a look at this value number 7. So again for the 7 we compare with the last element in this case. So 7 is actually greater than 6, which means there does not exist a conflict between these two values. So we can start creating a new interval from 7. And now again for this 11 we are going to compare it with the last element. So over here this value is 9. So 9 is actually less than 11, which means in this case there does not exist a conflict. So 7 to 9 is an interval in its own. We are good with this one. Now we have calculated this one. Now again over here this is 13 and this is 15. So we know that 13 is actually less than 15. So in this case there exists a conflict between these two values. So because there exists a conflict, we are going to do the same conflict resolution technique. We are amongst this 11 and 13 we are going to pick the smaller value. So smaller value is going to be 11. So we pick this one, and for this 15 and 16 we are going to pick the greater value. So 16 is the greater value. So again we are going to create an interval like this, that is from 11 to 16. So essentially we have taken care of two overlaps that existed between these two values and these two values, but we were able to identify them immediately. Why? Because all we have to do is at any point we just have to compare one value that was in the previous interval at any given moment. And now over here we can just simply start iterating over whatever the answer we have found so far. So in this case we can simply return the answer as 2 to 6, 7 to 9, and 11 to 16, and this would be our solution. Now if you look at the solution over here, essentially all we had to do is just iterate over the sorted input once. So basically to generate this answer we are only doing big O of n work, but the total time complexity in this case is actually going to be big O of n log n. And why n log n? Because we will have to generate the sorted input from this given original input, and that takes n log n time. First of all, we are going to sort the given input. Okay, after sorting the given input based on this based on the starting values, we are going to create a linked list, and we are going to store answer in this linked list. Now we are going to iterate every single interval inside the given input. So now we are going to check that whether we are at the first position or whether the given interval, if that is in conflict or not. So if that is not in conflict or there does not exist an overlap, we are simply going to add it to our answer. Okay, if that's not the case, we have detected a conflict, and the moment we detect a conflict, we will have to resolve the conflict. So essentially we are going to add the new interval that is merged. Okay, and after this loop ends, essentially our answer should be in the answer linked list, so we can return that. But in this case we need to return a two-dimensional array, so we will convert our answer list to a 2D array. Okay, let's try to run this code. Seems like our solution is working. Let's try to submit this code. Okay, our solution works pretty efficiently. I would be posting this solution in the comments. You can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do non-overlapping intervals problem, and this problem is actually very similar to merge interval problems and insert interval problems. I have solved both of these problems and I will be posting their links in the description so you can check it out from there. Like, though this problem seems like it has not been asked by many companies, actually this can be a very interesting post question after these two interview questions. So usually, like, all the interval problems, they are done in sync, and even for this particular problem, if we see, it has been asked by tech giants like Facebook, Amazon, Microsoft, Bloomberg, Apple, Oracle, Google, ByteDance, which is TikTok, and Snapchat, and these are my dream companies, so I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem, and we are basically given an array of intervals where every single entry has a starting point and an ending point that represents that particular interval. Now our aim is in this problem is that we need to return that how many minimum numbers of intervals that if we remove from this given original input, if we remove those, then the remaining result should be such that all the intervals becomes non-overlapping. So we need to return the number of intervals that we need to remove. So let's try to understand this problem with an example that is given over here. And over here we are given some set of intervals, and let's try to plot them on this given number series and see that what would be the answer. Okay, so after plotting all of these, our aim is to see that, okay, if there exists an overlap inside this given interval, we need to return the minimum number of intervals such that all the remaining intervals becomes non-overlapping. So over here we can clearly see that, okay, there exists an overlap between these points, and the overlap is actually mainly caused by because of this particular interval and these two intervals. So our aim is to remove the minimum number of intervals that that basically allows all the remaining intervals to become non-overlapping. So in this case, if we simply remove this particular interval that starts at position number 1 and ends at position number 3, this big one. So if we get rid of this particular big interval, we will have a result where all the intervals, they are actually not in collision with each other and they are not overlapping with each other. Over here we can see that they actually connect at some point, but that is not an overlap. Like, I know that in previous questions we used to consider this as an overlap, but you can confirm this with your interviewer that with what approach they want to go. So in this case, we only get rid of this one interval that was existing, and because we get rid of one, we will return one. That in this given input, if we simply remove one interval, we can determine that, okay, there exists one interval such that if we remove that, then all the other intervals becomes non-overlapping. Now to generate the optimal solution, the main thing is that we will have to determine that whether there exists an overlap inside the given interval or not. Now, in the previous examples we saw, the input was already sorted, but in the problem statement, it is nowhere written that the input should be sorted. So input could be something like this, where everything is different value. Now the thing is, first of all, over here, we need to determine that what are the intervals that are actually causing the overlap, and then we can determine that which one should be removed and what not, blah blah blah, what should be the strategy for that. Now the thing is, if we plot these this given input on side on a number system, we will get a result like this. Over here we can clearly see that there exists a conflict between these two intervals, which is represented over here. The thing is, how we were able to identify that there exists a conflict. We were able to identify it because the starting point of this particular interval was actually falling between the two values of some already existing interval. So that is the condition we will have to determine if we want to find that whether there exists an overlap or not. So over here, suppose we get at value number 5, and we want to check that whether 5 has an overlap anywhere. So 5, we will have to check all the other intervals. So 5 does not exist between this 2 to 4, so there is no overlap with this one. It also does not exist between 8 to 9, so there is no overlap, and it does not exist between 1 and 3, so that's why there is no overlap. So now we are say that, okay, this 5 7 has no overlap with any other interval. Now we check for this value number 2 to 4. So again we check the starting point for the value number 2. So value number 2 does not fall between 8 to 9. So there is no overlap. but 2 actually falls between this 1 2 3, because 1 is actually less than the value 2 and 2 is actually less than the value number 3. So which means 2 falls between this interval. So that's why the interval 2 to 4 and 1 to 3 are in between an overlap, and then we will have to take care of that scenario. Now, do you see a problem with this one? And the problem is that I can see is that for every single value, we will have to check all the other remaining values, that whether there exists an overlap or not. And that actually causes big O of n square time. And this is unnecessary work. Like, even just to determine that whether there exists an overlap or not, we are actually doing big O of n square work, which is like pointless. There exists a better approach, and the better approach is that if we sort the given input and then we sort them based on their starting values, things becomes a lot easier. So let's see that what should be the sorted array. Now we have sorted this given original set of intervals, and now we have all the values sorted. So now if we want to identify that whether there exists an overlap, all we need to do is we just need to compare any two adjacent values, and the moment we compare any two adjacent values, we can directly tell that whether there exists a conflict between them or not. How can we tell them is that we only need to check that whether the starting point of any second interval compared to its previous interval, if that is smaller, then we know that there exists a conflict. So in this case, we can say that between this 1 and 3 and 2 and 4, there exists a conflict because this particular interval ends at value number 3 and this particular interval starts at value number 2. So that's why there is a conflict. Meanwhile, if we see over here, this particular interval ends at value number 4 and this one starts at value number 5. So that's why there is no conflict. So this is a very easy way for us to determine that whether there exists a conflict or not. And if we see in terms of time complexity, the time complexity for the sorted operation takes only big O of n log n, which is a big improvement compared to the previous time complexity for this one, which was big O of n square. Okay, now we have determined that how to identify overlap. The question is that how to find that what should be the most number of nodes that we will have to remove, and what should be the strategy for it. So essentially there can be three different scenarios at any given moment. The first scenario is that between two intervals there does not exist an overlap. So if there does not exist an overlap, there is no need for removal. So we don't need to remove at anything. So we are good in this case. This is like the most beautiful thing. The second scenario is that we are given one interval that is clearly bigger compared to the second interval. So essentially we can say that this second interval is actually subset of this given bigger interval. So in this case, things actually becomes pretty easy for us. All we need to do is that we simply need to remove the bigger interval, because there is a conflict between these two intervals right now, which we can see, but there could be possibility that there might exist some other interval, something like this. So say in this scenario, if we got rid of this interval, we will still find ourselves to be having conflict between these two intervals, and again, in order to resolve that, we will have to remove this one as well. But rather doing this, suppose in this scenario we only had two intervals like this, and originally if we just got rid of this bigger interval, then immediately, even though there exists another interval somewhere down which was actually causing an overlap between this original interval, still we will have to perform less remove operations. So that is why the strategy should be that always remove the bigger interval. Now the question comes in scenario like this, where the starting point of one interval is actually falling before and the starting point of second interval actually falls somewhere in between. So what should be our approach in this scenario? And in this scenario as well, what I'm suggesting is that we remove the interval that has the longer end point. Essentially, if we at any point identify ourselves in this kind of scenario, our strategy should be to remove the interval with the end point that is greater. So suppose we consider that the starting point for this interval is actually 1 2 3, and suppose we consider that starting point for this interval is 2 to 4. So in this scenario, the strategy we are going to use is that we are always going to remove the interval 2 to 4. Why? Because we are going to compare the end values, and whichever interval has the greater end value, we will decide to remove that particular interval. So essentially we are using a greedy approach, But by using this greedy approach, what we are going to do is that over here we know that for this particular case, for this particular interval, we only had an interval that was causing an overlap over here. But again, the same thing could happen, that we might have another interval like this, where this particular interval was causing an overlap between this and also this. So immediately remember, our input is sorted, so we are coming from left to right inside the number sequence. So the moment we identify that whatever has the greater endpoint, if we decide to remove that, so even over here we already got rid of this one. So even over here, if there exists another interval that comes after this 1 2 3, still it would not be in overlap with this 1 2 3, and we will have to do less remove operation. And this would be our ideal approach. If we calculate the time and space complexity, basically the time complexity in this case is going to be big O of n log n. And why n log n? Essentially, doing this interval, converting this interval from a normal input to sorted input takes n log n time. And then after that, once we have this input given, essentially all we need to do is just we have to iterate over the given input once, because it is already sorted, and then we can perform the remove operation and we can count the number of times we removed any interval. So that this second part takes big O of n time. So total work we are doing is actually big O of n log n plus big O of n, but in general we can write this as big O of n log n. And in terms of space complexity, we are not using anything extra, so we can just say that it's a constant time space complexity. At most we are just going to use couple of extra variables. So first of all, we are going to check that if the given intervals is empty, so we are going to return 0. Okay, if that's not the case, we will have to sort the given input, and we are going to sort the given input based on the starting values. Okay, after the sorting, we are going to initialize couple of variables. So we are going to keep a variable called previous to keep track of the previous element, and we will initialize it to 0. We are also going to have a variable called count to keep track of the number of elements that we will have to remove. So we are also going to initialize it to 0. And now we are going to run a for loop that runs over the given sorted input. And over here we are going to start it as int I is equal to 1, because we already have the previous value as 0 for the comparison. And remember that because the input is sorted, at any given moment we are only comparing two adjacent elements inside the given interval. So first of all, we are going to check that if there exists an overlap between two adjacent elements, and if there exists an overlap, we are going to check that which element is having the greater end value. So we will update the previous counter based on that, and if there exists an overlap, we are going to increase our count. This second if condition dictates that if the previous interval is actually greater than the current interval we are at, we will have to update the previous counter to next element. And in any case, we are going to increment our count variable. And if this is not the case, essentially we have found that between two adjacent intervals there does not exist any overlap, so we are going to increase our value of our previous previous variable to the current I, so that we can use it for further implementation. And once we are done with this loop, essentially this count variable should have our answer, so we can simply return the count variable, and this should be our solution. Let's try to run the code. Okay, seems like our solution is working. Let's try to submit the code. Okay, our solution is working as expected, and it's actually pretty efficient in terms of memory usage, and even in terms of time complexity, it's not that bad compared to other solutions. I would be posting this in the comments and you can check it out from there. We are not gonna stop till we get into FAANG, and see you next time. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do meeting rooms lead code problem, and this is actually a lead code premium problem. So if you want to know that what are the list of companies that have asked this question in their interviews, that comes later in the video, and I have provided the timestamp for that, so you can directly go and check it out. Let's understand the problem statement. Essentially, we are given an array of meetings called intervals, and we are given start time and an end time for every single meetings inside this given array. Now we need to determine that if one person can attend all the meetings or not. So let's try to understand this given problem by an example. So over here we are given 3 different meeting times, and let's try to plot them on this number sequence that we have created. So first meeting starts from 0 time and it lasts until 30 minutes. Second meeting starts at 5 minutes and ends at 10 minutes, and third meeting starts at 15 minutes and ends at 20 minutes. So over here we can clearly see that there is no way possible for one person to attend all the meetings, because there exists a conflict between this meeting and this meeting, and there also exists a conflict between this meeting and this meeting and this meeting. So because there is an overlap between intervals, and essentially that's what we will have to determine in this problem. So over here we can clearly return false, that there does not exist any way possible for one person to attend all the different meetings that are given in this interval. Now if we take a look at the second example, and let's try to plot it in on a number sequence. So over here we can imagine a number sequence like this, and over here we are given one meeting that starts at 7 and ends at value number 10, and second meeting starts at 2 and ends at value number 4. So over here we can clearly see that it's possible for one person to attend this meeting, and after that he can attend he or she can attend this meeting. So in this case we will return true, and basically that's what we will need to determine. Now the tricky part over here is that we will have to determine that how do we identify that there exists overlap between any two values. So suppose over here in this example, if we are given an another meeting that starts at 3 and ends at 5, something like that. Now in this case, can we say that can one person attend all the meetings or not? Well, we can clearly see that because there is an overlap between these two meetings, one person won't be able to attend all 3 meetings, and over here we will have to return false. The thing is, why we were able to determine that over here there exists an overlap. So because over here we see that the starting point for this meeting and ending point for this meeting is from 2 to 4, so that is one interval. And if we look at this one, the starting point from this for this one and this ending point for this one is 3 to 5, so this is 3 to 5. So over here if we consider this particular interval, we can see that the starting point of this interval actually falls somewhere between any other interval that already exists. So at any moment, if we determine that the starting point of some interval, if it falls between any interval and this condition is satisfied, that 2 is actually less than 3 and 3 is actually less than 4, which means 3 falls in between this interval. So that's why we can determine that there exists an overlap, and the moment we identify that there is an overlap over here, we will immediately return false, and this is how we are going to approach. Suppose we are given an input like this, the different intervals are given, and this is the number sequence that we are going to use. Now over here, essentially if we want to determine that can one person attend all the meetings, we will have to check that whether there exists a conflict or not. So if we look at this first scenario, previously we determined that how to identify an overlap. So if we look at the starting value of this 20, we will have to check that whether this 20 exists in between some intervals. So over here, this is 10 to 15. So 20 does not exist over here. This is 35 to 45. So 20 does not exist over here. And this is 10 to 20. Now this meeting ends at 20 and this meeting starts at 20. So this is also a legitimate scenario because 20 is not part of this interval. So that is why we can determine that, okay, this meeting is good, like the starting point does not have a conflict with any other meetings. Now let's see about this one. So this meeting is from 0 to 15, right? So does there exist any conflict between these two, between this 0? So 0 does not exist between this one. 0 also does not exist over here, and 0 does not exist over here. So we are good. Same goes for this 35, that 35 does not exist between these two, this one or this one. So we are good. But when we come to this value number 10, we can clearly see that this 10 actually falls between this 0 to 15, because this condition is satisfied. 0 is less than 10 and 10 is less than 15. So over here we can clearly see that there exists an overlap between these two elements, and we can immediately return false. So this approach would work perfectly fine. But what is the issue with this approach? The issue is that this takes big O of n square time. Why big O of n square time? Because remember, for every single element we will have to check all the remaining elements based on the starting point. Same goes for this one, same goes for this one. So that's why we are doing n square work. So this work can greatly reduce if we just sort the given input based on the meeting start times. And let me show you how. So let me clean this up and let me sort this given input. So now we have the sorted input. Now in the sorted input, if you take a look at it, we are actually able to determine that whether there exists an overlap immediately. How? All we need to do is we'll need to compare the starting point with the ending point of the previous interval. If the starting point is actually less than the ending point of previous interval, we can determine that this meeting actually starts before the previous meeting ends, and immediately we can identify that whether there exists an overlap or not. So this is basically our solution. Like in this scenario, we can clearly see that the moment we are in the meeting from 0 to 15, so there is a meeting going on from 0 to 15, and before this meeting ends, there is another meeting that starts at 10 and lasts up until 20-minute mark. So there is an overlap over here, and immediately we will return false in this case. So this approach actually works, and it is more efficient than the previous approach we suggested. Why it is more efficient? Because if we calculate the time complexity in this case is going to be big O of n log n for the sorting operation, because from this given input, first of all, we will have to create a sorted input, and once we are done with that, if we want to identify the overlap, we only need to check any two adjacent values at any given moment, and the moment we reach to the end point and we don't find any issues, we can return true, or if we find any issue, we can return false before that. So this takes big O of n time. So total time complexity can be considered as big O of n log n. And in terms of space complexity, we are not using any additional space, so we can say that we are only using constant time to run this problem. And this is the final approach. Now let me show you the list of companies that have asked this problem, and if you are not interested, you can directly go to coding. So essentially, companies like Amazon, Google, Facebook, they have all asked this problem recently, and Microsoft and Wayfair, they are also really popular, well-paying companies that have asked this problem. Also companies like Bloomberg, Adobe, and eBay, that one of my dream companies that I want to join in, apart from the original, these tech giants. So first of all, we are going to sort the given input based on the start times of the given intervals. After sorting, we will have to iterate over all the sorted intervals, and we are going to check that whether there exists an overlap or not. We are going to check that whether the end point of any meeting is greater than the starting point of next meeting. If that is the case, we are going to return false immediately. And if this loop ends and we are able to reach to the last element, we are going to return true, that there does not exist an overlap. And now let's try to run this code. Okay, seems like our code is working. Let's try to submit the code. Okay, our submission works, and the code is actually pretty efficient, and I would be posting this in the comments. It is not too many lines of code, and this problem is very similar to the previous 3 interval problems that we have done. So I would be posting them in the comments. You can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCode until we get there. Today we are going to do a LeetCode premium problem, and you can clearly see that this has been one of the most popular LeetCode premium problems. This has been asked in companies like Amazon, Facebook, Google, Bloomberg, Microsoft, Oracle, Walmart, Uber, Twitter, Apple, Goldman Sachs, TikTok, and ByteDance, and also some other companies like eBay, Adobe, Swiggy. They all have also asked this question fairly recently. So my aim, you all know that I want to get a job at any top tier FAANG company, and that's why I'm making these videos. So I'm paying my utmost attention, and I hope you also enjoy the video. LeetCode medium problem, and it is one of the most popular problems on LeetCode. If you see the like to dislike ratio, also the name is meeting rooms too. So basically it is the next version of the original problem meeting rooms that I have already solved over here, so you can check it out from there. Now in this given problem, we are basically given an array of meeting times called intervals, and we are given a start value and an end value, and obviously start value is always going to come before the end value, like as it should be. Now we need to say that based on the given number of meetings, how many number of minimum conference rooms we are required so that all the meetings can be accommodated. And we know that for any single meeting we need at least one conference room, and when that meeting ends, that conference room can be used for some other meeting. So suppose say for example we have a meeting that starts at 5 and ends at 15 minutes, and we have another meeting that starts at, let's say, 17 minutes and ends at 27 minutes, something like that. So in this case, if we only have one conference room, we are still good. Why? Because first of all, this meeting will take place, all the attendees will attend this meeting. At 15 this meeting is going to end, and then they are going to leave away from this meeting, and then these new people are going to attend the meeting in the same conference room. So in this case we can clearly determine that okay, with one conference room we are sufficient to complete all the meetings. Now but problem comes when, say for example, we have a meeting that starts at 0 and ends at 30 minutes. I'm using this original example that is given. So suppose we have a meeting that starts at 0 minute and ends at 30 minutes. We have another meeting that, let's say, starts at 5 minutes and ends at 10 minutes. And we have another meeting that, let's say, starts at 15 minutes and end at 20 minutes. So something like that. So essentially over here we are having 3 different meetings. And now for these 3 meetings, how many minimum number of rooms we need to accommodate all the meetings? So clearly we can see that essentially there exists an overlap between this meeting and this meeting. There also exists an overlap between this meeting and this meeting. So because there exists an overlap, that is causing us to have more than one rooms, because at any given moment two meetings are happening at the same time, but they cannot be placed in one conference rooms. So now we will have to determine that how many number of conference room we need. Well, we will need, in this case, we will need 2 conference rooms. Why 2 conference rooms? If we look at this start time and end time for all the meetings, initially, let's say we have a conference room like this. So initially this first meeting takes place, which starts at this 0 minute, right? So let's say that, okay, this meeting is being taken place over here. Now, when we reach at this time number 5, we know that another meeting also needs to be started. But this conference room is also already occupied, so we cannot use this conference room. So what we will have to do is we will have to use another conference room, and let me draw it over here. So we will have to use another conference room to accommodate this meeting over here. Now at this time number 5 we started the meeting, but we noticed that at value number 10 we also finished this meeting, which means that now all the folks that attended this meeting, they are actually coming out of the conference room, and now this conference room is empty. But this conference room is still occupied with this original ongoing meeting, so that we will have to take care of. So at value number 10 we already emptied this conference room, but again we start seeing in this order. So we can find that at time number 15 we still need one more conference room to attend the meeting. So we check, okay, this conference room is already occupied, so we can't do anything. But this conference room is empty because this meeting has already been completed, which means we don't have to worry about it. So this meeting that starts at time number 15 needs to be placed on this second conference room again, and then it ends at minute number 20. So at 20 minutes all the folks, they empty this conference room. So again this conference room is now empty. Now there is no one, but this meeting is still going on. And when the clock hits 30 minutes, we can see that okay, now this particular conference room, the first conference room, is also going to be empty, and folks are going to leave it at time number 30. And this is basically the approach. So at any given moment, the maximum number of conference rooms we were using to accommodate all the meetings were actually 2. So in this case, we will need to return 2 as our answer. The question comes that why we were able to generate this 2, why not some other value, and how do we programmatically solve this problem? Well, the approach is actually quite simple. That over here, what we needed is only two things. The first thing we needed is that at any point, what was the start point, what is the end point, and based on the start and end points, we can actually come up with some very interesting results. So if we see over here in this example, what we were doing is that at any given moment, we are iterating over this time sequence, and based on the starting point of the meeting and ending point of the meeting, we are either occupying the room or we are emptying the room. And just by keeping track of those two activities, we can determine that what is the minimum number of rooms that we need in order for us to accommodate all the meetings. Let me show you how. So over here, again, keeping up with the same example. So let's say that in this example, we already have the start and end times of all of them. So what we can do is we can have two arrays. So first array would be for starting values and second array would be for ending values. And we are going to sort both the arrays based on the timing. So over here, the sorting values would be that what are the starting points? Starting points we have over here is 0, 5 and 15. So we have 3 starting points originally. And over here you can see that they are in sorted order, but if you look at the original input, we can't see them in sorted order. Like they can be jumbled up or the values can be given in any order, right? So first of all, we will sort everything, and then that sorting is going to take big O of n log n time. So that is some activity that we will discuss when we come to the time and space complexity. So initially the sorting position, currently this value is 0, 5 and 15. Okay, let me get rid of this extra space. Okay, now for the ending values are 10, 20 and 30. So again, let's sort based on the ending values. So 10, 20 and 30. And now what we are going to do is at any given moment, we are going to check both of these arrays, and amongst these two arrays, we are going to see that what is the minimum value amongst either starting value or ending value. And we are going to keep a count or keep a variable called meetings, and we are going to increase the value based on whatever the results we find over here. So let's try to do that. So initially we compare these two values. We see that okay, 0 is minimum amongst these two. So because we are starting a new meeting, which means we will have to occupy a room, and because we have to occupy a room, what we are going to do is we are going to do meeting plus plus. So essentially the value of meeting was originally 0, so we are going to keep the value as 1. Now we are keeping the value as 1. What we are going to do is we are going to iterate over. So this we are keeping at this because this has not been updated in the ending value, but in the starting value, the 0 has already been taken care of, so we ignore this case. And now for the starting value, we compare this value number 5. So again, we compare this value number 5 with this value number 10. We see that okay, the smaller value amongst these two is still the starting point in the starting array, and because we are starting a new meeting, which means that we haven't completed any meeting, but we are starting a new meeting. So because we are starting a new meeting, we'll still have to add the value of meeting. So currently the number of conference rooms we will need, we are going to increase it to 2. And by the way, this you can consider as meeting rooms. I just named it meeting just for simplicity. Okay, now again we are done with this 5. So again, for the start value we increment, and over here we are still at this position number 10. Again we compare this 15 and 10. So over here we realize that this 10 is actually smaller than 15, which means we are ending a meeting before. So now because we are ending the meeting, so we will jump on this ending array. Now we will come to this place, and because we ended a meeting, which means we will have to subtract the value over here. So what we are going to do is, rather than having 2, we will reduce this value back to 1. But and so now we are at this 15 and 20. So we compare both the values and we realize that okay, this 15 comes first. So we are starting a meeting now. So because we are starting a meeting, will again do plus plus. So now this 1 becomes 2, and we compare this meeting with this answer. So both values are 2, so we don't need to update anything. And that's why over here we are done with this case. So now there is no more place to start the meetings. So actually we can end over here. Why? Because over here, the moment we are going to like reach this and this value, all we are going to do is we are simply going to reduce the value of this meeting parameter back to 1 and then again back to 0. So there is no point in us for doing all this work if the starting array has already been dealt with. And this would be our solution. Like this is a very simple solution to understand and easy to come up with, and this is also very optimal and it solves the problem efficiently. So let's see that what would be the time and space complexity. The time complexity in this case is going to be big O of n log n. So this is initially for sorting, as I mentioned earlier, plus big O of n, and this big O of n is to iterate over the start and end array. So in general we can write this as big O of n log n only. And now we are done with this one. In terms of space complexity, for the space complexity it would be big O of 2n, because we are storing 2 arrays, and in the both arrays we are storing some n values. So but in general we can write this as big O of n as well. And this would be the optimal time and space complexity. First of all, we are going to check that if the given array of intervals is empty or not. If it is empty, we are going to return 0. That is not the case. We are going to create 2 integer arrays, start and end, and for both the arrays we are actually going to fill out all the values in the start array and end array. Once that is done, we are going to iterate over the given input, and from the given intervals we are going to fill out the start and end array. Once this is done, we are going to sort the given start and end array. And once sorting is done, we are going to initialize a couple of pointers. So we are going to name them a start pointer and an end pointer, and we are going to initialize the values as 0, and these pointers are going to be used to iterate over this start and end array. And once these two are done, we are also going to have a variable called result to keep track of the number of meeting rooms that are needed, and we are also going to initialize it to 0. And now we are going to run a loop, but remember that we only need to run a loop until the start array has some values. So we are only going to iterate over the start array, because once start array is done, the result value is always gonna go down. And at any point we are going to check that whether the current start value is actually greater than or equal to the end value or not. If that is the case, we will have to update the end array. And the reason we are doing it is, suppose we are given a couple of arrays like this, that a meeting starts at 0 and ends at 10 minutes, and there is another meeting that starts at 10 and ends at 15. So in this case we can actually use just one room or one conference room to iterate over. Why? Because first meeting has to end first before the second meeting starts. This is a condition that is given, and we are going to use that. Hence, if this is the case, we are going to decrement the number of result that is, and we are going to increment the end pointer. And if that is not the case, so which means that we essentially have a meeting starting before the previous meeting ending, and in that case we will always have to increase the number of rooms needed. So we can simply increase the result, and we will also have to update the starting pointer. And at the end, once this loop is done, we can simply return whatever the result we found. Let's try to run this code. Seems like our solution is working. Let's try to submit this code. And we are actually solving this problem way faster than a lot of other Java solutions. And you can see it over here. So I would be posting this code in the solution in the comments. You can check it out from there. So friends, I was actually hoping to complete all NeetCode 150 questions by the end of this video, but because of YouTube's 12-hour maximum limit on my channel, I cannot upload the remaining 16 questions. So looks like I will have to create a part 4 for completing those 16 questions that I would be uploading soon. But if you made up until this far, once again, many power to you and kudos to you for doing this. I know it's not difficult to sit through 36 hours of NeetCode problems, but anyways, whatever doesn't kill you simply makes you stronger. And if this hard work can result into you getting a job that would double or triple or quadruple your salary, then of course it's definitely worth the effort. Now I would be creating the last and final part for the remaining 16 questions. And till then, take care.